null. If the value you are checking is trying to be validated against a null value, you'll get null. So if you're trying to check null against values, you'll get null. If you're trying to get one against null, you'll get null. Just be careful with null values. That's what we're trying to get at here. But in actuality, what we're referencing here is that in checks if any of the values are validated against that column and / row value. So the row value that we're trying to validate here is in a range of values that we're getting back from the inner query. And then not in checks if the value is not equal to any of the rows that were returned. And to the same effect, it has the same tendencies as the in operator. It's just checking the inverse. So you can see here that I use not in, and here you could also use not in, so you would get the inverse. I happen to leave it as an in, but not in basically would do the same to the outer query. It would inverse it and then say, hey, show me everything other than comedy, family, and classics. That's what would happen here. And then we have any and some, which are just the same but a different word. They're kind of comparable to each other. They're basically trying to check if any of the values relate to a value that is returned. So when we do this, if we say category is equal to any, and the way that you write any and some is that you write a column that is going to denote a row value, and then you use a comparison operator, and then you use any. And behind that, you run your subquery. And what this does is it checks against each row the operator, and if the comparison matches, it will return true. So it's checking against a range of values if any of them are correlated to that specific row. It's an easy way for you to say, hey, this subquery might return multiple rows, not a single row, but I still want to use my comparison operators. Because as you know, comparison operators can only be applied against a single record. So by doing this, what we're saying is we can use our comparison operators and we can check if they apply against any of the values. And if any of them match, returning it true. The inverse of that is all. It will check each row value against each row value from the subquery. And if all the comparisons match, it will return true. So if you have a multiple row situation where you're returning multiple rows from a subquery, with all, the value that you're checking must match all of the returned values. So let's say you were trying to check 1 against all of the rows in the subquery must return a 1, and it's going to validate against each and every one of those rows. So it's going to check 1 against 1, 1 against 1, 1 against 1, 1 against 1. And so with that being said, the multiple rows that are returned from here, they must all yield the exact same value that you're trying to check. In this specific query right here, you can see we're selecting product ID, title, sales, and we're joining on inventory so that we can have the sales value available. And then our subquery is in the where clause, and we're saying where the sales of the inventory are greater than all. And then the subquery is an interesting one. We're selecting the average sales, and then we're joining on the products, and we're grouping by the categories. So we're calculating the average sales for each and every single category. So we're getting basically all of the products where the sales were larger than the average sales of every category. So we're getting the top performers across all categories. So what this does is it's going to check sales against each and every row, which is multiple averages by category. And if the comparison is true, then it will return true. If the comparison is true for all of the records. So if sales is greater than each and every average for each and every category in this case. So all is also an interesting one. And so the final one, the final operator we'll be looking at are the single value comparisons. A subquery must return a single row and then check the comparator against that row. So as you remember, the different types of subqueries we saw, single row comparators where you're not using all, any, or some, when you use greater than, less than, equal to, and all of those comparators that we saw, they can only be checked against a single row. Here you see a very, very redundant subquery where we're just basically saying, hey, I don't know the number for the category comedy, so let me run a subquery and let me just get a single row back that is against comedy because I'm too lazy to look up the number basically. But in any case, the subquery must return a single row for this to work. If it returns multiple rows, the query will complain. And having shown you all of those operators, I think it's time to dive into some of the subquery exercises that we've prepared that you can try out. Have fun. So here we are, new section, time to create some stuff. So far, we've learned so much about SQL. We've created a foundation that really can form as a bedrock for you to be able to pretty much do SQL in any environment. Even though we've picked Postgres as the mainstay or the technology of choice for this course, the majority of things and exercises and concepts you've learned are almost completely transferable to other technologies. And the whole point of this is to create that foundation that will make you take off like a rocket ship once you leave this course. Once you're done with this course, what we want you to be able to do is, oh, you want me to pick up Postgres? I can do that real quick. Want me to learn MySQL? Give me a day. Hey, what's that obscure technology over there, that database technology? Huh, I got that. Because we've created such a foundation of learning and concepts and basics, the mastery really comes with practice. But the ability for you to take off like a rocket ship really stems from those principles and foundations that we've laid in. And so from there is one more core of SQL that we really need to touch on in order to say that you've seen pretty much all of the principles and foundations, basic to advanced topics, in order to say, hey, how do I go from A to Z when I'm working with a database technology? And so what will we be learning in this section? Well, we'll be learning about the different types of data. And data is what databases are all about. So far, we've really encapsulated and kind of narrowed down our focus on those core SQL principles, how to do a select query, how to do advanced subqueries, and everything in between. But now comes the time where you will be creating your own databases and your own tables and looking at all of those different commands that come into play when you do those things. And for that, we are going to need to understand the different types of data. You'll also learn how to create a database, your own database. So far, everything has been provided to you, and the whole idea behind that and the whole idea behind how we structured this course is to layer the knowledge like you would layer a cake. We started with the principles and foundation. We went into an SQL deep dive. We taught you all of the basic concepts around querying, and we really wanted to narrow our vision on those queries, really get you to hone all of the different skills that go into the querying language, because at the end of the day, that is the main source of knowledge within SQL, is that data querying language. And as you get more and more familiar with all of the things that happen on that end of the spectrum, well, now we're going to focus on the other end of the spectrum, which is creation. And so we're also going to look at how you create your own tables, how to insert, update, delete, etc. Do everything possible with data so that you can create your own universe of a database and play with your own data and kind of fiddle around with all of those nuances when it comes to a database. And we're also going to be looking at so much more. Now, this is a blast from the past. We were looking at the SQL commands all the way at the beginning of the course, and we saw all of these different concepts: DDL, DQL, DML, and DCL. And all of these different buckets, so to speak, have their specific purposes. And over here, you see like a broad scale overview of all the different commands that you can execute within these buckets. And for the majority of this course, we've been focusing on DQL, specifically on the select query and all the different things you can do with the select. And it's crazy how versatile this one little command is, how much you can do with it. It's absolutely amazing. But now we're going to go over to DML, and we're going to focus on the insert, the update, delete, and over in the DDL column, we're going to be looking at create, alter, drop, and some of the other commands. And we're doing this so that you have the ability to have a full-scale toolkit at your disposal when it comes to databases, because we want you to have transferable skills. We want you to have that foundation that can make you an SQL master. And when we look at this schema, well, we've pretty much created the broadest possible foundation for querying. We know the select statement inside and out. We know everything that has to do with the select statement. And we even went as deep as to look at some of the more advanced concepts. But now we're going to be looking at the data definition language and the data modification language in order to create our own universe. And so why is it important? Well, creating and maintaining data is extremely hard. You know, when you have a database, a lot of people think of it like, okay, we have this SQL database and we have data over here. But what really comes down to it is who is consuming the data? Who is updating and adding data? Who's the insert and the updates, and what kind of transactions are we looking at? And data is constantly being created and flowed through and put into your database. And so it can become extremely difficult to manage and maintain data. What we want to show you in this portion of the course is, well, how do I create my own data? Like, what does it look like, and what are some of the nuances around it? Because once you're able to do something, it really supercharges you to be able to understand, well, hey, if I have all of these consumers and I have all of these things that I need to do, well, this is how I can formulate a strategy around it, right? Understanding something and being able to do something gives you the ability to look at it from a higher level. Once you know how to create databases, create tables, insert data, update data, well, with that foundational knowledge, you can go ahead and you can understand how a wide array of applications is working with your database. Because at the end of the day, when people insert data, when APIs insert data into your database, it's nothing more than a create, an insert, an update statement, or anything in between. So the data definition language, these are commands to create, modify, delete different structures. We are defining structures. What do I mean when I talk about structures? I'm talking about creating databases, creating tables, creating roles. Roles, you can do role management in Postgres. There's so many things you can do, and the data definition language gives you the ability to do this. And when we look at the data manipulation language, or DML, we are looking at commands for adding, deleting, modifying data. We're looking at the data that is stored at that level, specifically inside of those tables. So we're looking at a more granular view. And so to give you a quick refresher, this is one of the diagrams that we looked at during Principles and Foundations. And for the majority of the course, we've been looking over on this side of the fence, right? We've been looking at, well, how do we actually do these select statements in order to get our data back? And we've become pretty much very, very advanced at these select statements. We know how to do them. But now we're going to go look at this side of the fence, and we're going to look at, hey, how do I create a database? How do I create tables inside this database? And how do I store data in order for my queries to actually be able to get back data? That's a great little way of looking at it. And that's why we structured the course this way, is we wanted you to be on this side of the fence and become very, very familiar with SQL and its syntax and the select queries and being able to query data before we went and looked at how to set up these structures. Because setting up these structures is usually a one-time thing. Once you set up a database and once you set up the tables and once you set up all the structures, well, then it's all about maintaining these structures and updating these structures and keeping them relevant rather than remaking them. Unless you are going into a migration, which is a completely different set of skills and requirements and thought process that goes into the planning of migration. Migrations are hard, but for now, we want to give you those principles and foundational skills in order to understand, well, hey, if I want to create my own database and I want to create my own data, how do I go about that? How does that work? And what all goes into it? And so for the first portion of the course, we'll be looking at how to create databases and what all goes into the creation of databases. So let's kick this off with a bang. All right, so here we are about to create our very first database. But before we get into that, I wanted to talk a little bit about the types of databases, and specifically the types of databases that are available when you look at database management systems. Because over the majority of this course, we've mostly been focusing on DQL, or data querying language. And we've mostly focused on looking at everything from basic select statements all the way to subquerying and everything in between. We're not shy to say that we've become fairly confident in our SQL querying skills. But now we're reaching into a completely different area. A completely different area that has to do with the databases, the management, the whole back office affair, operations, so to speak. Now, this area of what I would call database management is completely different depending on the job you're trying to do. Now, if you're at a startup, you may do everything in between from database management to creation and all of that good stuff. But if you're in a more rigorous environment with a more structured company, they may have departments that deal with certain aspects. If you're a business analyst, you may be writing a lot of queries to get data out of regular databases. But if you're on the operations side, you may be doing a lot of sharding, replication, backups, database management type tasks. And all of those tasks, like drawing backups and doing the management of those areas, they are completely separate. Like IT is one of those fields where people think just because you're in IT, you know everything. But even within a domain as small as databases, you have the management side, you have the querying side, you have all of these different entities trying to work together to create data. And then at the end point, you have these people that are managing. And when we look at management, we can directly note two distinct types of databases, I will say. When we create databases, what we're doing is we're running a create database command, and that creates us a regular database. And in that regular database, we can go ahead and we can create tables and relations and all of these good things that we've learned about. But what exactly is the process that goes behind creating that database? Because for everything that is created, there must be a map, a blueprint, some kind of structure behind it that tells it, what am I making? And that is what a template database is. So when we look at the types of databases in a database management system and from the management perspective, well, the regular databases are what we're used to. We're basically professionals in querying them. And on the other end, there's the template database where you're looking at, hey, this is the structure I kind of want to have in place whenever I create a database. They're kind of related to each other because a template is a blueprint and the regular database is built off of a blueprint, right? So to speak, a template database is that secret sauce, that kind of like structure that we were talking about, and it's configurable. We can create our own templates. We can say, hey, put this in, put that in. And anytime you create a database based off of that, it's going to do it based off of that template, and it's going to take those structures with it. You could put tables in there, you could put functions in there, you could put custom types in there, you could put anything in a template, and when you create a database based off of it, it's going to take it with it. Well, not necessarily everything. It doesn't take everything, but it's a blueprint. So it's one of those things where you're saying, hey, shape it like this. And then when you create a database, it's going to shape it like that. So now that we know about the types of databases, what I really want to zoom in on is how does Postgres set up the shape of the world? Like, how did that happen? What happens when Postgres, when we set it up? We're going back to the past here. We're going back to the very beginning of the course when we did all of our setup. We didn't really pay attention to any of that setup. We didn't look at anything that happened. But a lot happened behind the scenes. And I really want to zoom in on that. So let's zoom in on that. So zooming in on what happened way back when we set up. That's like hours and hours of content to go. But very important things happen back there. And the reason I want to zoom in on these necessarily is because when we look at something like database management, it's going to be very hard to make you seasoned database managers just based off of a couple of hours of content. It's something that takes a lot of practice and a lot of knowledge. And so we want to build that foundational knowledge for you. We want you to understand, hey, if I'm looking at Postgres and I'm looking at how it's set up, let me at least understand, what goes behind it. Like, where does it start and how did it start? Because, we're practically pros at querying. We know databases inside and out. And so with that, our query language is on point. But now we're looking at something else. Now we're looking at, hey, how is this thing set up? And, what's going on there, Mo? For that, those questions will be answered. When you set up Postgres, 3 databases were created. When we created the shape of the universe that is Postgres, we created 3 different databases during that setup, but you knew of none of them. You may have seen them here or there popping up around, depending on if you were playing around with the command line during your setup or using some other tool. You may have seen these, but those 3 databases were created. And those 3 databases, they reign supreme during our shape of the universe. I'm using this analogy to death, but, I'm butchering it slightly, but, what I'm trying to get at here is, when we set up Postgres, what we were trying to accomplish was setting up this shape of the universe that we could go ahead use to create more and more things. Because when we look at data is something that continues to expand. We get more and more and more data. And with that more and more and more data, you could theoretically look at it as kind of a universe, I guess. But analogy aside, like I've been using it a lot. What we created was a Postgres database, a template database, another template database. You're going to love this one. Why 2 template databases? Well, we'll get into that. But let's zoom in on this guy first, the Postgres database. Why was this created? And why these 3? Let's zoom in on that. Well, the Postgres database was the default database that is created when you set up Postgres. So when you do initialize DB, initdb, this is the command that, depending on how you set up Postgres, you may or may not have had to use. Now, we've automated the majority of the process for you during the setup to hide as much implementation from you as possible because we really, really wanted to focus on making you SQL masters, focusing on those SQL skills, those raw querying skills. All this management and this and that, we're getting to it now, but at the beginning, we really didn't want to overload you. When you set up your database infrastructure, you're setting up a Postgres database by default. And this is always going to happen by default because the default user you get with a Postgres installation is Postgres. So Postgres is the user and it creates a database called Postgres. Coincidence? I think not. Now, the first time you initialize Postgres, you can connect to the Postgres database that it's set up for you, the very first database. So here we see some command line. Again, something that we're going to be zooming in on during this portion of the course for a bit to get you some of those command line skills going. And we used some command line during setup to run some backups and restore some databases, but we really didn't focus on it throughout the course because, again, we chose a tool that was cross-platform, easy to use, easy for entry, that you could really go zone in, hone your skills on for select queries. And also, if you liked it, use with other database providers down the line. Now, with command line, the command line changes depending on which provider you use, PSQL or MySQL or Oracle. The command line interface will change heavily. So we wanted to give you that tool that is your bedrock. And you can change tools to change different bedrocks. And all these tools are basically doing the same thing for you. They're hiding the details so that you have an easy time managing different databases. The first time that you initialize, you can do the PSQL command. And the PSQL command is the main command that you use to log into a database and a host of other commands. And when we use it, we can give it a -u, which tells it, hey, I'm going to give you a user. So we give it the user Postgres, and then we can give it a database. And when we give it a database, that is the database it is going to connect to. Now, something interesting to note here. What if you don't give it a database? What would happen? Well, Postgres by default will assume a connection to a database with the same name as the user if no database is supplied. So if you did something like this, what it's going to do behind the scenes is it's going to assume that you're trying to connect to a database called Postgres. Now, why would it do that? Well, it's default behavior. What the architects were thinking, I can't necessarily tell you, but the default behavior is there. So it's by default always going to assume a connection to a database with the same name as the user. And this is true for any user. Who would ever do this? No one. You always give a database name when you are connecting. You always have to give a database name when you're connecting. There's no reason not to. If you do, well, now we know what the default behavior of Postgres is going to be. It's going to try to connect to a database with the same name as the user. And in the case of Postgres, if you're able to log in with that user, if you're not another user, well, yeah, it may work. But if you're a different user, you may not have a database with the same name as your user. So tough luck. Noting this default behavior, again, random, nitpicky knowledge, call it what you will, but it gives us an understanding of how this software actually is working a little bit. And with that, if we connected this way, and we went into the Postgres database and we connected, and we ran the command /coninfo, CONNINFO, it would tell us you are connected to the database Postgres. As the user, Postgres. Interesting. So it did exactly what we said. If we connected without giving it a database, it would do this. If you set up Postgres for the first time, you will not have any other database. So you have no choice but connecting to Postgres to create a different database. But what's most important here, and what I wanted to highlight, is this coninfo command. Because this command shows you your current connection. It's super useful. It's showing you where you are, what you're connected to. It's an amazing, amazing, amazing command. Remember it, cherish it, because it's just useful to know where you are. If you're switching around a lot, if you're switching between databases, sometimes you could forget where exactly you are and you just want to verify, hey, am I here? Am I in the right database? Am I with the right user? Do I have the right permissions? All good stuff. This won't check your permissions, of course, but based on which user you're logging in with, I assume that you would know whether or not you have access. So with that said, let's look at template databases and let's zoom in on those a bit. So template databases, what are they about? We kind of zoomed in on them and we know their purpose. We know that they're used to be a blueprint for regular databases. But we zoomed in on two specific ones, template 0 and template 1. Now, what is template 0? Well, template 0 is the template that is used to create template 1. Isn't that funny? Right? What does that exactly mean? Well, in essence, it means that it's a backup for template 1. It's kind of like saying, hey, I'm going to give you a template that's going to be your default for everything, but I'm also going to give you the template that I used to make that template just in case you screw up that template. So never change it. Never change template 0. Don't touch it. Don't touch it. But with that said, it is in essence a backup template. That's what it's used for. Think of it as your safety net, your safety template. If you went ahead and you changed template 1 with a bunch of different things, I've never had to change template 1 necessarily. You can create other templates based off of template 1 and then use that as a template. But I've never had to change template 1. But let's say you change template 1 and you put a bunch of stuff in there. Well, now if you wanted to create a database based off of the original template, well, you still have template 0 available. So don't change it. Don't touch it. Now, template 1 is the interesting one. This one has more functions. It's used to create new databases. That is its function. That's all it does. Like if you run the create database command, it's going to use template 1 unless you tell it to use something else. It is your default. Any changes that you make to this template are automatically applied to all new databases. That is what it does. So if you change template 1, all of the databases you already created up till now, not going to be affected by it. But all of the new ones moving forward, well, depending on what you added, removed, changed, you're going to see that in the new databases moving forward. So be careful with what you change here and create different templates if you want to play around with it. Also, one thing to note is that because template 1 is the default template, if it is being accessed, if we're connected to it like we connected to the Postgres database, No new databases can be created until the connection is closed. Interesting. Okay, so if we connect to template 1 and we start like fiddling around with it, no one else can create databases. Well, let's see how that works. So over here, I'm in my command prompt. What I'm doing over here is basically I'm going to PSQL -u, and I'm going to use the user Postgres. But what I'm going to connect to is template 1. And if I do coninfo, which we know is the best command ever, we're going to see that we are connected to template 1 as the user Postgres. Okay, so now to prove our hypothesis, right? That's what we're here for. If we created a new prompt, let's say I PSQL -u, and I use Postgres, and I connect to the employees database, just the employees database, but I'm going to create a different database from there. I'm just going to connect to this one, and I'm going to say, hey, create database, and let's say I call it my blocked DB, because we know it's going to be blocked. Well, now it's hanging. It's not really, nothing's happening. Okay, so we get an error. And what this error is telling us is source database template 1 is being accessed by other users. There is one other session using the database. Interesting. So if we went back here and we said exit, and then we went back over here and we ran that command again, boom, database created. We got confirmation, baby. Now, with that said, this doesn't mean very much, right? We created our database. We were able to connect. Now, with that being said, creating this database explains something crucial to us. It explains to us that when we are connected to a template database, template 1, we cannot create other databases because it is the default template. But hey, what if I connected back to it and then I said, well, my block DB2, okay, that's not going to work. That's just going to break, right? Well, what if I said with template 0? What will it do? Oh, created the database. Interestingly enough, let's go look at that. And we can see here, I have my block DB and my block DB2. So because template 1 is the default template, it is going to be used by default by the command. But if I specify a different template, I get around that. But I'm also creating something with a completely different template, right? That's the catch right here. You can get around this, but it depends. If you're going to use different templates, you can use different templates, but by default, everyone uses template 1. So it's an interesting behavior to note, and it's an interesting behavior to see. And so with that, what we just saw, we know now you can create your own template database and create other databases with it. But this is not very common. Like, I don't know a lot of people that go out of their way to create multiple template databases and whatnot. You start with the default template and you create a database. Unless you're creating hundreds and hundreds of databases or many, many of the same, it's not very, very common. But you could do something like create database, my super duper template, because a template database is in essence a database. And then you connect to that super duper template and you create the table, my super duper table. And after creating that database, you can connect to it. You will see the table. We created that table inside of that template. But now if we create a database and we say my super duper database and we say with template, my super duper template, what you're going to see is if you connect to my super duper database, you're going to see a table, my super duper table, because it was used as a blueprint. So now comes the question. Mo, you've been telling us all of this random stuff about how Postgres is set up, and it's been useful, but how do I create a database? We're going to answer that right now. All right. I've held you up long enough. We're finally going to look at how to create an actual database. And first up, as always, we're going to look at the syntax. How exactly do you create a database? Well, the syntax is nothing simpler than create database and then you give it a name. That's all you have to do. That basic command will create a database for you with all of the defaults. It'll use template 1. It will set all of the same defaults. But if you want to override it, you can. You can override certain things by using the with statement. You can say with a specific owner, Because by default, when you create a database, the user that creates the database is the owner of that database. So you can specify a different owner. You can say with a different template, with a different encoding, and all of these other options. And the connection limit is basically what says, hey, how many concurrent connections can I have to this database? Can one user connect at a time? Can two? By default, the connection limit is 100. So all of these different options, let's zoom into them. I'm going to zoom into the subset that is most important for the purposes of this course. When we create a database, we may want to specify a different template. By default, the template is 01. We may want to specify an encoding. By default, the encoding is UTF-8. Never change this. UTF-8 is great. Don't even go play with the other encodings. An encoding is basically the way that characters are going to be stored, the way text is going to be stored. Can you store emojis, for instance? Don't store emojis in your database, please. But just to say, UTF-8 is one of those encodings that allows you to store characters in certain ways, and it has the broadest availability. Please do not change the encoding of your database. It was often the case in the past that the encodings would be regional, like people would choose an encoding that was local to whatever region in the world they were from, but that doesn't really garner international support. UTF-8 supports almost every character set in the world. You can store Arabic, you can store other languages. If you stored in a different encoding, you may miss out on all of those other alphabets, including the emoji alphabet, I guess. And then there's the connection limit, by default 100. 100 is a lot. But let's say you wanted to narrow that down. You only wanted 2 concurrent connections to a database. That could be, I guess, something you may want to do. It could also be considered a type of security, I guess, if you limit it to a very, very, very small amount, and you had an application that was talking and you only wanted one more connection open for an administrator to go in or whatnot. Although, don't do that, I guess. And then you have the owner. The owner is the current user. The current user that creates the database. And that user can specify a different owner if he so pleases. Now, let's look at creating an example database to store courses. That's what we're going to do. I had this little fun idea of actually creating a database to store some courses in. So let's create a database called ZTM, or Zero to Mastery, and we're going to create a very, very, very basic database that's going to store some courses for us. Sound like fun? Well, let's get into it. But before we get into it, I want to zoom in on one more thing here. Database organization. Now, let's go create our database, and then let's hop back here to talk about database organization after. So here we are, back in command line land. And let's do PSQL -u. And let's do Postgres, database Postgres. Just connect there. And let's run a create database command. And let's do ZTM. And as you can see, I already have the database ZTM, but all of you don't yet. Let's get into that. Let's quickly drop this database. And let's create it again. Seems like I'm still connected to my template, so let's exit here. And I'm still connected to it from Valentina Studio, so let me quickly quit that. With an open connection, you can't really do something. So now I've dropped the database, and if I go ahead and I create the database again, now I have the database. What we can see is that the database is over here. So now that I have the database all set up, let's go talk about some organization. All right, zooming into database organization. Now I know I've been talking about a lot of niche theoretical topics, and we really haven't zoomed in on any practical things. But again, what we're trying to do is give you that foundation, that foundational knowledge that will help you throughout your career. Now, when we look at databases, we often have many tables, many views, and depending on how much you care, you may want to organize them in a logical way, kind of like sweeping. You don't want things to be cluttered and dirty. You want a method to the madness, so to speak. What we talk about in Postgres are called Postgres schemas. This is a construct in Postgres. It's a concept. And you have to think of it like a box, right? You have to think of it like a box in which you can organize things. And so over here, you can see 4 boxes. And these 4 boxes represent 4 different schemas. And in these boxes, we can organize tables, views, indexes, types. We can basically say, hey, these are separate from each other. And why would we want to do that? Well, let's say we were creating a database structure for a company. And we had a sales department, a marketing department, all of these other different departments. Are we going to create a database per department? No, all the data needs to be intermixed so that we can kind of select and pluck data and query effectively among that one database. Why would you go and split that prematurely? That sounds like a lot of work, creating a database per organizational unit, so to speak, per department. No. That's not what we're going to do. We're going to organize the tables, the views, and the indexes in schemas. And so we can create a schema called sales. We can create a schema called payroll. We can create a schema called HR and technology and engineering and all of the different departments that you want. You can structure it any way you want. It doesn't even have to be by department. You can just create these constructs of boxes in which you put things. By default, each database gets a public schema. So when you create a database, you have that public schema. That is the schema that is available to every other schema. And it is the one that will be called by default. It is the one that, is assumed to be the default schema whenever you're trying to reach a table. So if you have a table in the public schema and you have a table in, let's say, the sales schema that has the exact same name, well, it's going to get the public schema first. That's what it's going to assume you're referring to. And unless you specify a schema, the default is always going to be assumed public. Very, very, very important. It is always going to assume public. Over here, we can see select star from employees is the same as select star from public employees. Public dot is the schema notation. This is how we kind of denote a schema. And so writing public dot is the same as not writing it at all. There is a way to show all the schemas. You can do \dn, and this will show you all of the different schemas that are on the database and who is the owner of the schema, because whoever creates the schema, again, is the owner of that schema. So with \dn, we can see that public is our only schema in the super duper database we created, for instance. And we can create different schemas by using the create schema command. If we created the schema sales, then we would see that we would have a schema sales. And I would say pause the video here and go try this out. Go create a schema. Go create multiple schemas and try out the dn command and see what happens. Now, you may be asking yourself, okay, Mo, I get it. Schemas are like these boxes in which I can organize things, but why would I use them? And this is plucked directly from the Postgres docs. But it's important to know, why would I use schemas? And it's to allow many users to use one database without interfering with each other. So interfering with each other, what does that mean? Well, if we only had a public schema and each department, for instance, needed a table that had the exact same name, well, they would interfere with each other because in one schema, you can't have 2 tables with the exact same name. And what are you going to call it? Table 1, table 2, sales _ table? You can do that, but it's not great. Schemas are a better way of optimizing for this. It's also good to organize your database objects in a logical group, and it makes it more manageable. And then the third one and the final one, if you have third-party applications that need certain tables and data and whatnot, you can put them into separate schemas so that they do not collide with the names of other objects. Again, very important. It's about not interfering with the global data, right? If you separate things into schemas, you can have duplicate names. You can have duplicate named objects that are not necessarily the same because they're in a different logical group, but you're still operating on the same database. And so the question becomes, well, why wouldn't I expand to a different database? Well, because maybe you want to make it easy for yourself to be able to query across the multitude of things that are stored in your database. The only reason that you would go off into a completely separate database is if it's for a completely separate purpose that has nothing to do with the data that you have in your current database. So always reach to the things that make it easiest to manage before you go and do something like creating a completely different database, or as I like to call it, a completely different universe, because you're not going to have any of the data from the other database. And so with that, with schemas out of the way, the one thing that I wanted to zoom in on, it's very easy for us to go ahead and like at willy-nilly, create a database. It's very easy. We run the command and, we're hot shots. We can create databases left and right. Super, super easy, straightforward. Well, creating a database is actually a restricted action. Not everyone is allowed to do it. And so what I wanted to do is I wanted to zoom in a bit on permission management, because that's also important when it comes to databases, when it comes to managing databases. Who is allowed to access what? How do we structure those rules? Because, we set up this database world and we're a super user. We're an admin. We have like the Superman logo on our chest. We can do whatever we want, but not everyone is allowed to do it in a bigger company, in a bigger scale. There are rules and permissions. And so let's look at how those work in Postgres. Roles in Postgres. I know it's been a lot of theory so far, and we haven't really zoomed in on anything concrete, on any exercises. But again, I promise you, this foundation is worth it, because the more you understand about all of these concepts, the stronger you are positioned to know what is going on around you. And all these areas you may want to dive deeper into as you go along. You may find something that interests you. So when we talk about roles in Postgres, we're talking about security. And when we talk about security, security is vital. So roles are vital to any DBMS, any database management system. Roles are absolutely vital, because they determine what is allowed, right? When we set up roles, we're basically setting up the functions to which people are allowed or not allowed to do things. So this is a very, very important part of database management. And it's very hard to get right. As with everything, it's very hard to get right, but rightfully is so, because when it comes to roles, when it comes to what's allowed, you have to be very, very careful. You don't want something accidentally going wrong because you gave the wrong rules and permissions. It's a trust-based system. So when we look at roles in Postgres, what a role is, it can be a user or a group. It depends on how the setup is done for that role. So it can be an individual user, or it can be a group in which we put multiple users. That's interesting. So any which way you slice it, a role can either be an individual or a group of individuals. Now, when you think of a role as a term, you think of a group of individuals having a role, because you think of it being something that someone has, right? You think of it as something you give to someone, a role you give to someone. Well, in Postgres, you can basically make it an individual as well. So it can function as a user. It can be a role that's given to only one user. That's interesting. Another thing to note about roles is that roles have the ability to grant membership to another role. So you can give a role to a role, and when that role is given to someone else, they automatically have both of those roles. So roles have the ability to grant membership to another role as well. It's very interesting. So there's the chain of permissions, of which roles can have roles and then give roles to users. And roles can also grant membership to another role. So they're very versatile. Now, are you confused yet? Because it can become very confusing, but in actuality, it's pretty simple. When you look at roles, roles have attributes and privileges. And attributes are basically the same thing as a privilege. Like, attributes define a privilege, but there are privileges that aren't attributes as well. Like, you can have an attribute that says you're a super user, and that could give you the privilege to do whatever you want. But you can give individual privileges to a role that have nothing to do with an attribute, just like super user. Super user is an attribute, and it specifies a couple of privileges. But the individual privilege could be read access, write access to everything. The ability to create databases. Those are privileges. Now, attributes can define privileges. Privileges are linked to attributes, and privileges can be given independently. Let's take a closer look at some of those role attributes. All right, so let's zoom into some of those role attributes. Because when a role is created, it is given certain attributes. The privileges of a role are determined in part by its attributes. It's like I said, when you define a role, there are two different parts to it. There are the attributes and there are the privileges. And some of the attributes of that role can determine some of those privileges. They can say, hey, you can do this and this and this because you have this attribute. But privileges can be more granular than that. You can give specific privileges as well on top of what the attributes give you. So when we look at certain attributes that can be given to a role is, for instance, create DB, no create DB. So you can tell a role whether or not it is allowed to create databases. You can give a role the ability to create a role or not create a role. You can give a role the attribute to log in or not be able to log in. And on top of that, you can give a role the ability to be a super user or not be a super user. So interestingly enough, what you see here is these attributes that we're defining, super user, no super user, create DB, no create DB. In part, we're telling a role, hey, these are some of the attributes that you can have. And, by giving it the attribute, you're also defining a privilege. You're also saying, hey, you're allowed to create a DB or you're not allowed to create a DB. You're a super user, so you're allowed to do everything, or you're not a super user, so you're not allowed to do everything. So attributes that can define privileges. There are a vast array of privileges outside of attributes as well. So when you define a role, there are certain attributes you can give it, and on top of that, you can give it privileges after that are more granular. So common attributes, like we saw, are the login privilege. The ability for a role to log in can be considered the same thing as making a role a database user. There is the attribute of a super user status. A database super user can bypass all permission checks. You basically have the Superman logo on your chest at that point because you have free reign. Then there is the database creation attribute, which is a role must be specifically given the permission to create databases. You don't just get it out of the box. Okay, if you're a super user, good, great for you. Postgres, for instance, the user that we log in with, that's a super user. So it has this by default, this attribute. It is an attribute that must specifically be given to a role. And then there is the attribute of role creation. A role must be explicitly given the permission to create more roles. And then, as the last but not least, there is the attribute password. If you give the attribute login, well, then a password is very significant in that case. Now, there are more attributes to be listed here, but these are the most common attributes. Now, here we go. Creating a role. Well, here we are creating a role. So we're creating a role called read-only, and we're giving it login ability, and we're encrypting the password. Always encrypt the password. Always encrypt the password. Don't ever not encrypt the password, but you have to specifically pass encrypted here. And we're giving it the password read-only. And why encrypt the password is because it'll be encrypted. Just always encrypt the password. So when you encrypt and store a password and give it with login ability, you can now log in with that role. And so what if we wanted to view the roles that are available to us? Well, in that case, we have the \du command. And what that gives us is the ability to see, hey, what is the list of roles and attributes for those roles? And you can see here that we have the read-only that has meager attributes. Now, when you create a role, by default, only the creator of the database or super user has access to its objects. That is pretty interesting. When you create a database, only the creator or the super user has access to its objects. That's important to note here. Anyone else needs to be given access to its objects. We've been very lucky that we're a super user, but by default, only the super user or the creator has access to the objects of that database. So that's important to note here when we're talking about roles and permissions. Now, let's look at creating a user. All right, welcome back. So we've seen a lot of theory around roles and users and all of that good stuff. But we haven't really gone through the motion of creating a user or a role specifically. So let's get back to the practical stuff. And so here you can see I'm in my command prompt and I am not connected to anything yet. There's two things that I want to go through in this video. Creating users, creating roles, but specifically also the authentication portion, because I'm going to show you something cool here. As we saw in our previous videos, when we're connected to a database, we're able to create a role. We could create a role and we could say test role with login, and we could say create with login. We could potentially give it a password, but for now we'll just give it a login. Actually, let's give it an encrypted password. And let's say that it's password. Note that I need these braces around the text of password. So I've created that role. And if I do /du, you can see here that I have test role with login. And we could do the same with create user. We could say test user with login. It's by default going to get with login, but we could say with encrypted password, and we want to encrypt the password. Always want to encrypt the password. And we could say password. And so when we do that and we do /du, we can see test user with login. Now they don't have any specific roles or attributes really. Now this is two ways of creating a role, creating a user, but here is another way. Now if you're not connected to Postgres and you still want to create a user, there is a create user command that is exposed by the binaries of Postgres. And if we do create user -- interactive, what that's going to allow us to do is it's going to ask us a bunch of questions, much more pleasant. So we could say test interactive. Let's just call it that. We're not going to make it a super user. We're not going to allow it to create databases. Let's allow it to create more roles. Sure. And so with that, if we now go back into Postgres, we can see, hey, we created test interactive and it has the create role privilege. Great. But it doesn't have a password. So we could do something as alter role and we could say test interactive and we could say give it with encrypted password. Actually, it already has the login privilege because we used create user. So with encrypted password, and we'll say password as well. And then we altered the role. So this is a way if you want to change a role, you could use alter role and then you can specify the same with to change things. So now we have 3 users that have a login. So what if we do PSQL -u and let's say we use test interactive because it has a password, right? And we said, you know what, connect to the employees database. So what's going to happen here? Well, it stands to reason that we would be prompted for a password, but we're not. Why is that? Well, if we exit out and we did -w, we would force authentication. And if we gave the wrong password, it's still going to go in. That's interesting. So it's not paying attention to passwords. It's not paying attention to any of the encryption that we gave it. When we look at this, we're kind of confused. We're like, hey, what's going on? And this has to do with the configuration of Postgres. The configuration of Postgres by default will trust all default connections. So let's go look at that. So over here, we're in Visual Studio Code. And you can see that we have 2 files open, something called pghbaconf and postgresql.conf. What are these files? Well, the HBAconf specifies how you're allowed to connect. It has everything to do with the authentication. And the PostgreSQL config is the general configuration of PostgreSQL. Now, you may be asking yourself, well, how do I find these files? That's a good question. If we go back over to our command prompt and we said, for instance, show HBA file, it's going to tell us, oh, you must be a super user. So let's quickly exit out and let's PSQL and let's log in with Postgres and let's say show HBA file. And what it's going to tell us is it's going to tell us the path at which the HBA file can be found. For the config file, it's the same thing. So if we set config file, it's going to show us where our Postgres config is. This is how you find where these files are. But what's more important is what is actually in these files. So if we go back over here in the HBA file, which has everything to do with login and interaction, you can see that for the local system, by default, for all databases, for all users, it's going to trust the connection. So everything that has to do with local connections by default is trusted. It's not going to verify a password. It's not even going to ask for a password, really. We need to change this. But what kind of options do we have? And so over here, we're on the Postgres documentation. And we can see that we're on the password authentication page. And why is that? Well, the methods that you can fill in other than trust, which is the default that is set up for local connections, is these authentication types, which also correspond to encryption methodologies. Scram SHA-256 is the most comprehensive one. MD5 is a less secure type of challenge. And then you have password, which sends clear text and is vulnerable to sniffing and all these other things. And this page explains basically how you can go through what you should choose. But by default, you should choose the strongest type of encryption for your authentication. That being said, this authentication type, Scram SHA-256, we use this usually for external connections, other computers that are trying to connect to your database. For local connections, it is typically common to allow the super user that is on the same machine to be able to just automatically connect to whatever database it needs to so that you can do maintenance and so forth. But I always suggest just turn on password authentication because it's better to have to fill in the password than not. It's good to have authentication. Authentication is very important and security is very important. So turning on password authentication is not a bad practice. A lot of people prefer on the local machine not to turn it on. It really depends. And so if we go back over to this file, what we can see here is that everything is set to trust. So if we set everything to Scram SHA-256, and let's just copy that quickly, and we save this file, well, we're going to have to restart our database, first of all. Stop and start it again. Let's look at what that looks like. So we had our test interactive. And what happens now if I don't give -W and I just try to connect? Well, it's going to ask for a password. And we filled in our password as password. Interesting. So the authentication failed for the user test interactive. Now, why is that? Well, in order to be able to have a password that is Scram SHA-256 enabled, we actually need to tell Postgres that it needs to use that as the encryption methodology. Because right now, okay, we created a user with a password, but none of the passwords were actually encrypted, even though we gave the encrypted flag. So you need to tell Postgres, hey, encrypt your passwords with Scram SHA-256. And over here, we're in the Postgres config file, so the main config of Postgres, that's going to tell it, hey, for authentication, use this encryption methodology. By default, it didn't use any, and by default, all the users we created with a password are not available. So let's go back here and let's set this back to trust so that we can actually log in and alter our users. And let's quickly restart our server so that the changes take effect. And if we PSQL -u and we do this, we can do alter user and we can say test interactive. And now we have to do the same thing with password. And let's give it password. And then we've altered that user. So now let's exit and let's turn this back over to Scram HSA-256. Let's restart our server. And what we can see now is that if we try to log in with Test Interactive and we gave it the password, we're in. We're able to go in. So two things happened here. One, the HBA file told us, hey, what kind of authentication methodology should I use? It's going by type of connection, then what database, so by default all, what kind of users, all users, just for all users, use this methodology of logging in. So we got that down. So for all users, for the local connections, the connections that happen on my machine, use an authentication method that requires you to have Scram SHA-256. Now we created users before we set this up. So they were using the default methodology of encryption, which as we saw, it was just turned off. So there was no encryption. So when we turned that on, we had to set it to the encryption method that corresponds to the method of connection. Okay, interesting. But that didn't fix it, right? Because when we turned that on and we turned the other thing on, Well, the users that we had created passwords with, they didn't have any encryption type. Even though we used the encrypted keyword at that time, they were not encrypted. So now the encryption is by default. I can just say with password, and it's going to create that user with that encryption key. So now what happens is when I altered that user, their password is being encrypted with the right encryption methodology. It's always good to send the encrypted keyword with it, but for this intent and purpose, it encrypted the password correctly. And when we logged in, we were able to log in because the password was encrypted correctly and could be decrypted correctly. But now, as we see, if we were to want to log in with Postgres, well, what's the password? Well, it was Postgres, but the authentication failed. So interestingly enough, what a lot of people tend to do is they tend to say, hey, okay, for local all, not the user all, for the user Postgres, which is our default user, our super user, let's just trust them. And so if you stop and start this, now I can just log in with Postgres. This is a type of configuration that you may find. For local machines, I would suggest, okay, allow Postgres user to be trusted, but all other users should still log in. It's important to log in. Why not log in? If you have the password, why not log in? But that being said, these are all only for the local connections. And so for external connections as well, we need to probably go in here and set up what kind of methodologies external connections are allowed to have. And if you're connecting to the host, so this is connecting to the host. If you connect to the actual IP address, well, it's going to authenticate through the encryption. So all of this has to do with the configuration of authentication. So how do you log in? And a lot of this is nitty-gritty type of stuff. It goes very deep into database management, and it goes very deep into authentication methodologies and setup and configuration. And you can see how all of this becomes very, very, very specific. It's all management type of stuff. We're not really touching SQL. We're touching configuration. We're touching the way that things are set up and the way that Postgres is configured. I thought it would be important for you to, first of all, kind of have an insight into this and know how authentication works and what all goes into it, but it's not the main focus. Knowing these files is important. There is configuration behind Postgres, this whole world of setup and configuration that you can go through to tell Postgres, hey, do this, do that, more granularly only allow secure connections and all of this other stuff that goes into network and database management. And so knowing about these files is important when you're trying to maybe set up your own production Postgres database. So keep in mind that these files control the configuration of Postgres. That being said, creating users and determining roles and how you're going to set up the world around your users, that is extremely difficult. Defining roles and defining who to give roles to, that is a whole other plethora of management on its own, because you really have to think deeply about what's going to be given to whom. Now let's look at some of the more granular privileges that can be given to users. All right, so in the previous video, we saw a lot of information related to creating users, logging in with a password, and all of that good stuff. Now, all of that is pretty heavy, right? And all of that really is tangentially related to SQL and writing queries. But it's important to know what is behind Postgres, right? Like, what is behind that iron curtain, and how do you configure Postgres? This course isn't meant to make you database administrators or configurators, but it's important to know what files are available to you and where to look when trying to configure a Postgres database for production. And so when we look at something like privileges, we just showed you that the login attribute and the password attribute give you the privileges of logging in and being able to authenticate. But that authentication isn't by default. You need the HBA file and you need the config file. Now, from that, we can see, okay, attributes give you privileges, but attributes can only give you so many privileges, right? We only saw a subset of the attributes, and what those attributes told us is, hey, you can log in, you can be a super user, you can do this or that, and those attributes define some type of privilege. But when you are not a super user, what you can do is fairly limited. Like when we saw the interactive creation of a user, what we saw there is there was a limited subset of attributes that it was telling us to choose from. Can you create new roles? Can you create new databases? Are you a super user? So those attributes that we saw, they only define a small subset of privileges. And it really depends on what default privileges are set, what you can do as a user. So if you're not a super user, what you can do is fairly limited. By default, objects, so tables and all that other stuff, are only available to the one who creates them. So the user that creates the table, the objects, and all of the stuff in a database, well, that user, that individual, is the only one who has access to those objects. And that is interesting. So how do we give the privileges to users that are created but aren't super users? Privileges needed to be granted for roles and users to have access to certain data, right? So we're used to working with a super user, but let's say you wanted to create 2-3 more users. You wanted to create a user for a backend system or a user for something else that has a login privilege and only has access to certain data on the database. Well, now we have to grant them privileges on certain tables. We have to tell them, hey, you can access these objects. And so by giving those privileges away, well, how do you do that? Because we've only seen how to give attributes to users when we create them. Well, granting privileges is the following command. You can do something like grant all privileges on a table to a user. You could also go ahead and if you have multiple schemas, you can say grant all on all tables in a schema to a user. So here we're granting all privileges on all tables, so that all privileges being, okay, the ability to write, the ability to read, the ability to update, the ability to delete. And we're saying on all tables. So you can also grant it on specific tables, or you can grant it on all tables. You can grant it on all tables in a specific schema, or you can grant more granular privileges. You could grant select, update, insert. You can grant specific abilities to a user. Be wise about the privileges you grant, because the privileges you grant determine what a user is able to do. Let's take a look at granting privileges. Let's take a look at some of the things that we can do. All right, so we're about to grant some privileges to a user. And before we do that, it is extremely important that we put back our method to trust, because it's going to be irritating when we're trying to go through the course to always have to log in, unless you want to leave it that way. But if you put the methods back to trust, you won't have to authenticate the whole time. So over here, I'm back in command line. And what we're going to do is we're going to create a user. And we're going to do it the interactive way. And we're going to call it privilege test. So that's the user we're going to create. We're not going to make it a super user. It's not going to be allowed to create databases. It's not going to be allowed to create roles. That's just what it's going to be defined as. And then we're going to log into Postgres user on employees database. And in another command prompt, what we're going to do is we're going to log in as privilege test onto the employees database. Always use coninfo to make sure that you're logged in correctly and all that stuff is right and that you're on the right user. So let's do a select star. Actually, let's look at what tables are here. So let's do a select star from titles. And what we can see is we don't have permission for the table titles. Interestingly enough, only the owner has access, or super users. So that's something we need to fix here, because privilege test is a new user we created and we want to give it access. So if we go over here and we do coninfo, what we're going to see is we're logged in as Postgres, which is a super user. So if we DT, we'll see the exact same thing. And if we select star from titles, what we're going to see is that we'll get access to the data. Now, a super user can grant roles to other users by default. You can create a user that can grant other roles as well. But what we want to do is we want to grant select. Let's give privilege test select privileges on, and let's see. So we want to grant select on titles, and let's give that to privilege test. So we've granted select privileges to privilege test on the table. So if we go back over here now, and we did the same select, what we're going to see is that we're able to select now. That's great. So we've granted a privilege. For the same reason, we could also revoke select on titles from privilege test. and that will revoke his privilege to select from titles. Very straightforward, very simple. You can grant and revoke privileges. But what if you wanted to grant everything? We don't want to like grant select, comma, update. Well, you could say grant all on all tables. So you can select, update, delete, all that good stuff. So we're going to grant all on all tables. And if we do this, we have to say in what schema. So we have to say in the schema public, because it depends on what schema you're in. You can't just give access to everything. So you always have to specify the schema if you're going to grant all on all tables. And we're going to give that to privilege test. Now, before we execute this, let's just confirm can't select from titles. And if we grant this, can select from titles. Mainly what we're trying to show you here is that when you grant and revoke and do whatever with privileges, it's pretty instantaneous, but also you can be very granular in the way that you add and remove. Like we could create specific roles, like we could say create role. Let's revoke the privileges. So let's revoke all. I had to revoke somewhere here. Revoke all privileges on all tables in the schema public from privilege test. So let's remove everything and let's create a role. Create role, and let's say that it is employee read. That's what it's going to be. And we're not going to give it anything else. It's just going to be employee read. And what we're going to say is grant select on all tables in schema public to employee read. But we don't want to grant all. We don't want to grant all the privileges. We only want to grant select because the only thing employee read is allowed to do is read. So we granted it to employee read. And so now that we've created that role, employee read, and we've granted it the ability to read from that table, we can see over here that we're still not able to select from the table, but we can grant a role. So we can grant employee read to, and we can say privilege test. And by granting that role, what we're able to do now is we're able to select. And we could just as easily revoke that role, employee read, from privilege test. And we've revoked the role, and now you're not able to select again. So you can create roles that have specific granular options of what they're allowed to do in a certain database and what they're allowed to read from or update from. You could grant those roles to specific users. And that way, a user is a combination of multiple roles that have multiple granular privileges so that you don't have to go in and grant specific privileges all the time. No, there is a specific subset of roles that have that privilege, and you just have to give that role to someone. And so when it comes to role management, user management, privilege management, it's always important to give the least access possible. Start off with no access at all and really granularly look at what you're supposed to grant and revoke. And that way you have total control. How do you structure your role management and what not to do? Follow the principle of least privilege. Start off with nothing and start building upon that and defining roles that have specific privileges and granting those roles to specific users, and have consistency. Consistency is key. Consistency in the naming convention of your roles, consistency in the naming convention of your users. And that way you'll be able to manage your Postgres more properly. So let's go look at some of those best practices. Best practices. We've seen a lot so far when it comes to roles and privileges and the management of it all. But what are the best practices? How do we go about managing this in a proper way? And as I've said throughout this portion, all of what I've shown you here is not super related to all of the things that we've been doing so far. It doesn't make you better at writing SQL queries, and it doesn't make you better at managing that data. But what it does give you is that foundation of knowledge around how databases work, and if you were to go and manage your own database, how you could go about it. And that is what's most important. And when managing roles and permissions, it's important to know the best practices, because the best practices are what give you the ability to manage your database in a way that is maintainable. And so with that, I wanted to go through some of the best practices, which I've mentioned in the previous video. Now, the point here isn't to make you a database administrator, but it is to give you that solid foundation and knowledge to go ahead and look at these things and become better at these things as you go along. If you wanted to manage your own database, if you wanted to create it, security is important. Security is vital. And just having a root user, just having that Postgres user, just having that super user, well, that isn't really managing roles in a proper way. That's just giving full access, keys to the castle type of stuff. We don't want that. We want you to know how to manage roles and permissions. And so always, always, always go with the principle of least privilege. Now, the principle of least privilege says, give no privileges at all, and then start layering them. Don't start off with super users and then revoke privileges, or not that you could, but don't start with users that have all of the privileges and then remove privileges. No, start with no privileges at all and start layering them like a cake. The principle of least privilege says, you have no privileges until someone gives you them. You have to be given the privilege to do something. And with that, you have total control, because when you create new users, well, they're not allowed to do anything. And then you start giving them access to certain portions, and they have to continuously ask for access. Now, some of you may say, well, this is not favorable. I don't want to constantly be going back and forth, but it's how you gain the ability to control access strictly, because we're talking about data here. We're talking about things that make the company tick. You have to be extremely cautious with data. You can't just go willy-nilly. And, when we were looking at role management, well, we had these attributes, the ability to give super user, the ability to grant roles, the ability to log in and all these things, and they gave certain privileges. But then when we looked at the more granular privileges, we saw, hey, not everything is immediately accessible unless you're the owner of this data or a super user. So we have to go in and grant more specific privileges. And the way we could do that is we could create roles that have those specific privileges, the ability to select, the ability to update, the ability to delete on certain parts. And we can go split those into specific roles. We could create an employee read, an employee update, an employee delete, and we could grant those specific roles to users. And that would be a way to manage. But there are also other ways to manage. But the point here being is you want your privileges to be as granular as possible so that you can add and remove privileges as you go along, because you don't want a user or multiple users to just have the keys to the castle. That's not a best practice when it comes to security, when it comes to protecting your data and protecting the ability for malicious intent, but also maybe stupidity. Someone may do something that they didn't mean to do, and because of that, suddenly a lot of data is deleted. You want to be very careful with the permissions and privileges that you grant. You want to be very careful. And another best practice when it comes to the role in user management is don't use your admin super user by default. There is someone in the company that will be the admin and the super user. And they have the keys to the castle, and they should be trusted in this way to be the admin and the super user. But don't give it away by default. Give users specific accounts and give them specific permissions. That way you have control. Control is key when it comes to user and role management. Keep that in mind. Let's talk data types. So far throughout the course, we've done a lot with data. We've done a lot with data. We've written so many queries, we've seen so many examples, but we haven't really gone deep on what these different types of data are. Before we create a full-fledged database, it's important that we know what types of data we can store in the database, because when we were writing queries, it was self-explanatory. The data was already there, the configuration was already there. But now that we're going to create our own database and our own tables, I think it's important to zoom out and then zoom in specifically on data types, because now we have to make decisions. And those decisions dictate how the rest of your data is going to look like. You are in control. You are the one making the decisions now. What am I going to store? How am I going to store it? What is it going to look like? And to do that, you need to know what's available to you. We've seen some data types that we can store throughout the course. We've looked at date and time. We've looked at Boolean, but we haven't had a comprehensive list so far. We haven't really kind of focused. When we talk about data types, we're talking about the types of data that we can store. Mo, that sentence is very confusing. I know. We're talking about types of data. And the best way we can describe this is kind of like buckets. In each bucket, we can store a specific type. When we looked at date and time, we're looking at a specific type of data. You can only store a date in there. Month, day, year, and time. And so the reason that a database categorizes it by types is so that it can put constraints on that data type. You're only allowed to store it like this. Now, why data types? Well, let's say that we were in the Wild West and everything was text. Well, how are you going to enforce that only a specific type of information can go in there? Are you going to trust the system that's inputting the data? Well, that's bad practice. You kind of want data integrity. You want your data to be of a certain type. So Postgres ships with certain types. And the data types in Postgres are categorized in these buckets. We can store numbers. We can store boxes of data, multiple pieces of data inside of a single box. We can store text. We can store date and time. We can store true or false, Booleans, or UUID types, which is unique identifiers, completely random pieces of data that are completely unique. And there are many, many more types, and you can go look at the Postgres docs if you want, and they'll kind of show you, hey, there are so many more types. We have geometric types to store geometric shapes. We can store network addresses, bits, XML, JSON, all these types, weird types that you may not have heard of, but it can store so many different types of shapes. And so what we're going to zoom in on and focus on is the core types that are used the most. And the reason that we're doing that is because these core types are the ones that you will use the most. When you go towards the complex end of typing, you're looking at storing very specific types of data, and you can always reach back to the docs to see what can I actually store here. And it's important to always read the docs because they can alleviate some of the questions you may have. They can show you ways to do things that you may not have thought possible. When you come from a different DBMS provider, they may not have a UUID type specifically. They may not have arrays. They may not have these things. Older databases didn't store, for instance, arrays or boxes of data. They may not have had a UUID type specifically for unique identifiers. And their date and time types may be completely different. So it's important when you look at data types that you go not specifically off of what Postgres offers, but you go look at the docs based on what your DBMS provider allows you to store. And it's important that you go deep into that because you need to understand what you can store and what the best practices are to know how to store something in that database. And so when we look at a data type is nothing more than a constraint placed on a field to allow only that type of data to be filled in. So just like we looked at date and time, the date and time field is nothing more than a constraint. We're constraining what's allowed to be filled in there, a date and a time, or text, or a number. We're saying, hey, only store this. And specifying a type is important because it tells the system how it can and should handle that data in that field. It's important for the system to know, hey, I'm storing text here, or I'm storing a date and time here, or I'm storing a Boolean here, true, false. Why should it know this? Because as the system has more information about what that data field is, it can be smarter about how it handles it. When we looked at indexes, well, when you index a type, the system needs to know what type of data is there so that it can be smart with that indexing strategy. The more information you give the system, the more the system can be smart with your data. So data types are extremely important for Postgres. If we just stored everything in plain text, well, we might as well use something like Excel. It is also important that it allows us to optimize our algorithms for processing the data by knowing its type. Like I said, the more information you give the system, the more the system can give back to you as long as it has that feature set. That being said, data types are constraints on the data, so keep that in mind. Now, the first data type we're going to look at is Boolean, true, false. And we saw this in the 3-type value when we were looking at null values. A Boolean type can be true, false, or null in Postgres. Null is a valid value for Boolean. So true, null, or false. It can also do smart conversions. So when we look at this data type, well, it's true, null, or false. But when we fill it into Postgres, Postgres will accept different types of values in this field. So you don't necessarily have to say true or false. You could fill in 1 or 0, which correspond to true or false, yes or no. Y or F, true or false. And what Postgres is going to do behind the scenes is it's going to understand that this value maps to a certain conversion, and that is going to be true. And then when you request the data, it will return back the original value to you. So Boolean fields are smarter than just true or false. Postgres has gone ahead and made these smarter values. So Boolean type is true or false, and this can be used for many different applications. For instance, if you want to subscribe to marketing for a company, you could store that in a Boolean field, true or false, and that would tell the system, hey, I can send marketing emails to this person. Many different types of fields that you could choose a Boolean value for. The next value type we're going to look at is character. So let's zoom into that. The character type, also known as text. We're just storing text here. Postgres provides us 3 types of character data types. And so the reason we're looking at these from a theoretical perspective is because when it comes to actually creating the database and creating the data types, it's nothing more than just specifying a type, but it's important to understand what this type can hold. And so when we look at Postgres, what it provides us is something called character. And character is nothing more than something that will hold text. And the 3 types that Postgres provides us are char, and then over here you see this weird notation that is parentheses, parentheses, n. And this denotes a length. So you can say store characters of a specific length. So you could say store of 10. Then you have variable character of type n. And then you have text. All right, so what are the differences between these? For instance, what is the difference between char and varchar? And what is the difference with text? Well, let's look at that. When we have char n, we're specifying a fixed length of characters with space padding. With space padding, what do you mean? Well, let's just look at it this way. If I had said something is char 10, and then I said, well, what I'm going to fill into this value is Mo, which is my name. What Postgres is going to do is it's going to say, okay, Mo is of 2, but char is of 10. So because I only have 2 characters in here, I'm going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. It's going to put 8 spaces because the character length is 10, Mo is of length 2, so I have to pad that with 10 spaces. So what char n does is it's always going to fill in that entire space, whether or not you decide to fill it completely. It's going to fill it with space padding. So it's going to pad the value with extra spaces. Now, if you go over that amount, it's going to throw an error because you're only allowed to fill in, for instance, 10 characters. Now, when we look at, for instance, varchar n, well, that's going to be variable length. So it's not going to pad at all. If I fill in Mo, Mo is the value it's going to store. It's not going to pad the value with extra spaces. Now, you can immediately see the difference here. This is going to be space saving because it's not going to store those additional characters behind the scenes to pad the value. It's very, very useful. And then you have text. And what text does is unlimited text length. So you can store an infinite amount range of text in there. Now, why would you not always choose text over varchar and char? Well, sometimes you want to put that constraint on. You don't want to allow an infinite amount of text in a certain field because that's just going to mess with your storage. So you want to limit the amount that can be filled in. Just like when you look at Twitter, they limit the amount of characters you can fill in. They're not going to store it in a text field. That would be stupid because now they have a data type that could support an infinite length, but they're limiting your character set. And so over here, I'm on DB Fiddle. And as you can see, I have some syntax here to create a table and insert some data into the table. And all of the specific syntax we're going to look at as we go along throughout this section of the course. But what you can see here is that I'm creating a table called test text, and I'm putting in a fixed char, a variable varchar with a length of 20, and an unlimited. And then inside of it, I'm inserting mo, and I have unlimited space. And when we look at it, it's filling in just fine. But what if we were to go over the 4 characters, mo? Well, now we're going to get an error. Too long for character 4. Okay, so we can fill in 3 characters, and here we can fill in 20. So mo. Now let's just keep going. Let's keep going. We may be over 20 here, and variable too long for varying 20. Okay, so we can see here that there is a constraint placed on the length. So this can only contain 4, and this can only contain up to 20. Now the main difference between these two is the space padding. So this will automatically always fill in the 4 characters. It's always going to take in the exact same amount of space, and this is only going to take in the amount of characters that you're going to store. So there's a space saving feature. And then over here we have unlimited text. So in this field, I can store an unlimited length text. I could copy this 1,000 times. It doesn't really matter. It's going to store it, and it's not going to complain about the length. So knowing that and knowing about the features of the different types of text we can store and the limitations we can place and kind of the pros and cons of them, let's go look at how we can store numeric data types. Numeric data types. So far we've looked at Boolean values and storing text. But when we store numbers, we talk about numeric values. And there are 2 types of numeric values in Postgres. 2 types of numbers that you can store. One is called integers, and the other is called floating points. And I hear you saying, what is the difference between these? Like, what are these? Well, integers are a whole number, a number that is not a fraction, a number that doesn't have anything beyond the comma. It's not 1.2. It's a whole number. It's 1, 2, 3, 4, 5, 6. It's 126. It's 1,000. It's nothing that contains a fraction. It's nothing that contains anything beyond the comma from math. And when we look at it, a whole number is a number that is not a fraction. Okay, we're saying the same thing twice. I know. There are 3 types of integers in Postgres. There is something called small int, something called int for integer. These are shorthands: small integer, integer, and big integer. What's the difference between these? Well, a small integer, is a number that can range from negative 32,768 to positive 32,767. Any number within that range. That's a pretty big number. You'd be surprised how fast you could potentially go over that number, but still, it's a pretty decent sized number. And then when you look at int, an integer, to type, and when you look at the type integer, it's a number that can range from negative 2 million to positive 2 million. That's massive. That's a very, very big number. And then when you look at big int, it goes all the way from 922 billion or something like that, all the way to positive 922 billion. It's a massive, massive number. That's what we need to know. But why store 3 different types of numbers? Why, Mo? Why not just keep big int and store everything as big int? It takes up more space, and we're trying to save space. We don't want to unnecessarily store large types of data and allocate large pieces of space to be able to store a number this big. No. In most cases, we may only need a small integer. In some cases, we may need a big integer. It really depends on the use case. So given that variety, everyone likes a bit of variety, right? Like, it's nice to have. So knowing that, having 3 different types of integers to choose from is just useful to you as a user. And they can store pretty much any variety of number. Now, make sure you do pick the right size. You don't want to be migrating to a different type, maybe a pain. And then the other type of number we can store is floating point. And floating point is a type of number that does contain a fraction. It's simply put numbers that can contain a decimal point, kind of like pi, or what we see here, 3.17. It's a number that contains a bunch beyond the decimal point. And when we look at numbers that can contain beyond the decimal point, it is important to know that you can store any number with a specific range beyond the decimal point. And so when we look at that, when we look at floating point, there are 2 different types of floating point. We have float 4 and float 8. So this is single and double precision, meaning that you can have 6 or 15 digits of precision. So what do I mean by single or double precision? Well, by single or double precision, I'm meaning that there are 6 or 15 digits of precision when you use the type float4 or float8. So you can go with float4 up to 6 digits past the dot. So you can do 3 dot and then 6 digits. Or if you use float8, you can do 3 dot and then 15 digits. So those are two of the floating point numbers. And then the other one you have is called decimal or numeric. And that has up to 131,000 digits before the decimal point and up to 16,383 digits after the decimal point. So it's a big number that can contain a big decimal point precision. It's way bigger than float4 or float8. It's kind of like the big int of floating point, so to speak. So let's look at what that looks like. So over here, I'm in dbfiddle, and I repurposed the original test text. But what I put in there was a float4, a float8, and a decimal. And this is just to illustrate what exactly happens when you fill in a value into one of these. And so over here, we can see that we're inserting a value into float4, a value into float8, and a value into decimal. And let's see what happens here when we select from. Well, we can see here that we're having 1.1234568. Okay. Well, it went 3, 6, and then the 7th character, it rounded up. Interesting. So it has a precision of 7. 0 to 6, 7. And then over here, it's 3, 4, 5, 6. So that's 6. 7, 8, 9, that's 9. 10, 11, 12, 13, 14, 15, 16. Interestingly enough, when we talk about the precision, what we're trying to say here is that it is precise up to the 6th character, and it is precise here up until the 15th character. And then it'll store a 16th character, in this case a 7th character, which it will take the rest of what comes behind and round it up. So you can see here, we're storing a way larger number than a 15-point precision. So it's going to go all the way up to 16, and it's going to round it up. And over here, it's going to go up to 6 precision. So when we say precision, we're saying this is where it ends its precision. This is where it loses, where it's precise. And then the following number is not going to be precise anymore. No, it's going to be a rounded up version of anything that came behind. And if we look at that, well, if we took this number and we stored it in both fields of float8 and float16, we're going to see that the precision is what counts. So it's cutting off the number, and here it's cutting off the number as well. And over here in the decimal, well, it's storing the whole thing. So that's the interesting thing when you look at floating point. When you look at a float4 versus a float8 versus a decimal, it's important to pick the right one so that you have the right precision. And looking at the precision of 4 versus 8, you can see where the precision falls off. One of the last and most important data types we're going to look at is arrays. Now, we've looked at date and time in the previous videos, and you can reach back to that to refamiliarize yourself with that data type. But arrays is a new data type. It's something we haven't seen before, and it's something we haven't seen in any of our databases so far. And what an array is it is nothing more than a group of elements of the same type. So it's a group of elements. So far, throughout the course, we've only seen fields that store one specific type of data, a number, a piece of text, so forth, so forward, and date and time, and all of these other things. So we've only seen one type being stored, but this is a group of elements of the same type. An array is denoted by a bracket syntax. So when we look at arrays, it's like boxes of the same data. We can store multiple pieces of the same data inside of that box. And we denote it by a bracket syntax. What do I mean by denoting it by a bracket syntax? Well, if we look at a phone number, if we were to store this, we would probably store it in a text field, and we would store one phone number. But if we were to store multiple phone numbers, well, here's the bracket syntax that we were talking about. And it's denoted by a comma on each line. So each individual line is a new phone number. So you can store multiple phone numbers by having an array of type text. Every data type in Postgres gets an array equivalent. You can store any data type as an array. Float 4, float 8, text, small int, char, varchar, every type has an array equivalent. So let's look at that. So over here, we're in dbfiddle, and we've repurposed the test text again, and we've changed the type. So for 4, we chose a char2 array. For 8, we chose text array. And for big, we chose float 4 array. So we have 3 array types here. One is of type text that can contain 2 characters at a time. One is of type text that can contain an infinite amount of characters, and they're all arrays. So they can all contain multiple values. And as you can see here, when we insert into test text, we're denoting everything we're inserting with an array syntax. So we're specifying, hey, this is an array. And we're specifying the bracket syntax, and then we're telling it, hey, store a value of this type, and then insert these values into that type. And so here we can see that we're inserting into char2. And let's say we didn't follow the rules and we did this. Well, we're going to get an error because the value is too long for character 2. So it is indeed inserting with the correct constraints. And in 8, we can store text arrays. So we can store multiple values of text that can have any length. And then for big, we're storing a float 4 array. So what we can see here is we've stored values that correspond to a float 4, and then we stored one larger float that will be cut off. And as you can see here, it is being cut off at the 344 length. So it is denoted by a fixed amount of value that can go past the decimal point. And so with that, what we can see here is that with the array notation, we can just store multiple values in a single field. This is extremely powerful, and this is extremely useful because now we are not constrained by only being able to store one piece of data in a field. We can store multiple pieces of data in a field. Now, they're slightly harder to work with, but arrays can be extremely useful when you need to store a lot of information in one field and varying information in one field. And so with that, we've seen pretty much all of the data types that are most commonly used. As I said, there are many, many more data types that you can sink your teeth into, and there are many use cases for those data types, but we really wanted to give you that foundation of data types that can help you build pretty much most data models. And so with that, let's look at creating tables. In one of our previous videos, we created our database, ZTM. All that was left to do was put data in it, right? And you're right. All that's left to do is put data in it. And we went on a tangent that kind of focused on roles and permissions and data types, and we steered away from the core of practicality, but it is to give you that foundation of knowledge that you need before you dig too deeply into all of these commands and things that you can do. And the reason for that is, well, we could teach you all of these commands and we could show you how to create things, but it doesn't really bode well for a foundation. So we wanted to really hone in on that theoretical side and kind of give that base. And then from there, we can go ahead and create a bunch of data. Now, I promise we have to hold up for a second. And we have to think about, what do we put in? Because I said in the previous video, well, let's go ahead and create some tables. But hold up. What are we going to create? What kind of table are we going to create? What are we trying to do here, right? We have a database, but now that we have a database, what are we going to do with it? That takes some forethought, right? You need to think about it. You need to create maybe a model of some sort, and you would be right. We would have to create something called a database model. Usually before we create a database, before we get into the nitty-gritty of the practicality, we usually end up creating a model. What's a model? What does that do for us? Can I just go in and hack my way through creating tables and creating all of this crazy stuff and just figure it out as I go along and change things? You could. You definitely could. But a model would help you think ahead up front and not have to make as many changes as you go along. A little bit of thinking ahead will take you way farther. And so what I mean by that is a model is a design that is used to visualize what we are going to build. And that is extremely important. We want to know what we're going to build before we build it, because if we don't put a little bit of thought into it, things are going to change and shift so often. Your database is going to be a moving target, and all of the software that may potentially be built against it, or all of the queries you write against it, they're continuously going to have to change. So we're going to have to think about it before we build it. This is what we would call an entity relationship diagram. It denotes what exactly we are going to build. Now, what do I mean by entity relationship diagram? Well, if we look at what we're trying to build, we're trying to build a zero to mastery database, which is going to contain courses. And we're going to store courses, we're going to store course information, and we're basically, in a very basic way, going to build that system. And an entity relationship diagram is what we would use to create that model. That is what we use to create a model. And it denotes entities. What is an entity? Well, an entity is nothing more than something that says what something is, right? When we look at storing, for instance, courses, we know that one of the entities we want to store is a course. We know that we're talking about courses. And so when we start thinking about this, we start thinking about modeling a database. And when we model a database, we have to define the entities that we want to store. An entity is a thing that we want to store. When we define that thing, we have to define what we want to store for that thing. So for a course, what we would want to store is a name, a description, a subject, and then we would want to store some feedback, for instance. That's what we would want to store for a course. And then, well, when we think about it, well, a course also has a subject. So we're going to have to store subjects for a course. You know, it may be IT related, it may be business related, it may have a different thing. And so when we think about subjects, we think about subjects as entities. And then, well, we need students. We need students to follow the course. So we'll have students, and students can be enrolled in a bunch of courses. Getting to this diagram is a whole different set of skills. It's an architecture skill. It's a skill that you will need in order to build out a diagram. It has less to do with actual SQL and more to do with conceptual thinking. And so when we look at this, you may be thinking, well, Mo, like, okay, you created this diagram, but how am I going to create one? And so we'll have an entire section on how to build up a diagram like this and what mental models you'll need to follow in order to be able to think about this more granularly. Basically, what we're trying to show you here is that there are ways to think about how to build a database. There are structures in place and ways of defining a way to formulate what a database should look like before you go ahead and create all the tables and all this stuff. Diagrams and architecture is vital to specifying what your database is going to look like and how it's going to be sound, how it's going to be something that, you know, can withstand different changes. And when we look at this, when we look at, for instance, our entity relationship diagram, well, what we know is that we have primary keys and foreign keys. This is something we've seen. And what primary keys and foreign keys have in common is they say when something's unique, but they also say when a relationship is being formed, right? And what we see over here in this diagram is we have all of our entities: enrollment, student, course, subject, teacher, but we also have these weird lines here. And these weird lines are what we call crow's feet notation. And crow's feet notation is nothing more than trying to tell you what kind of relationship is being formed. Like if we look at student and enrollment, how do we read this? Did you randomly draw this line? No, I didn't randomly draw this line, I promise. What we did here is we decided to say, hey, one student can have 0 or more enrollments. So this denotes 1. So one student can have 0, that's why the circle is here, or more enrollments. And if we look at this, one course belongs to 1 or more enrollments, but an enrollment can only belong to one course. One specific enrollment can belong to one course. You can be enrolled as a student into multiple courses, but the enrollment itself can only belong to one course. You can be enrolled into multiple courses, but the concept of an enrollment can only belong to one specific course. So when a student enrolls into a course, a student is enrolling into a specific course, not multiple courses at the same time. A student can still have multiple enrollments and have multiple courses that he or she is enrolled into. But when we denote it like this, what we're trying to say is we're trying to map that relational model that we talked about way back in the beginning. This is how we get towards defining that relational model. And there are specific rules that you need to follow in order to build a diagram that follows that relational model. Now, with that said, what is important here and what is most important here is not to understand how to build up a diagram like this, but it is to understand the necessity of a diagram like this. A diagram like this, the architecture up front, makes it so that you can build a coherent database. And it's not to say that this database is the most spectacular database or it couldn't be made better. No, we're trying to give a good baseline here and explain a concept that is absolutely necessary when building out a database. Now, we've seen a lot of different sample databases so far, right? Lots and lots of sample databases. We have our employees database, we have our world database, we have all of these databases that we've been doing exercises against. And a lot of them do not follow the best practices. And when we look at when we're going to do this, when we're going to create a database, when we are going to create a data shape, we're going to try to follow as many of the best practices as possible. Now that we're modeling our own database, it's important to follow the common standards. We want to follow those common standards because we want to build something that when other people come in and look at, they're like, okay, yeah, this looks good. Everyone will always have an opinion, but when you follow common standards, it's much easier for other people to be able to come in and understand what's going on. And so let's talk about naming conventions. When we talk about naming conventions, when we talk about, for instance, table names, and when it comes to naming things in software is the hardest problem. It is. Different programming languages and different technologies have different conventions. Well, when it comes to table names must be singular. This is a common convention, and there are a lot of different rules for this, theoretical rules, database rules that come into play, and it's good to follow this common practice. We don't want to name our table students, because when we store data in that table, we're always storing one single student. When we talk about table names being singular, it's because when we read the relationship, we can read it in that way. Table names being singular is just a common practice. And then when we talk about naming conventions, columns must be lowercase with underscores. So when we name columns, a common convention in Postgres and other database languages is because it's case insensitive. You can store uppercase, lowercase. Storing columns in lowercase with underscores is a common practice so that you don't have to use, for instance, the quotation marks. You can just underscore, 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 and everything is easily accessible. So storing column names with lowercase and underscore is a common practice. Columns with mixed case are acceptable. You could do student and then ID with uppercase. They're acceptable. Columns with uppercase, unacceptable. Just a common convention, don't do columns with uppercase. You know, all these rules that I just told you, they're common practice, but at the end of the day, just be consistent and write down your rules. Those are the best practices I can give you. Let's create some data. Now, I promise you, up until now, we've been all over the place. We've done some commands, but we haven't really created anything other than our database. We've played around with some roles and rules and permissions, but now what we're going to do, now that we know what our model looks like and what the rules are going to be that we're going to follow, well, we can finally create a table. We can finally put something in that database that previously was just empty. Here is our data model. And if you look at our data model, what I've done is I've highlighted student right here. And student can belong to one or more enrollments, to 0 or more enrollments more precisely. A student can be enrolled in nothing as well. So one student can belong to 0 or more enrollments. And an enrollment can only belong to one course. But why did I highlight student? Because it's the first table we're going to create. Now that we have a model Now that we have something to base what we're going to build off, now we can actually make something. And we can see here that we have student ID, first name, last name, email, date of birth. And here I've chosen not to follow the underscore underscore syntax. And so what you might immediately see is that I've chosen to ignore some of the best practices I just gave you. Interesting, right? All of my names are singular: an enrollment, a student, a course, a subject, a teacher, feedback. But when it came to naming my columns, I didn't really follow the rule that we set out. And so what are we going to do about that? Well, we're going to change this. So the way this should actually look is like this. And so over here, what we see is that I've named or renamed all of my columns to follow a consistent, proper naming convention. There is no confusion here over what something is or how I should name it. And over here, you see a custom data type that we'll be making later. But for now, let's focus on student. So we've renamed everything to be proper according to some of the best practices that you could follow. And so now the question becomes, well, how do I create a table? Like, what are all the options that go into it? What can I do here? And we've seen create table syntax here and there throughout some of the exercises that we've done, but we really haven't zoomed in on it. And so when we look at create table is simple, right? It's create table, you give it a name, and then you open the parentheses here, and you give it columns with a type, and optionally you can give it a constraint. You can constrain what that data is. And we've looked at constraints. Something can't be null. It has to have a value. That's, for instance, a good constraint. Something has to be a primary key. That's a constraint. A foreign key. That's a constraint. Many constraints that we can follow here. And optionally, you can make it inherit a different table so that it gets some of the columns and properties that are already set up in those tables. It's pretty simple, right? Pretty straightforward. So let's look at what a create statement would look for the student table. And so over here, we see the student table. And we see everything that has to do with creating that table. So we create the table and we name it student. Now we could have uppercase s this, but then again, case sensitivity and all that stuff. So let's stick with lowercase. We're calling it student. And then we have our student ID, which is of type UUID, which is a unique universal identifier. We're setting it as the primary key as a constraint, and we're giving it a default value, something else you can do. You can also give something a default value, and we're saying, hey, by default, generate a unique identifier, because I don't want to fill it in. I may potentially be able to, but let Postgres decide what value goes in here, because it's just a unique ID. So why doesn't Postgres just generate this for me? Give it that default value. And then for first name, we're saying it's a variable character of 255. We don't want names over 255 characters. That's just a waste of space. You could limit this even more if you wanted to. We're saying the last name is exactly the same. Both of them have a constraint of not null. And we have email over here, which is variable character of 255, also not null. We could go further on email and we could place a constraint that says that it needs to follow a particular pattern, for instance, or we could offload that onto the API, the server or the software that's trying to fill something into your database to follow those rules. If it's a person filling in, you may want to put in some constraint here, potentially. But for email right now, we've chosen variable character 255, not null. For date of birth, we've chosen date, and we're also going to specify not null. Pretty simple, right? That's pretty easy, pretty straightforward. So let's go ahead and execute that. All right, so here we are in our command prompt, and there's a couple of things we need to do here. First off, we need to connect. So we do PSQL -u, and we do Postgres. And let's connect to the ZTM database, because that's where we want to be. And let's double check this. Of course, we see the name over here, but And so the first thing we're going to do is we're going to try to execute this query. So we have our create table statement, and it's a multi-line statement. So we have create table student, and we have our student ID with a UUID and all of this good stuff, not null, everything we said. And then, UUID generate for is not available. Okay. So in order to actually properly generate a UUID, this looks oddly familiar. So UUID is a data type that Postgres can enable, but as you can see here, for our default value, we're executing a function. And this function, well, Postgres doesn't know what this function is. So what we need to do here is we need to create an extension. So Postgres allows you to install extensions. These are extensions on top of Postgres that allow it to extend its functionality outward, have more options, and so forth. And so we need to create an extension for this bad boy right here. So how do we do that? Well, there is this command called create extension, if not exists, UUID OSSP. So this is an extension that is just available with Postgres. Someone made it. And what it allows you to do is extend the ability of the UUID type, therefore having this generate function that will generate a UUID for you so that you have the ability to generate unique IDs. So it's extending Postgres with the ability to generate unique identifiers. And it has more functionality than just this. Right now we're calling UUID generate v4. There are other functions that this package, this extension gives you, but this is the one we're most concerned with. So if we go and we execute our create table for student again, we're going to have created that table. And if we do DT, what we're going to see is I still have the my table from creating the database based off of the blueprint that had the table in it. So let's go ahead, and we can see that because it's created by education. And so let's go ahead and drop that table, drop table, my table. Pretty easy. And so if we look at student now, well, we have our student table, but we have no data in it, but we've created it. How do we look at what student looks like? Well, if we look at /d students, what we're going to see here is that we have a student ID, our first name, our last name, our email, our date of birth. And we can see here that student became a primary key because we denoted it to be a primary key. We can see the types here, UUID, character varying. We can see that they're not nullable. And we can see that the default value has been set to UUID generate v4. So /d with a table tells us all we need to know about how we created that table. And we can even see that we created it in the public schema. So it's in the public schema by default because we created it there. And so now that we've created our table student, what I really want to zoom in on are these constraints, because so far we've only seen not null. We've seen what primary key does for us, and we've seen that it generates an index for us, but let's zoom in on the types of constraints that we can apply. All right, let's talk constraints. Constraints are a tool to apply a validation against data that will be inserted. And so we've looked at this throughout the course. We've seen many different types of constraints. In the previous video, we even mentioned constraints on the primary key, constraints on not being null. But I really wanted to zoom in here on constraints and look at how constraints work and how they help us. Because at the end of the day, they are a tool to apply validation methods against data that will be inserted. So what we're trying to say here is that when you apply a constraint, what you're trying to do is you're trying to say, hey, when you insert data into my table, follow my rules. Follow my rules and make sure that the data corresponds with what I want to be inserted. Let's say you wanted to put a constraint on the email field and you wanted to apply a bunch of crazy checks to make sure that it is actually a valid email. That's a valid constraint. Or let's say you wanted to constrain the validation of a phone number to adhere to a certain structure. That's a valid constraint. Primary keys are a valid constraint. Again, not null, foreign key. All of these are constraints. All of these are validation methods that are saying, hey, data must be inserted this way. When we think about constraints, there are two very, very important distinctions to make. Column constraints is one of them. Applying a constraint as part of a column definition. And we've seen this happen. We've done this. On the student table, we applied a column constraint that said that certain columns could not be null. Now, when we talk about column constraints, what we're talking about is a constraint that is part of the definition. So part of that same line, when we're defining the column and we're saying column student ID is UUID, and then it's a primary key. Well, we're saying at that point in time, well, this is going to be the primary. When we look at column constraints only apply to that column. They don't apply to multiple columns. They can't cross concerns. They're just for that specific column. Here are some different constraints that you can apply on a column and the meaning. So what do? So when we look at column constraints, we're trying to look at a constraint that will be applied uniquely to that specific column, not multiple columns, just that one. And so one that we're very, very familiar with and one that we've seen throughout the course, not null. It cannot be null. It has to have a value. It cannot be the value null. So that's pretty easy. We know all about null values. We're null professionals. When we look here, primary key is another one, and we just applied this to the student table. And the column will be the primary key, and that is very important. We're saying, hey, this column is going to be the primary key. Now, when we talked about primary keys, we also talked about primary keys being able to be multiple columns. Well, when you apply a column constraint, you're not going to be able to do that. It is for that column specifically. So one column is the primary key. And then we have the unique constraint. And what the unique constraint says is it can only contain unique values. So you can only have unique values in this column. They can't overlap with any other values. And null is considered unique. You can't just fill in anything. It has to be a unique value. Null is considered to be unique as well. Remember that. No null is the same. Then we get into some interesting territory. Because these we've seen throughout the course. We've seen unique, we've seen not null, we've seen primary key. We know all about them. But what is this one? Well, this one is check. So what is it going to check? What are we going to do with this one? Well, we're applying a special condition to check against. So, hey, here's a custom check. Here's something that Postgres doesn't have out of the box, but here's a special condition that I want you to check for the values in this column. And this could be, for instance, that email validation we spoke about, that phone number validation we spoke about, that you want a specific sequence or that you want specific characters to be present or whatever else. You can fill in unique special conditions to check against. And that is what check is for. And then last but not least, the constraint references. What does references do? What does it mean? Well, we've talked about primary keys and we've talked about unique, but where are foreign keys at? Well, that's what references is for. References to constrain values of a column to only be the values that exist in a column in another table. Well, that sounds oddly like a foreign key. So what we're saying here is when you apply the constraint references, you're pointing to a different table and a specific column in that table. So you're referencing somewhere else and you're saying, hey, anything you fill in here, it has to correspond with a value in that column in that other table. So a foreign key constraint. And so now that we know all of these column constraints, we're basically column constraint masters. But hold up. These are not the only types of constraints that we can apply. And so let's go a bit deeper here. And let's look at table constraints. Table constraints. So far we've seen column constraints and constraining data on a column level. But then again, we are able to constrain multiple things. We are able to, for instance, create a primary key that has multiple columns. But how do we do that? Because we only have seen how we can do things at the column level. Well, that's where table constraints come into play. A table constraint is a definition that is not tied to a particular column. And it can encompass more than one column. It doesn't apply directly to a column. It's above that. It's at the table level, right? When you define a table, you're defining individual columns, but that table can also have checks against one or multiple of its columns. You don't need to define every constraint at the column level. It is useful when that column has specific constraints, and any time that column has a specific constraint, you should do it at the column level because it's easier to read. But sometimes you may have multiple columns that need constraints. You may have other necessities that need to go into this, and that's where table constraints come into play. You see, when you apply table constraints, you can basically write any column constraint as a table constraint. And when we look at table constraints, well, we have pretty much the same constraints we did at the column level. We can make something unique. It can only contain unique values, and null is also unique. Remember that. We could set a primary key, but we could give a column list. So the main differentiation here is you can give a list of columns that need to adhere to this constraint. At the table level, it's a column list. It's not a specific column. And then when we write check conditions, check conditions are applied on inserting or updating. So you can check a condition against one or multiple columns. That's pretty good because a check constraint at the column level will check at insert or update at that column. But at the table level, you could check multiple things at the same time. So pretty useful. And then again, our foreign key references keyword that can reference another table. Extremely useful stuff here that you can write constraints in this way. Now, if we were to look at how we would write a table constraint, well, over here we can see our student table, and we can see that we had our UUID, and we're just giving it a default now. And we have our first name, last name. We're still giving the table constraints not null here at this level. But then here at the bottom, you can see I wrote the keyword constraint. And this is how you define a table level constraint. You're writing constraint at the bottom after all the columns are defined. And then you're giving that constraint a name so you can name it at this point. Postgres isn't going to name it for you. No, you're going to give it a name. So you have to have a naming convention. In this case, I chose PK for primary key, and then I gave it the column name that I'm applying the primary key to. And then I say, hey, here's a primary key, and here's my column list. In this case, the column list only contains one column, but you could do comma something else. So table constraints are very easy, very straightforward, very fluent in the way that you define them, because it's just a different way of defining your create table statement. And every column constraint can be written as a table constraint. Now let's go look at some of them. So over here, I'm in DB Fiddle because it's an easy place to fiddle around with some concepts or show you guys some stuff. And you can see here, I've created a table called category, in which I've put a category ID and a type of type text and small int. I didn't use a UUID here because in DB Fiddle, they do not have the plugin installed. Thus, giving a UUID type is a bit irrelevant. So we went with small int for this one. And then we created a table called column constraints, in which we'll define columns with a couple of column constraints. And we've created a table constraints, in which we'll take the same data, but we'll apply it as a table constraint. Pretty straightforward. So if we look at column constraints over here, we can see we have a column constraint ID. We have a column called something with text. And column constraint ID is a primary key. Something is text and not null. And then we've defined an email here. And now I've went ahead and created the check for this column. It is of type text and it has a check constraint. And what we're doing here is we're checking the value of email to match the following. And over here you see this random mishmash of all these different types of characters and all these crazy kind of constraints. What is this? Well, this is what we would call a regex, or a regular expression. And regular expressions are a validation mechanism. They're basically a way to write down, hey, I only want things that match the alphabet A to Z, 0 to 9. They can contain a dot potentially and match the same value. For instance, if your email was mo.beanie@gmail.com or whatever the case may be, and then you can kind of constrain the input of text. It's basically a regular expression is to validate an input. That's what it's used for. When we look at regular expressions, they're a whole different language. They're implemented in a ton of different languages. They're implemented in SQL, you have them in JavaScript, in Python, in Java. They're something that crosses the realm of programming and databases because they're an easy and well-established way to do validation against text and input. When it comes to regex, we've compiled a list of resources and explanations and easy introductory level material that will help you get into regex and kind of learn about it. Now, we're not here to become regex masters, but it is an important skill. And so we've compiled what we find are some of the easiest, most comprehensive resources to get you into regex and to get you to understand how to apply regexes because they are a useful validation input mechanism. And when it comes to data, what we want to do is we want to make sure that whatever we fill in here, that it adheres to certain rules. And if a regex is the way that we need to write those rules, well, we can learn how to write regexes and we can apply them. In this case, this regex I pulled from somewhere, and it's a simple validation mechanism that's gonna kind of validate a email address. And there are websites where we can test this visually. If you take regex 101, it is a website where you can go and you can copy a regex into place, and then you can go ahead and say, hey, if I type mo at beanie.io, what's going to happen? Well, it matches, so it's valid. And then if I, for instance, typed at beanie.io, so someone, for instance, went ahead and typed, hey, I'm going to not fill in the full thing. Well, it's not going to match, so we know this is going to error. But if I wrote an H here, okay, now we're valid. Now we're invalid. If I remove the @ sign, now we're invalid. So you can see here how we're trying to validate the matching against this case. And you can see here, match a single character. So we're matching a single character set between A and Z, lowercase a and z, 0 and 9, and then match a character literal. So this will kind of go ahead and explain to you what all of these different parts mean, because it's kind of gibberish when you look at it, right? But I promise you, regexes aren't hard. You just need to go to the resources we've linked for you, read through it a bit, get familiar with the regex syntax. And once you're familiar with the regex syntax, it becomes very, very easy. And there are regexes all over the internet that can give you a starting place to kind of figure out how you want to apply checks. And this regex tester, regex 101, is a great place to go ahead and test out and see what your regex means. Now, with that said, what we've done here is we've applied this regex that's basically going to do an email validation, and we've just validated that it indeed checks emails. If you don't fill in a valid email, it's not going to match against what this says. So here we've also created a category ID with a small int, and it's referencing. So it's creating a foreign key to category, which is the upper table, category ID. So we have a foreign key transaction. And then here we have a create table where we're doing everything but with table constraints. So you can see we've done the same ID. We call it column constraints ID. We could have called it TC ID, but for all intents and purposes, we named it the same. We have something. We kept the column constraint on this one. And we have email where we removed the check. And then we have our category ID where we kept the foreign key. And what you can see at the bottom here is we've defined a constraint and we've named it primary key table constraints, and we've called it primary key of this. And then here we've done our constraint valid email where we check our email field against our regex. And so if we go ahead and run this, what we'll see is that there is a table constraint validation for valid email. And this is because over here you can see we're inserting into category and we're inserting proper category values. But when we insert into table constraints, we're doing a value, we're filling in a something, and we're giving an email. But the email is invalid, so we're hitting our constraint here. But if I made that mo, well then suddenly we have proper constraints. And if we select it from table constraints here, then we will see that what's filled into our database is one something mo at beanie.io. And the same is true for column constraints. If we take column constraints and we removed the mo, we'll see that we're going to hit a column constraint against column constraint email check. So you see the difference in the name here? At column constraints, we defined it at the column level. So Postgres named it column constraints email check. But at the table level, we called it valid email. So it created a table constraint valid email. So it takes the name, right? At the end of the day, these constraints work the exact same way. But what you should remember here is that if you can define something that is at the column level, make it a column level constraint. But if it encompasses multiple values, make it a table level constraint. If it concerns multiple columns, for instance. So let's go ahead and fix this. And then let's select star from column constraints. And if we run this, what we're going to see is it allowed it to be filled in. Amazing. Column constraints and table constraints, although they are a different concept, they operate in the exact same fashion. It's just a different way of writing the same thing. And so you can decide which way you want to write it. But again, the best way that I found of applying constraints is if they're related to one column, write them at the column level. If they're related to multiple columns, write them as a table constraint. But make sure you have a proper naming convention in place so that your constraints are named the same every time you create a constraint on somewhere else. And so with all of that, let's jump into some exercises around creating tables. The last thing I wanted to zoom into was this whole UUID business, because we kind of said it matter-of-factly during the creation of the student table, right? Unique identifier, easy peasy lemon squeezy. But what is a UUID even? Well, when we looked at UUID, we knew we had to create this extension, UUID OSSP, right? We need to install an extension. And this extension gives us the ability to generate unique identifiers. First of all, let's zoom into extensions. What are extensions? Well, extensions are pieces of software that allow you to expand what Postgres can do and expand how certain processes run. It basically expands your ability to do things in Postgres. And so if we look here, we have select from PG available extensions. This will give you the ability to look at all of the available extensions that came with Postgres. And UUID OSSP is one of them. UUID, what is it? Because we've seen that extensions are just those pieces of software that give us the ability to do these things. But what is a UUID? Well, with UUID, this extension in Postgres allows us to generate unique identifiers, and I've said it many times. Unique identifiers for primary keys. What does that unique identifier look like? UUID stands for Universally Unique Identifier. And what it basically does is it generates this random mishmash of stuff that's always going to be unique because it bases it off of multiple factors that are unique to generate something random. And over here, we can see what a UUID would look like. No one knows what exactly this means, but it's unique, and it will continue to be unique because it's generated based off of information that is unique at that moment. So you'll never have a conflict. You'll never have a conflict of an identifier. And so the question becomes like, well, Mo, why am I using this? Like, I see that it's unique and I see that it's useful and I see that, nothing's going to conflict with this, but why can't I just use a number from 1 to 100 and just go 1, 2, 3, 4, 5? Well, that's a good question. That goes into the question of like, why should I use them? What's the purpose? And the purpose is, again, this is another point of contention. Not everyone is a super fan of UUIDs. Everyone agrees that you should use them in some way, shape, or form because they're unique and they help you out in certain scenarios. But a lot of people advocate also for numbers that go from 1 to 100. And so UUIDs have a lot of pros and cons. Some of the pros are that they are unique everywhere. They're easier to shard, and sharding is one of these concepts that we haven't looked at because it's an extremely advanced concept that you use when your database is getting extremely large. Now, it also becomes easier to merge and replicate your data. Like if you're merging data, you want your identifiers to be unique. Could you imagine if you had two tables where you were using 1, 2, 3, 4, 5, 6, 7 as the ID, and then you had to merge it with a different table of information? Well, now you have two users that have the ID, the unique ID of one. How are you going to merge that? It becomes extremely complex. So using a UUID, you know that the IDs are going to be unique, that you're not going to clash on an ID. You could also easily replicate the data, create a replicate. One of the important last pros, and there are many other pros, but one of the most important last pros is that you expose less information about your system. If you expose that a user is 1, 2, 3, 4, or 5, 26 in your system, you're exposing some information about your system that you don't want people to know about. A unique identifier is way more pleasant in that regard. There are also cons to UUIDs. They're larger values to store. As you could see, it was a long string. It can have a performance impact because it stores more data, and it's way more difficult to debug. Like it's hard to go and look at a unique identifier and be like, oh yeah, it's that person or it's over there. Like they're just unreadable pieces of information that are unique. So UUIDs have their pros and cons. But at the end of the day, what we're aiming for here is to give you the concepts and the structures that are easiest and most commonly used. So where you can and where it seems valid, try to use UUIDs as much as possible for your primary keys. As a practice, it will make it easier for you, generally speaking, in the long run. When you get more seasoned and you see more types of data and you see more types of patterns, there may be specific use cases in which these just don't fit. These just don't work out for that particular pattern. But in general, and generally speaking, we want to give you the foundation that makes the most sense. So what makes the most sense, even though it costs more space to save, even though it can have a slight performance impact when you're talking about millions and millions and millions of records, the pros still outweigh the cons. So when you're starting off, use UUIDs for your primary keys as much as possible. And as you grow throughout your career and you see more and more patterns evolve and you see more and more different types of tables and different structures, there may be cases where you want an auto-incrementing number. You could even store one beside a UUID for easy indexing, for instance. There are many different reasons to use auto-incrementing numbers over UUIDs, but in general, I advocate to stick with UUIDs because they're unique and they're easy, and the pros outweigh the cons mostly. Hey everyone! Before we get into it, I wanted to dive into something called custom data types. Now, in this data model, we decided it would be good to show you how to create a custom data type. A custom data type being something that Postgres doesn't have out of the box. We looked at all of these data types, integers, floats, text, but what if you wanted to create your own? Well, what would that look like? And custom data types is something that you may come across depending on what databases you end up working with. And it's important to know, well, what they are and how they work. Now, you can go extremely complex when composing a custom data type, but for the purposes of this course, we wanted to go simple. And so what we decided to do was make a poor design choice. It's a poor design choice because it would have theoretically been better to model feedback in a way that was relational, aka having a table and properties like that. But for the intent and purpose of this course, we wanted to loop you through the thought process that can go into creating a model. And this model is by no means perfect. But in any given data model, poor decisions can be made. It happens. It just happens. Not every decision you make will scale properly or will be the best choice. And so in this model, we decided for a course, well, every course needs feedback. And for feedback, hey, let's create a custom data type that we're going to use the array syntax. So we're going to store multiple feedbacks directly against the course. Feedback will be a custom data type that will have a student ID, a rating, and feedback. And the rating will be a small integer that can range from 1 to 5. The student ID will be a UUID, and feedback will be text. And we'll show you how to do all of this. But remember, this particular custom data type isn't a good decision. But we'll get to that. Now, Postgres allows you to create custom data types to store shapes of data that are more complex. But not only that, it allows you to adjust and apply whatever you need in terms of a shape in order to get where you need to go. So with that said, we're going to create a custom data type here and we're going to show you how to work with it, but it's not particularly the best decision. Now let's go ahead and create that data type. So for this portion, we're going to go back to Valentina Studio. We've done the command line and it's great, but when writing queries, it really is beneficial to use something like full featured suite just because of all of the features it can give you: autocorrect, it can do autocomplete, it can do all of these different things. It can do formatting for you. So it's just a nicer environment, and you can kind of go ahead and look into your schema and see what's available to you, what functions you have, all of that good stuff. So right now what we want to do is we want to create a type, and we want to create the type feedback. And what we're going to do is we're going to say, hey, well, for feedback, I want a student ID because I need to keep track of that, and that's going to be of type UUID. And then I want a type of rating that's going to be a small int. Now, this small int doesn't really give you a check. And that check being like well, what's my rating going to be? Is it going to be 1 to 5, 1 to 10? Small int can hold any given number. So here you have to make the decision whether your backend is going to do the check or the database. And that you could do this in a more complex way, create a domain, and a domain is just a specific type of data that can have a check. So we could have something like a rating here. Let's do that. Let's say, okay, create domain, and let's call it rating. Let's say that rating is of type small int. So we know that. And let's put a check on it. And let's say value has to be greater than 0 and value has to be smaller than or equal to 5. And so that way we know now that we have a domain of type rating. So last but not least, we need our actual feedback, and our feedback is going to be type text. So one more thing we need to do here before we execute this is we need to put as. And so what this basically will do is it will create a type that has a student ID of type UUID, a rating of the domain rating, and feedback of type text. And so don't get types and domains conflicted. A domain is nothing more than an alias for an existing type that can have a check constraint, a not null constraint. It can a default value. It's basically an alias for an existing type that can be a bit smarter than that existing type. And a type, a fully newly created type, acts as an independent type. So they're a bit different in that respect. And now that we have this, we know that our rating has to be between 0 and 5. We know that our feedback is text, and we know that our student ID has to be a UUID. And so now that we have a custom data type, and now that we have a custom domain, which is nothing more than an alias, we can go ahead and we can create the rest of our tables based on what we see here. So we've just created this part over here, feedback, which is the custom data type of UUID. And we even went so far as to create a small int alias called a rating that can go from 0 to 5. So with all of that, we have our custom feedback type ready to be used in the course table. And let's go ahead and create our tables now. Here we go. We're going to create all of these tables in one fell swoop. We've already created this custom data type behind the scenes, and we've adjusted the rating to be of type domain, which is an alias type that can have a constraint. So we've already set this up. Now it's time to set the rest up. And so we're going to start off with student. And as you can see, a student can belong to one or multiple enrollments, but an enrollment can only belong to one student. Sorry, that's 0 or more enrollments. But an enrollment can only belong to one student. So when we set up a student, what you can see here is that because the student is on this side of the relationship, it doesn't really have any bearing on the student, the enrollment, but the enrollment needs to know about the student. So we can pretty much set up this table without having to take into account any foreign keys. And as you can see here, I've taken the liberty of telling you which parts should be the primary key. Now, throughout this video, feel free to pause the video and try out the create table statement on your own, and then come back to the video and see how we apply the create table statement and how closely you align to that. So let's go ahead and create student. And so over here, we're back in Valentina Studio. And what we can see here is that if we do a create table, what we're going to see is that we can apply student. And then what we need to do now is we need to define the columns that go in here. So we say student ID, the ID of the student is of type UUID, and we're going to say default, and we're going to say UUID generate v4. That's the one we need. And we're also going to say that this needs to be the primary key as the constraint. So let's put primary key here. So we have a constraint, we have a default value, and we have a type. Okay, then we have first name. And this was of varchar, and we need to give it 255. And last name is the same. It's varchar 255. And then the last property we had was date of birth. And this one we want to give type date. And so we could give these individual constraints, and we can say here, you know, this can be null and this can be null. and this can't be null. So none of it can be null. And so if we go ahead and execute that statement, and we go back to our schema editor, and we go to the tables overview, and we quickly refresh this, we can see that we have a student now with a student ID that has a primary key, first name, last name, and date of birth. Awesome. So now that we have that, what we want to do next is we want to create our following table, right? So let's go over to enrollment. Oh wait, enrollment needs a course ID as a foreign key. So if it has two relationships, well, let's go ahead and create course first. But course also needs a foreign key to teacher and student. Okay, so let's isolate the tables that we can make the easiest. So subject has no relationship. So let's go ahead and create subject. And so we'll go ahead and create table subject. And what we'll give it is a subject ID of type UUID. And we'll say it's the primary key. And we'll default it. And we'll say UUID generate v4. That's the one we need. And then we'll give it a subject of type text. And we'll say not null. And we'll give it a description of type text. But this is optional. So did we get that right? Yep. Seems like we did. Subject is of type text. Description is of type text. This is optional. We added the constraint not null to this. And so we could have put the constraints visually inside of this diagram as well. I just chose not to keep it as simple as possible. And so if we create this table and we go over here to our schema editor and we refresh our schema again, we can see that we have a subject and we have all of that good stuff. All right, 2 tables down, 3 to go. So now that we've isolated the 2 tables here that didn't need any foreign key relationships, well, let's go to the third one, teacher. All right, so teacher has a teacher ID, first name, last name, email, and date of birth. And it seems like we forgot the email on the student. So I'm gonna have to show you how to add that after the fact. So let's go ahead and create the teacher. Create table teacher. And let's give it a teacher ID. Again, UUID, primary key, and let's default it to UUID generate v4. And now that we have that, the next part of this is the first name, which is a varchar of 255. And let's give it a not null. And then let's copy that. Let's paste it. A little lazy. Last name. Same deal. Date of birth is of type date. Let's give that a not null. And then let's say email is of type text. Now we did show you how to do the constraint on the value, the check constraint to check the email validation. For all intents and purposes, I'm going to leave that alone for now. And let's execute that teacher creation. And we can also just quickly over here do a refresh, and we'll see that we have 3 tables now, teacher, subject, and student. And we did see that we forgot a field on student, so let's go ahead and alter that table. An alter table is a way to change tables that already exist. And so what we want to do now is we want to alter the table student, and we want to do an add column, and we want to do email of type text. And once we execute that, what we'll see here is that our student didn't have the field. But let's go ahead and refresh this. And suddenly it has a 5th field, email. So we're good now. Happens, you can forget a field here or there. So now that we have teacher, student, subject, let's go ahead and create our course. So create table course. And this one is interesting, right? Because this one has foreign keys, it has a primary key, it has some text, it has a custom data field, it has all the fun stuff. So let's go ahead and let's put in course ID, and let's give it UUID, primary key, all the good stuff, default, UUID generate v4, so that we don't have to worry about generating a value for it. And then we'll give it a course name and description of type text. So let's say name. Oh, Name is a reserved keyword, so let's put name, and then let's say text. And then what we need to do now is say not null. We want to give that constraint. We want to give it a description. And so description is of type text. We'll optionally leave that empty. And so now we get to the fun stuff, subject ID and teacher ID. So let's put them in here, subject ID, teacher ID. And so now we have to do a foreign key reference. So we say references subject, subject ID. And here we say references teacher, teacher ID. And so with that, we now have created our foreign key relationships. Now, interestingly enough, let's see what happens when we do this. And let's add feedback as well. So feedback, our type feedback, and it's of an array type. As you can see here, our type feedback got lowercase because we didn't use the double quotes to uppercase it to feedback. Always good to remember to use these when you want to do case sensitivity. So we're going to do feedback of type feedback, and let's create that table. Interestingly enough, it seems I've made a mistake here. And what it seems I did was I forgot to give it a type. So subject ID is of type UUID and teacher ID is of type UUID. And so when we execute that, what we'll see happen here now is if we refresh this real quick, we're going to see an extra table, and we're going to see the table course. And if we open up the fields, we'll see course ID, subject ID, teacher ID. Now comes the last part, the enrollment. So let's go ahead and create the enrollment. And what we need to do here is we need to give it a course ID, a student ID, and so let's do UUID, UUID, and let's say references course ID. And here this references student ID. And then what else do we need here? Well, of course, we need an enrollment date. So let's put that. Let's say date. Let's say not null. And then one more thing we need is a primary key, because we didn't have one here. Because we have two foreign keys here, what we can do is we can combine them and say the primary key is course ID and student ID. And let's go ahead and name this constraint primary key enrollment. And let's execute this. And so now that we've executed this, what we'll see here is if we do a refresh on this, what we can see is if we go into enrollment and we open our fields, course and student ID are the primary key. And we can see that because they both have a key symbol beside them. And so with all of this, what we've ended up creating is the entirety of this here data model. Now this data model is by no means perfect, but we can start putting data into this data model, and we can start creating an environment in which we have more and more to work with. And with that, we may uncover some of the flaws that can come with a data model. No data model is perfect. Every data model can have flaws. And by putting data into the model, we may uncover some of these flaws and change the model perhaps, as many data models change over time because the needs change or the model isn't progressive enough to handle future-proofing itself. So let's take a look at inserting the data into the tables. We created our entire data model. We've created a student, an enrollment, a course, a subject, a teacher. We've even created a custom data type called feedback. But now comes the interesting part. Because we put together our entire model and we have everything ready to receive data, but we don't have data just yet. And so you may ask yourself, well, in what order, what fashion do I go ahead and create data? Well, that's very dependent on the user journey, because not often will you be creating data on the database layer specifically for what would be considered a user journey. If we were to apply the ZTM database to an actual platform, well, a student would go ahead and register themselves, and a teacher would go ahead and register themselves, and then a teacher would go and create a course, and there would be a course creation flow, and then a student would go and buy a course and thus be enrolled into that course. And because they get an enrollment by buying that course, so the whole flow goes. And when a student buys a course and is enrolled in the course, they can submit feedback eventually to that course. Now, with all of that said, we're going to learn how to insert data at the database layer. But that is not necessarily representative of a user journey or an actual flow. It's just a way of manipulating and injecting data into your environment. Let's start off by creating a student. So over here, we are in Valentina Studio yet again, and we're in the ZTM database. And as you can see here, we have all of our tables ready. And we have a student object, and we can see the fields that it needs to accept. So what we want to do is we want to insert into. This is the command that we will use to insert data. And we want to insert into student because that's the table that is going to receive our values. The following part are the parentheses that follow. And this will determine in what order you want to inject data. If you do not tell it which order, it's going to accept the order in which the fields are injected into the actual table. And so how would we see what that looks like? Well, we would go over to our schema editor and we would open up student, and what we would see is that it accepts student ID, then first name, then last name, then date of birth, then email. So it's according to the order in which we added them when we created the table. It's not according to the order in which the data editor is showing us the fields, because it's showing us them alphabetically. So it's always useful to tell the insert statement in which order it should receive it. So let's do student ID first. Well, oh wait, didn't we say that student ID had a default value? Silly me, we don't need to actually inject anything into there. So that's also a big plus of telling it specifically what fields you want to populate. So let's populate first name, last name, email, and date of birth. And by doing this, what we're going to enable ourselves to do is inject values. And the values we're going to inject are, well, Mo, last name Beanie, email mo@beanie.io, and then, well, my date of birth. Well, we've seen how to do this. We can fill it in different ways and format it, but let's start year, month, day, because that's the easiest, and then let's convert this to a date with our conversion operator. Awesome. So if we go ahead and execute this, what we're going to see is that we've inserted info into student. And if we go ahead to student enrollment and we refresh by pressing Command R or Control R, depending on what environment you're on, we can see that a student ID was automatically generated. So we automatically have our primary key by using that default keyword. And first name, last name, and date of birth and email have been filled in. So we have our very first student. All right, let's go ahead and create a teacher. And teacher accepts almost the same things. Now, here's the thing. A student can also be a teacher. So theoretically, I can inject or insert the exact same information. Well, let's go ahead and do that for simplicity's sake. And by inserting this into the teacher, what we can see now is that if I opened up the teacher, well, Mo's also a teacher, but it's a separate entity. It would almost be like considering it a separate person. We don't have the concept of a user. The first flaw in this data model is that we completely separated the concept of a teacher and a student, but we don't have a holistic user to which we could give quote unquote a role, not a Postgres role, not a database role, but if we were to model a database, we would be able to give them the role of a teacher and the role of a student, and they could be both at the same time. Now they're completely separate entities. And so our system would already fail at this level because, well, how are you going to let them log in? What if they want to be a teacher and a student? How is that going to work? And so this model is already exploding outwards. So how would we solve for this? We could maybe create a user table over here, and we could have a user ID, and then a student, instead of having a first name, last name, date of birth, we don't need to keep track of this potentially. We could just give them an is student flag or an is teacher flag. Wouldn't that even be better? And then everyone by default that registers is considered a student, but being a teacher is opting in. That would be interesting. Now, of course, you can expand the data model and make it easier, because the way that we structured this, we weren't really thinking of the end system and the end user. We just went ahead and we said, well, we have a teacher and we have a student, and let's go model those. But we really didn't think of our end system and how this scales. So now we could see that, well, Mo can be a teacher, but Mo can also be a student. But how is the system going to handle that if we were to build something eventually? It's going to be very difficult, because Mo the student and Mo the teacher, although they have unique IDs, they're theoretically the same email address. By using the same email address, well, how are they going to log in? We could make them log in by teacher ID, but that teacher ID is jarbled. We could give the teacher a username and the student a username, but that's also jarbled. So you can already see by us explaining and going through this exercise of inserting data, we're already seeing flaws in some of the parts of our data model for expanding it outwards. And with every data model, there comes a point where there are certain flaws in the data model that need to be addressed. Now, this specific data model issue we could address, but it's much easier to trek forward with the data model we have and explain all the different concepts around updating, deleting, inserting, instead of creating the most robust model up front. This is, of course, an educational course. When we get to database design, that's when we'll look at all of the different ways that we can look at designing a system. Because that is, again, a very, very different skill set. And you're never going to get it right on the first go. Designing a system, designing a database is a very hard task. And just rudimentarily creating this data schema that seemingly covers all the bases can already show flaws in an end system. Now, let's go ahead and create a course. Next up, we're going to make our very first course. We're going to have a course with a name, a description, a subject. We're even going to give it a teacher, and maybe eventually some feedback. So over here, you can see that before we create our course, we may need a subject. So let's go ahead and create a subject first. So again, we're going to insert into subject, and we already know that our subject ID is going to have a value defaulted into it. So let's give it a subject and a description. And then let's say values. And then let's go ahead and let's say, well, let's call it SQL 0 to Mastery. Just a simple course name. Nothing to do with this course at all. Just what came to mind. And let's call it the Art of SQL Mastery. Again, nothing to do with this course at all. It has no bearing. I wasn't thinking of this course at all. It's just a random thing that came to mind. And so when we execute this, well, what we're going to see is that, is this actually a subject? Huh. Oh, I mixed it up. This is what I actually wanted to give my course name. This is the course name I wanted to give, and this is the description of the course. I accidentally inserted it into subject. Well, stupid me. We can go ahead and we could delete that. So let's do a delete from subject, where, let's say, where the subject is equal to this. We could also go ahead and find the ID and do it that way, but it's a whole thing. If we did this, well, let's go see what's in our subject. CTM, public, subject. And nothing in here. Let's just confirm that we actually deleted it, right? Like, I did it, but I didn't really show you if it was there or not. So if we execute this and we go over here, we can see, yeah, SQL 0 to Mastery, the Art of SQL Mastery. Well, that's not really a subject, is it? So, we went ahead and we used the delete from syntax. So we delete from a table, And then with the where clause, we can go ahead and we could write a query. We could write a simple comparison. It's basically the where clause that we're used to from our SQL queries, and this is what gives us a lot of power. I didn't even have to check here on the ID. I could just say where it's equal to this. So, if we execute that, again, no more course, no more subject. So that little mistake, easily rectified. What do we actually want to inject in here? Well, as a subject, we wanted to inject SQL. And then as a description, we wanted to inject a database management language. So let's execute that. And in subject, we can see, okay, we have our SQL as a subject. Okay, now let's go and insert into course. What do we have in course? Well, that's where this comes in handy because I can just quickly go check the fields and we can see that we need to give it a name. And let's just make sure that we do that correctly. We can give it a description. Here's where we need to make a decision. So how does feedback work? Well, feedback is something that's given by the student. So we're not going to inject it while we're doing the course. That's not how it would work in a real system. You're not going to inject the course and then inject a bunch of feedback into it unless you're doing a migration from an existing system. Feedback is something organic. Feedback is something that the student gives. So it would usually be an update command. You would be inserting a value or updating a record and then inserting a value into that feedback array that we have. So we're not going to give it feedback right now, but we may need to give it a subject ID and we may need to give it a teacher ID. Let's go ahead and just create our course for now. Normally a course is created by a teacher, so we would need the teacher ID, but let's go ahead and say, all right, let's call it SQL 0 to Mastery. Let's boost it up a little. The number one resource for SQL Mastery. Easy. This has nothing to do with this course. I'm not thinking about this course. It's, purely hypothetical. So let's go ahead and create that course. And what we can see now is if we went ahead and we went to look at our course, well, hey, we were allowed to create a course, but we didn't have to give it a teacher ID and we didn't have to give it a subject ID. Interesting. So when we created our foreign key reference, we didn't actually tell it that it had to enforce it. So it's allowed to be null. Well, we don't want that, do we? We want our table to we need a teacher. A teacher for sure has to make a course. And every course needs a subject. You can't have a course without a subject. So how are we going to do that? Well, silly me, I forgot to actually give it the proper constraints. So we're going to do an alter table, right? And what we're going to do is we're going to alter the table course. Well, if we go ahead and alter the table course, what we want to do is we want to alter the column subject ID. And we want to set not null. And so the first thing we see here is subject ID contains null values. So before we can even alter it, we would need to delete our existing course. Well, that's not good. So how would we go about that? And so technically what we're looking at here is a mini migration scenario because we can't just go ahead and alter the table to set the subject ID to not null because we have a course that doesn't have a subject ID. And because we have a course that doesn't have a subject ID, well, what we now need to do is we need to fill in the gaps. We need to fill in the gaps before we alter the table because we can't just go ahead and alter the table. We need to maintain the integrity. So how would you go about that? Well, if you were looking at this from a migration perspective, what you would go and do is you would potentially maybe create a subject that has a specific subject that would flag other systems to say, hey, this user needs to add subjects. Null is not an allowed value. But now we need to give it a subject ID that references a primary key over here. So we would go and create a subject that is, quote unquote, a fake subject. And then if you have that fake subject, well, now the other systems can be like, they have this fake subject, so we need to tell them to select a different one. So that's how you could progressively migrate, for instance. Many, many different strategies can go in here. This is just one, very simple one. That said, what we need to do basically is we need to go and update the courses and fill in a subject ID before we go ahead and migrate. And we only have one subject. We could go ahead and do all of this stuff, but let's just give it the subject we have because we're in a very simple state. So how do we do that? Well, we would go over here and let's forego our alter table for now. Let's do an update statement. So update statements work like this. You update the table course, and then you have the option to set something. So we'll set subject ID, and we can set it to whatever we want. So let's go over here to our courses subject, and let's copy the subject ID. And we're going to set the subject IDs to SQL, but we're going to do it specifically in specific scenarios. So we're going to say where subject ID is null. Otherwise, we would do it everywhere. So if we run this, what we're going to do is we're going to see now, if we refresh here, well, now we have a subject ID. Okay, awesome. That means that we can go ahead and we can run this alter table, right? And if we run this alter table, oh, no issues. And now if I were to say insert into course, and we said that we were going to insert just a name and a description, well, what's going to happen now is we're going to get an issue. Name and then description. Just to give an example, and we did this. Well, okay, name and description are mandatory. Course ID is going to be generated, but what's going to happen here is we're going to get an error. Null value in column subject ID values not null constraint, so we cannot add a course without a subject anymore. And the same should be true for a teacher ID. So if we do alter table course, well, what we want to do now is we want to be able to set that teacher ID to also not be null. So let's go ahead and let's alter the column, and let's say teacher ID, and let's say set not null. Now what's going to happen is, oh, teacher ID contains null values, so we have to do an update statement here. So what we're going to do is we're going to update course, and we're going to set teacher ID, and we're going to have to set it to a value where teacher ID is null. And this one would be a more complicated migration, right? Because if you have a bunch of courses that don't have a teacher, well, what are you going to do with them? Well, you can't just go and sunset them. They probably have course material, although maybe they're owned by the system at this point. So you would maybe create a teacher called system, and it would just be owned by the system, not a specific teacher, or you would probably sunset them. Who's to say? It really depends. Now we need to figure out a teacher ID. So let's go to teacher. Let's copy Mo's ID. And I know this is going to be funny. Mo's going to be teaching Mo. In any case, we'll set the teacher ID where teacher ID is null. And then when we go over here, over to the course, what we'll see is that we have a subject ID and we have a teacher ID. We have no feedback yet, but feedback is an organic thing. We don't have feedback. So, but now what we need to do is we need to do the same alter table again, and we need to set the teacher ID to not be null. And from now moving forward, you cannot create courses without giving it a teacher ID. And so now you can kind of see why it is very, very important to put the right constraints in place and to think about the constraints of your system. This is more about system modeling than it is about specifically the database commands and queries. You have to put a lot of forethought into what exactly you're going to build before you go ahead and create this model. And even when you create this model, you can make mistakes and you may need to alter some things. And these alter commands and these update commands, they're very useful in your toolkit to be able to go ahead and alter certain things, migrate certain things, make sure that everything is in a good state so that you can make the data your own. Because once you create this database and once you put it into production and once you have all of your data, well, that's when it becomes very, very hard to do these migrations. That's why systems go into maintenance mode, because when you touch the data behind the scenes, well, you don't want clients and software injecting data into your system while you're trying to migrate to a completely different schematic. If we, for instance, said altered teacher ID's name or feedback to a different type or whatnot, all of that stuff, you would have to put the systems that are trying to talk to you into maintenance mode. You'd have to put them to sleep because you don't want systems touching your data while you're changing things. So once you put this out there, it's very important that you're 100% certain of your model and that you test it and that you validate it. And that's what the software development lifecycle is for. databases and database engineers have to live very closely to the developers in order to make sure that everything that they're putting together and that the system design is coherent. The final thing left to do is enroll a student into a course. We've basically set it all up. Okay, we don't have a ton of data, nor do we have a ton of things set up in the best way. This model is very, very simple, but it's very, very effective at teaching the absolute basic necessities of these commands and where and when to place them. Because at the end of the day, when we write queries, what we're trying to accomplish is fetching data. That data shape, that model, is extremely important in the way that you're going to interact with that data. Looking at how we have to shift and make that model more and more malleable and better towards those outcomes is extremely important. So with that being said, well, let's go ahead and enroll a student into a course. And what we can see here is that we need a course ID, a student ID, and an enrollment date. So if we went to say insert into enrollment, we need a student ID, we need a course ID, and we need an enrollment date. Well, on this table, we also didn't put any foreign key validations. Not at all, actually. We didn't put any not null checks on any foreign keys. So that was our first mistake. But if we insert the values into here, what we need is we need the student ID. So if we go here, here, and we quickly do this, we can get the student ID, and we'll just fill that in here. And then let's go into course ID, and let's go into course. And there we go. And then as last thing, we need an enrollment date. So let's put now, and let's convert that to a date. And let's execute this. And there we go. We have now enrolled a student into our course. So if we go into enrollment, our student is enrolled into the course today. So we've done a full, so to speak, flow of what a user journey would look like if there was an actual website or app backing this thing, and we did it in the right steps. One other thing we need to do is, well, the student is going to go through the course. And once the student goes through the course, what needs to happen is feedback needs to be given. So let's look at how we would give feedback. So obviously now that we're going to add some feedback to a course, we need to do some kind of update command because we're going to update this existing course with SQL 0 to Mastery with some feedback. And so I've put together this update command that we're going to run through. And what this update command is basically doing is saying it's going to update the course table. And we're going to set feedback and we're going to array append. So now that we're working with arrays, we have a feedback array. And we have to append to that array. We're going to add something to that array. To this, you could also do array.delete. You could delete something off of an array, or array remove, I believe it is. Let's take a look. Array remove. You could replace, and so forth and so forward. But we're going to append right now. And what we're going to do is to the feedback array, the existing array, we're going to append a row. Now, this is the syntax you can use to define a custom row of any specific type that you will append to an array. So with row, what we can say is, well, we have the student ID, we have our score, which is a 5, and we have our feedback, which is great course. Now that we have this, we're going to cast it to the type feedback. And we're going to say, hey, do it where the course ID is equal to this course ID. And this is exactly how a potential backend system would formulate a query to insert feedback into this array. It would just append it to the array. We don't want to go ahead and do kind of deletions and stuff like that. That would be more complex. We could potentially do a deletion where the row is equal to the student ID. A student could potentially leave multiple feedbacks. We don't know. There are really no rules around this custom type since it's just an array. You can just keep putting stuff into the box. There's no real constraints, and that's one of the downfalls of this type. So when we append to this array, when we do this, and we execute this, what we're going to see is we've inserted successfully into this course a feedback. And if we go see here, we can see that if we refresh here, we now have our feedback. And our feedback is an element on the array. So knowing this, well, we can now start adding feedback to the array. But one of the downfalls of this is I could do whatever I want here. I could do PE74. I could do, interesting, PE is invalid syntax for a UUID. So let's do something like FC73, and let's do something like DC73, and let's do something like 4571. And we can change whatever we want as long as we fall within the proper ranges of a UUID, which is A to F. What I'm basically showcasing here is I could generate whatever I want here. It doesn't really matter. It's not going to check if this student ID exists. And sure, I'm getting a lot of 5 stars, but I can't verify from who they are. And that's one of the other drawbacks. I'm storing all of this feedback, but the shape that I'm storing it in really isn't the most ideal shape, right? Like I have this box of feedback, and of course it can hold all of this information, but it really isn't the most ideal. And you can see now the query has to be more complex. I have to do an update instead of an insert, and I have to update the course information every time. I don't want to be updating my course every time. I want to insert feedback somewhere, and I want to keep it separate from the course. There are more efficient ways of doing this. And as this array grows, like we don't have any integrity checks. We have to do this complex mechanism of generating a row and converting it. Like the query is immensely complex for what it's giving us right now. So how would we go about fixing this? Well, we would need to change the data type that we have here. We would need to change the model. And so let's go look at what that would look like. So you may be asking yourself, well, how are we going to change this in order to accommodate feedback from multiple students and to a course? Well, to do that, we need to change our custom data type into something completely different. We need to shape it into a table. And the reason we're going to shape it into the table is because when we use tables, we can follow the relational model. And what does the relational model warrant? Primary key, foreign key interaction, constraints, checks. There's so much more you can do with tables than you can do with custom data types. Custom data types don't allow you to do complex checks, foreign key references, all of that good stuff. And then on top of that, arrays add this complexity onto any data shape and query you're trying to write. Could you imagine having to query the arrays and do complex calculations against each individual? Well, you're going to have to write array iterations and all of this stuff. And it doesn't make sense for what we're trying to accomplish. It doesn't make sense in terms of the data shape. The data shape needs too much love. And what I mean by love is we want to query that data a lot. It's something very important. Feedback is something very important. So to demote it almost to a data shape instead of a table is kind of offensive to feedback. But that doesn't mean that there aren't good cases, for instance, custom data shapes. For instance, a phone number. A phone number could easily be an array because you may have multiple phone numbers, and you may have multiple phone numbers for your home, your cell phone, and all of that good stuff. And you may want to store a custom data shape for that. That already sounds like a way better use case. Feedback is just too important to us. So as you can see here, what we did is we changed our custom data shape. And what we did was we made it a relationship. Each individual feedback can belong to one student, but a student can leave multiple feedback, right? So a student can leave multiple feedback, and feedback belongs to one course, but a course can have multiple feedback. So one individual feedback has to belong to a certain course and a certain student, but students and courses can have multiple feedbacks. So it's kind of an interesting way of shaping this relationship. What you can see here is that we have a student ID and a course ID as foreign keys, and I've highlighted them as potentially being the primary key. But let's look at that. Let's look at potentially making the combination of these two the primary key. First and foremost, what we have to do is we got to go change what we already put in place. We have a custom data type, and we have a domain for the rating that is rating, and it's of type small int, and it has a range and all that stuff. We have to change everything. And this is potentially a scenario where you would get into a migration of the existing shape and taking that array and taking the values of each individual part of that array and putting it into the new feedback table. Now, since we only have one feedback within that array, we're not going to go into a migration scenario. What we are going to do is we're going to create a new table. So we're going to do create table feedback. And what we're going to do is we're going to give it the student ID. We're going to give it the course ID. Okay, so these are the two things that we knew were going to be UUIDs, right? They're both UUID. And both of them are foreign keys, so they're going to reference. So this references student ID. And this references course ID. All right. So knowing that a feedback is the sum of these two, this is the unique relationship. We know that these together should be the primary key. Now we can't give them the primary key on this particular key, but in order to make them the primary key, we also have to make sure that they are not null, right? We don't want that. All right. So then we have our feedback, which is of type text. And then as final thing that we needed to do was rating. And that was of type rating. Okay. So knowing that, now we need to do the constraint. So let's do constraint primary key feedback. And let's say that it refers to student ID and course ID. The combination of these two is the primary key. All right. So what's going to happen when we execute this query? Any guesses? It's going to fail. Well, it failed for a different reason. I forgot to add the primary key. Lol. But when we execute this, what it's basically going to say is, hey, you already have a feedback. Interesting. Our type feedback is conflicting with the table feedback because they're both objects in the database and they can't just have the same name. So what we need to do here, and I could go and alter the name through a query command, but let's use the niceties of Valentina to quickly change this. And if we go into design on feedback by right clicking, we could do feedback deprecated. And once we apply these changes, what's going to happen is once we refresh here and we go into the course table and we press design here, what we're going to see is if we look at the fields, we're going to have feedback and it's of type public feedback deprecated. So it's already cascaded through the system. And the one more thing we want to do, let's also call this feedback deprecated, this field, because this is our deprecated feedback. We're not going to use this anymore. We may want to query it at some point, but we don't need it, right? It's gone. We might as well even delete it, but let's just keep it there for now. So now we have our create table here. And what happens if we execute it now? Well, it executes successfully. Shocker, we don't have a conflicting element. If we refresh here again, then we can see that we have our feedback now, and it has 4 fields, and the student ID and the course ID are our primary keys. So how do we go about inserting data into this now? Well, if we do insert into feedback, we have a very different experience. So now we have to say, okay, well, the course ID and the UUID aren't going to be given to us, so we need to give it to them. We have student ID, course ID, feedback, and rating. So those are the 4 things we need to give to it. And we're going to give them in this order. And we're going to say values. So how are we going to get our values? Well, we need to get a course. So let's go and see. Let's open the data editor. We have a course. Got it. So we have a course ID. Where was our course ID? It was a second value. So in the second value, we're going to put this. Great. In the first value, we need a student ID. So let's go ahead and get ourselves a student. And let's open the data editor here. And we got ourselves a student ID. So that goes into the first value. And then we need to give ourselves some feedback. Well, this was great. And then we need to give ourselves a rating. And that could be from 0 to 5. Let's give ourselves a rating of 1,000 or 100,000 or whatever. And let's see what happens. Well, that's going to fail because the small int is out of range. We said it had to be from 0 to 5. So let's give ourselves a 5. Let's give ourselves a 4. So let's execute that, and we've inserted. So now if we go look at feedback and we open the data editor, we now have feedback from this student on this course, and the feedback, well, this was great, and the rating was a 4. And so now we can query this actively. We can query this in a smart way, we don't have to go out of our way to use array syntax to kind of mangle this stuff and write custom select and update queries and all that stuff. We can just insert, and we have a relationship and we have integrity. I can't just go ahead and say, do F2 and 7664 here, whatever the case is. It's going to error because there's a foreign key constraint. So we have safety. It's great. Overall, it's great. That's why we use the relational model. And that's why the relational model is so great. All of these constraints, these checks, these data integrity, we got it on lock. And, of course, custom data types still have their place. They're not a bad thing, but you can make bad decisions with them. And that's what we're trying to highlight here. So with our feedback table, all here, we could basically add data to this as we go. And there are 100 different customizations we could make to this data model to make it more robust, more applicable to current software needs, and so forward and so forth. But with this, we basically have successfully created a solid base for a good data model to write queries against and learn and insert data into and try things out. We've been from A to Z. We've seen everything from basic SQL commands to database commands to role management and everything in between. And now that we know how to create a database, and now that we know how to query a database and manage a database and all of these good things, well, we have to prepare for the worst case. And so that's why I want to talk about backups. Backups are so important. You may ask why. We all know backups are important. Generally speaking, the majority of the population doesn't even take backups of their personal stuff, but when you're managing databases and when you're doing this as a profession, safety first. That's what I preach. Safety first. Because disaster will strike. You will hit a scenario where something unexpected happens. You may not know what it is, and it depends very much on the scenario you're working in. Are your databases in the cloud? Are they on-premise? Do you have your own hardware? What's going on? All of these different aspects play a part in how you're going to manage this. You may ask yourself, okay, Mo, I get it. We know how to create a database. We know how to manage. We know how to do all of this stuff. And, backups are fairly easy. We can just take a full backup of our Postgres database. And yeah, you can. You definitely can. But as with everything else, when disaster strikes, when unexpected things happen, we need to have a strategy in place. And that strategy can be complex. It can be simple. It really depends on the size, the complexity. All of these things play a role. And so what we want to do here is we want to show you some of the ways that you can go about formulating a strategy around your backups, because there are many, many different ways of going about this. And it's just important that we run through it. So it's important. That's what we're getting at. It's important. Backups are vital to a system, and especially when we're talking about databases. When we're talking about databases, it's so important because this is the data. This is the crux of the company. How you store and manage your data is important. And we can't stress this enough. We can't stress this enough because something will happen. And it's important that you're in the right position, that you know the right techniques, the right way of going about it in order to manage the situation correctly. Now, what we're going to do is we're going to make sure that you have a plan. There are many, many different tools. There are many, many different ways of going about backups. But the essence of it all is that you have a plan, that you are this happy apple over here. Now, there are 3 things you need when you're thinking about backups. You need to have a backup plan. How am I going to make the backups? What type of backups am I going to make? Why am I going to make these backups? All these questions need to be answered. Then you need a disaster recovery plan. When things go wrong, people underestimate how important it is to have an operation in place. When things happen, okay, you may have your backups. You may have them all in place and all of that stuff may be taken care of. But what's most important is that, well, when things like this happen, how are we going to handle it? If a database goes down, well, how are the applications going to react? Are we just going to allow them to continue operating, or are they going to poll for a health check for instance, just a simple health check? And will they go into a quote unquote maintenance mode? The disaster recovery plan tells you exactly, okay, a database went down. What are we going to do? The applications go into maintenance mode. Everything is basically put to a stop, a halt. And these are the procedures we're going to follow. From the first hour, we're going to assess what exactly happened and why it happened. The second hour, we're going to start putting in place the backups and the recovery procedures in place. The third hour, we're going to give a status report. This disaster recovery plan tells you exactly how you're supposed to operate when things go wrong. And putting in place the disaster recovery plan is extremely important. There's many different ways of putting this in place, but what we want to do is we want to tell you, hey, these are the things you may want to think about. And then you can go ahead and try to draft a way around it, because it's important to know how to operate when things go wrong. And then the third and most important thing is when you put in place these plans, well, test them out. Always test out your plans, because you never know, is my disaster recovery plan going to work? Are all systems a go? Does my backup plan have all of the different pieces it needs in place? You need to test these things out, because if things actually happen and you can't follow your procedure to a T and there's some kind of hiccup, well, that's going to cost you time. And more importantly, that's going to cost your company a lot of money. What we don't want to do is incur revenue loss, because at the end of the day, we're operating a business, and determining what the importance is of our data is determining what the importance it is to the company. And data is one of those cruxes of any given company. You really have to have this in place, and you have to think about this. Now, you may be asking yourself, well, what can go wrong? If we're in the cloud, if we're on AWS or Google Cloud or all of these things, they do it, they handle it for us. Yeah, those are different scenarios. You may end up in a place where everything is on premise, meaning they have their own hardware, they have their own servers. And even when you're in the cloud, you need to think about your backup strategy. You can rely on these cloud services to have sane defaults, but you still need to think about these things. So what can go wrong? And these aren't all applicable to cloud versus on-premise. We took this from the most raw approach, which is you are the owner of your database, you are the owner of your data, and you are the owner of the hardware. Well, given those parameters, what could go wrong? Well, your hardware could fail. Your hard drive could be 5 years old, 6 years old, have a lot of reads and writes, just one day decide, you know what? I'm done. I'm going to sleep. And suddenly, with a hardware failure, well, what are we going to do? We have to swap out the hard drive. And there are many different layers that you could go here in terms of hardware redundancy failure, some kind of recovery plan when you swap out a hard drive. There are many different ways of doing this. RAID, R-A-I-D, is one way, a redundant array of disks. And the disks will basically hold some kind of copy of each other so that when you swap out disks, there's some kind of fault tolerance at the hardware level. Viruses, understated problem, but they can happen. You can get a virus on your system. It can wreak havoc. And what you have to do then, you may have to reinstall the operating system. You may have to flesh out you may even have to go across systems. It could infect multiple computers. Power outages, also a very understated problem. Now, when power outages happen, if you're on premise, you have to make sure that you have some kind of backup generator that's going to power your servers as the power goes out. Because hardware failures usually, if not most of the time, will probably come from a power outage of some sort. Power outages, short circuiting of components. We're working with very fragile material at the end of the day. We don't really think about it that much, but hardware is very fragile. And we have to take that very seriously. So with power outages, one strategy, have a backup generator. Hackers, another understated problem. If Twitter can get hacked and Instagram can get hacked and all of these services that seemingly have impenetrable security analysis, they pay through the nose, yet hackers get through. Don't underestimate hackers. Where there's a will, there is a way. So make sure that you have redundancy and safety, because when hackers come in, they can do whatever they want. And then there's human error. You may do something wrong. You may run a wrong query. You may accidentally delete a bunch of records. It can happen. And there's many, many more reasons that things can go wrong. These are only 5 of a list of potential hundreds of things that may end up happening. So be very careful and have that strategy in place. Think about it. Keep it in mind. How do I make a backup plan? What do I do? Well, first of all, you need to determine what needs to be backed up. What is absolutely important and what needs to be backed up. This could vary from anything. Like if we look at that list of issues that could happen, well, you may have to back up your operating system because your operating system may have certain options in place and applications in place and settings in place that you don't want to have to go ahead, set up a new system and then rejig all of these settings. No, you need a backup of that. Then you have the question of, well, do I back up my entire database? Do I back up a part of it? Always do a full backup of your database first. Always have one full backup. And then from there, you can go and decide, well, am I going to do more full backups or what am I going to do from here on out? But you need to determine what needs to be backed up. Then you can say, hey, okay, I need a full backup. That's the very first thing you need, a full backup. You need a backup of your entire database. And then you can go and decide, well, am I going to do more full backups? Is that going to be my strategy? Am I always going to do a full? That's a very good strategy. It's a potential. Then you could say, hey, let me do an incremental backup. And an incremental backup is basically saying, hey, here's my full backup. When you do your very first full backup, when you do an incremental backup, you're doing everything that changed since the last incremental backup. That's very important to note. It's everything that changed since the last incremental. If you had your very first full backup, it's everything that changed since the full backup. And then if you have your first incremental, well, if you do your second incremental, it's everything that changed since the first incremental. So that's what an incremental backup is. Then you have a differential backup. And what a differential backup is, it's always everything that changed since the first full backup. So you can already go and see, hey, this is going to be a bit faster than this is. Because this is always going to take a backup of everything that changed since that full backup. So when it comes to determining a strategy, speed is important. What's the fastest? If you're going to take, for instance, a full backup once a month, then an incremental backup will be fast because it's always going to do everything since the last incremental. If the last incremental was the first full backup, it's going to increment. So this is a good strategy if you're only taking a full backup, let's say once every 2, 3, 4 months. Then you can have all of your incrementals go over time. If you're taking a differential backup, well, you can already think, well, if it's since the last full backup, it depends on how heavy my database is. If you have 1 million users, taking a full backup is going to take a long time. But taking a differential backup, let's say, if the database had, for instance, 1 million records, and then we're taking a differential day by day. And suddenly you have a spike, and now there's 2 million records. That differential is always going to be based off of the last full backup, so you're going to have to back up 1 million records. So a differential always has to be based on the last full backup, meaning that you may want to take full backups more frequently to keep the differentials going fast. So there's different strategies in here, incremental being one of the fastest. And then you have transaction log. Transaction log is one of those things where on a day-to-day basis, transactions are happening. People are committing to the code base. Changes are happening. This is like a live snapshot of what happened that hour, that day, that whatever increment you take transaction logs at, which should be at a short interval. You want it maybe every 15, half an hour, maybe every hour, maybe every 2 hours. The more frequently you take these transaction logs, the less data you will lose. Because they're basically a hot backup and you have to have in place a policy for them. How long are you going to keep them? If your incremental happens every night, well, you only need to keep your transaction logs for that day, for instance. So a lot of factors go into this. And so when we look at it, a full backup is backup all the data. An incremental backup is backup since last incremental. A differential is backup since last full backup. And a transaction log is a backup of the database transactions. They all have different levels of freshness. A transaction log is the freshest. It has the most recent log of things that have happened. And you want to take these as often as possible because based on how often you're going to take either an incremental, a differential, or a full, you may want to take transaction logs more or less frequently. You can already think, okay, if I'm taking a full backup once a month, for instance, and I'm not doing an incremental or differential, well, then I'm going to want to keep transaction logs all throughout that month. Maybe on an hourly basis, maybe on every 15 minutes, whatever the case is, depending on how heavy your database load is. If you have a very heavy database load, maybe don't follow this strategy. All these strategies have a time and a place, and you have to decide them with a team. You have to think about it. But let's say you take a full backup once a month, and then you take transaction logs every 15 minutes of every hour of every day. Well, then you're going to keep transaction logs all throughout the month. Disaster strikes. Well, what do you do now? Well, then you have to run your full backup, and then you have to run transaction logs all throughout that month. So you're going to be running transactions. There's many transactions. So it's not as fast as, for instance, if you say, okay, I'm going to take a full backup once a month, and then I'm going to take incremental backups throughout the month. Well, now you have 30 or 31 incrementals. But if you took transaction logs every 15 minutes, you may have 200, 300, 400, depending on the amount of transactions that happened. So it's 30 incrementals happening versus 200, 300 transactions. And it really depends on how heavy these transactions are. Like an incremental is nothing more than the sum of a couple of transactions, but they're all handled differently, right? Like backing up and restoring data, it really depends on how heavy your database is and what you're trying to accomplish. And even with differentials, a differential is also great because, well, in that case, if you took a full backup once a month and you took a differential at the end of the month, disaster strikes, you only have to run one full backup and one differential. It really depends on how heavy your database is and how much risk you're willing to tolerate. Now, I read somewhere a statistic, and I'm not going to quote the exact number, but a large number of companies prefer to do just full backups. I once worked for a company where they would take an incremental every night at 3 a.m. And by the time you came into the office, that incremental will have finished, and they would keep tapes and tapes of the incrementals. And one time I actually did need to do disaster recovery, and I needed to run tapes throughout the system. And, from the history of data, they were still backing up on tapes. At the time, it was, I think, 2011 when I was doing this and running these tapes through the system. Really not a fun job, especially since business was halted that day in order to run these incrementals. So it's important to pick the right backup strategy. It's very, very important. Now, the next decision you need to make is, what's an appropriate way to back up? And what do we mean by this? What's the appropriate way? Well, when we talk about the appropriate way of backing up, it really becomes of that same question. Are we going to back up the operating system? Are we going to back up at the hardware level? Are we just going to back up the database itself? And so there's different layers to this. The appropriate way of backing up is very much determined by, well, what strategy are we going to follow? So, for instance, one strategy you could do is you could back up the operating system once a month. And then you could back up the full database once a month. And then you could do incremental backups of the database each day. And at the end of that month, you're going to back up the operating system again, and you're going to back up the database again in a logical way. So this is just us running, for instance, PG backup. This is what we call a logical backup. It's an appropriate backup. It's a way of doing a backup, but then think one layer lower. So when you think one layer lower, well, we're thinking about the hard drives. When we think about the hard drives, there are different appropriate ways to back up hard drives. You could take a full copy of a hard drive at the hardware level. You could copy section by section off of that hard drive and just create a clone of that hard drive at the hardware level. This is a very different type of backup. We're not running PG backup. We're not doing any of those software type related things. We're doing a hardware backup. We're saying this hard drive is a clone of this hard drive. So that's a different strategy. So you need to determine, hey, what's the appropriate way that we want to back up? Do we want to back up at the hardware level, at the software level, both? A lot of companies determine a lot of different things. And when you're in the cloud, all of this changes. You have to think about it differently because you don't have anything on premise. You don't actually have any hardware. So you're taking a lot of logical backups at that point. And AWS is managing all of this hardware for you. It's a big advantage of the cloud because at that point, the vector of what you need to think about narrows, right? You don't need to think about everything, the hardware, the software, all of this stuff. You're just thinking about the logical database and how you're going to back up that data. You only think about the data at that point because AWS is managing all of this other hardcore stuff behind the scenes for you. Another thing that you need to think about, how frequently are you going to back up? How frequently? That's also what you put into your backup plan. How frequently are you going to back up? Are you going to do incrementals by day? Are you going to do differentials by day? Are you going to do differentials by week? It really depends also on how busy your database is and how frequent you get transactions. If you have a very small number of visitors, transactions, all of this stuff, you may be able to get away with a weekly differential or a weekly incremental even, or you could get away with something as much as bi-weekly. Maybe you need daily, maybe you need every 12 hours. Who knows? It really depends, but you need to decide how frequently you're going to do this and how volatile your data is. This is extremely important. Then once you have that narrowed down, well, then you have to look at, well, what is the general frequency of these types that I just showed you? What's the frequency of this full backup? Well, people tend to do it less often because it takes a long time and you're backing up all of the data. Incrementals happen more often because they're a backup since the last incremental. So they have a shorter amount of data that they need to increment against, whether it be daily or every 2 days, every 3 days. Differentials are backups since the last full backup. So they can become more heavy the more data that has changed over time. So you really need to determine if they can happen often. Once they start to take too long, if the backup is still running, for instance, a day later, well, that's not a good sign because the next backup should maybe start. It really depends on how much data is changing in your system. And then transaction logs, these need to happen a lot generally. You want to keep a backup of the transactions that happen because if disaster strikes in that minute, well, you want to be able to back up to the spot by the minute where the last transaction happened. And hopefully the rest of the system catches that failure at that time and stops the transactions from happening so that you don't lose a lot of data from that point forward. Fault tolerance is extremely important in a system, and systems vary so heavily. You have apps and you have servers and you have all these things that could potentially be writing transactions to your database. So it's important that all of these systems be able to be notified when disaster strikes so that they can take the appropriate action to be put, for instance, immediately in maintenance mode so that you don't lose a lot of transactions moving forward. Or even that if your app is able to hold on to that transaction until the database is back up. There's all kinds of strategies you can do, but the frequency of the backup is also important to note. Transaction logs can, for instance, happen every 15 minutes. How do I make a plan? The fourth key point, you need to decide where you're going to store your data. And in the cloud, it becomes self-evident that you're going to store them in a cloud instance. For instance, if you're on AWS, you may store it in S3, which is a simple storage solution. But if you're on-premise, you may have backup servers somewhere, or you may have backup servers in the cloud as well. It really depends, but you have to decide where you're going to store them, and it could be anywhere in the world. Last but not least, a very important point that not a lot of people tend to think about. What's our retention policy for the backup? Now, if you're in a regulated space like HIPAA regulated space or some other kind of medical or financial space, you may have to keep records for up to 10 years. So you need a retention policy for your backup. Now, if you're taking full backups and incrementals, well, you don't want to store full backups and incrementals for 10 years. You may end up taking a full backup once a year that's going to be held as a retention policy for 10 years somewhere, and every year you swap out that backup or you keep all of them. You keep them year by year. But the retention policy for your backup is basically how long am I going to keep this data? How long am I going to keep this backup? So it's important to think, well, how long do I need to store this for? Because storage may be cheap, but depending on how much data you need to store, it may be expensive. So it's important to take all of these things into account when creating a backup. You may think, okay, Mo, well, we talked a lot about all of the different aspects that need to go into backups and a backup plan and a disaster recovery plan and all of these things. How do I make a backup? That's a good question. Let's look at that. When it comes to backups, Postgres has the ability to backup and restore built into it. And when we talk about that ability, we're talking basically about creating an SQL dump. An SQL dump is nothing more than a text file that gets generated from a database that can contain either the schema, so the tables, or the schema in the data, or just the data. And when we generate this, well, we can create dump files in very different ways. We could export them as scripts that can be easily run against a different RDBMS and is readable, or we could create them as backup files, which aren't SQL commands, generally speaking, but Postgres can understand to back up and restore more quickly. And so when we talk about this, there are many different ways of creating that dump and creating archives and all of those different things. Now, what we want to focus on is the ability for you to, in a simple way, be able to just back up your database. But that being said, we don't want to leave you without the ability to look into a tool more deeply. And so that's why we're going to point you towards PG Backrest. It is a reliable Postgres backup and restore tool that is aimed at simply and reliably creating a restoration solution. It's not shipped by default by Postgres, but it has the ability to do the incremental backups, the differential backups, all of those things that we talked about. It's very, very strong and capable as a backup solution. But for all intents and purposes, we want to give you the simplest and most straightforward way of backing up with Postgres. So let's go take a look at that. Now over here, we're in Valentina Studio. And in Valentina Studio, we are going to look at the simplest, easiest way of creating a backup in a visual way. Because running commands is cool and all, but any given software can run these commands for you. So we want to make it as easy and as visual as possible for you guys to be able to select and go through a graphical user interface, because it just makes things easier. It really does. So if we, for instance, look at our employees database, what would we do if we wanted to create a backup? Well, we could do something like create dump by right-clicking. So over here, when we create a dump, what we can see is that Valentina Studio gives us a lot of different options. And over here, you can see you can select an output format. You could select custom. You could say export it as a directory. You could say export it as Excel. You could even export it as JSON, which is a JavaScript notation. It's just an object notation. You could export it as SQL, as a zip file, as XML. There's many, many different ways. Now, the most common and the most used are either SQL, tar, or custom. And so let's go in SQL so that we can actually see what it's going to export, because we can read SQL. We're SQL masters at this point. And so then you have to decide, okay, what's going to be in my dump? What am I actually creating a backup of? Well, you could say structure only, which is going to take only the tables, their relationships, their constraints, all of those things. You could say structure and records, which is going to take both the create table statements, the constraint statements, and the data. It's also going to take the data. And then you could say, hey, only give me the data. So we're going to take structure and records, and we're going to continue here. And then we can see that you can select a dump utility. Since we're running Postgres 12, we're going to use backup utility that comes with Postgres 12. What we can see here is that we have additional options. We could include the create database statement so that we don't have to run it. We could do a clean before restore. It's going to add a clean script to a database that we're going to run against. We're going to add the create database statement though. And then when we say use insert commands, well, we could say use column inserts, which is going to specify the columns. It's going to say, well, can we use multiple row insert statement? So inserting multiple rows inside of one insert statement. So we could say, hey, do 250 rows per insert. Insert data in these increments. One insert statement inserts 250 rows, for instance. Then we could say, don't save the following. Don't save the owners of the database. Don't save the privileges. Don't save the table space. We don't want to necessarily add any of these. We could potentially drop the owner, which, as you know, the person who creates the data in the database and the tables is the owner. And then miscellaneous, you could set certain odd options that may or may not be required. So if we continue along this, well, it's going to say, I'm going to make this file in the documents, and it's going to be an SQL file. We're going to encode it as UTF-8. We don't want to encode it as anything else. And if we continue, now it's starting to dump and create the tables. As it dumps, what it's doing is it's basically generating create database, create tables, the constraints, it's doing the inserts. And once this is done, we can show it on the disk. And when we show it on the disk, what we can see over here is that we have an SQL file. So let's open that up. And what we're going to see in that SQL file is it's going to be a very, very large file. As you can see, it's gigantic. So we can see a Postgres dump. We dumped it from database version 12.3. It sets all of these different things, all of these obscure SQL commands just to make sure that the database mimics each other. We have our create database command with the template. It's going to do a connect. So it's actually going to connect to that database, and it's going to set some options on that database. It's going to create a custom type gender. It's going to set a table space. It's going to create the tables, as we said, in the public schema. And then if we go down, it's inserting records. It's inserting many, many records, and it's doing them by column name. And as you can see, like we specified, it's doing 250 per insert statement. And then the next insert statement starts, and so forward and so forth. And as we go along this route, what we can see here is that we have all of our data. All of our data is in this SQL document. You may think to yourself, this doesn't seem like a good way of backing up. And if you have an extremely, extremely large database, you don't want to store it all in this single text file. It would take forever to run. There are more efficient ways of backing up. That's why, for instance, we also do hardware backups, cloning hard drives and such as our first line of defense, for instance. There are many different ways, but as you can see, with Postgres, we have the ability to easily focus and export our database in a simple way. And as our database grows, our backup needs will change. And that's why we wanted to give you the ability to think about and orchestrate a backup plan if you need to, and look at different tooling. Because the Postgres tooling, although it can dump and it can create these nice files that have a copy of the database, it's not the most efficient way of backing up by any means. Differential, incremental, all of those different strategies we taught you, those are the things you need to focus on going forward. So with that, we know now how to back up in Postgres. So let's look at restoring. Time to restore our backup. As we said in the previous video, we created this backup that was an SQL file, and it had the create database command in it. It had all of the good hallmarks of being a file that we could first of all read. It had all of the data, it had all of the records, it had all of the constraints. Now, how do we restore it? And what I want to show you here is that the way you decide to create a backup influences the way that you're able to load it. So over here, we're in Valentina Studio, and you would say, hey, Valentina Studio can load a dump, right? Yes, it can. Let's see. You have two options. You can restore to a database, which we deleted employees, and we have our create database statement in there. So we don't want to restore to an existing database. So let's do it connection-based. And if we do a connection-based, now we're going to do SQL, and it knows that it needs structure and records. And it's already pointing to the employees file for which we created the backup. And we know it's UTF-8. And we're going to deselect execute multiple dump statements. And we're going to start running. And already we can see we have an error. So why is this happening? Well, the way that you decide to create a dump really influences the way that you're able to restore that dump. Depending on how you created that dump, it may be easier for you to actually run commands in order to figure out how to restore. When we're restoring this database, as you can see, as it goes along, it may be successful, but we already have an error. So let's take a look at what that error is once this is complete. And it's processing queries. This is a very visual way of looking at it, and it's very nice. And as we finish up here, what we're going to see is that we had a syntax error at the beginning, but all in all, it was done. So if we refresh here, we can see we have our employees database. And we can see that if we go inside of here, we have our public schema, but we have no tables. And we have no tables because the way that the SQL file was generated created that error at the beginning. So even though we ran all the queries and we did all the things, Valentina Studio was unable to process the script. Now, let's delete this physically again. And let's go take a look at how that would work if we were to do it from, for instance, let's say, terminal. So over here, we're in our terminal. And what we can see over here in our terminal is that we're able to run our PSQL command, and we can connect to a certain database. So let's connect to the Postgres database, and I don't need to use a user because it's by default going to log in. And if we do con info, we can see that because I'm using the Postgres app, I'm logged in as user education. That's all clear. Because we decided to generate our SQL script with a create database command, we could see that Valentina Studio hiccuped on the loading of the dump. Now there's different ways of generating that dump in which Valentina Studio could potentially process that, or we could even go and fix the script. But let's just load the dump as it is, because this is not generally speaking how you would load a dump. Normally you would load a dump against the database and it would insert everything into it. Now we're running a script because that's what basically what we generated is a script. So we have to point it to documents, and then we have to point it to employees, SQL, and now it's starting to insert. Now it's starting to run all of those good commands. And if we go up here, we can see that it's running many inserts, and I can't even scroll all the way to the bottom. We made it back. And as it goes through this, what you're going to see at the end is some tooling like Valentina Studio. Valentina Studio is built to process multiple database connections, MySQL, Postgres, all of these other providers. So the way that it decides to run commands may not necessarily be beneficial to the way that you want to back up and restore. So it's important to know, first of all, how are you backing up and how do you want to restore, and to use those tools directly. Graphical user interfaces, although easy to generate backups, can generally make it more difficult for you to be able to back up and restore. We would have to go and figure out a way for Valentina Studio, for instance, to generate a backup that it could properly restore. We would need to figure out how we need to adjust the script in order for it to be able to process it, because the script was built by PSQL to be run in command line, not to be run in Valentina Studio. So even though Valentina Studio can't process the script, it generated the correct script with the PSQL command. So now over here, what we can see is we did all our grants and alter tables and indexes and inserts. And if we go over here to Valentina Studio and we refresh, what we're going to see is we have our employees database back, and it has all of the tables. Even though we generated the right backup with Valentina Studio in an easy way, we can see it's easy to hiccup on the restoration part. Don't trust solely on tooling. Also know what you're backing up and how you're backing it up and how that may impact backup and restore. And with all of that being said, keep in mind that there are multiple strategies here, and they can become more and more complex as you go along. The purpose here isn't to make you back up and restore masters. These strategies are often driven by teams, operations, the corporate strategy, all different parties and all different architects coming together to think about these things, because it's extremely important. But if you're in a smaller scale and you're maintaining your own database, it's good to think about this, and it's good to know what options you have so you can dive deeper into them as you go along your SQL journey. And with that said, we were able to back up, we were able to restore, and we're good to go. We can even see that we have data in these tables. That's all on the up and up. Amazing. Transactions. Let's talk about transactions. Now, we've talked about a lot of different things when it comes to databases and the database management software. But one thing we haven't really gotten into is transactions and what exactly transactions are. Because that is an important concept when it comes to the database management software. At the end of the day, a database is a shared resource. So many users will access it concurrently. And so what this means is that when a lot of people are doing what we would call transactions, selects, updates, deletes, drops, creates, all of these things affect the state of the database. And since the database is shared, well, how do we make sure that when 5 or 6 or 7 people are accessing it, that the database stays consistent? That's where we look at transactions. Transactions are a unit of instructions. You see, with transactions, basically what we're trying to achieve is a unit of instructions that is going to run in isolation and not affect the state of the database until it's done. So with a transaction, we're looking, for instance, at a query. We've seen different types of queries, and queries can do different types of things. For instance, a select query, well, that would be what we would consider a read transaction, because we're only reading. We're not really doing anything that will alter the state of the database. But nevertheless, we consider it a transaction because you are transacting with the database. You are trading something. You are giving it an instruction. It is giving you something back. But then we have things like update queries and delete queries, and they altered the state of the database, and thus those transactions need to be warranted. If, for instance, 5 people came in and they started deleting a bunch of stuff, well, how do we make sure that if they're trying to delete the same stuff, that nothing happens? And so the concept of a transaction is to keep things consistent, right? How do we keep things consistent? This is the question we're trying to ask ourselves. And so with a transaction, we're basically saying, okay, anytime you do anything, we're going to start, quote unquote, the concept of a transaction. And whatever happens during that transaction stays in that transaction until you either decide that you want to commit it or roll it back. Database management software has a mechanism in place to manage transactions. So if you're doing 5, 6, 7, 8 transactions, if 5 or 6 people are doing update queries, they will all run in isolation within a transaction. And then it becomes a question of, if someone is going to commit those changes, then it becomes a question of, well, who's first? And that's where the database will get smart, and it will lock certain resources while an update is happening so that other transactions won't get into a weird state. It becomes very smart in this scenario. So when we look at the life cycle of a transaction, we see that a transaction will start. So you're running your query, right? And it goes into an active state. And so when it goes into an active state, well, then it's going to run itself. And so then it's going to execute itself. This is what we call partially committed. So when it's partially committed, it's executed itself. But if it fails for any reason, well, then it'll get aborted. So if it fails because something else is utilizing that resource, or it just failed because of a query mishap, then it will go into a failed state, it will be aborted, and the transaction will automatically be ended. But if you're partially committed, and let's say you like the state of whatever you did, an update, an insert, whatever, well, then you're going to commit that transaction. And then you'll end up right back at the end of the transaction, and you're at the end of it all. Let's take a look at what that would look like. So over here, I'm in my command prompt again. And as you can see, I am connected to the database employees as the user Postgres. And so what I wanted to show you here is basically a couple of things about transactions. And there are many, many, many things that you can say about transactions. It's a very, very deep topic that has a lot of nuance, a lot of architecture surrounding it. Every database management provider will handle transactions in different ways and have different concepts of how to manage all of this stream. But basically what it boils down to is when you run an update command, when you run an insert command, or when you run a select command even, all of these are inherently wrapped in a transaction. Your database management software is already wrapping it in a transaction for you because it knows that these are transactions. Now, granted, for select statements, you will never get into a state where it potentially may fail because it's a read-only transaction. But for updates and inserts and deletes and drops and all of that stuff, yes, you could definitely run into a scenario where an update or an insert will fail because another transaction is happening that's trying to do something with a record. And so the database management software tries to orchestrate this with transaction. And these commands are already wrapped in a transaction. But let's say you wanted to go through the process of creating your own transaction and running multiple things inside of that transaction other than one update statement. Well, what you would do is you would write begin with a semicolon. You have to use a semicolon. And when you begin, now you're in a transaction. Now I can't run begin again because what it'll say is, hey, there is already a transaction in progress. Don't create another one. We don't need this from you. You're already inside of one. So now that I'm inside this transaction, I could say, for instance, delete from employees where and I could say the employee number is between 10,000 and 10,006 or 10,005. Let's go 10,005. And don't forget the semicolon. Every query in a transaction block has to be denoted with a semicolon so that it knows what it's doing. Okay, so now we've deleted 5. And if we select star from employees, well, then you can see that they're gone. We're starting at 10,006. So it's happened. This is what we would call a partially committed state. We're there, but we're not actually executing it just yet. We're in a partially committed state. It isn't really on the database just yet. And the way that I could prove this is if I went into a different terminal and I did PSQL Postgres U and I did select star from employees here. Let's up this a little bit more. What you're going to see happen here is I still have 10,001, 10,002. Now this is a different connection, right? I connected with Postgres, but I have a secondary connection. This is not the same session. This is a separate session inside of Postgres. So these are two separate sessions, even though I have the same user logged in. Now over here, you can see when I do my select, in this session where I'm in a transaction, I've deleted 5 records. But in this session over here where I'm just connected to the database, I don't have that transaction yet. Okay, so what would happen, let's say if I did a transaction here as well in this session, and I said, well, you know what? Also delete from employees, and let's say the same thing, where employee number, and then between 10,000 and 10,005. Okay, well, I'm trying to delete from employees where my employee number is between 10,000 and 10,005. But as you can see, it's hanging. Nothing is happening. Why? The resource over here is being locked. You see, I'm in a transaction over here, and the resource is being locked. So let's say that I, for instance, said over here, okay, I don't want to commit this. I'm going to roll this back. I don't want to do what I just did over here. Well, then I'll roll back, and then over here you can see, oh, it suddenly deleted 5. It suddenly deleted 5. Interesting. Now, what this is called is locking. So the resource was locked in this session over here, and when I rolled back, I basically said, hey, end this transaction. I don't want what's happening here. But over here, we were stuck on the delete. It wasn't executing, it was holding, and that signified to us that there was a lock on that resource at that second. Now, usually the resource wouldn't lock for that long. It would occur, and then maybe something would happen. Now, if we went back over here and we did another transaction block, and then we decided, let's do the same thing over here, let's do the delete again. Well, now this resource is not going to execute because this transaction is still in flux, so it's rolling. So if we were to commit this, so you could either write commit or you could write end. Well, now we've committed it. And if we go over here, it's going to say deleted 0 because the other transaction committed. So suddenly this one didn't have anything to delete, and we deleted 5 employees. So interestingly enough, the way that a database manager manages transactions is through wrapping things in these transaction blocks. And over here, I'm still in a transaction. If I said end, well, now I'm out of my transaction. I committed the changes. No changes actually happened. So these transaction blocks are the way that the database manager basically handles the ability for multiple sessions to go back and forth and try things out. And then if they roll back or if they commit, it may affect other transactions that may be trying to do the same thing or try to change the resource in a different way. So basically what it comes down to is in a transaction, when you're in this partially committed state, what you decide to do, whether you decide to commit or abort, really determines how other transactions are going to play out. As you saw, resources get locked while transactions are happening and they are in this partially committed state if you're trying to access or do something to the same resource. So as we said, update, delete commands, insert commands are inherently wrapped in a transaction. And while they're executing, other resources can't just go and partially commit against it either. You saw that with our delete, our other delete had to wait until the transaction ended. And so this comes down to the properties of a transaction. The properties of a transaction dictate why things happen this way. To maintain the integrity of a database, all transactions must obey the ACID properties. No, this is not some science experiment. We're not going to play with actual ACID. The ACID properties are an acronym, and they stand for, first of all, atomicity. You either execute the entirety of the transaction or none of it at all. The transaction has to happen entirely or none at all. So as you saw with our delete transaction, luckily it went through after the other transaction deleted 5 records, but it just would delete 0. But if that delete had failed for whatever reason, if the transaction contained like 6 or 7 or 8 queries inside of that transaction block, when you start a transaction block, you can run 6 or 7 queries in sequence and see the state of the database in a partially committed state without it affecting other sessions. But then when you want to end or commit the transaction, if any of the commands in that transaction fail, your entire transaction fails. So you have to execute it entirely or not at all. Now, the second, or the C in ACID, is each transaction should leave the database in a consistent state. It either has to commit or roll back. So if the transaction succeeds in whole, it's going to commit. Or if anything in the transaction fails, anything at all, any of the queries, it's going to roll back. So if your transaction fails, you may have to go and adjust your transaction in order for it to commit. So each transaction should leave the database in a consistent state. This is a hallmark of a transaction and should always happen this way. And that's the way that database management softwares implement transactions, so that they always leave the database in a consistent state. Then the I in ACID, isolation. Transactions should be executed in isolation from other transactions. Okay, this is important because when we look at transactions, they can't go and affect each other. They're both basically, think of it like them executing in 2 separate sandboxes. So you start a transaction, 2 sessions start a transaction. Well, now they both have access to the same database. But what's actually happening is they've created this little sandbox in which they can play. They can update, delete, insert, select. They can do all of these things within that transaction. And then when they decide, hey, I'm going to commit, well, that's when the database management software kicks in and says, well, this transaction is doing these things, so what you're doing may fail. And so the order in which transactions occur is very important. If transaction A happens before transaction B, transaction A may affect how transaction B will execute, because transaction B may trying to access the same resources. And so if they're trying to access the same resources, if transaction A goes first and it does something, it may cause something in transaction B to fail. So this one is going to roll back probably. But what we're trying to say here is that transaction A and transaction B started off with the same sandbox. But what happened in transaction A isn't known to transaction B until time of commit or rollback, because the database management software is going to say, hey, transaction A occurred, transaction A, B, C, D, E occurred, and now you're trying to do this transaction. Well, you started off way back when transaction A occurred, so let me see what happened in that meantime. And then it's going to say, hey, you can't execute this because something's going to fail because you're doing an insert or an update or something wrong in here that may fail because all these other transactions did something to that as well. So they happen in isolation from each other. They don't really know what each other is doing. But at the end of a transaction, the database management software is going to go and it's going to say, hey, I'm going to check out what you're doing. I may make something fail because all of these other transactions happened that may have touched the same resources that you touched. So isolation is important. They may start at the same begin point, depending on when the transactions occur. They're in isolation from each other. So transaction A and B are touching resources in a sandbox. And only when they decide to commit or roll back does it actually matter to the database management software. And it's going to orchestrate whether a transaction can commit or has to roll back. And then the D in ACID, durability. After the completion of a transaction, the changes in the database should persist. There is no halfway here. When your transaction commits, it is in the database. It has happened. It's done. There is no ability for it to be in a wonky state, a partially committed state. No, this is how it's going to be. So each transaction must in turn have durability. The completion of a transaction means that that data, that change that you did, is persisted. It's persisted in the database and it's there. And so with all of this, foundationally what we're looking at here is that unit of operation that we call transactions that is trying to make the database consistent, right? What we're trying to do here is follow those ACID properties and make it so that when people operate against our database, that the database will never be in an inconsistent state. That's what you don't want to happen. You don't want 5 updates to occur and suddenly a record to be corrupted. You don't want it to be corrupted. That would be horrible. So that's why a transaction follows this sandbox approach and this begin to commit approach and locking the resource, right? It really wants to make sure that transactions happen in order and that they are ACID compliant and that whatever happens in that transaction is durable, that the database is durable. And there's so many more things that could go into transactions. But foundationally speaking, we're talking about that operational consistency of your database and your data. And transactions are just that unit of operation.
Hey, wake up over there. Whoa, you just wake up from your daydream. Felt like you were daydreaming for a long time. But Bruno says you were just gone for 5 minutes. Are you going to solve our problem or not? Can you figure this out? You look at Bruno and say, yep, no problem. I'm an SQL master. So you start talking to Bruno, and Bruno gives you 2 pieces of information that is crucial to the case. First is clue number 1. Bruno tells you that there is no way anybody could have accessed this information unless there were employees. Their security practices are really, really good, and they needed internal access to gain access to the data. So it has to be one of Keiko Corp's employees. The second clue is that the data breach happened during a certain time. Bruno is not certain, but he knows that this breach happened during a certain period. Now, using these 2 pieces of information, you'll need to solve this mystery. Along the way, we're going to give you clues that we find. But right now, using these 2 pieces of information, we can get some interesting data. The 2 pieces of data that Bruno gives us access to is 1, the employee database with all the employee records, and 2, a security camera database that collects data on which cars come through the Keiko Corp office and the parking lot. Maybe using these databases and these 2 clues, we can get a little bit further in the case. Let's get started. All right, good job getting this far. We're getting closer and closer, and we just got a 3rd clue from Bruno. He told us that in order to even grab the data from their offices, you had to be on location to steal the data. So what does that tell us? Well, it tells us that whoever was on premise at Keiko Corp during that time, any car that was in the area during that time that was caught on the security footage could be a suspect. Perhaps if we take a look at which cars came through the office, maybe the drivers or the passengers are one of the culprits. Let's think about this.
Oh gosh, I'm so excited. We get to solve a mystery. Now, it's unfortunate that data was stolen and breached, but there's nothing better than solving a good mystery. And so far, it's been exhilarating. We've gained a lot of insight into Keiko Corp and their core product offering. And we know 3 clues so far. We know that it was an inside job and we have the employee database up and ready to run. But before we do that, before we get to solving the mystery, we first need to figure out what exactly happened here. Although we know that information was stolen, we don't know who did it yet. And we know the date on which it happened. We know that it happened at the office. But who did it? Who did it? This is what we're trying to solve. And so with the clues we have, we should be able to figure out what rides happened near the office on that day. And so we went ahead and we tried to figure out, hey, well, in vehicle location histories, we should be able to get the locations of the vehicles that were in and around the office on the day of the atrocity that occurred at Keiko Corp. Now, when we select everything from vehicle location histories, and so we go ahead and we filter on the city, we know it's in New York for sure. That being said, we also know the exact longitude and latitude of Keiko Corp. So we want to know specifically which rides occurred very, very close to the office. So we go ahead and we filter the longitude and the latitude between the exact position of Keiko Corp. And we filter on the exact day of the atrocity. And we can order by longitude if we want, not necessarily a step we need to do. But when we execute this, what we see is that exactly on that day around the office, 428 rides occurred. And knowing those rides, knowing specifically which rides happened, well, 428 sounds like a lot of rides, but given that it's Keiko Corp's #1 product offering and we serve millions and millions of clients each day around the globe, given that only 428 rides occurred around the office on that day, well, that is a blessing to us because it narrows down our pool so much so that we are now able to go ahead and, based on these rides, interrogate the drivers. And so what we decide to do is we decide to create a view of the suspected rides. That way, we will always have the same information and we don't have to rewrite this query in order to get the same results. And we can do whatever we want against those results. So we create a view called suspected rides. And by doing that, we now have the information stored in a view and we have it safeguarded. Bruno is exhilarated. We're one step closer to solving the mystery in his mind. Although we're not very far, we have 428 rides. So what we need to do now is we need to narrow down those rides to the drivers. And so what we decide to do is we decide to query that view, suspected rides. And we decide to get the vehicle IDs. And by getting the vehicle IDs and other information, we're able to figure out who was driving the car. And what we find by running this query, by narrowing it down to the specific vehicles that did the 428 rides that day, we find that it was 89 vehicles that did it that day. So by selecting the distinct vehicle IDs, we figure out that those 428 rides were done by 89 drivers. So we've gone from 428 suspected rides to 89 potential drivers that may know something. Bruno is jumping out of his chair. He doesn't know what's going on, but he knows 89 drivers may know something. But this information isn't enough to go on. So Bruno wants you to narrow down the exact owner information of each and every owner of one of these vehicles. And so that's exactly what we do. And so the query we write is a multi-join where we're joining on the rides, joining on the vehicles, and joining on the users. And what we do there is, based on the suspected rides, we get the ride IDs that are correlated to it. Then we go look at the vehicles and we say, okay, where the ride vehicle ID matches the vehicle from the vehicles, let's get that information. And then we say join the user table, because from the vehicle, we have the owner ID, and that should match a user in the system. And then we'll find the specific owner. And when we execute that, we find the 89 specific drivers that were in and around Keiko Corp that exact day. That exact day. And so Bruno says, Go interrogate all 89 of them right now. And that's exactly what we did.
You figured out all the vehicles that were on premise during the time of the data breach. So you go ahead and interrogate all the drivers. And, nothing conclusive. You don't really uncover anything, and none of the drivers seem suspect. So here's your next clue. It's not the drivers. It's most likely one of the riders. Let's find out which riders were in the area during those times.
Well, that was a bummer. All that work interrogating those 89 drivers, and we came up with nothing. But Bruno hasn't given up yet. He knows that someone in this mover database has something to do with this. He knows that it will lead to something good. So he asks us, okay, we interrogated all of the drivers, but what about the riders? So we go ahead and we figure out what riders specifically took those suspected rides. And we do it in a distinct way because we don't want the duplicate information. People may have taken multiple trips that day. We don't need to know specifically how many times they took a trip. We just need to know who was on that trip. So we go ahead and we interrogate all of the riders. Now, this is a very simple query. We just join on the rides, join on the users, and we match the user ID based on the rider ID. With that, we go and interrogate all of the riders.
Oh boy, this is a lot tougher than you thought. You just interrogated all the riders that were in the area, and there's nothing conclusive. They all seem innocent, and nobody says anything bad. But you know that one of the drivers or riders is the culprit. It's not the riders, it's not the drivers. But then, luckily, there's a breakthrough in the case. You get another clue. And this clue is a big one. Somebody calls you from an anonymous phone and says, this was an inside job. That somebody on the outside was helped by an employee on the inside. And that's what Bruno was saying. Only employees could have done this. But it wasn't just one person. It was two people that collaborated together. But who could have worked together? Let's take a look at the employee data and the drivers and riders and see if there's any commonalities between them. Whether some of these drivers or riders knew somebody at the company.
We are so close to solving this mystery. Now, granted, in this last clue, we left you to investigate and learn new concepts. DB link, a new string function, split part. And we didn't do this without reason. We believe that at this point, you should be able to go out, read documentation on SQL, and figure out how to apply it. Granted, DB link is one of those things that is a bit more complicated. So, if you didn't get the right solution right off the bat, that's okay. Linking across databases is quite difficult. You could have just as easily written two queries and correlated them manually across both databases. But Postgres gives us a function in order to connect to two separate databases. So we wanted to hand you the information and the documentation around that concept and an example and see if you could write a query that would cross-reference mover and employees and figure out once and for all what happened at Kaiko Corp. Okay, so first things first. In order to solve this mystery, we needed to figure out the suspected rider names. Okay, so how did we do that? Well, in order to do that, we needed to create a view. In that view, suspected rider names was our existing suspected rides where we got all of the riders, right? Now, there was one specific thing. There is a difference between the employee database and the employees. We split the first name and the last name in the employee database. But in the mover database, when we look at the users, everything is in this one name field. Poorly normalized, one would say. But with that said, we have to go ahead and work with that data as if it was normalized properly and we split out first and last name. So how would we do that? Well, we would take that data from the suspected rides, and we would take the user's name and we would use a function called split part, where we split on the spacing in the name, and we took the first part of it and we called it first name, and we took the last part of it and we called it last name. And because we're putting it in a view, what we're doing basically here is we're acting as if it was its own table. Okay, and so now that we have that, if we select star from suspect rider names, what we're going to see is that we have all of the riders' names and they're separated into their own columns. Okay, so now we can use this information to correlate against the employees. Now comes the hard part. How do we set up our DB link correctly? And so over here, you can see the query. And so let's start at the from clause, because the from clause is where all the magic happens, right? Assuming that you've already created the DB link extension and you've already run that and you have it available on the Mover database, what we're doing here is we're selecting a DB link. So we're linking to an external database on the same server or on a different server, because when we do DB link, we can give it a host. So we can tell it where to point to. It could be local, it could be an external one. And we're telling it what user it can log in with. So we're giving a username and a password. And if you remember our database management section, this is important because we need to authenticate. If it was external, it would be extremely important. And then we give it a DB name. So we're saying select from employees, right? So we're linking it to employees. Okay, now comes the funny part of DB link. When you execute DB link, the second parameter is the query that you want to execute on the external database. And so the query that we want to execute on the external database is select first name and last name from employees, because we want to cross-reference them. Okay, if we want to cross-reference them, now comes the funny part. When you do a DB link, it expects you to create a column definition list for the returning data. So that's why we do the alias as T1. And we say, okay, we selected first name, so give me the first name column by name, and give me the last name column by name. And there's one more thing we're missing here. You see, once we execute this query, we're going to know who did it. But my join needs to be on the suspect rider names, because that is the view we just created with all of the suspect rider names. And I'm joining on it on the last names being equal. Okay. But there were 89 rides, so there's one more thing we may need to do. Now, when we execute this query, we're going to narrow down our pool of suspects. Now, when we execute this, what we're going to see is that we have a lot of results, right? But we're having duplicate results as well. We're having duplicate results. So, another important part of this is the distinct keyword. Because you may have taken a ride multiple times and we're not filtering out that potential. You may have taken a ride to and from. So when we do the distinct keyword, we now have our 11 suspect employees and who they may be related to. Interesting. With this information, we'll definitely be able to solve the mystery.
There you have it. The 11 suspects. It looks like their relationship is that they're family, or at least they have the same last name. So somebody in this group worked together to steal the data. But why would they do such a thing? Bruno has been an excellent boss. He tells us that everybody loves working there. But we're not sure yet. So we investigate and interrogate every single person, every one of these employees, and finally, somebody confesses. Right here, Park Morris. Out of all our employees, after interrogating them for hours, Park Morris confesses. It was him. And what was the motive? Park has been working at this company since 1989. He's put his heart and soul into Keiko Corp, and he helped build it. But Bruno had stopped promoting him. Bruno just loved talking about himself, his perfect hair, and Park just had enough of it. He wasn't getting the recognition that he deserved, and he was sick and tired of Keiko Corp. So he wanted to take matters into his own hands. He had access to the database, made copies, and then handed off that data to a family member that came to visit him so that it looked like he was at work the entire time. But luckily, because of our SQL knowledge, we're able to solve this mystery. And you know what? Congratulations. Because you tell Bruno what you found, and Park agrees to give you back all the data without selling anything before it was released to the public. So Bruno is super excited. He thought he was going to get fired, but he also learned an important lesson here. You got to be good to your employees, Bruno. Stop talking about your hair all the time. Anyway, you look at Bruno and he says, "What? What are you looking at?" And you remember something he mentioned. He said, "You're going to get an awesome present for helping us out if you solve this mystery," which, because of your SQL expertise, we're able to do. So, Bruno, what's our present? And this blows your mind. That's right, Keiko Corp's latest duck robot. One of the most sought after high-tech toys on the market. You can barely find it, and Bruno gives it to you in your favorite color, duck yellow. Give yourself a high five because you earned it. Congratulations. Mystery solved. Until next time. Bye-bye.
All right, hey folks. So far we've seen a lot of different things. We've seen everything from database management to SQL, advanced and basic concepts, and we even did some backup strategies. We looked at transaction management, but the one thing we didn't look at is system design. And it's one of those things that when you're looking at building software, when you're looking at building a system design is critical. Now, in this part of the course, we're specifically going to focus on database design and how to design databases. But I wanted to give you the overall principles that go into system design and what exactly it entails. And to do that, we have to look at something called the SDLC, or Software Development Lifecycle. You see, when we develop software, we go through phases, and these phases are there in order to give us a guideline of specifically what should happen. There needs to be structure, otherwise there is chaos. And so the software development lifecycle, what it basically says is, hey, broadly speaking, when you build software, you're going to go through these phases. And these phases depict what exactly is going to happen, and one cannot happen without the other. And throughout the ages, we've adapted and adjusted this process to better fit our modern needs. Think of agile software development, which is a methodology of the software development lifecycle. It is an application of these phases that fits a fast-paced development lifecycle where you constantly iterate. So, when we look at the software development lifecycle, what we're basically looking at here is these phases. And in phase 1, when you're doing software development and system design, when you're trying to build out a product or some kind of software application, you're going to want to do some system planning and selection. Then you go into phase 2, where you're going to analyze that system. So over here, we went and said, okay, I broadly speaking want to build this. These are kind of the features I want. This is the reasoning behind it. This is everything every single one of these pieces needs to do. So you're kind of planning out what the system needs to do. And then you go into phase 2, system analysis. Based on what we want, what do we need? Do we need databases? Do we need mobile applications? What kind of things do we need to put in place? What kind of teams do we need? What's the allocation going to be? You're going to analyze what the system actually needs. And then when you have determined what kind of parts need to be in place, you go and you design the system. And when you design the system, what you're basically doing is you're creating architecture diagrams. You're trying to figure out, okay, based on what was determined in phase 1, what exactly do we need, broadly speaking, when we looked at our database design? We spoke of entities and things like that, and we would determine what kind of data needed to be stored against those entities. So phase 3 is really where you're taking a step back, you're looking at, hey, okay, so now that we need to actually build this, let's put in place more concrete diagrams and requirements, and let's refine everything a little bit so that we have a concrete design. And then in phase 4, you go into system implementation and operation. So after you build it, you operate it. And the reason that you see these arrows flow back and forth is because it's a life cycle. A system is never completely finished. You're always adding on and tacking on to it. You may have an existing system. You're still going to follow this life cycle. It doesn't have to start from zero. You may have an existing product, and every time you want to add on, you need to, broadly speaking, follow these phases in order to have concrete, solidified plans. Otherwise, you dip into chaos and you cause burnout, and people are running left and right, and things in stage 3 and 4 are constantly changing, and you're feeling the pressure, and it's going and it's going and it's going, and it's not really a fun experience. And so when we look at the software development lifecycle, we need to specify the goal. And the development lifecycle literally stipulates the phases we go through. And the purpose, the goal of this is to design robust systems. What we really want at the end of the day is a system with low coupling and high cohesion. What we're trying to say there is that we're trying to build a system that is independent enough and not coupled to all the pieces that we can always add onto it. We can add modules onto it. We're not stuck. You know, often you walk into a company and they have all these existing systems and you can't really untangle them because they're so intertwined. Changing one thing is a ripple effect across 5 other parts, and it becomes impossible for you to touch anything. The goal of the software development lifecycle, if followed properly, is to design robust systems that we can add on to. And adding on to it and being able to change things, well, when we talk about that in an architectural sense for robust systems, we're talking about low coupling. The parts aren't coupled together, and high cohesion. Everything works together properly. So, the process of the software development lifecycle, I referenced Agile before. The process of the software development lifecycle is just a step of, broadly speaking, a couple of phases, trying to tell you, hey, broadly speaking, we need to do this, this, and this, and we need to flow it in this particular direction. Now, the process of the software development lifecycle can be implemented in different ways. You see, we spoke of Agile, which is a methodology that is common in modern software development. And what Agile means is literally what the word stands for. You pivot, you try to move rapidly, you adjust as you go. And so what you're basically saying is these 4 phases, well, they're constantly moving. They're moving at a faster pace. You see, when you see these 4 phases, you may think, okay, I need to do them independently and slowly and meticulously. And yes, you should do all of those things. But that doesn't mean that one part can't happen before another part happens. You see, requirement gathering and implementation in Agile are pulled closer together so that you can continuously ship. You don't want long processes. Hey, so I got these new requirements. Well, that's going to take you 6 months to ship. No, in Agile, the whole purpose of it is to ship frequently and test. Then you have good old waterfall. Waterfall is all about the process needs to be followed in a regimented way. And in some industries, you cannot get out of this cycle. You have a lot of people that preach Agile everything and use Scrum, which is a methodology of Agile, and you can't Agile everything. If we were in the healthcare industry, for instance, and we're building this software that's used to monitor patients, well, you don't really want them to constantly ship that software with updates because you don't want bugs in that software, in that heart monitor or whatever. You want that to be well tested. You want that to be rigorously battle tested for production. It cannot go through one day to the next changing it up. That it could cost people's lives. So that's why waterfall is there. It's a regimented process for industries that are heavily regulated. And in the modern times, we forget because we're building all these fast-paced products, Facebook, Google, Twitter, Snapchat. We forget about these industries that are heavily rooted in process and can't actually break out. And so their software development lifecycle is much slower than an Agile lifecycle because they follow a regimented pattern. And then you over here have the V model. And the V model is a model that also dictates a software development lifecycle that is more V-shaped. You see, you're going to follow the same process of phases 1 to 4, but you're going to do them down and then you're going to do them up again. And the reason for the V model is in hardware, you have very slow life cycles, and this process used to be heavily used in that industry. Now, that's not to say that all of these methodologies are still used or still used as frequently. They change, they adapt, people implement them differently in their companies, and it really depends. You also have something called Scrum Fall, where the development team will operate fast internally, but the process outside of the development team will be a bit slower. And so what we're basically trying to get at here at the end of the day, because I'm throwing a lot at you. I'm throwing at you the software development lifecycle and the 4 phases. And then I'm throwing at you that, well, these 4 phases can be implemented in different ways, and it's all a lot. But the core principle of this, and the core that you have to keep in mind, is that any time you build software, broadly speaking, you're going to follow these 4 phases. And these 4 phases, well, they're there because software needs to be built with a certain structure. There needs to be a certain order in place. Now, as I said, these different models cycle through different steps at different paces. So the agile model versus the waterfall model of the software development lifecycle, well, they'll go at different paces. They're not the same. And so it's important to remember that depending on what model you're following, you may follow a different pace. Now, in modern software development, waterfall is basically the root of all evil. Do not do it. It's horrible. It's bad. And it is slow and it is painful to work through. But the reality of business is that a lot of industries are still in this model. And you have to be able to work with them and you have to be able to help them out, get out of this cycle. Now, for that to be a thing, they need to want to be helped, of course. But the software development lifecycle, broadly speaking, does follow different paces depending on the strategy you implement. Now, I want to dive deeper into the software development lifecycle, and let's go take a look at phase 1, because I quickly glanced over what happens in each step, but it's important to know what exactly is happening. So in phase 1, what we're basically doing is requirements analysis. And this entire phase is about getting the information that needs to be done. We call this scope. You're trying to figure out what is the scope of what I'm trying to accomplish. What am I all trying to build? Then in phase 2, you go into the system analysis. And here you're basically, if we boil it down, taking in those requirements and analyzing if it can be done on time and on budget and what all will be needed. So you're trying to figure that out. Then if we go to phase 3, you're looking at system design. And here, we're designing the system architecture for all related components. We're trying to look at every individual component, databases, apps, websites, and we're going to create a system architecture for it and kind of glue together how the pieces will work. And then in phase 4, we're putting on our building hats. We're going to the building site and we're starting to build that software. Now, you may be thinking to yourself, Mo, well, there's only 4 phases. Could there be more? And I'm like, yes, there definitely can be more. Testing can be a phase, an entire phase. Testing is a phase in so many industries, in the medical industry, in the building industry, and all of those industries. Testing is important. I would say in every industry, testing is the most vital part of anything. Test. We so often ship software without testing. How would we know if it works? And then if it breaks and we fix it and we don't retest it, testing is so vital. And then you can have a maintenance phase and you can have different phases. And if we look at the software development lifecycle, well, depending on the strategy you implement, testing should be a continuous thing in phase 4. It shouldn't be a separate phase that happens after phase 4. And this is what Agile preaches as well. You should keep the implementation and the testing as close as possible. Because let's say you went into a hole for 6 months and built software and it wasn't tested. And then suddenly you ship it to a separate phase for testing. And then it has to come back to you. And then it has to come back to you again and come back to you again. Test early, test often, test as frequently as possible. Tightly knit that phase of testing to the implementation and operation. Now, you could consider it a separate phase. We've made that mistake in the past in the software development lifecycle, and what it causes is an infinite amount of pain for the developers in phase 4 because they're constantly coming back. So these phases aren't hard set. They're a guideline, and you can determine in each phase what exactly you may need. If you need to pull testing closer to phase 4, pull testing closer to phase 4. If system design and implementation need to be closer together because you need to pivot on the fly, pull them closer together. It's okay, but just have the communication structures in place for reporting, because it's important that everyone in every single part of these phases knows what's going on, and you need to communicate. You need to be a unit, a team. Now, I'm talking a lot about all of these different phases and all of these different practices, but in reality, we're going to be focusing on phase 3, and we're going to be focusing specifically on database design, because so far we've been playing around in phase 4, which is implementation and operation. But now we'll be taking a look at how you can do phase 3 for databases. And the reason for that is, hey, look, we've played around with SQL. We know the advanced concepts. We know backups. We know all these things. We know how transactions work. And now, well, when databases get made, we kind of looked at how to make databases from a creation standpoint, a implementation standpoint, the create, update, delete queries. But we haven't really looked at how do I actually go and build that entity diagram and what all goes into it. Phase 1 and 2, that is a completely different set of life cycle. It's closer to the business. But 3 and 4 are so tightly coupled. It's important, I find, for you as individuals when you're looking at databases and when you're looking at database operation and SQL in general, well, you can know all of the query language you want to play around in this realm. But it's equally important to understand how system design works. And it's a long trajectory to master system design. But getting the foundational basics and concepts in place will help you in your job understand and operate more efficiently. So we're going to take a close and deep look what system design looks like for databases. So let's get into that. Let's dive a bit deeper into system design, the third phase in the software development lifecycle. And so far, when we've looked at the software development lifecycle, we've broken it down into these 4 phases, and we've looked at each individual phase at a high level of what it is trying to accomplish. Now, throughout these 4 phases that are highly abstract, phase 1 and phase 2 are phases that really happen behind the scenes with business stakeholders and so forth and architects of a higher level. And phase 3 and 4 come closer to implementation, design, and software programming. Now, when we look at database design, what we said is that before you go and implement a database, you need to design it. And it is one of those things that, unlike software, and unlike just hitting the floor running, when you go into a database design, you can technically start from create table and all of those different things and just go as you want. But it isn't really fruitful. It becomes very difficult for you to have that upfront picture in your head. So thinking a bit about the design upfront in phase 3 is what we're going to give you some toolkits for, some skill sets. We're going to build some of those skill sets that you want to utilize to think upfront before you go into the create database, create table, alter database, all of those SQL commands that we learned. Before you go and use those, we need to think a bit more abstract. We need to take a step back and really look at what we're trying to accomplish. And so what we're trying to do is we're trying to go from chaos to structure. That is what system design is all about. Creating structure that can be understood and communicated. Because at the end of the day, what we're trying to get to is a common goal. Software is all about enabling business. Of course, there is parts of it that are free and expressive and very, very fun. But at the end of the day, when you're getting paid to implement databases, implement software, you want what you are creating to be able to be understood and communicate it clearly. And that's one of those things that queries, although they are readable to us, when we want to bring them to business people, to other people, you need to understand and communicate them properly. And what system design is all about is taking those things that the business people came with, boiling them down into high-level diagrams that, although they are still technically more technical, that what you are doing is taking in what business people want to accomplish. Let's just talk about them as stakeholders, what stakeholders want to accomplish, and form a structure around it. And you want to be able to communicate that structure. That is what system design is all about. Now, when we look specifically at database design, what we talk about is, in any system, there is data. I would argue that data is the most important part of the system. It is the thing that drives the day-to-day operation of any business. You are holding a piece of infrastructure that can cripple a business. And in any system, the data that is used is vital to the operation of that system. And when we talk about a system, we're talking about, hey, I want to build some kind of software. Let's take Facebook as an example. Facebook as a system has multiple parts. It has the mobile apps, the web apps, it has the databases. And when we look at the ecosystem of social media that is Facebook, in the system, there is a lot of data. And when we design that database, we want that design to reflect the requirements that that system has, right? Now, there are different techniques to design databases. And these techniques, what they're trying to accomplish is indeed creating that order from chaos. When we design databases, what we're trying to do is formulate something that will hold data in a way that can accomplish what the business needs as their requirements. For instance, let's take a step back and let's look at Uber. Their main goal is get people to order cars and get from point A to point B. And so when we design a database for Uber, our main goal is to hold the data that will accomplish that need. And so we need to formulate a design that encompasses all of those requirements. Now, at its basis, it's getting people from point A to point B, but there are so many more requirements. Like, what type of car do you want? Do you want Uber Pool, Uber Lux? There are many different things that go into this design. Now, when we talk about database design, there are two very, very popular ways of designing. Now, we're getting theoretical here. And when we get theoretical, it becomes very easy to get lost. And I don't want you guys to get lost. So we're going to break this down in a way that is very, very simple. And we're going to use some diagrams along the way to make it very clear. So let's take a deeper look at top-down versus bottom-up design. When we talk about database design, we're coming into the third phase of the software development lifecycle, right? We're coming into system design before we go and make our databases and after everything has been done on the back end. Now, depending on in what phase your company is in, you can either do top-down or bottom-up database design. I hear you saying, Mo, what is this? What is this top-down, bottom-up stuff? I just want to create databases, and that we will. But when we get into it, when we really look at it at a high level, and I want to give you that high-level thought process, because at the end of the day, what makes you the best type of database engineer, software developer, is being able to think abstract and communicate clearly. Those are the skill sets that will get you the highest paying jobs. Now, there is raw technical skill involved. Always there is raw technical skill involved, being able to write those queries and create those databases. But don't underestimate the abstract thought process and the communication skills. They are vital. Now, when we look at database design and we look at top-down versus bottom-up, we need to define what they are. And when we look at top-down, what we're trying to say here is you're starting from zero. There is no existing system. There is no existing data. There's nothing in existence. A company is just coming to you and saying, hey, I want you to build me this product and I want it to do roughly this. And you're going through the first and second phase of the software development lifecycle, which is, the analysis and the requirements gathering and trying to formulate that deep knowledge. You're trying to understand very clearly what the starting point is of the product and what its goal is. And then once you get all that, once you get all of that information, well, when you look at top-down, it is the optimal choice when creating a new database. That's what it boils down to. You're creating something from zero, from scratch, from zilch. You don't have an existing system and you don't have anything to base your system off of. You just have a person with an idea or a business with an idea, and you really have to go and think with them about what it is they're trying to accomplish and figure out what the requirements are. Requirements being, what does it need to accomplish? And you need to gather all of that up front, because there is nothing. You need to talk to the stakeholders. You need to talk to some of the potential users. You need to gather all of that information and summarize it and make documents that say, hey, this is what we're trying to accomplish. And when you do all of that, that's when you're doing top-down design. There is nothing, and you're creating these requirements, these specifications, and then you're creating a design out of that. So this kind of bleeds into top-down comes from when you do not have anything up front. Then you have something called bottom-up. And bottom-up is when there is an existing system or specific data in place. Now, I want to link this back to more realistic examples. When we look at bottom-up, for instance, what are some things that are bottom-up in real life? Well, doctors operate on a bottom-up strategy. If you took existing system and specific data and you replaced it by a human and symptoms, well, what a doctor tries to do is, based on your symptoms as a person, he tries to diagnose you with something. So he's starting from something very specific, which is you have a set of symptoms, and then trying to come up with what you may have and a strategy to combat that. That is bottom up. You're starting from something very specific and you're coming to an answer. And so in database design, bottom up basically is there's an existing system, there are existing forms, there's some kind of existing user input and experience, and there's specific data that you already need to store for sure. And you want to shape a new system around the existing data. Think about a migration. So when you do bottom up, you're usually coming in at a point where a company already has an existing product, an existing experience, and they want to shape a new experience around it, but they also have to take into account that they have all of this existing data. Now, this is the optimal choice for when you have an existing database. Bottom up is for existing data, existing experiences. Top down is for when there is no shape of the universe, there is no data, and you have to create it. Now, you may be asking yourself, Mo, what do I use? I get it. Top down, you don't know. Bottom up, you know something. There is something. Well, I want to tell you something about what to use. Because once you get a hang of both techniques, what you'll often do as an individual is you'll end up using a bit of both. Because as a person, you have your own thought process, your own patterns. You know what the end goal is. As you get more familiar with system design and database design, you're going to end up mixing a bit of everything. And that doesn't mean that you'll come to a subpar outcome. It just means that you're going to race to the end because that's the way your mind works. You're going to end up using a bit of both, a bit of everything. That's just the way that certain people think. Some people are more systematic and will follow the procedures as prescribed and do A, then B, then C, and come up with an equal solution. I often find myself using a bit of both myself. I'll use a bit of top down, a bit of bottom up, a bit of sideways, up, down, left, right, diagonal. I'm joking, of course, but what I'm trying to say here is that in system design and database design, of course there are right answers, but the way that you get to that answer is holistically up to you. And we're giving you the procedures that you'll be able to follow to validate and create those solutions. Now that we're designing systems, and now that we're taking a deeper look at how to design a system, We actually need a system to design. And so welcome to the case study introduction of Drive Me Academy. Okay, I made that sound way more intense than it should be, but we need something to build. And so before we dive into top-down design and look at top-down design, because in top-down design, you're creating the universe based on the requirements, we need some type of requirements to build against, because we don't want to just teach you the raw, boring, theoretical aspect of database design that would put you to sleep. We actually want to apply it to something that matters, which is Drive Me Academy. Now, all jokes aside, Drive Me Academy is a driving school, and we're going to use that driving school to kind of go through the motions of doing top-down or bottom-up design. Go at it from both angles. Now, in the first phase, we're going to approach it from the top-down design perspective, which is, well, someone comes to us and they don't have any type of existing online presence, right? All of it is word to mouth. It's a small driving school. So Drive Me is a driving school where people can take lessons based across the USA. They just have driving schools, one in each state, for instance, and every school has instructors, payroll, and an inventory of cars, truck, and motorcycles for teaching. They're just a small driving school that teaches people how to drive. And so after getting through a grueling phase of requirements gathering with the initial stakeholders, the CEO, CTO, BAs, we did some customer interviews, we were able to gather a firm understanding of the firm or business and its positioning and its growth. So, we went through phase 1 and 2 and we just talk to everyone. And that's where we gained a firm understanding of the business, because understanding a business and being technical is super valuable. So what we learned is that they want to become a household name across the USA for learning how to drive. If you want to learn how to drive, you have to come to Drive Me Academy. That's our core mission. Now, currently Drive Me, they have an outdated website. They don't really use it. It just has some flat text, flat information, and the customer acquisition is mostly word of mouth, because people go to people and they say, hey, when I go to Drive Me Academy, that's where I learn how to drive. And so what they want to do is they want to start gaining market share through an online presence. They actually want to go and they want to build an online platform where you can actually sign up through the website and have customer acquisition and share funnels through the website. Flat text and word of mouth is great. Word of mouth is one of the best types of marketing. But diversify to become a household name, the core mission. They've done this for so many years that they're now saying, hey, all these youngsters with their Instagram and their Facebooks, we want a piece of that. So Drive Me situation has some core requirements. Now, usually the core requirements are a well thought out document with sections of functionality. You go and you talk to the stakeholders and you go and figure out from the customers what they like most about Drive Me Academy, the best driving school in the USA. And so for this example, we've gone ahead and summarized the requirements for you. There is no phase 1, phase 2 for you. You're going straight into phase 3, and we have the requirements outlined here for you. And because we're going the top-down approach, the requirements are very much like someone coming to you and saying, hey, we want people to register and, we want them to be able to get their lessons going. And, we have cars and they need to rent the cars. It's very much that business savvy approach. You have someone that's very business savvy and has built this business from the ground up, and they know what they want online, but they're not technical. And so you have to go and take their non-technical aspect and understanding and formulate it into requirements that can be made into phase 3, phase 4 design and implementation. And so when we look at the requirements, when we look at those core requirements, what they said to us through conversations, when we talk to them and we gain the core understanding of their business, they were like, hey, there's vehicle inventory for students to rent. A student needs to be able to rent a vehicle for driving. And one of the core offerings of Drive Me, the best driving school in the USA, is that when a student rents a vehicle, they get to keep that vehicle throughout their course so that they're used to driving with the same car. Because could you imagine driving with a different car every week for your lesson? That would be brutal. You're learning how to drive, so you want to keep that same car. And their competitors, they don't offer this. They don't offer that same vehicle. That's DriveMe's core business model. I'm not saying that it's smart for the competitors not to do that, but in this use case, this is what differentiates DriveMe from the competitors, just hypothetically. Then the second requirement. There are employees at every branch. So they have branches across the USA. So there are employees across every branch. And there is maintenance for the vehicles. Very important. They do maintenance for the vehicles. So you want to make sure that maintenance schedule doesn't coincide with someone's lesson, of course, because they need to be able to use that same vehicle. Then the fourth requirement. There is an optional exam at the end of your lessons. It's optional. You can take it if you want, or you can go practice on your own for a bit more. You can only take the exam twice, and if you fail twice, you must take more lessons. Okay, so there's a lot of information in these requirements, and what we need to do now is we need to go ahead and see, well, how do we model a database? We're all a bit confused right now, right? We've looked at top-down versus bottom-up, and we know that with these requirements, we're going to do a top-down design. But how exactly do we model a database right now? And so we're going to look at what's necessary for top-down design specifically. So let's dive a bit deeper into that, knowing all of the requirements that we just learned. So we looked at Drive Me Academy, the best driving school in the USA. They came to us as a client. They told us, hey, we really want to build a website where people can register and do all of these things. And we came in and we said, hey, we're going to help you take over the USA, and we're going to do it with top-down design. Now, all jokes aside, when we looked at their requirements and we looked at what they need, being a driving school with vehicles and maintenance and all this stuff, what they basically need is a platform for students to be able to register, to have a price plan. And they don't have any of that. They have their back office and they do it all on pen and paper right now. We're going to modernize that a bit, and we're going to build them a platform that can handle this. With top-down, when we talk about top-down, we need to talk about the goal of top-down. We need to understand. We need to be top-down masters. We need to look at from everything that we see from top to bottom. The goal of top-down design is to create a data model that is based on the requirements. So we get requirements, we talk to people, we do all of these things. And then when we get those requirements, what we want to do is we want to create a data model. The requirements we heard were that they want cars and a schedule and all these things. But when we look at requirements, what is a requirement? What exactly do we talk about when we talk about requirements? Because you're saying, Mo, okay, we get that requirements are something that's required. That's a very basic definition. But when we look at it conceptually, what are we looking for? Well, we're looking for high-level requirements. There's high-level and there's low-level communication, right? There are things that the client says that are very specific needs, and there are things that they say that are implicit needs. So a client often doesn't know the difference between explicit and implicit requirements. They just talk about their business. They talk about what their business needs and what their business does. And it's up to you as an architect to sift through that and say, hey, this is what they need. And no architect does this 100% perfectly. No architect I've ever met has designed a perfect system from the get-go. And if you are an architect that has, great job. But oftentimes, all software I've ever seen has been iterative. Requirements change, requirements pivot. You go through the software development lifecycle, you miss something, you have to go back, you have to re-implement, you have new requirements. So requirements often come from that high-level, low-level context communication that you have with a client. But there's also user interviews. You can go talk to users and talk to them about their experience, what they like, what they don't like about the business, and gain some insight into some other requirements that may be necessary. You could look at data collection. They've been operating a business for so long. You could go look at what specifically it is they do on pen and paper and so forth. But most importantly, you want that deep understanding. Because any startup or any business at all, if you want it to be successful, you need to be on the same page and you need to have a deep understanding. Now, if you're a technical person and you're a consultant or a freelancer or otherwise, anytime you work for a client, the moment you are most valuable to them is when you have a deep understanding of their business and how it functions. So having that is more important than having what I would call the deepest technical skill. Now you need technical skill. Don't get me wrong. You need that technical skill. But being the most brilliant architect in the world versus being able to have a deep understanding with a client and being a great architect, I would pick being a great architect as opposed to being the best architect in the world for being able to deeply understand. And in my opinion, the best architects are the ones that can get that deep understanding. When we look at top-down, we have certain methods that we will employ. And one of the methods that we use in top-down design, one of the most important methods we are going to use is ER modeling. Now you may be asking yourself, Mo, what's ER modeling? Well, we've kind of already seen it in the course when we were doing database maintenance and implementation and alter create tables. But let's take a deeper look at that. All right. So far, we've talked about the software development lifecycle, and we've talked about all the phases we go through and what's important and what every phase is for. And we really honed in on phase 3, system design, the part of the software development lifecycle where you're getting very close to implementation in those SQL syntax that we spoke about. But we posed a very, very important question. We asked ourselves, how do we design? Or how to design? And we had 2 answers, 2 very important, distinctive ways to design. Top down, bottom up. And when we talked about top-down design, we talked about it shaping the form of the universe. You have requirements. They don't have an existing database or platform or anything like that you need to migrate. And you basically go into a company where they're doing a lot on pen and paper and they really need a system. And you're talking to stakeholders, CEOs, customers, so forth, and gaining all of those requirements. And so now that you have that phase 1, phase 2 behind you, and you're going into system design and you have all of these requirements already, well, how do you actually do top-down design as a concept? And so we spoke about ER modeling. What does ER stand for? Well, it stands for entity relationship modeling. Now, if we think back to the course, what have we been doing this whole time? We've been doing relational databases. And so when we do entity relationship modeling, what we're trying to do is that top-down approach, that thinking of, hey, I need my entities and I need my relationships. Okay. I said a lot here. Entities, relationships, modeling, top-down. But just follow the flow of the diagram and you'll see where we're going. So when we look at entity relationship model, an ER model is an entity relationship model or diagram. So an ERD or an ER model. Okay. So 2 ways of saying the same thing. Always confusing and always great about software development when you can say something in 3 different ways. Just great. But for all intents and purposes, I'll probably end up saying ERD or entity relationship diagram the most. But if you see me speaking about an ER model, just know it means the same exact thing. You may be asking yourself, okay, what is it? Well, it's something we've already seen in the course, right? I alluded to it previously, and we saw it during database maintenance. It's a diagram. And it's a diagram that functions as a way to structure high-level requirements. Now, what does that mean? Well, we talked about requirements and what requirements are. But basically, what we're trying to accomplish is formulating a shape of the world. And if you remember this diagram at all, well, this is an entity relationship diagram. And what it depicts is the way that we are forming our shape of the universe. And we talked a little bit about these crow's feet, and we'll talk a little bit more about them as we go along. And we talked about what all of these mean. But what it basically boils down to is these are relationships and these are entities. So it's an entity relationship diagram. You're formulating entities, subject, course, student, enrollment, and you're drawing relationships between them. ER modeling is all about that. You're trying to formulate the shape of the universe by defining these entities and these relationships. What I want to do now is, when I showed you this diagram initially, what we used it for is just to do the create syntax and all of these things, and creating tables and altering tables, and creating those IDs and having those fields, columns that we're going to create. But it was already there. So what we're going to do is we're going to create one for Drive Me Academy, the best driving academy in the USA. But before we do that, we're going to end up with something like this, but we're not going to start here. We're going to start conceptualizing something. We're going to start from nothing at all, blank slate, blank page, nothing at all. But before we do that, we need to understand the steps that are involved when we do ER modeling, because we don't want to do a chaotic process. No. We want something that is regimented and that has clear steps to create these entities and get these relationships and get these columns with their types. We want to get here, but when we're starting from zero, we need a process to get here. And so we're going to talk about that process, because at the end of it all, we're going to have this diagram, but for Drive Me Academy. And we're going to learn the steps to get there. So in the next video, we'll be going over the very first step. Now that we know all about entity relationship diagrams, what we need to do is follow some steps in order to formulate a diagram. But again, we're trying to create order from chaos. So we're going to follow some steps. And these steps are going to help you build up a mental model, because it isn't a race. It's a marathon, and we need to get there step by step. There's certain processes involved, certain mental models you need to build in order to build solid entity diagrams. And so I've broken it down in steps, logical steps that most people would inherently follow very quickly, but nevertheless, we're going to follow it in these broken down aspects. And at the end of it all, we're going to have an entity diagram. So step one is determining the entities. When we talked about entity relationship diagrams, we talked a lot about entities. And when we make an entity relationship diagram, entities are the most vital part. Now, you may have heard this funny saying, naming things in software is hard. Well, determining what the entities are in a system is one of the hardest things you can do, because now you have to think architecturally. Now you have to break down a system, and you have to think in order to make sure that what you're coming up with makes sense. And so naming entities and formulating those entities is the hardest part. But there are some rules you can follow. You see, when you ask the question, what is an entity? Well, there are certain things that we can predetermine, kind of like rules or guidelines, in order to say, hey, this can or can't be an entity. And so when we look at entities, well, the first rule or guideline is, well, it can be a person, place, or a thing. Okay, a person, a place, or a thing. It needs to be a person, a place, or a thing. Keep that in mind. It has to have a singular name. When we look at entity relationship diagrams, we're trying to formulate a single entity, a singular person, place, or thing. So it has to have a singular name. And then the next thing is, it has to have an identifier. Now we've looked at this. We've talked about primary keys and foreign keys and all that good stuff. And we need to make it uniquely identifiable. And then the last thing, it should contain more than one instance of data. It should be able to contain more than one instance of data. When we look at something, if you had a business that only had a single place of business and wasn't looking to expand, well, you can't go and store multiple entities of that business because there's only one instance of that business. So it's important to know that you should always form entities that are going to hold more than one piece of data in the system. Now, when we look at our current example, Drive Me Academy, the best driving school in the USA. Well, what are the entities that we need in order to formulate the system or ER diagram. How do we break that down? Well, let's take a look at that. Before we go all out on diagramming, it's important to note that there are a lot of options out there. A lot of options. You can have tooling around everything. And when it comes to diagramming, there's no shortage of tools. Now, when it comes to tooling, I have my preferences. Other developers have their preferences. It's important to get an experience and software that tailors best to you. And when it comes to that, well, I would just suggest test out as many softwares for diagramming as possible. And make sure that they have the UML or Unified Modeling Language, which is the language that we use when we create ER diagrams, syntax available. Now, I'm going to give you a couple of tools here that can help you with this. Oomlet being one of them, very popular, cross-platform with a simple interface, doesn't have any bells or whistles. It works on every single platform, Windows, Linux, and Mac, and it's very simple to use, but it's not the prettiest and it's not the greatest. If we go down here, you can see it has a very simple user interface and a very simple way of actually operating, and it also operates in the browser. You can use Oomletino, and it runs completely in the browser, no huss, no fuss, but it doesn't look amazing. Another tool that you can use is called Lucidchart. Lucidchart is a paid experience usually. There is a free version in which you can create up to 3 documents that you can edit for free. And it has a much nicer interface for creating graphical processes and making things happen. And it runs completely in the browser, no software, no nothing. So when it comes to diagramming, I strongly suggest using Lucidchart since you can use it for free and register through the platform. It's a very simple interface to use. You can drag and drop. It's very nice. But as you scale, it does become paid because you can't hold in more than 3 documents. But it has export features for all of your diagrams. You can import from different software. It's a very nice experience. And so that being said, you can use any software you like just as long as it works for you. These are just some of the options that you can use. So Oomletino, browser-based. You can also download Oomlet, and when you download it, it gives you an executable for Windows, and then it comes with a jar that you can execute on Mac. Just make sure that when you run it on Mac, you go into privacy, security and privacy, and that you allow it to run because it otherwise will not have the permissions that it needs in order to run. And so this way you can also create very simple diagrams. But as you can see, the experience is slightly less pleasurable compared to what I would suggest Lucidchart is. Very easy drag and drop, snap tooling, all that good stuff. So whatever tool you pick, just make sure that it works good for you. For the intent of this course, we'll be using Lucidchart, which you can use for free up to 3 diagrams. And so now that we have the rules of what an entity is, now that we know exactly what it is, this is where it gets very powerful, very free, and very creative. You see, in step 1, what we're going to do is we're going to define the entities of Drive Me Academy. And in order to do that, we need to look at the core requirements once more. If we look at Drive Me's core requirements, there's 5 core requirements. We say there is a vehicle, inventory, for students to rent. There are employees at every branch. Employees at every branch. There are maintenance for the vehicles. And then we speak of an optional exam at the end of your lessons. So a student takes lessons, and at the end of his or her lessons, there is an optional exam. You can only take the exam twice. Fail twice and you must take more lessons. So this is a constraint. Interesting. Our requirements dictate constraints. And so now it's up to us to determine, hey, how are we going to shape this universe? Well, let's get into it. Over here, I've set up a Drive Me Lucidchart. And what we're going to do here is we're just going to describe the entities. So what all did we hear? Well, we heard student. So let's go ahead and let's change, first of all, the font, and let's set it to 38. And then let's go ahead. So first of all, we talked about a student. That was in there, right? Student was in the requirements. So we know you're going to have a student. We said that there are multiple branches. So we can call those either branches, branch, singular names, or we could call it a school, whichever one you prefer. Then we heard that there were teachers. Okay. Over here we say there are employees at every branch. So employees at a branch. Well, we could have named it employee in branch, but we chose a different terminology based on Drive Me Academy. Driver instructor. We could have called it an instructor as well. Instead of a teacher, we could have said instructor. So you can see how you can name things differently, but they can mean the same thing. That is why there is no one absolute right answer here. So we have employees at every branch. We have our schools. And then we have maintenance for vehicles. Okay. So we have an inventory of vehicles and we have maintenance for the vehicles. Okay, so we have vehicles. Well, let's add some vehicles. Vehicle. So we have a vehicle. And then when we think about maintenance, well, what does maintenance hold? Well, if we were talking about maintenance, we would typically say that, what would you hold in a maintenance field? Well, you could hold the date of the maintenance, which is a singular field, date of maintenance. That's a piece of data. And why are we thinking about this? Why are we talking about maintenance right now? Well, we're trying to determine whether it should be an entity or it's just data that we hold. You see, when we think about entities, all of the requirements are vague. We could go ahead and we can make every single thing an entity, but we need to think about it. So we know that vehicles are individual. We know that students are individual because we're holding makes and models, BMWs and so forth. We know that a school is an individual entity because you can have multiple schools. There are multiple things of schools. We know that each individual instructor is an individual in him or herself. But maintenance is a tricky one because when we think of maintenance, well, we're thinking about a date of maintenance. But when we dig deeper, well, maybe we want to know what kind of maintenance. Who did it? Where did it happen? And so now it becomes tricky because vehicles are maintained multiple times a year. We can't store it inside a vehicle because all of these feel like columns, right? The date of maintenance, the type of maintenance, who did it, where did it happen? So we're edging towards it actually becoming an entity because we're storing multiple facts about maintenance. If we just stored the date of last maintenance, we could have stored it in a vehicle, but we want to be more granular. We want to actually know what happened and when it happened so that we have some kind of information about it. We can't just offhand the maintenance to a singular field. We need a bit more granularity about what exactly happened. So then we go into maintenance. So vehicles have maintenance. Okay. And then we talked about exams. So a student takes an exam. Now, a student can take an exam twice, so there are multiple instances of an exam. And we want to know the pass or fail. And you can take it 2 times and then take more lessons and then take it 2 more times. So you can take it multiple times. So again, this doesn't feel like columns that we can store inside of student because we're just going to be adding and adding and adding columns. So we want individually for exams to be an entity. So an exam. And since it is optional, that is completely a thing. Now comes the fun part though. You see, we took our requirements, vehicle inventory for renting employees at a branch. We have the employees, we have the branch, we have maintenance for vehicles, we have exam, but this one, you can only take the exam twice, fail twice, and you must take more lessons. This is a constraint. Now, as a system architect, you have to start thinking very heavily. Is this going to be something that I put as a constraint on the database level? And if I put it as a constraint on the database level, am I hurting the system? You see, there are second and third orders of effect here. If I were to say, put a constraint here on the exam and say that a student can only take an exam twice, lest he need to take more lessons, it becomes very difficult for an instructor to then say, manage the exam of the student. Let's say something wild happened. the vehicle was out of service, but the exam was still logged. Now, since an instance of the exam was logged, how are we going to make sure that they don't need to buy more lessons in order to have to not retake lessons in the system? So we have to start thinking about this. And even talking about this, didn't we miss something here? You see, a student takes an exam, a student has a vehicle, a school has students and instructors, we have maintenance. Wait, students take lessons. Interesting. Okay, lesson. Because you have to take lessons in order to be able to take an exam, and a student has to take lessons. So, we have a relationship here, an entity that we missed. The ability to take a lesson. And instructors teach the lessons, so it makes even more sense. You see, when it comes to entities, there are always more entities that can be formed. And through what we will do in relationship mapping later, we may even split out into more entities. So it's important to think about every possible entity up front. And then maybe you'll miss one or two and you have to add them. And that's completely fine. There is no hard set rule. When it comes to these things, you have to really think it through. And that's why I say that this is a team sport. The more eyes you have on a problem, the better results you're going to get. So let's order these in a way that makes sense. So the school has students and instructors. Students follow a lesson. So let's put this here. Students will follow a lesson. Lessons will have a vehicle, and a vehicle has maintenance. And students can take exams. So interestingly enough, what we're getting at here is that you can almost form relationships. Now, at this stage, at this step, we don't want to form relationships just yet, but we want to reason about why we have these entities. So typically what is done is you draw a line. So you would draw a line like this. You would say a school has students and a school has instructors, right? And so you can say has. So you have students and you have instructors. Okay, now we can say that a student takes a lesson, right? And so you start reasoning about it in this way, and you can write down every time what you think. So a student takes lessons, and a lesson is taught by instructors. So you can say that the instructor teaches lessons, and so on and so forth. So the instructor teaches. And so you're starting to denote some type of relationship. And you can do this in step one just to make sure that your entities are valid. And as you reason about them in this way, you'll get a more accurate depiction of what's happening. See, you can say that vehicles have maintenance, and that a student has to take an exam, and that a lesson has a vehicle. But this is an interesting one, because you could also say that a student has a vehicle. It really depends on how you want the relationship to be formed. Do you want the vehicle to be linked to the lessons of the student, or do you want it to be linked to the student, in which case, if he ever took lessons again, that he could get the exact same vehicle? Well, it becomes a tit-for-tat discussion. You can argue both. In this case, I feel that it is best to have the vehicle linked to the lesson package, as when you take another lesson package, the vehicle goes back into the vehicle pool. And it is not always held by that student, so it makes more sense to reason about a vehicle being linked to a lesson package. But you can make the opposite argument as well. And then you can say vehicles have maintenance, but here's where it gets interesting. You see, you could also say that the school has lessons, the school has vehicles, the school has exams. You could argue that school can be linked to everything. Now, why don't we link it to everything with lines and just do this and link it to every single thing? Well, because there are orders of relationships. Because school is linked to student and because school is linked to instructor, it can derive through the relationships all of the different information. There is nothing that school is not connected to by being connected to instructor and student. By being connected to the instructor and the student, you can derive all of the chain downward. So the one thing you wouldn't want to happen, for instance, is that this relationship wouldn't be there. Well, now you would have to only go through the instructor to know which instructor gives lessons to which students, but you don't know which students are in which school. So this is an important relationship, a very important relationship. So with that, we need to be very clear about everything being linked together in the right way. You wouldn't want school to be linked to vehicle and then vehicle to be linked to student in that way. It would make less sense. You see, everything has a right reason. Students go to a school. Instructors teach at a school. Lessons are given at a school, but lessons are given by an instructor. So by knowing the instructor, you can know which lessons are given. Now, if a school were to offer specific lessons, you could, for instance, make the argument of giving this. Link a lesson to a school. If a school offers, for instance, a specific lesson package on driving in the snow, well, then you need the specific relationship to know where the lessons are given. If you, for instance, said that Drive Me Academy, all the schools offer the exact same lesson packages, then it is less important to know which schools offer which lessons, because by knowing the instructors and knowing the students, you could derive this information. Now, that said, different requirements invoke different relationships. For now, this is the simplest relationship tree that we need for the system. All schools give the same lesson package. All schools have instructors and students. Students take exams. Students take lessons. A lesson has a vehicle package, and vehicles undergo maintenance. So with this pseudo relationship tree, we're starting to formulate an understanding of Drive Me Academy. But now we need to move on to step 2. And step 2 involves looking at the entities and determining what they need to store. And then from there, we'll go and we'll look at these relationships and we'll reevaluate them and we'll structure them in a way that can be made into a database. But let's look at the attributes first. Step 2, attributes. Attributes are one of those things that we looked at when we were doing the relational model. And when we talk about it this way, we're talking about it in a way that is theoretical. Give entities the information they will store, also known as the columns of the table. But when you talk about architecture, you need to think at a higher level than implementation. But when it comes down to implementation, it's nothing more than the columns that the entities are going to store. But the reason that we think about it at this higher level is because when you're thinking conceptually in architecture terms, you want to be more free than the rigidness of the system implementation of Postgres or other database management systems. You need to free think, and then when it comes down to implementation, things could differ a little. But what you want to do at the end of the day is give the entities the information that they will store. And so when we look at that, we look at what attributes are. What are attributes? Well, they must be a property of the entity. Okay, so they have to belong to that entity. They must be atomic. They can only hold a single value. Now, we all know that in Postgres, you can hold multiple values in a field. That's a different concept, though. When we talk about atomicity, we're talking about it being a singular value, not multiple values in one. Address is a good example of this. You could have a street number, a street name, postal code, all of these things encompassed in address. Address is way too broad. It's not atomic enough. That's what we talk about when we talk about atomic. And then we talk about single versus multi-valued. This is where the confusion with atomic happens often. A field can contain a singular phone number or multiple phone numbers, for instance, array values. So single and multi-valued is not the same as being atomic. When we talk about being atomic, it's about narrowing it down to the most small amount of information that needs to be stored for an individual field. For instance, with address, street number, street name, postal code, region, all of these things are encompassed in the word address. It's not atomic enough. So there's a difference between atomic and single versus multi-valued. And then we talk about keys, and we know everything there is to know about keys. Or do we? Let's take a refresher of the relational model. Let's go back and let's look at primary key, foreign key, because there are also other types of keys that we need to look at. And we haven't really defined the relational instance. So let's take a step back. Let's take that refresher and then let's dive right into attributes. So far, we've seen the relational model, or parts of it. You see, we've talked about attributes, degrees, tuples, columns, tables, even domains. But a couple of things laid dormant, things that we didn't touch on necessarily when we were going over all of these things. You see, we didn't dive really deep on the relational schema, nor did we talk about the relation instance or the different types of relation keys all too deeply. You see, we all know about primary keys and foreign keys, but there are so many more different types of keys. You see, we differentiate in SQL between the theoretical and the practical. In theory, we can apply many, many more constructs. But in practice, we often stick to what is best or most well known, which is primary keys and foreign keys and using UUIDs and all of those things that I've shown you along the way. But let's refresh some of that theory that we've seen so far. So a relation schema. What are we talking about here? This is getting more to the abstract portion of the relational model. Because as we talk more and more about the relational model, we're talking about concepts. And the relation schema refers to, in essence, what we would call the table schema. It is a representation of the data that is going to go into the table. So if we were to simplify the view on this, if we looked at the relation schema from a high level, the relation schema is the user table. And when we talk about the relation schema for user, we're saying in the user table, we are going to store ID, first name, last name, sex, and date of birth. That is what we call the relation schema. Counter that with what we call the relation instance. And the relation instance is the set of data that relates to the relation schema. So it's referring to all of the tuples or rows or data inside of that table. That is what we would call the relation instance. Now, all of this is becoming a bit abstract, right? Relation schema, relation instance, but all of these refer to the same thing. They're just different ways of referring to certain parts of a table, columns, rows. We have different terminology for all of these different parts that go into how we are modeling the data in the relational model. We talked about constraints, columns, rows, tuples, and then we have encompassing terminology like cardinality, degree, and relation schema and relation instance are nothing more than encompassing terminology. And what do I mean by encompassing? They're trying to describe a greater sum of all of these parts, right? We have all of these different parts, and a relation schema is trying to refer to the sum of those parts, being all of the different columns and the name of the table. So the table schema. And the relation instance is trying to refer to the data that is available in that schema. All right, so now that we've looked at that, there is one more thing we need to look at. And it is extremely important and it is super vital to the relational model because it is going to determine how we draw our relationships. And we call them relation keys. So let's go over that in the next video. So the relation key. Now we're hitting a pivotal point in the relational model because we're pinpointing a part of the relational model that is vital to the way that we are going to structure our relationships. If you remember, the way that we structure our relationships is by uniquely identifying each and every row. And the relation key's purpose is to do that it's going to uniquely identify each and every row in a data set. And this is necessary in the relational model because, as you remember, we are structuring our data in an unsorted and unordered manner. We're not concerned if Mo comes before Charles or Charles comes before Mo. The data just gets inserted. We don't care about the order. But that being said, Mo Bini is not unique. Someone else could insert Mo Bini. Each and every table that wants to form a relationship with a different set of data, if you want to have a teacher linked to a class or a student linked to a library, if you want to form a relation, then you are going to need a relation key. If you're not going to form relationships, you can just store your data unsorted, flat, with duplicates. It wouldn't even matter. But the moment that you want to form a relationship, you're going to have to uniquely identify your row. Now, what do I mean by that? You could just as easily create a table that contained all of this information without the relation key. But there is going to be no way for you to create relationships with other tables. There is going to be no way for you to uniquely identify each and every record. So every time you do a search with a query, you're going to have to filter based on multiple parameters. Maybe my first name, my last name, my sex, my date of birth. So the relation key has two jobs. It is going to uniquely identify each row, and it is going to uniquely identify the relationship. And so you may ask yourself, why do we need this? Well, like we said with the network model and with the hierarchical model, you can have a one-to-many relationship or you can have a many-to-many relationship. You can create relations with data. As your data grows, you want to link data together to be able to retrieve certain information, to create relationships. This is why we use these models, to create these relationships in a structured way, to save our data in a structured way, and to not have the overhead or complexity that comes with it. So the relation key is that glue. It glues together the relationship. And now, you may ask yourself, what type of relation keys do we have? Because I see ID over here. But what is the purpose of ID? Well, the purpose of ID is, if we look at first name, last name, sex, and date of birth, none of these are inherently unique. We can't say that if I take first name, last name, and my date of birth, that I'm going to be unique. Nor if I add in sex, because male or female, if we add that to the equation, yes, maybe we'll filter a certain part of data, but there may be two Mobinis, one male, one female, both born on the same day. We don't know. Now, the chances are very unlikely, but they're still there. So we put an ID that is, in this case, an auto-incrementing number. Auto-incrementing meaning it goes 1, 2, 3, 4, 5, 6, 7, and so forth. It's always going to go one further. We put in this ID because it's going to now uniquely identify the row. And by uniquely identifying the row, now we can form relationships. But that being said, you don't always need an ID of this type to create a relation key. You could, for instance, use a super key. And what is a super key? Well, a super key is any combination of attributes that could uniquely identify a row. Now, what do I mean by that? Well, over here you see ID and first name. The combination of ID and first name uniquely identifies a row. But you could also say that a super key is ID first name last name, or ID first name last name sex, ID first name last name sex, and date of birth. These are all now super keys because they uniquely identify the row, because ID is here. But you also see that I added email here. Now, if we look at that, email is unique. You're not going to allow users to register with the same email. An email is a unique thing. No two people have the same email in the world. So we could also say that the combination of email and first name, or the combination of email, first name, and last name, or the combination of email and ID, these are all considered super keys. So any combination of attributes, doesn't matter how many. All right, so now that we know that, that's one type called a super key. Then we have a subset of that, a candidate key. What do I mean by subset? Well, we're narrowing the field. With a super key, we said any combination of these attributes can form a super key, as long as they uniquely identify the row. But a candidate key says the minimal amount of attributes that are needed to uniquely identify the row are candidate keys. So ID and email are candidate keys. Email can be a candidate key. ID can be a candidate key. Email and ID can be a candidate key. ID and first name can be a candidate key. But now we couldn't take ID, first name, last name, sex, date of birth. We couldn't combine all of them to form a candidate key because we're looking at the minimal amount of keys that uniquely identify a row. I hope that makes sense. Let's reiterate that. A relation key is something that will uniquely identify the row and uniquely identify the relationship. A super key is any combination of attributes that uniquely identify the row. And the candidate key is the minimal amount of attributes that uniquely identify the row. All right, so now that we've defined these three concepts of keys, what other types of keys are there? Well, let's take a closer look at the primary key. So primary keys. So far, we've talked about relation keys, and relation keys being the thing that uniquely identify the row and the relationship. There are not enough times to reiterate this because it is super important. The concept of a relation key has those two jobs. And then we talked about super keys and candidate keys. So in this group of a relation key, we have two subgroups. We have a super key and we have a candidate key. A super key is any combination of these attributes that uniquely identify a row. So any combination of all of these columns that could uniquely identify the row are considered a super key. And then we take that and we narrow it down and we say a candidate key is the minimum amount of attributes that are necessary to identify a row uniquely. And so if we look at that definition, we can say that ID would be a candidate key. Email would be a candidate key. But what are we going to do with this candidate key? Well, once we have the key that uniquely identifies the row, we are going to call that our primary key. And what is the primary key? Well, the primary key is that relation key. It's that key that's going to uniquely identify the relationship. Once we decide what our relation key is going to be, that becomes our primary key. Now, in this case, like I said, ID is the sole column that we need to uniquely identify the relationship. Before we added email to the mix, none of these columns could uniquely identify a row. That's why ID was there, the auto-incrementing number. Now that we added email, we had two candidate keys. We could choose between ID and email. But we chose ID. And that became our primary key. That became our relation key, the key that warrants our relationship. That being said, if we had had 2 or 3 different attributes here that could uniquely identify the relationship, that could have become our primary key. Now, why would we select one column as a primary key over multiple columns as a primary key? Well, because it simplifies our design. You could, in theory, have multiple columns that identify a relationship, but in practice, it's always better to have one column that will uniquely identify each and every item in that table, because it simplifies the way you have to draw your relationships. It simplifies the way that you have to look at the data, and it simplifies the way that you can look up data. Because like we said, if you now selected first name, last name, date of birth, or first name and email, although email could be a primary key on its own, you now have to search for an item by 2 or more columns. By having that singular column that identifies each and every row uniquely and has a unique identifier, being the number, we have simplified the way that we can draw our relationships, and we have simplified the way that we can look up data. Okay, the relation key, the super key, the candidate key, the primary key. And we finally went from like the big picture to the small picture, the primary key. And now, how do we draw our relationships? Well, we finally have that primary key that uniquely identifies our relationship. 1, 2, 3, 4, 5. Unique key. But now, we want to draw relationships. So over here, you see the data that we inserted as, let's say, for instance, an employee. And over here, you have the managers, and you have the manager ID, which is also a primary key. Orange indicates the primary key. So we see manager 1, 2, and 3. Clyde, Connor, and Sarah. And now we need to draw the relationship. So we have our primary keys, and we have them in both the manager table and the employee table. And now we want to say, okay, Who does Mo report to? Well, that's what we call a foreign key. When we reference a key from a different table into the employee table, when we say, okay, now I want to link the managers to their employees, who does Mo report to? We add a column to the employee table, and we call that the foreign key. We give the column a very specific name, manager ID. That way we know that this is referencing an ID from somewhere else. And that becomes the foreign key. It's foreign to us. We don't know where it came from, but we're going to give it a name that tells us what it's linked to. And that way, by giving it a specific name and by defining it as the foreign key and linking it to the manager table, now we can only fill in values that match a value of the primary key in the manager table. Okay, I hear you thinking, wait, what? It's simpler than it sounds. Our primary keys uniquely identify each and every row. When we want to make a relationship, what we're going to do is we're going to add a column to our table. And that column we can give any name we want, but we are going to define a relationship of a foreign key. We're going to say, hey, okay, we're adding this column, but we're going to specifically say that this column links to the primary key of this table. And that's what we call a foreign key relationship. And by doing that, by specifically saying, hey, this column here is linked to this primary key in this table, now the data that is filled in automatically has a constraint. And that constraint is that we can only fill in values that match a value that exists in the manager table primary key. So now we have warranted our relationships. What do I mean by warranted our relationships? We are making sure that our relationships are always going to be linked to a manager that exists in the manager table. And we have that direct correlation. One employee can only report to one manager. Amazing. We have just made our first relationship. And it's so simple. All we needed was a column. And all we needed was to say that that column linked to this table's primary key. Amazing. Now we know the concepts of a relation key, a super key, a candidate key. These are the concepts that we're going to take with us when we start designing. And then we have the practical implementation of a primary key and a foreign key. Once you've dumbed down everything and you've selected what's going to uniquely identify something, we can now select our primary keys. And now we can create relationships. Because we have our primary keys in multiple tables, we can create foreign keys that create relationships between data. Here, we did a one-to-one relationship. One employee can only report to one manager. That is what we call a one-to-one relationship. That's why we can keep the column inside of the employees. Manager ID links to manager ID. Now, there are many other types of relationships that we can form, and we'll be looking at those as we go along. Compound keys. Now, I hear you thinking, how many types of keys are there? Well, we're almost through them all. Now, there are many types of keys, and conceptually speaking, all we're trying to do here is lay the foundation so that you know the terminology of the types of keys we talk about. Because even though we know all of the different keys that you can pick from and how to form them, because we've talked about the super key and the primary key and the foreign key and all these different types of keys, all of the types of keys from the superset, which is a super key, right? The superset, it encompasses all of the different types of keys, all the way down to the primary key, which is the key you're initially going to choose to uniquely identify your data. Well, then we get into the compound keys. And so if you remember with the super key, I said multiple columns can form a primary key. Multiple rows can uniquely identify a singular piece of data, a tuple. Well, a compound key is nothing more than a key that says, hey, multiple columns here are uniquely identifying my data. And a foreign key can be used to uniquely identify the data as well. So a compound key says, hey, I can use multiple columns and any of my foreign keys, I can also use them. Now, you may be thinking, wait, what does that mean? Well, when we define the terminology multiple columns, well, you can say email and first name, email and last name. But what are you going to say? What are you going to call the key when, for instance, you have multiple foreign keys available, multiple keys that are referencing a different table? Well, when you use a key that is creating a uniqueness to a tuple or a row, and it's using a foreign key to form a key, we call that a compound key. It's pretty simple. Now I hear you saying, okay, but what about the keys that are not allowed to use the foreign key to form a relationship? Well, those we call composite keys. Composite keys are keys that are formed between multiple columns to uniquely identify data without using the foreign key. Pretty simple, right? So, compound key, composite key. Compound key can use a foreign key as a column, composite key can't. So then we jump into the surrogate key. And if you remember, when we were talking about primary key, I kept yabbering on about this ID being the ideal primary key because it's an auto-incrementing ID, yada, yada, yada. Well, the reason I said that the ID was a perfect key is because it's completely separate from all of this data. It has nothing to do with first name, last name, sex, date of birth. It doesn't have anything to do with the user's data necessarily. And so when we choose a primary key that is a piece of information that will uniquely identify a row but has nothing to do with the individual's data, we call that a surrogate key. We're basically picking our own key. We're saying, hey, I could pick multiple columns here and I can do all of this fancy stuff, but I'd rather just pick one column to use as a primary key, and I want that data to represent every single row in a unique way without me having to pick multiple columns. That's what we call a surrogate key. So when we said our ID is our primary key, we were saying, hey, we're injecting this ID column that is going to be an auto-incrementing number, and we're going to make it our primary key. Well, that ID field, that ID column, we call that a surrogate key. All right, so that's all I have for you. Those are all of the different types of keys that you can use. And just so you know, all of these keys that we described, all these different types of combinations and stuff with the composite key and the compound key, we call those alternate keys. That's the final key that I'll leave you on. I promise. Now that we're more familiar with the relational model and the relation instance, the different types of relation keys that are beyond primary key and foreign key, and even seen a refresher of primary key and foreign key, it's time for us to look at Drive Me again. And what we're going to do now is we're going to determine the attributes that need to go in to the entities that we determined. And you can see here that I am in Google Docs. Now, there is a reason that I am in Google Docs. You see, when we were working with Lucidchart, we built this nice diagram. So why wouldn't we add the attributes to this diagram? Well, it's a bit early to build the fully fledged diagram. And the attributes, almost in top-down model, have little bearing on what will occur here. They could spawn new entities. Determining the attributes for the entities can spawn new entities. But for this particular model, what we're going to do is we're going to think about the attributes upfront in a different format, and then after the fact, we're going to add them to the entities, because we haven't drawn the relationships between the entities yet, and we have yet to determine what the entities exactly are going to store. And so what I've done here is I've put each and every entity on a separate line. And what we're going to do is for each individual entity, we're going to go ahead and formulate all of the different things that it will store. So what will a school store? Well, each and every school has an identifier. So we'll for sure have a school ID. And then once we have a school ID, well, what else relates to a school? Well, an address, of course. But we just talked about address and the fact that it is actually a term that isn't atomic enough. So what we're going to do is we're going to put street name, street number, and then we're going to add a postal code. And once we have the postal code, now we can add the state, we can add the town or city. City would be better. And so now that we have all of this information about a school, well, what else does a school have? Well, let's get back to that. Let's think about a teacher now. You see, you don't have to answer this all right up front. You can do it in stages. It makes more sense for you to get all of the attributes that are obvious out of the way. So teacher ID, first name, and then let's put last name. Let's put date of birth. Let's add in hiring date. And then let's move on to the next one. So now we have student, and student is going to be very similar to a teacher, except instead of a teacher ID, it's going to have a student ID. You will keep the first name and the last name, and you will store a enrollment date. And this is the date that the student joined. But wait, doesn't a student enroll into lessons? That is correct. So this one may become an issue. So let's go ahead and underline that because we need to know what exactly it is going to entail. So an exam has a student ID. It has a teacher ID because a teacher administrates an exam. It has a date taken. This is the date on which the exam was taken. And it has passed, which is a Boolean flag, true or false, whether or not you passed. So based on this, we can also say what lesson package it was on. So we'll have a lesson ID. And the lesson ID will refer to the package of the lesson that the exam was administered against. Because if you failed 2 exams, you need to take a new pair of lessons in order to take the exam again. So we need that link to the lesson in order to know against which lesson package they took the exam. Okay. So this is a foreign key, and this is a foreign key, and this is a foreign key. So exam has a lot of foreign keys. And so the reason that we're thinking about it this way is because, hey, this creates a new relationship that we didn't have. And hey, this creates a new relationship we didn't have. And whoa, the pass, fail, and the date taken, just normal data. And whoa, this lesson ID, that's another relationship we didn't have. So thinking about the data and thinking about what needs to be stored in here is extremely important. Now, you could go the other way and you could say, hey, let me think about the relationships a bit more first, and then let me think about the attributes. If that is the way that you can form the relationships better, you can invert those steps. You can go ahead and on step 2, think about the relationships and draw out the relationships a bit more. These steps are guidelines. They're not set in stone. Everyone has different ways of drawing these relationships and coming to conclusions. But it's important that you weigh out your decisions. You see, through my experience, I assume right now that I have to link my exam to the lessons. But when we drew our diagram, lesson wasn't linked to an exam because the relationship just wasn't there. It didn't make sense to us. A student takes an exam, but inherently, actually, an exam is linked to a lesson package because you can only take the exam twice. That's interesting because when I'm thinking about the attributes, I'm also thinking a little bit about the relationships. Now, you could go ahead here and when we learn step 3, you could apply step 3 as step 2 very easily. But it's important to just think about what's going to be stored here. When I start thinking about it, I'll reason about it, and that reasoning is what strengthens my argument. But everyone comes to conclusions in a different way. Now, what is a lesson store? Well, we'll need a lesson ID. We'll need a date. We'll need a date of enrollment. We'll need lesson package type. We can call it the package, whether it's package A, B, C, or D. So we have a lesson package. And then we have the student ID based on the relationship that we drew on our diagram. Student takes lessons. So this is already telling me kind of what my foreign keys are going to be. Right now, we drew a new foreign key, but we also drew a third foreign key. So you can see now how thinking about these entities and their attributes draw new relationships, but it can also create new entity types potentially. But we don't know specifically if they are one-to-one relationships, one-to-many. We still have to look at that. So we're just thinking out of the box. Now, how do I know that student ID is linked? Well, we made that relationship in step 1. Student ID exam, student ID lesson. I know that the foreign key is going to be there. Generally speaking, you could also take this exercise and put none of the foreign keys or primary keys in or any of the keys in and just think about the raw data, the identifiers aside. That's completely valid as well. I like to invert that process and think a little bit about the relationships up front before I start making the relationships concrete. Sometimes I do step 3 about the relationships before I do the attributes. It really depends. But there is no rhyme or reason. It's whatever works for you and whatever makes you come to the right outcome. So over here in student, I had an enrollment date, but the enrollment date is actually part of the lesson because the student takes the lesson and the lesson has an enrollment date. All right. And so with that, we also know that teacher needs a school ID. And we also know that student needs a school ID. Why is that? Because school is linked to a student and an instructor. And so this is actually instructor. You can see that I'm already thinking about the naming conventions incorrectly. I went over to this document and I called the teacher the instructor, but as the entity, I called it instructor. So naming things is extremely hard, and you can catch yourself actually naming an entity or thinking about an entity differently. Maybe if I call it teacher often enough, I should actually name it teacher. It's all about determining the domains of the business and giving them the right name. If the client speaks of instructors, call it instructor. If the client speaks of teachers, call it teacher. Follow the business language of the individual you're building the system for, and that will make it much easier for them to reason with you, even if they don't understand all of the technical stuff. You need to talk about the same things. You need to talk about it the way the business talks about it. Way too often do I see architects that are pig-headed and decide to call something the client doesn't call it, and then the system and the way the system is built doesn't mesh with how the business talks about it, and so the developers end up talking about things the business knows nothing about, and there's a communication gap. So name it what the client names it. If the client talks about instructors, name it instructor. If the client talks about teachers, call it teachers. And make an agreement with the client on what you're going to call things, what the things are. So with that, we now know that instructor and student need a school ID. So we can start identifying the keys, or we can leave the keys out of it for now. And we can determine the keys when we go into relationships. But for now, what we have is roughly most of the data that we're going to store against each and every one of these entities. And that is what we want to come to. We want to know, hey, what is going to be stored in each and every one of these entities? And determining the IDs up front can be a good or bad thing. You don't have to do it. You can do it. You can look at those initial lines you drew that dictate some type of relationship and already put them in, or you can leave that to the wayside. It really depends on what you want to accomplish. If you want to have some type of idea of what the relationships are going to be like, then do it, or do the relationships up front. Now that we have all of this put in place, what we can do is we can take this information, set it aside, because we can start drawing the relationships between the entities. We're going to go on to step 3, and we're going to start talking about the relationships. And by drawing these IDs, we already have an idea of what the relationship's going to look like. But again, you can just think about the core data of the instructor and leave the IDs to the wayside if you don't want to do it. It's just about getting an idea of what information needs to be stored in this specific scenario. Street name, street number, etc., etc. All of that information is super vital, super important. So now that we have all of our attributes, let's look at relationships. Step 3, relationships. As I said in step 2, when you determine entities, you often go on to determining the attributes. What exactly is each entity going to store? But as you gain more experience, it may become difficult for you, and you may start intertwining the entities and the relationships, and you will want to depict the IDs and the relationships before determining the entities. And you can kind of get into this mishmash of things. Now, why should you follow these steps in the way that I depicted them? Because when you do it in this way, it becomes very easy for you to reason about certain things. When you determine the entities first, and then you look at each individual entity and you say, hey, you're going to store an address. You're going to store some type of information about the user, first name, last name, date of birth. You're going to store a subject, or whatever the case is. When you reason about it in that core logic, and you just put in place those rigid roadblocks and constraints, you can start building upon something. Now, as you saw me do in step 2, I started determining some of the foreign keys and primary keys that would come into play. And these are depictions of the relationships between, quote unquote, the tables that we're going to make. Or, more accurately, the entities, the relationships between the entities. We're trying to link the entities together. And so as you start thinking about these things, it becomes very difficult for you to separate thinking about the relationships from thinking in rigid buckets. You see, this process, although you can follow it step by step, oftentimes what is done is you think about it in different ways and you follow the steps at different paces, or you intermingle things. And as you gain more experience, it becomes very easy for you to separate out what needs to happen and reason about the why, and you can start mixing and matching things. But following these steps gives you the building blocks in order to start reasoning at a lower level, and as you gain more experience, you'll start to see the relationships form ahead of time. Even as you determine the attributes, you already see the relationships because you're thinking about it. You're thinking about the relationships and how the tables are going to be formed. Some people even like to go as far as to do this in create table statements. They like to create the SQL statements before creating the diagram. Now, I wouldn't suggest this necessarily, but everyone has a different process. Everyone has a different way of thinking about how to do these things. Now, at the end of the day, what this is trying to give you, what these steps are trying to tell you is, hey, this is how you break things down, and this is how you build things up, and this is how you reason about things. Because at the end of the day, all we're trying to do here is build a system and determine how to build it for the client in the best way possible. And we have to have reasons for why we do things. And this is just trying to give you a solid foundation of how you came to that reasoning. Now, a lot of clients won't care about what steps you follow or how you get there. But for yourself and for your organization, this may be extremely helpful. If you asked yourself, what is a relationship? Well, we've seen that tables can be linked through primary keys and foreign keys. This is how we depict a relationship in relational databases, and this is how we've traditionally seen relationships go. But when we look at relationships from a conceptual level, we're trying to link two entities together. And when we link those two entities together, what we're trying to accomplish is either a one-to-one relationship or a one-to-many relationship. For instance, one student can be taught by many teachers, or a one-to-one relationship. One student has one car. It really depends on the constraints of the system and the requirements in terms of what would be a one-to-one versus a one-to-many relationship. The last but not least relationship, and the one that we have to solve for the most, is the many-to-many relationship. So when we link two entities together, these are the three states that the relationship can be in. One entity belongs to one of another entity. Think of it like one teacher teaches at one school and only one school. But, you could also say that one teacher can teach at multiple schools. That's also a possibility in our system. You could say, hey, in one state, we have 3 schools. And so in that one state, a teacher teaches at many of those same schools. But if you had the constraint that in every state we only have one school, well, then you could say one teacher can only teach at one school. You see how the requirements of the system change the way that the relationships interact? And then you have the many-to-many relationship. The many-to-many relationship is when one entity and another entity have many different combinations. One instance of this, for instance, is a movie theater and a movie showing. You see, there could be multiple movie showings in multiple movie showrooms in a movie theater. When we look at this, we're trying to connect entities with a line that tells us the relationship. One to one, one to many, many to many. So we're going to depict this through a line. And so far we've drawn lines that kind of depict, hey, there's some type of relationship here. It doesn't really depict the exact type of relationship, but we kind of know what's going to happen there. But when we go into step 3, we're connecting entities with lines that tell us the relationship. And this is why I'm telling you things can get intermingled. You could do step 3 during step 1 or step 3 instead of step 2, is because when we look at these lines, we're calling them crow's feet. And we've seen this in our prior diagrams. The crow's feet depict the type of relationship that can occur. The first line tells you the relationship. This line over here tells you the relationship. So this is a many sign. This right here. This is a many sign. This over here is a one sign. So the first line over here is one. This is many. This is how you depict the many. This is how you depict the one. And then the second line, the optional line, is a constraint. So it tells you what kind of constraint that there is. 0 or more. 1 or more. 1 and only 1. 0 or 1. So it's telling us some kind of constraint. Something can have a value but doesn't need to. Something needs to have a value. Something can have multiple values. Something needs to have multiple values. This is just telling us whether or not, when the relationship is there, if each individual field needs to be linked, if the relationship is a strict relationship that every entity must have a relationship with a different entity, or that there's the option of having 0 or more. For instance, we could say that a student can have 0 or more lessons. You can sign up a student, but he doesn't immediately need to sign up for lessons. So he can have a 0 to many lesson package relationship. He doesn't take one lesson, he takes multiple lessons or multiple lesson packages. It's strictly the way you look at it. Or you could say when a student signs up to the system, he or she must take one or multiple lessons. This is a must. So when you inject something into the system, a value needs to be given. This is 0 or 1 and only 1. So the crow's feet depict a relationship, and the second line, the optional line, this word here is optional, can depict a constraint. You don't necessarily need to put that there. I wanted to break it down a little more of everything that we've seen so far. So far, we've looked at an entity. And an entity is a person, place, or thing, has a singular name spelled in capital letters. That's not necessarily needed, but it is something that you can do. You can spell the entity completely in capital letters. It has to have an identifier and should contain one or more instances of data. And this is the different ways that you can depict an entity. These are different standards of depicting entities. And we have been looking at crow's feet. And crow's feet is the way that we're going to depict the entities. And so in crow's feet, this is how you would depict it. You say entity name, and then you add the attributes underneath, and you add an identifier. So when we looked at attributes, we said it's a property of an entity, should be at least one business process. So it should be related in some way to the value. It should contain a value that is linked to a business process, first name, last name, etc., and is broken down to the most useful level of detail. For instance, address. It has to be broken down because it's not at the most useful level of value. And then we looked at relationships. And what relationships do is they show an association between two entities. You can have a parent entity and a child entity, which basically means that one entity is driving the relationship towards the other entity, for instance, between a student and a lesson, and is described as a verb or phrase. When you draw a relationship, what you're trying to do is say, hey, a student takes lessons. A school has students. You're trying to verbalize a concrete relationship and think about it that way. it has a cardinality, one to one, one to many, many to many. You can say it has a modality, null or not null. So like a constraint, does it have to have a value in the relationship or not? That optional second line that we can put there. And you could say, is it dependent or independent? Is the relationship dependent upon the other entity or not? So there's a lot of things that we can talk about here in terms of a relationship. But at the end of the day, what we're trying to do is associate two entities. Getting super theoretical about this is extremely useful if you're diving very deep into architecture and design. But it's not the most useful thing that you can do to create a foundation to reason about these things. What we at the end of the day want to do is we want to create meaningful relationships between entities and create a system that is as robust as possible with the requirements that we have at that time. Because requirements can change relationships. Requirements can change attributes, and requirements can change the amount of entities. So depending on what is happening in a system, all of these things are variable. We're trying to do the best we can with the information we have at the time in architecting the system and always keeping a close eye on how it needs to change or pivot in order to cover everything. Hopefully, you cover it enough up front that only small things need to change, like adding attributes or adding a new relationship with an intermediary entity. You formulate a new small entity on the side, for instance, to hold some specific information. With all of that said, with all of this knowledge that we've just downloaded, let's take a look at how we would draw relationships in DriveMe. Here we are back in Lucidchart, and we have our entities that we've drawn rudimentary relationships. These aren't really relationships, these are just linkages or links between entities that we've thought of as we were coming up with them. The main purpose of that was to reason about our entities and whether or not they should be there. And so now what we need to do is we actually need to make these relationships more concrete. We actually need to give them meaning. And so to give them meaning, we need to take a step back and think about it a bit more. So when we looked at this initially, we're looking at it with relationships in mind, but not really. So now what we're going to do is we're going to reshuffle everything and we're going to actually reason about the relationships now that we know that we have all of our entities. So when we look at a school, we can say that a school has instructors. Now, what do we say about these instructors? Well, we need to say that a school has multiple instructors, but an instructor can only teach at one school. So our crow's feet look like this. Why are they depicted like this? Because we're drawing the relationship in this direction, right? So a school has multiple instructors, but you can invert the relationship and you can say an instructor can only teach at one school. School has multiple teachers. So if we go ahead and we edit that, we can say a school has multiple instructors. An instructor teaches at one and only one school. But since we're drawing the relationship in this way, we're going to depict it with a sentence in this direction. So a school has one or more teachers, and a teacher can only teach at one school. And then we can say, hey, a school has students, right? But how does this relationship work? Well, we can say a school has one or more students. So what we would say here is one or more students. But a student can only go to one school. So when we add a student to the system, they only go to one and only one school. And the reason it's not 1 or 0 is because when a student is in our system, we assume he's going to this school. That's when he registers. So now that we have this in place, we have a clear path. Let's look at lesson. Well, an instructor can teach one or more lessons, but a lesson only belongs to one instructor. Multiple instructors don't teach the same lesson. You're not going to get a different teacher every week. You're going to stick with the teacher you have. Now, some schools could have the rule that multiple instructors can teach a lesson and that every other week you're going to get a different instructor. But this is what differentiates Drive Me from all of those other schools. So this is the business rule. Now, students, when we look at students, well, students can take one or multiple lessons. They can take multiple lessons if they need to, but they're taking at least one. And then what we say is that, hey, a lesson can only belong to one student. We're sure about that. And when a lesson is booked, it belongs to at least one student. For sure will belong to one student because we don't want ghost lessons being booked and instructors' times being wasted. And now comes the interesting part. We had exam. And when we had exam was linked to student in a way that was kind of like this, but without the crow's feet, of course. But when we looked at the attributes of exam, well, an exam is administered by an instructor and is taken by a student. So interestingly enough, we kind of looked at this and we said, well, an exam can have a student ID and it can have an instructor ID and it should also have a lesson ID. But the interesting thing about this is, well, if we think about this, how is this going to look in data? There are multiple right answers here of how to put this together. There is an efficient way and a less efficient way, of course, but there are multiple ways. And so it really depends on the requirements of the system. And the requirements of the system tell us that a student can take an exam up to 2 times. Otherwise, he or she needs to take more lessons. So, should an exam be linked to the lessons? That is a good question. When we looked at the attributes of exam, we put in instructor ID and student ID because it felt right. It felt right as a concept. You know, an instructor is administering an exam, a student is taking an exam, you can fail twice. So how do we architect this relationship? It's a conundrum, right? Should we say that a lesson can have one or more exams, but they're typically done after the lessons, right? Why would we need the lessons specifically? Well, we said to link them to the package of the lessons, which is a valid reason. You know, if you're taking lessons, you're entitled to an exam, but at the same time, what if you take more than 2 exams? Well, then you need a different lesson package to be linked to it. Okay, so that makes sense. If we say that in order to take exams, you need to have taken lessons, there is a relationship here. In order to take an exam, you have to have taken lessons. Okay, so that means that lesson is linked to exam. And that means that an exam can only be linked to one lesson. So, an exam belongs to one and only one lesson package. But a lesson can have multiple exams, up to 2. So 1 or more. So up to 2. And then what we can say, hey, what about the student? Because the student is taking the exam, right? Well, yes, and the instructor is administering the exam, right? That's also correct. So what do we do about these relationships? Well, that's an interesting question because an instructor can give one or more exams, but an exam can only be linked to one instructor because not multiple instructors administering an exam. There's only one instructor administering an exam. And a student can take one or more exams, but an exam can only belong to one student. So interestingly enough, all of these relationships are valid. But at the same time, because they are linked through the lesson, don't we already know this relationship? Some would argue yes, you do know the relationship because a lesson is linked to a student and an instructor. So is this a redundant relationship? Technically, yes. Is it bad to hold the reference to these things? Not necessarily. At least at this point, you immediately know the uniqueness of the relationship. So you can keep it or you can remove it. It really doesn't matter. But the constraint on the exam being 2 lessons, that is the important part of this entire entity relationship diagram. And so where are we going to put this constraint? Because according to this, a lesson can have multiple exams. So who's going to hard stop it at 2. Well, this can be done at the software level. Or this could be just done as a business rule. Someone behind the desk could say, hey, you've already done 2 exams, no more. If it's a hard stop rule, maybe the client wants us to put it in the system, but maybe the client also says like, hey, we're a little bit more lenient on it. Some of our students, they have a hard time, they're stressed out, this and that. We'll give them a 3rd exam try. If you hard code a 2 limit into the system, now you're making it very rigid for the instructor in the school to administer the ability for multiple exams to be taken. Because maybe this should be a more loosely coupled business constraint. Maybe we shouldn't architect it into the system. And so with that said, these are all considerations that need to be made. You need to make the requirement very clear. Now, in this case, the requirement is a loosely coupled constraint. I went to Drive Me. I said, hey, I saw this constraint. What do you think about keeping the exam tied to the lesson? But it's up to the instructor in the school to determine whether or not 2 is the hard limit. We don't want to really force a full stop into the system. We just kind of want to have a track of the exams of the student. We are first and foremost a student-oriented business. We want to help our students succeed. So we want to be more lenient about the exam and the constraints around the exam. And so we're not going to force the system to be rigid and force people to have to pay automatically for more lessons in order to take an exam. Of course, if you fail twice, the instructor will go in and say, hey, you need to buy more lessons, and then we'll administer more exams. But we don't want to put a hard constraint on the database level. It's not necessary. And so the final relationship we have here, after determining that constraint was a soft constraint, is the vehicle. And so the vehicle is an interesting one, because what we're trying to accomplish here is the ability for a lesson to have a singular vehicle. That's what we want. We don't want anything too complicated. So we're saying a lesson can have one and only one vehicle, and a vehicle can belong to one or multiple lessons. So that makes sense, right? A lesson has only one vehicle. When you buy a lesson package, there's only one vehicle linked to your lesson package. We don't want you driving a Volkswagen one week and a Mazda the next week. When you're learning to drive, you're stressed out enough. And then what we're saying is that a vehicle can have 0 or multiple maintenances. If we buy it new, it doesn't necessarily need to have had maintenance. And then a maintenance can belong only to one car, and it has to belong to at least one car. We don't want any ghost maintenances happening around here. And so with that, we have drawn the relationships of Drive Me Academy. And interestingly enough, we have architected a system that does not have any many-to-many relationships. And that's a great thing, because now we can go ahead and, since we have our entities and we determined our attributes, we can now say, hey, let me go put the attributes on top of this, and I have a full entity relationship diagram. And that's a great thing. If we didn't put lesson in between here, we could have had a many-to-many relationship right here. A teacher could teach multiple students, an instructor could teach multiple students, but a student could have multiple teachers. But that doesn't really make sense because they're linked to a lesson package. And the way that you would solve that many-to-many is, of course, with that lesson table. But we had the requirement up front of them serving lesson packages, 6, 8, 12, whatever the case is. So we didn't have that need for that many-to-many relationship. We knew up front about the lesson packages in the requirements. So no many-to-manys is a great thing, because the next step would be how to solve the many-to-many relationships. And let's take a look at some of the many-to-many relationships that could happen and how you would solve them now. We've landed on step 4. Many-to-many. Now I'm going to say something controversial, and I'm going to say something that a lot of people will think I'm crazy, but in the relational model, it isn't possible to store many-to-many relationships. Or this is what they at least teach you, and this is what they taught me in computer science, that in the relational model, it isn't possible to store many-to-many relationships. And the reason they teach you this isn't because it isn't technically possible. Technically, you can do it. but you really, really, really don't want to. And the reason for this is you're creating more overhead. You're creating insert overhead, update overhead, delete overhead, and potential redundancy. All of the things we hate. Running update and insert queries and delete queries, painful enough. But redundancy? Duplicate data? Are you crazy? Now, I have my own thoughts on redundancy and redundant data. It's not all bad. Some people are purists. But at the end of the day, all of these negative aspects of storing a many-to-many relationship are what cause us to say it isn't possible. Because you're just overcomplicating your system at that point. You see, we want our relationships to be crystal clear. And with a one-to-many relationship, instead of a many-to-many relationship, what you're creating is, in essence, a simple way for you to store a relationship in a single row without having to create update and delete overhead. There is, of course, some insert overhead. You have to insert the relationship, of course, but it isn't all that crazy. Now, as a rule of thumb, always try to resolve many-to-many. Now, there will be instances in which a many-to-many relationship may be valid. And those instances are very dependent on the system. And if you ever see them happen in a system, ask the architect why. Don't go up to them and say, "You're crazy, you added a many-to-many relational model, yada, yada, yada." Of course, technically speaking, you're right, but there's always a time and a place for something, and there's always reasons for things to happen. And some systems, they may be rigid, they may be old, there may be specific reasons that there are many-to-many relationships. But as a rule of thumb, when you're creating your own system, try to resolve the many-to-manys. And the reason for this is the oldest example in the book. Literally the book. If you look at book and author, it's one of those ye old tales. Is there a single author or are there multiple authors? And an author can be an author of multiple books. So did he write it with someone else or she write it with someone else? Who knows? So it's a many-to-many relationship. A book can have many authors and an author can write many books. So the way that we resolve this problem, well, if we look right down here, a book has, and it seems that I've made a mistake right here. This should be a 1, but apparently I put it as a many. So right here, it should be 1 and only 1. But so what we're trying to depict here with the relationship is a book can have many book authors, but a book author can only belong to one book. So imagine that this was just a 1. One and only one book. And an author can be the author of multiple book authors. So he can belong multiple times in a book author table. But a book author can only belong to one author. Okay, this is really confusing. This entity really doesn't tell us what it's doing. But I've taken the liberty of going ahead and putting it into concrete data. Now, if we put this many-to-many relationship in this format, which is a table format, which is what you're all familiar with, if we were to do the many-to-many relationship in this way, well, now suddenly we have to have multiple foreign keys because we have 2 authors, Mo and Andre. And Andre was the author of book 1, and so was Mo. But for book 2, it was only Andre. So if we look at book 1, well, I went a bit overboard here. This is sample data, but it's just to depict the scenario. We have to have multiple foreign keys because there are multiple authors. Author ID 1, author ID 2, author ID 3. So the book number 1, has multiple authors. And over here in the author table, we also now need to tell every single author which book they authored. So book 1 and 2. It becomes a column-based insert, update, delete anomaly. Every time you create a relationship between these two, you have to add more columns because there are more relationships, and it becomes difficult for you to update and delete if you need to remove an author. You're creating all of these anomalies. It's so hard. It's way too much mental overhead. This doesn't mean that many-to-manys are bad in every single scenario. Not that I've ever seen one personally that has struck me as something that needed to be a many-to-many, but I'm sure to believe that there are many cases out there in which these relationships had to happen in some databases. That said, this you can feel this feels wrong. And so why we created the entity book author is because now we've simplified it. And this is the correct relationship. A book can have multiple book authors, and an author can author multiple books. But because we are linking them with an intermediate table that only contains their ID, now we don't have that insert column anomaly, delete anomaly. Because they are rows in a table, we can now manage them more effectively. And we have the relationships to back it. So we can now say, hey, Mo authored book 1, Andre authored book 1, and there's no extra info needed in this table or this table in order to warrant this relationship. The relationship lives somewhere else, and we've solved the many-to-many debacle. And so with that, this is what we call intermediate entity types or intermediate tables. They're there to solve the many-to-many, but naming them is extremely hard. For instance, when we had our prior database of teachers and students, we had an intermediate table called enrollment. The sole purpose of that was to link a student to a course and a course to a student in a way that wasn't a many-to-many, just like we do here with book and author. So now we know for which book, which authors, and for which authors, which books. So we have a clear way of doing our queries now, as well as getting rid of all of those insert, update, delete anomalies and potentially redundant data because they live in this intermediate type. And that's the power. This is how we resolve many-to-many relationships, creating these intermediate types. But finding the right name for them is hard. We call these intermediate entities or intermediate tables. And the sole purpose of them is to get rid of those many-to-many. Now, if you ever come across a many-to-many, make sure to think about how you can create an intermediate type. In Drive Me, it was lesson. Lesson was the glue between a teacher and a student. If we didn't have lesson between teacher and student, there would be a many-to-many relationship. So if we look over here, this is saving us from having that many-to-many over here. An instructor can teach multiple students, and students can have multiple instructors. At the end of the day, in this format, there isn't a lesson package, which means you could have 5 lessons from the same instructor or a different instructor, but we decided as a business requirement that there were lessons. This is our intermediate type. It's a little bit more elaborate than an intermediate type because we have a package and we have all these other things that are linked in a lesson, but at the end of the day, this is a solid form of an intermediate type, intermediate entity. And so with that, we now know what many-to-manys are, why they hurt us, and how we can potentially solve them. The final step of top-down design that we will look at is subject areas. And let's take a closer look at that. Last but not least, step 5, subject area. So far, we've given you the 5 steps to success with top-down design. These aren't the only 5 steps you can follow. And you can shuffle them around, you can add on to them. It really is a guideline for you to follow in terms of being able to wrap your head around the broad scope of a problem that is designing a system. It's there to bring order to the chaos of design. And so subject areas is one of those things that I don't ever do really when I do the top-down design, but it's an extremely important step if you want to divide and conquer a system. If you're doing it at a distributed level, at a global level, it's good to think about when you're designing. In step 5, subject areas, what you're trying to basically do is divide entities into logical groups that are related. And the reason for this is when you split them into separate buckets, well, now you can hand them off to different teams to further refine and broaden and look at the requirements and add on to. Dividing into logical groups that are related is a good final step for your first design because you're going to iterate on this design regardless of what you think. You will not get entity relationship diagram fully fledged out from the first go. This needs time, patience, and iteration. But dividing into logical groups, what that gives you is the ability to separate, segregate, and look at requirements in individual buckets and figure out if what you have encompasses everything you need or you need more. And so when we look at subject areas, you can think of them like schemas, but not really, because you're never going to really go one-to-one from a subject area to a schema, but it is a way to like categorize and group. Now, there are rules to subject areas. All entities must belong to one. So no matter how big your system, all your entities must belong to at least one subject area. An entity can only belong to one subject area, and you can nest subject areas. So you can create subject areas within subject areas. Those are the only rules that we have to play with, but they're important because you need to follow them. Okay, so with all of that said and knowing what subject areas are, let's go apply it to Drive Me Academy. When it comes to subject areas, it's a very open-ended discussion. Different interpretations lead to different subject areas. That being said, with everything in design, it's partially objective and partially subjective. I, as an individual looking at this problem, may come up with a vastly, well, hopefully not vastly, but a different solution than a different architect. And I may look at the domain differently than a different architect. That's why it's important to work together. And that is what I strive to teach in this course, is that with everything, asking for insight, asking for help, and working together is the most vital part of database design. But it is important to have the fundamentals of looking at an issue and trying out different things in order to get the right outcomes. And when it comes to subject areas, it's one of those things that, well, interpretation lies in the eye of the person architecting the system. And so with that, I've gone ahead and I have divided Drive Me, the diagram that we've made here, into different subject areas. I've put school and administration because a school has administration and there is administration to do with the lesson packages and the school itself outside of everything else. And then I have gone ahead and put student, lesson, instructor, and exam inside of education because these have everything in my eye to do with the education of the student. You have the instructor, the lesson, and the exam. And then I went ahead and put vehicle and maintenance in inventory. Because although they are related to education and they are an educational tool, they are not directly corresponding to the education of the student. They're just a means to an end, teaching the student with a vehicle how to drive. The instructor is doing the heavy lifting in terms of teaching the concepts and so forth. So these three subject areas, I think, encompass Drive Me perfectly. Now, just because this is the way I look at it, doesn't mean it's necessarily the way you would look at it. So I would really appreciate it if each and every individual that follows this course paused the video right here, went ahead and tried to come up with their own subject areas and thought about the why and wrote down the why and just started to mull it over. The next videos will be looking at some exercise cases in which you can apply these theories and go ahead and think about these things separate from Drive Me Academy, the best driving school in the USA. But with that said, and with these examples out of the way, you have seen the 5 steps to top-down design that give you a solid foundation to go ahead and think about these problem areas. And with that, let's dive into some exercises. Awesome. We have seen top-down design, and we have seen the 5 steps to success. And now we need to put it to the test. But as with everything, with database design, there is no one absolute right answer. There are right answers and there are definitely wrong answers. But within the right answers, there is a vast spectrum of right answers. So with this, always take the solution as a guideline and have reasoning for your design. And as long as you have reasons for which you have implemented the design, and you can prove that your design doesn't have adverse effects on inserts, deletes, and all of those things, you pretty much have solid footing and ground to stand on to defend your design. And that is what is important in this portion of the course, is the freedom to design, the freedom to draw out your version of the world. And I would suggest that when you create these models, create a small database, try out some scenarios, come up with some scenarios, and try out your design, just so that you can test out if you have hit all of the scenarios you wanted to catch. For this exercise, we're going to be looking at paintings. And I'm going to give you a scenario in which someone needs a design. And what you're going to do is you're going to pause the video at one point and you're going to go ahead and do the 5 steps of design. And then you're going to come back and I'm going to go over my solution. And you can look at your solution and you can see how far you strayed off or how close you were or how yours differs, and you can reason about that. All of this is contingent upon you being able to think through these concepts and come up with solid designs. Because my designs, although they are my interpretation of the case and the solution, you can have your own interpretation of the case and the solution. You just have to look at mine and say, hey, what's different and why did I do this? And you can test your theory out. Now, to the business case. A rich businessman has tons of paintings and he wants to build a system to catalog and track where his art is. He lends it to museums all across the world. He even wants to see the reservations. So a rich businessman has a ton of paintings and he wants to build a system to catalog and track where the art is. We got that part. And he wants to see the reservations, and the museums can be anywhere in the world. So knowing that, here are some constraints to take in mind. A painting can only have one artist. We're not going into the book author scenario. There is one sole artist for every painting. So don't rack your head around. So let's answer some questions about the system. What is the goal of the system? And who are our stakeholders? Now, I would suggest you pause the video here, think about it a little bit, and come back to see my answer. Now, I hope you thought it through thoroughly. In my mind, the goal of the system is to track painting reservations for a wealthy man. And the stakeholders in this system, in my opinion, are, on the one hand, the owner of the system, and on the other hand, the museums that will be booking reservations against paintings. Now that we have all of this information, let's follow our 5 steps of success for top-down and create an entity relationship diagram of the system. Please feel free to pause the video here, go ahead and follow the 5 steps. And when you come back, we'll be going through each individual step and my solution for the database design of the painting database. All right. So now that we've been through all of that, and now that you have followed the 5 steps, let's go through what I solved for the 5 steps. In step 1, I had to determine the entities. So when I determined the entities, I looked at the system long and hard, and I thought to myself, well, the first entity must be painting, because we're booking reservations for paintings. But there's a caveat here. What if the requirement was, he has a bunch of art? Well, then my entity would have been art. But the requirement of the system was paintings, so I chose painting. I didn't choose to go too broad. I chose to stay within the constraints of the system. Now, I could have talked to my stakeholders and been like, do you only rent out your paintings? Or do you have other art? And are you renting that out as well? Yada, yada, yada. For all intents and purposes of this particular system, I chose painting. And then the second entity was pretty straightforward. We have reservations. Reservations that museums make. And we have artists for the painting. Now, we could have added an owner as an entity, but we know the owner. It's one sole owner for these paintings. So we added artist as well. And then in step 2, we went and we looked at the attributes for each entity. And we came up with, for painting, name, creation date, style. In this particular scenario, I didn't go and add the keys, the primary keys, the foreign keys. I didn't want to muddy the waters. Let's keep it simple and let's focus on the specific data that we're storing for each and every one of these entities. So for painting, it's name, creation date, and style. For reservation, creation date, date from, date to, and whether or not it's accepted, whether or not the reservation is accepted. And for the artist, we're keeping the name, birth date, and the email. Then for the museum, we're keeping the name, we're keeping the address, which is not a good entity type. We know we're going to need to split this out into multiple, but we'll put an asterisk here. We have phone number and we have email. So each and every one of these entities has their attributes. And so now we're on to step 3, relationships. And here you can see I've clearly depicted the relationships between the entities. So let me describe them to you. An artist can have 0 or multiple paintings. He may not have sold to the individual yet, but there is the potential of selling to the individual. So an artist can have 0 or more paintings. A painting can only belong to one artist. Now, paintings can have 0 or more reservations, and a reservation can belong to one or more paintings. So in one reservation, you can book multiple paintings, and a painting can belong to 0 or more reservations, because over time, reservations want to rent the same painting. Now, a museum can make 0 or more reservations. They can decide whether or not they want to rent a painting or not, and a reservation can only belong to one museum. And as you can see over here, we have a many-to-many relationship we need to solve. I'm so excited. Not really, because it always hurts to solve the many-to-manys. You need to determine what the intermediary type's going to be and what it's going to be named. But nevertheless, exciting times ahead. So we need to go to step 4, which is solving the many-to-many. And if we do that, what we can see now is an artist can have 0 or more paintings. A painting can belong to 0 or more reservation details. So there's a reservation detail type, intermediary entity type, and a reservation can have 1 or more reservation details. So we're creating this intermediary table or entity in order to store the ability to have a reservation against multiple paintings, and for paintings to belong to multiple reservations. And the rest of the relationship stays the same. Simple enough. We could go to step 5 and we could determine the subject areas. Now, for this particular exercise, I have not gone ahead and determined subject areas, but it is an extra step that you could potentially do if you would like to split it out. Now, you could say that reservation detail is part of administration. And then you could say painting and artist is part of inventory, and you could say museum is part of client. Those are some subject areas that come to mind. It really depends. And so it's a free thinking exercise when it comes to step 5. It's really how you see it. That is one example of what you could do. And so with that, we have architected a simple yet effective reservation system for paintings. Now let's go ahead and look at our next exercise. It's a fairly simple exercise related to movie theaters. For our final exercise, I thought it would be fun to look at something like a cinema or a movie theater. And over here, I have an existing ERD, a simple entity relationship diagram that depicts a relationship between a movie, an auditorium, and a theater. And a movie can be played in multiple auditoriums, and multiple auditoriums can play multiple movies. This is because they are played at multiple times during the day. So, for instance, Auditorium 1 can play The Avengers, and then it can play Forrest Gump, and then at 3 it'll play a different movie, and at 4 it'll play a different movie. So an auditorium can play different movies throughout the day. And a movie can be played in multiple auditoriums. The Avengers is often, when it's released, played in 3 or 4 auditoriums. So this is a very common many-to-many relationship. And so my question to you is, fix the many-to-many and keep it simple. Now I want you to pause the video here And given what I just told you about the show times and the ability for an auditorium to play multiple movies and so forth, fix this many to many. And when you come back, we'll go over the solution together. All right, I hope you had fun solving that one. And so this is my solution to the problem. A theater has multiple auditoriums, and an auditorium only belongs to one theater, of course, because you do not have the ability to put an auditorium in multiple theaters at the same time. It is in that theater. And so an auditorium can have multiple showings. It can have 0 or multiple showings, to be exact. So during the day, an auditorium can have 3 showings of the Avengers and 2 showings of Forrest Gump. And then for 2 hours, it doesn't have any showings at all. And then a movie can have 0 or more showings, depending on how popular the movie is. It may have 5, 6, 7, 8, 9, 10 showings in a day, but it's not dependent on the auditorium, because now the people managing the system have to say, okay, Avengers came out, we want to show it 10 times a day. And then they can go ahead and say, well, we're going to link it to these auditoriums, and these auditoriums are doing these showings. So that's how we would solve the many-to-many relationship for a movie theater. It is an intermediary type that is so obvious, but yet so difficult to find. Intermediary types are often hard to name. Sometimes they're obvious, and sometimes they are just part of the business context, like a movie theater having showings. But sometimes they're less obvious, like with our painting reservation system and having to have a reservation detail instead of something as obvious as a showing. This is one way to solve this many-to-many relationship. And so with that said, we've seen everything we need to see in terms of creating a great foundation for understanding top-down design and being able to create these robust entity relationship diagrams that depict a holistic system. But with that, we have only seen how to do top-down. What about bottom-up? Well, let's take a look at what we've seen so far. So if we zoom into where we started off with looking at the phase 3, the software development lifecycle, which was system design. And then we asked ourselves the question, well, how do you design? And the answer was, you can go either top down or bottom up. And so when we looked at top down, we learned about entity relationship diagrams. And we learned about how they are the cornerstone of doing a top-down design. And then when we looked and zoomed in at how to do entity relationship diagrams, well, we saw that there were multiple steps involved. First, you had to determine the entities. Then you had to determine the attributes. Then you had to determine the relationships. And then you had to resolve the many-to-many relationships. And then you could decide on some subject areas. And these were the 5 cornerstone pillar steps that we said you can follow in order to create a solid entity relationship diagram. But we also said that some of these steps can be interchangeable. Sometimes you want to determine the relationships after you determine the entities, and then you want to determine the attributes. Or sometimes you want to determine the entities, the relationships, resolve the many-to-manys, and then look at the attributes. It really depends on how you want to look at the systems. You can even start off with talking about subject areas if you want to think abstract enough. It really depends on the flow that works best for you and in suiting which way you should follow these 5 steps. But the 5 steps are there in order to give you a guideline. And now we're going to take a look at bottom up. And when we look at bottom up, we really don't have a way to design yet. We don't know how this works. So let's take a closer look at that. Now that we've seen top-down design and the techniques that go into top-down design, it is important to understand the opposite of top-down design, bottom-up. Now, why are we looking at top-down versus bottom-up? Why aren't I just showing you the techniques? Well, it's important to know that in order to create that structure from the chaos, we need to understand when and how to use these methodologies. And there are specific scenarios in which you want to design in a specific way. It's not to say that you may go and combine both strategies to sanity check yourself. All of the strategies that go into bottom up versus top down can be used to validate your data model. They're just ways of going about doing these things. Now, when we look at bottom-up design, we're trying to create a data model from specific details. Okay, when we talk about specific details, what are we talking about? Aren't requirements specific details? Like when we were doing top-down, didn't we get requirements from the client? Yes, we did. But when we talk about specific details in bottom-up design, what we're talking about is, hey, there are existing systems, legacy systems. There's some type of database that's already in use or some kind of process that is being followed that is logging data into a system. When we do bottom-up, we're going from specificity, something that exists, and we're trying to migrate it to something that is newer. So that's why we go from the bottom up. And so with that, what we need to understand is when we do bottom-up design and when we try to create this data model, is that we need to identify all of the data that is required. So we need to go into the existing systems and we need to say, hey, these are all the attributes I have. And then we need to go ahead and group them and create our entities. It's kind of like what we did with the entity relationship diagram, right? We went ahead and we looked at the requirements, but we went the other way around. We said, hey, these are our entities. And then we said, hey, the entities are going to kind of store this data. And then we went ahead and we drew relationships between the entities. It's a different methodology of getting to end state. But when you go in an existing system, you don't want to go and say, hey, okay, I'm going to come up with all of these entities and I'm going to tell you what you're going to store. No. We already have data we're storing. We already have attributes. And so we need to identify that data. And then we need to go ahead and deduce the entities from them. And it makes our job partially easy, but it also makes it hard because we need to use a different methodology. We won't be using entity relationship diagrams here. No. Our goal is to create a perfect data model without redundancy and anomalies from the existing data. That is our goal. And the entity relationship diagram, although it gave us a good data model when we came in with requirements, because we have existing data and because we have existing systems, we need to look at this with a more rigorous approach because we are not the chef in the kitchen. No, there have been multiple chefs in the kitchen. And so to create that perfect data model without redundancy and anomalies, we need to go and we need to look at the existing data. Now, you may be asking yourself, what do you mean redundancy? Redundancy, I mean duplicate data. We want to avoid as much as possible that duplicate data is in the table, that we have duplicate records. Okay, I get that. But what are anomalies? That's a good question. And we've kind of touched on anomalies multiple times throughout the course. We've looked at them and we've talked about them, but we haven't really given them a name. So let's zoom in on these anomalies and what exactly they are. But remember, the goal of the bottom-up approach is to take the existing specific data and create a data model that is going to, quote-unquote, be perfect. There is no perfect data model, but there is perfect to certain standards without redundancy and anomalies. And so we're going to show you how to do that. We're going to show you how to do a bottom-up approach. But just remember, whenever we do any type of design, depending on the methodologies you use, you want to validate that the end state of your data model has as little redundancy and as little anomalies as possible. That is what we're trying to accomplish here. So let's zoom in on what anomalies actually means. Anomalies. Things that literally you want to avoid when creating a database. Anomalies is one of those things that literally says that things are happening that you don't want to happen. And in database design, we talk about modification anomalies. These are problems that arise when your database is not structured correctly. And all of these design techniques that we're teaching you, entity relationship diagram, bottom-up design, top-down design, all of them come with their methodologies in order to create a structure that is correct, that tries to reduce these anomalies. Because what you really don't want to happen is that you have anomalies when you ship to production. It's going to be painful to maintain the database. And so there are 3 types of modification anomalies. And when we look at these anomalies, we put them into 3 separate groups: update anomalies, insert anomalies, delete anomalies. And so let's take a closer look at each and every one of those individual anomalies. You see, when we look at an update anomaly, what we're trying to do is make sure that changes apply to all of the related data. And over here, you can see I have a customer table. And I have a customer with an ID 1, 2, 3, 4, 5. And they have a balance in their bank account. And so with that balance, there is also a branch, the branch that they bank at. And over here, you can see that in red, I highlighted something. The branch name, Toronto. And so each and every one of these individuals, client 1, 4, and 5, they bank at Toronto. And they bank specifically at the address 100 Front Street. Now, let me pose you a question. Let's say that the branch Toronto changed their address to 101 Front Street. Well, when we update the record and we do an update command, now all of a sudden, we need to make sure that each and every one of these records gets updated correctly. So we have to make an update command that goes and looks at each branch that is in Toronto and updates the address for each and every one of those instances. Now, if we had 10 million users, well, now when we update a simple address, we're going to have to do it 10 million times because it's all in this same table. It's all inside of here. And so that is what we call an update anomaly. It's causing us to have to do heavy work in order to update something that isn't actually directly related to a customer. Of course, we need to know at which branch a customer banks at, but having it stored directly next to the customer individually, first of all, we have redundancy here. We're storing duplicate data in the table, but we also have the update anomaly. 10 million records, 10 million updates for a simple address fix. So redundant data and an update anomaly. And so how would we go ahead and fix that? Well, we'll look at that at the end. But first, let's take the same example and look at the delete anomaly. Well, over here, you can see we have our 5 customers, and we have a customer banking in Scarborough at 20 Beach Street. Well, with delete anomalies, what we want to make sure basically is that we don't lose important data. But if we delete client number 3, suddenly our branch disappears. Now, how is that a good thing? Suddenly in our system, because we're storing the branch with the customer, and we delete customer number 3, suddenly we know nothing about our branch in Scarborough, our branch at 20 Beach Street, because we have created a direct functional dependency between the customer and the branch. And we don't want that. We want these two to basically be separate. Of course, we need to know at which branch a customer banks, but deleting a customer should not lead to us losing important information about the entity of a branch. And by deleting this record, we are now functionally deleting our Scarborough branch. We don't have any information anywhere else about it. So that is a delete anomaly. And then we have an insert anomaly. Now, when we insert a new record into our database, we add a new customer. Let's say we added customer 5, and someone made a mistake and they put them at 101 Beach Street. They didn't update, they inserted someone. Well, now we need to make sure that the data is consistent. How do we make sure that when we want someone to bank in Toronto, that if someone fills in the street wrong, that we validate that? Well, that's going to be some complex logic that we now have to do either on the server side, or we need to write some complicated code in our database on insert in order to make sure that if someone inserts it wrong, that stuff doesn't go haywire. So data consistency with insert anomalies is key. Inserting new data means that, well, now we need to make sure that when someone new banks at Toronto, that when new data is inserted, that is consistent with the rest of the data. So this dependency between branch and customer, we really need to separate it. And so with bottom-up design, what we're trying to get to is basically looking at those dependencies between data and making them into their own entities, like we did with our entity relationship diagram. You can already feel from top-down design that we're going to have an entity branch, and we're going to have a primary key and a foreign key. And basically, at the end of the day, when we do all of these design techniques, what we're trying to do is cause low coupling between data. We don't want data to be tightly interweaved. We don't want there to be dependencies between data that cause issues for other data. So, what we're trying to achieve here is basically making it so that each individual customer only has the data that they need to update for themselves, that the dependency of the data of the customer only is about the customer. So in this case, it would be the customer ID and their balance. The customer, of course, needs to know about their branch as a relationship, but it doesn't need to store the information about the branch because that relationship causes all of these anomalies. And so that's where we follow the process of normalization. This is the process that you follow in bottom-up design to come to the same conclusion that we did in top-down design, which is coming to entities, individual entities that encompass their data in an isolated way and don't create these anomalies or redundancy of information being stored in a table. We really, really want to avoid storing redundant information, and we were storing the address so many times per customer. And then we were also causing anomalies, and oftentimes redundancy and anomalies go hand in hand. So over here you can see we split out the customer table to only care about customer and balance, and it has a foreign key relationship with branch, which is now its own table, right? Branch is its own table, and it has its branch ID, and it has a branch, and it has an address. And so now branch only cares about branch information, and customer only cares about customer information. And we can see here, okay, of course, we're storing some redundant information. We're storing the branch identifier, but that's not redundant. It's an important relationship. Redundant information is when we, for instance, stored 100 Front Street 10 million times in the customer table. We don't want that. Avoiding anomalies is key to database design. And it's the same thing that we're coming to when we did top-down design. When we devise these entities, we're trying to isolate data in terms of its dependency towards other data. We want the data to be isolated to the entity that needs to know about it. And we want the other entities to have relationships to that data, but not necessarily store that data. Is it kind of clicking at this point? Conceptually, it's hard, but what we're basically trying to do in the relational model is make it so that the dependencies between data are as loosely coupled as possible so that we don't have anomalies and we don't have redundancy of storage inside the same table. And the way we do that in top-down is through entity relationship diagrams. And the way we do that in bottom-up is through a process called normalization. Now that we know that this is our end goal, our end state, creating a loosely coupled system of data that has relationships that link data together, but reduce anomalies and reduce redundancy, we can go ahead and we can go see how we would come to this end state. This is the end state. We're going to go see how we would get to that end state if we did it with normalization. So let's take a deeper look at that. Hey everyone. So now we're going to talk about normalization. But before we do that, I wanted to take a step back because we've seen so much so far, and it becomes very difficult to understand the core foundation of what we're trying to achieve. So I just wanted to quickly reiterate everything that we've seen so far and why it's important. So when we look at the software development lifecycle, we're looking at system design. We're specifically looking at how to design a database. And when we pose ourselves the question, how are we going to design? Well, the question becomes a function of what specifically are we trying to accomplish? And so when we looked at that question, we asked ourselves, hey, do we have an existing system? Or do we have a new system? And if we had a new system, we were going to apply something called top-down design. Or if we had an existing system, we were going to apply something called bottom-up design. And the reasons for this is each and every one of these design methodologies, bottom-up versus top-down, has their own ways of achieving a design. And the end state of achieving that design is to have a design that has as little anomalies as possible and as little redundancy as possible. That's what we're trying to accomplish with database design. What we're trying to accomplish with database design is the ability to design a model that has little to no redundancy and little to no anomalies. And that's what bottom up and top down are trying to accomplish. And when we looked at top down, the way we did it with top down was something called entity relationship diagrams. And there were certain steps that we followed here. We had 5 steps in order to come to an entity relationship diagram that had as little redundancy and anomalies as possible. But even with that, when you follow entity relationship diagrams, you can sometimes come across issues and still come across anomalies. And with bottom-up design, we're going to look at something called normalization. And what I'm trying to get at here is that these two techniques, although they're specifically used for top-down and bottom-up, they're not specifically tied to that bucket. You can use entity relationship diagram mapping after you do normalization and bottom-up to validate your schema. And in top-down, you can draw your entity relationship diagram, and then you can go ahead and do some normalization if you want to validate your entity relationship diagram. What you end up doing in design is using a bit of both. You'll use whichever technique you need to in order to achieve the end state, which is having a database model with as little redundancy and as little anomalies as possible. And when we looked at entity relationship diagrams, we talked about anomalies a bit, but we didn't give them a specific name. And when we looked at normalization, we dove deeper into what anomalies specifically are. And so what I'm trying to get at here is when we ask ourselves the questions, how to design? Well, depending on the scenario, we may go top down, we may go bottom up. But depending on what you want to achieve, you can mix and match a little bit of both. There are no hard set rules. What you're trying to accomplish at the end of the day is just having a design that has as little anomalies and as little redundancy as possible. And these techniques help you do that. So you can go ahead and you can create your entity relationship diagram. And after the fact, you can say, hey, let me try to normalize this a bit more. Or you can do your normalization technique and then you can draw it into an entity relationship diagram. And you can go ahead and see when you have that visualization of those entities, if there's anything missing or you need anything more. All these methodologies are trying to do is create different ways to get that same end state. And when we look at normalization, normalization is a key way to avoid anomalies. It's a structured way to go about looking at your attributes, your data that you're storing, and creating a data schema and deriving entities from that data schema in a way that concretely tells you if you're going to have anomalies and concretely tells you if you're going to have redundancy. And the way that this is done is through the process of normalization. And that process we're going to look deeper at. It's a set of steps that we're going to follow. Normalization forms that you need to follow, and you're going to start at the first and go to the second and third and so forth. And when you do this, your end state will be, hopefully, a schema with minimal anomalies and minimal redundancy. Now, Edgar Codd, one of the inventors of SQL, proposed the theory of normalization. And what normalization is at the end of the day is just a design technique to reduce redundancy and anomalies. That's what we're trying to get at, reducing redundancy and anomalies. Now, to do normalization, we must understand two things. First off, we need to look at the functional dependencies of data. And I've already alluded to this, the dependencies of data. But we haven't really dove deep into what exactly that means. And then second of all, we need to understand the normal forms and what exactly those entail. And once we understand both of those things, it's going to become very easy for us to understand how to apply normalization. But in order to do that, first we need to understand, when we look at attributes, how their dependencies are towards each other. When we looked at the branch and the bank example, we could automatically already feel that branch needed to be separate from the customer. And this is because we're used to the primary key, foreign key relationship, and we're kind of feeling it out. This shouldn't be here, but it should be somewhere else, and it should be a relationship. And that's because you're looking at these functional dependencies. You're saying, well, branch doesn't really belong to the customer. There should be a relationship there, but branch should be its own thing, right? So that thought process, that feeling that you have, we need to extend that, and we need to look at bringing structure to that thought process, because there are functional dependencies that maybe aren't that clear, that also cause anomalies. And then once we understand how data is dependent on each other, we can go ahead and we can look at how the normalization process works and what every step entails in the normalization process. Because when we try to normalize, the majority of the normalization process goes into thinking about how data interacts and how we split it out from each other. So let's take a deeper look at that. This next part is going to be a bit theoretical when we talk about functional dependencies. And the reason for that is a functional dependency is a concept in database design. And when we talk about database design, a lot of these things are theoretical. And there are a lot of people that dedicate their entire career into understanding and being able to apply these concepts on a day-to-day basis to build scalable infrastructure for large corporations. Now, the purpose of this section is to give you that foundation in order to be able to think and ideate about design. But to be honest, in order to become a master of database design, it's going to take a lot of practice, and you're going to have to go through a lot of examples, work situations, and particularly you're going to have to draft many relationships and many database designs in order to be able to accomplish the full-on mastery of database design. This section, unlike teaching SQL, is something that is only mastered in practice. And we need to be very clear about that. No matter how you look at the theory, nothing is as valuable as the practice when it comes to database design. Now, with that being said, when we look at a functional dependency, when we define a functional dependency shows a relationship between attributes. So it's showing a relationship between the data itself. We're not talking about the relationships between tables. We're talking about the relationships between the data inside a table. Okay, so now that we've set the stage for that, when you ask me what is a functional dependency or when does it exist? Well, when a functional dependency exists, it basically exists between two attributes. When you can uniquely determine the value of another value. Okay, so this becomes very confusing. There is a functional dependency between two attributes when one attribute can uniquely determine the value of another attribute, otherwise known as a primary key relationship towards its data. When we looked at employee number, an employee number can determine the corresponding attribute's data because there is a unique dependency there. There is a dependency between the data. Because of the primary key, you can now say, hey, this uniquely identifies these columns. there is a dependency there. Okay, so this becomes confusing. Why isn't there a dependency the other way? We'll get to that. But we have to get more theoretical first. In the following section, we'll refer to an entity as R and attributes as A and B. So look at A as a column and B as a column. Now, if we said that A is functionally dependent on B, we would note it this way. A is functionally dependent on B because B determines the value of A. Okay, so that makes sense. This is how we note a functional dependency. And we're basically saying that, hey, A is functionally dependent on B, or there is a direct linkage between the two. Okay, so all of this becomes very confusing. And I can hear you thinking, what did I just hear and what did I just learn? But let me put it into a concrete example. What does this actually mean? Well, it means that based on the value of B, you can determine the value of A, otherwise known as, for instance, employee number and first name. How do we know that this is a functional dependency? Well, for the employee number, we will find one and only one first name. But if we did a functional dependency between first name and employee number, and we inverted this, for instance, we put first name over here and employee number over there, well, you can have a lot of first names that are the exact same. You could have 10 Mo's or 10 Andres, and they're all going to correspond to a different employee number. So the employee number is not functionally dependent on the first name. The relationship needs to be unique, and there needs to be a direct link between the two. Otherwise, you can look at it as, on the left side of the functional relationship, we talk about the determinant because it's determining something. And on the right side, we talk about the dependent because it is dependent on the determinant in order to identify its value. Another way of looking at this is, for instance, student ID and birth date. Based on the student ID, we will find the unique birth date of that individual. But if we inverted this and we just put birth date over here, well, based on the birth date, you may find multiple student IDs. There may be multiple students with the same birth date. So student ID is not functionally dependent on the birth date, but the birth date is functionally dependent on the student ID. So what we're trying to do here is create unique relationships between the data. And it just so happens that in this case, our primary keys are very clear. If we had data that didn't have a clear-cut primary key, well, we would go and we would create a composite key between multiple attributes. We could, for instance, say, well, student first name and student last name together with the email address potentially. Well, that's a composite key. And then we could say birth date is functionally dependent on those three columns. And so we're trying to figure out what the determinant in the relationship is going to be. Otherwise known as trying to find out, hey, what's the primary key here going to be and what's the relationship between this data? So we've talked about a lot of different things here. And you've gained a lot of information about functional dependencies. But I understand that it may not be completely clear what exactly is going on here. So let's put it to play in an example and let's go look at that example. So here are some examples of functional dependency. And over here, what you can see is that I've put together a small table with employee number, project ID, and salary. And as we can see here that employees can work on multiple projects. Employee 1 works on project 1 and employee 1 works on project 2. Employee 2 works on project 1 and employee 3 works on project 2. Now, each of these lines contains a salary. That means that the employee makes a different salary based on the project they work on. Now for this, underneath here, I've put together some functional dependencies, and we need to know if they are correct or incorrect. So I would suggest you pause the video here and take a deep look at these functional dependencies and determine which ones are right and which ones are wrong, and why they are right or wrong. Now over here we are stating that employee number has a functional dependency towards salary, or otherwise known as salary is functionally dependent on employee number. We also say that salary is functionally dependent on project ID. And then finally, we say salary is functionally dependent on project ID and employee number. Okay, so with that said, pause the video, think about it, and when you come back, we'll go over the answers. All right, so I hope you had a good time thinking about this and reasoning about it and kind of coming up with why one would or wouldn't be. Now let's look at the answers. And over here, you can see in red the ones that are wrong and in green the ones that are right. Now, salary is not functionally dependent on employee number. The reason for this being is that when we get a salary, the employee number doesn't necessarily tell us the unique salary because an employee can work on multiple projects. So there is no functional dependency between salary and employee number because employee number does not uniquely determine the salary. Now, salary is also not functionally dependent on project ID because when we pick a project ID, we can get multiple salaries back. We do not get a unique salary back. But when we combine project ID and employee number, when we do a combination of both of these, we get a unique record back of salary, meaning that we have a singular output. So salary is functionally dependent on project ID and employee number. I hope this is starting to make sense. Something is functionally dependent on something else when that something else can determine its value when it has one unique outcome. So salary is functionally dependent on project ID and employee number. Now here's one more example to go through. Over here I have student number, activity, and contribution. Okay, we're trying to determine here what's functionally dependent on what. A student can take multiple activities, and an activity can lead to multiple contributions. So each activity has a unique contribution per student. And since students can take multiple activities, which one of these functional dependencies is correct? We're saying that activity is functionally dependent on student number, meaning that if we grab the student number, we would uniquely get back an activity. And then we're saying that student number is functionally dependent on activity. So if we selected activity, we would get back a student. So based on an activity, you can derive a student. And then we're saying that contribution is functionally dependent on activity. So if we were to select an activity, we would get back a specific unique contributions. Okay, so which ones of these are right or wrong? Pause the video here, think about it, and then when you're back, we'll go over it. Okay, I hope that went well. Now, I have a small thing to confess. None of these were right. Based on a student number, you can't get back a unique activity because a student can take multiple activities. You see here, student 1 does swimming and shark diving. Okay, and then you see that student 2 does sailing and bungee, meaning that if we grab the student number, we cannot get back a unique activity that they do. And then if we grab the unique activity like bungee jumping, well, we can't derive a student number based solely off of the activity. You would get back multiple student numbers. So you can't uniquely identify a singular piece of data just based off the activity. And then if we look at contribution, well, you can't uniquely identify a contribution solely based off the activity. If we took bungee, for instance, well, you're going to get 150 from student 3 and 300 from student 2. So you can't uniquely identify a singular contribution just based off of activity. So what is the correct answer? Well, if we combine student number and activity, we can say that contribution is functionally dependent on student number and activity. So the combination of this and this creates a functional dependency on this. So this is functionally dependent on this one and this one. All right. And why is that? Because if we took student 1 in swimming, we're going to uniquely know their contribution for that combination of data. I hope this is starting to make sense. Functional dependencies are nothing more than uniquely identifying or determining a value based off of the combination of these two. Interestingly enough, this functional dependency is the cornerstone of how we normalize. And so we talked about normalization, and we talked about how normalization is seeking to avoid redundancy and avoid anomalies. So now that we know more about functional dependencies, let's take a deeper look at normalization and how that actually works. So far, we've seen a lot of information on bottom up. And to be fair, it's less straightforward and more theoretical than the top-down design. But that's because we took top-down design and we stripped away a lot of the heavy theoretical parts and we defined steps that are easy to follow. When it comes to normalization, however, there are no easy shortcuts. There are no easy ways to understanding this. When we do system design and we ask ourselves, how do we design? Well, top-down versus bottom-up are equally difficult in implementation. It just so happens that normalization as a process, conceptually and theoretically, is a bit harder to grok because you're going the inverse direction than with entity relationship diagram. I personally find entity relationship diagram mapping an easier exercise because I can define the entities and I can go from there toward the attributes. When I do normalization, it's a think twice exercise. Now, with that being said, we've seen functional dependencies and how they relate to normalization. The data that we are going to normalize has individual functional dependencies towards each other. And those functional dependencies is how we're going to derive the entities. By knowing how data is related to each other, by creating those relationships, we can easily figure out the entities. Now, here's the thing. 90% of the time, you're already going to know what data belongs together, and it's going to feel natural to move certain data together and form natural entities. Even when you're doing normalization, it just feels that way and it's natural. And that's why we usually say that when you're doing database design, you usually use a bit of both. With entity relationship diagram mapping, you can get very far, and with normalization, you can get far. Now, when we look at normalization, normalization happens through a process of running attributes through the normal forms. And so over here, you can see the normal forms. We run through steps. Now, each normal form aims to further separate relationships into smaller instances. So we're trying to get to a state where there's no redundancy and no anomalies. And as we know, the relationships between data, foreign key, primary key relationships, the further you split out data into entities, the less problems you have with redundancy and anomalies because the data is normalized. It is so far split out that each individual entity is holding information and the relationships between the data are telling us what is happening. Now, you can go too far. There is such a thing as normalizing too far. You can naturally feel where to stop. There are certain amounts of anomalies that you may find tolerable. Now, that being said, the normal forms 0 through B, C, and F, and this one is interesting because it kind of like fits its space between 3 and 4. This is Boyce-Codd normal form. Boyce-Codd normal form is also referred to as normal form 3.5. Now, 0 through 3.5, or Boyce-Codd normal form, are the most common normal forms to run through. 4, 5, and 6, well, rather 4 and 5 are there to further reduce anomalies and redundancy. And the 6th normal form, well, that is not yet standardized. It's being talked about, it's being discussed, but it isn't really standardized just yet. Now, the 4th and 5th normal form can take things to an extreme. And for all intents and purposes of bottom-up design, we are going to run through unnormalized data all the way through to Boyce-Codd normal form, or normalized data up to 3.5. And the reason for this is once you reach 3.5, you are in a good state. There may still be anomalies, but they may be tolerable, they may be acceptable. And running through 4 and 5 are most typically used when you have specific scenarios that are causing specific anomalies. Now, let's go ahead and take a look at 0 normal form. Alrighty, we're ready to jump down the deep end, and we're going to start with 0 normal form. Now, applying these normal forms can be tricky and a bit theoretical, and there are steps to follow in order to get it into the correct state. And what tends to happen is you tend to want to over-normalize when you go from 0 to 1. And I often find that the leaps you will make from 0 to 1 are almost kind of from 0 to 2 or even 3. But we're going to look at some simple examples of how and why you go from 0 to 1, and from 1 to 2, and from 2 to 3. And we're also going to see how to go from 3 to Boyce-Codd normal form. And we're going to give you some examples of the rules that imply 4th and 5th. But the 6th, again, is not standardized, so we won't be looking at that. Now, the reason we're only going to 3 and Boyce-Codd normal form is because in 3, in the third normal form, to be correct, you're often already normalized enough. And normalization is nothing more than a technique where we're trying to remove redundancy and figure out the best format for our data and reduce anomalies. And there is such a thing as over-normalization if you go into the 4th and 5th. I personally have never seen a database schema that I've had to take past Boyce-Codd normal form, but there are certain scenarios in which you want to go to 4th and 5th normal form. And all that basically means is that you're trying to maintain and secure the integrity of your data. This may be extremely important in something like a medical field. Now, with all of that said, what we're trying to look at here is 0 normal form. In the 0 normal form, what we're trying to do is determine what kind of data is there. And the data in the 0 normal form is when it is unnormalized. It's just raw data. It comes back in however we determined that it was, in whatever state it was. So it may have repeating groups of fields, positional dependence of data. We know that that's a bad thing in the relational model. It shouldn't matter the way that you store the data. It should only matter that the data is stored. The positional dependency of data towards each other is very much irrelevant. And it may have non-atomic data. So every row could store multiple values, and that's a no-no. Even though it's a possibility in Postgres, in normalization, this is a no-no. You can't have non-atomic data. Now, when going from 0 to first normal form, what we're trying to accomplish here is going from unnormalized data to data that has eliminated repeating columns of the same data, and that each attribute should contain a single value. So we're trying to strive towards that atomic data. And then third and foremost, we have to determine a primary key. Now, you may be asking yourself, what is a repeating group or repeating data? A repeating group means that the table contains 2 or more columns that are closely related. Now, let's take a look at that. Now, over here, we are in a simple Google Sheet, or you could use Excel, because it is the easiest way to visualize tables and visualize normalization as a procedure, and it's just very straightforward and simple. Now, if we looked at repeating groups over here, what we can see is basically our book author scenario, where we have a book, and for every book, we need to store every single author. So we have a repeating group of data inside of this table, so to speak. For book 1, we'll have author 1, 2, and 3. And for book 2, we'll have author 2, 1, and 3. And so forth and so forward. So we're trying to get rid of these repeating columns. We do not want these repeating groups of data. We're basically trying to get rid of as many many-to-many relationships as possible, and isolating data into their own entity when necessary. And the only way to do this, the only way to figure out if you have repeating groups of data, is to take your unnormalized data and make a shape like this, where you're trying to store what is being stored in the table. And that's the only way you'll understand what your 0 normal form is, and if and how you need to move it to first normal form. Now, the second part of this is the ability to go from 0 normal form to first normal form. And so over here, you can see a non-atomic data type. So this is a second example of 0 normal form, where we're looking at color, quantity, and price. And we can see in the color field that we're storing multiple colors. Now, this is also a no-no because we need atomic data. So that's a second part of first normal form. And then the third part of first normal form is determining key attributes. So how did we solve this? Well, if we go look at first normal form, what we can see here is that in zero normal form, we have color, quantity, and price. And when we move to first normal form, well, the first thing we need to do is we have this non-atomic attribute. So we have to split that out. It can't be part of the actual table because non-atomic attributes are not allowed. So over here, you can see I created an entity product and an entity product color. So I already split it out. And then over here, I said product contains product ID, quantity, and price. And product color contains product ID and color. And so we've solved for that non-atomic attribute. And then here below, what you can see is that we focused on the book. And in the book, we had book and author. And so rudimentarily speaking, we have a book ID and some other book information here potentially. And then in the book author, we have the book ID, the author ID, and some of the author information. And so what that basically comes to is we could put book title here. We could put other book information, of course. What basically matters here is that we got rid of the repeating columns. Repeating columns meaning that you have to repeat the column multiple times in the table in order to get the data available. Now, when we look at this, we already know this is an offender of something else, duplicate data. But that's different than repeating groups, because even though we have to store the author, the address, and the email every time there is a relation to a book, this is not offending first normal form. So repeating groups are different than repeating data. Repeating data is a different problem that we'll solve in a different normal form, but a repeating group is basically, think of that many-to-many relationship where you have to store multiple columns to achieve storing the same data. We're basically forming a many-to-many here between book and author, right? We have the book, and then we have our author, right? Remember with the crow's feet? And we basically don't want this because storing multiple columns is going to cause us anomalies. Okay, so now that we've seen how to go from zero to first normal form and some of the examples of solving multiple values in a single field as well as repetitive groups, let's go and look at how to go from first normal form to second normal form. Now we're going to talk about going into second normal form. And the second normal form is obviously after the first normal form. And what you're going to see every time you jump from normal form to normal form is that it always has to be in the previous normal form. That is a prerequisite. So going to 2, you need to be in 1. And going to 3, you need to be in 2, which also implies that you are in 1. Now, with all of that said, being in first normal form, we have a check on that. We're good. But the second constraint of being able to be in second normal form is that all non-key attributes are fully functionally dependent on the primary key. Okay, fully functionally dependent. Now, they need a functional dependency on the primary key. All the non-key attributes. So everything that's not a key needs a functional dependency on the primary key. Okay, so we've looked at functional dependencies, and it basically means, can I derive the value of something from the key? Now, let's go and take a look at that. Now, over here, we have our book example again. And we had book, we had title, we had author, author name, author address, and author email. And so for book, we stored book and title. And for book author, we stored book ID, author ID, and we had author name, address, and email. Now, in first normal form, we already knew and already felt that this was repetitive data, but that is not a repetitive group, and therefore we shouldn't remove it in first normal form because it's not an offender of it just yet. But in second normal form, this is where it gets fun, guys. Well, in second normal form, when we look at the functional dependency of author towards book ID. Let's say book ID, and we have our arrow syntax, and we say author name. So when we looked at this, we said that this was the determinant and this was the dependent. And so the question becomes, based on the value of what we would consider here to be B, remember this syntax, to A, based on the value of B, can I derive A? So based on the value of the book ID, can I derive the author name? Now, personally, I would say that this relationship is not there. They're not fully functionally dependent on each other. They may be partially dependent in some cases, or if you're looking at it in a different way. I would rather say that author ID has a full functional dependency against author name. Based on the author ID, I can derive the author name. Based on the book ID, you can derive some author names, but there may be multiple authors. So when you get multiple return values for something, right? If I said book ID, well, now I may have the author name John and Patrick and someone else, etc., etc. So they're not fully functionally dependent on each other. But when we take an author ID, for instance, well, there's only one John for that author ID. So there is a full functional dependency between author ID and author name. And that is also true for author address and author email. So we take that actor out and we create an author. And then we go ahead and we still link the author ID to the book ID. And so now when we look at that, if we took book ID and author ID, well, now we know that it's, for instance, book ID 1, author ID 1, book ID 2, 1, author ID 2, book ID 1, author ID 3. And so we've gotten rid of repetitive data. Repetitive data meaning redundant data. We were storing this too many times against a relationship, a functional dependency that wasn't fully functionally dependent. Book ID cannot derive the author name in a dependent way that gives us a unique value. Okay? So when we talk about unique value, when we look at book ID to author name, what we were saying is that you can't get a unique value out of this functional relationship, but you can when you do author ID. Okay, so with all of that said, we now know that we needed to split out author into its own entity, rather. So author is now its own entity, and that book author is now the combination of book ID and author ID. And book has a book ID and a title. So now we are in second normal form, and we've made sure that all non-key attributes are fully functionally dependent on their primary key. Fully functionally dependent. Now, if we took, for instance, book ID here, and we took author ID, we could have said that, well, there is a partial dependency on the author name, because with the combination of these two things, you can get a unique author name, but with the combination of these two, there's a partial dependency there. But we wanted it to be fully functionally dependent. That's why we said, hey, author ID can derive an author name. And sometimes you'll find that you can't remove all of the partial dependencies in the second normal form. And that is also why the third normal form is there. Now let's take a look at the third normal form. Third normal form, a state in which your data model is taken shape in order to be able to be implemented. Once we reach third normal form, we've basically reached an impasse in which we can say, hey, have we normalized far enough? Now, we're going to see all the way to Boycott normal form, because we don't want to do over normalization. That doesn't mean that these normal forms aren't used. They're very important in certain scenarios. But for the majority of databases, you normally never go past third or even Boycott. Now, why is that? Because third normal form gives you the most bang for buck in most scenarios. And in order to move to third normal form, we need to make sure that it is already in second normal form and that there are no transitive dependencies. Now here you're saying transitive dependencies? Well, you just taught us about functional dependencies. You didn't say anything about transitive dependencies. And you're right, I didn't talk about it. Now, what is a transitive dependency? Well, I didn't want to get too theoretical up front and throw a bunch at you. let's look at things as they come along. So transitive dependencies is when A is functionally dependent on B and B is functionally dependent on C. Then you could say that C is transitively dependent on A via B. So if we look at that in a diagram format, A is functionally dependent on B, B is functionally dependent on C, so we can say that C is transitively dependent on A. Okay, I kind of get it, but what does it actually mean? That's what I'm thinking right now. Well, it means that from B, we can derive one value of A. And from C, we can derive one single value of B. But that means that there is some kind of dependency, a transitive dependency between A and C. And that is what we want to get rid of. So let's take a look at an example of that. So over here, we're back in Excel, and we have this example or exercise that is based on a branch that is holding and logging work hours for specific individuals. When we moved to first normal form, we gave an employee its own entity, first name, last name, title, employee number, and we quickly split out branch, and we gave it the street number, the province, the postal code, etc. And we also put in the hours logged, the work date, and the country. And we said that there was a functional dependency between these two attributes towards hours logged, work date. And there is a functional dependency on that as well towards this other information. A partial functional dependency, not a full one. But we weren't really looking at that in first normal form. We were just looking to remove the repeating groups and primary key and atomic values. When we moved to second normal form, that's when we started looking at these functional dependencies and making sure that each and every one of these entities attributes is fully functionally dependent on its primary key. And that's where we went and we gave branch a new lease on life, because we removed all of the information that it did not need, that was not fully functionally dependent on the branch number. And so we created this new entity called timesheet, where we kept the branch number, the employee number, and where the fully functional dependency of hours logged and work date was against branch number, employee number combo. So we have this new entity called timesheet. Okay, so now that we know how we got to second normal form, how do we move to third normal form? And before you look over here at third normal form, what we basically want to do is we want to go look at the individual attributes that are stored inside these entities. And what we want to make sure is that no other attribute can basically determine the singular outcome of one attribute. And so when we look at first name, last name, title, there's nothing here that's going to give you a single value or a functional dependency against each other. And so when we look at timesheet, there's nothing here that's glaring at us either. But when we look at branch, what we can see, okay, street number, given a street, you're not going to get a single street number. Given a street number, you're not going to give a province. The postal code may give you an area, but it's not going to give you a singular street. It's also not going to give you a province because it's a subdivision of a province. Okay, interesting. So nothing there. But here's an interesting one. Province and country. Now, these two have an interesting relationship towards each other. And if we move over here, what we can see is that, okay, based on a branch number, we can determine a singular province. But based on a province, we can determine a singular country because not multiple countries have the same province. Or if that did happen, then this, of course, would be wrong. But given this scenario in this example, based on a province, for instance, Ontario, we know that the country is going to be Canada. Or given a province of Antwerp, we know the country is going to be Belgium. So there is a functional dependency between province and country. Country is functionally dependent on province. So what we can say then is that country is transitively dependent on branch number. And that's what we need to get rid of because there's this intermediary functional dependency between these two that shouldn't be in this data. And so now when we look at branch, well, how did we solve for this? Did we solve for this in a correct way? Well, let's look at it. The transitive dependency was that branch number determines country through province. So how are we going to split out the province to have the information we need? Well, over here you can see that I made a very clear mistake going to third normal form, because the province was in fact the information that I wanted to keep. Now, when you go to third normal form, it can become a bit confusing how to solve these transitive dependencies, because what is determining what? Country is functionally dependent on province, which means that province is the driver. But in your mind, country would be the driver, no? Because a country has provinces. But based on a country ID, you're going to get multiple provinces. And so in this particular example, what we need to know is, hey, in which province is this branch? We don't want to lose that information, right? Now, knowing a province, you know a country, but knowing a country, you don't necessarily know the province. So country isn't our entity, province is our entity. And instead of a country ID, we're going to have a province ID. And with a province ID, what we can do is we can keep track of the province the branch is in, and by knowing the province, we know the country. You see, removing a transitive dependency, really, you have to look at what the functional dependency is in order to know what the driver is going to be of that entity. And in this case, the driver of that new entity that we're going to remove is province, because by keeping a province ID in the branch, we now know the country. By keeping a country ID in the branch, we had no idea in which province the specific branch would be. So solving transitive dependencies can be a bit tricky, and you really have to look at the functional dependencies that are occurring in order to know how you're going to form that new entity. And so with that, we are now in third normal form. And what we can do now is we can do an intermediary move or shift towards Boyce-Codd normal form. So let's look at what that would look like. All right, so now we've reached Boyce-Codd normal form. Boyce-Codd normal form, or form 3.5. Now, Boyce-Codd normal form is a normal form that differs a bit from the third normal form, but not heavily enough, because a lot of third normal form tables are already in Boyce-Codd normal form, but there are specific ones that don't achieve this form, and those are the ones that we want to identify and change a bit. And so in order for a table or an entity to be in Boyce-Codd normal form, it has to be in third normal form. And then we say for any dependency where B is functionally dependent on A should be a super key. Okay, that's a mouthful. What do we mean by that? Well, what we mean is that most relationships are in third normal form, are also in Boyce-Codd normal form, but not all of them. And what we say is that third normal form allows attributes to be part of a candidate key. Now, we know what a candidate key is. It's basically a set of attributes that can form a primary key, but aren't necessarily the primary key, right? That is not the primary key. So a candidate key is a set of attributes that could form a unique relationship, but it isn't what we chose as our primary key. So third normal form allows the attributes to be part of a candidate key that is not the primary key. Boyce-Codd normal form does not. Now, again, conceptually, this is quite difficult, right? Because we choose a primary key, but the attributes of an entity can form multiple candidate keys. There could be multiple choices for what could be a primary key. Now, in third normal form, what we're saying is that, hey, some of these candidate keys that aren't the primary key, well, some attributes are functionally dependent on it. And we got to get rid of those. We want to get rid of the functional dependencies where attributes are functionally dependent on candidate keys that are not the primary key. Now, it's easier to say what is not in Boyce-Codd normal form than to say what is. A relationship is not in Boyce-Codd normal form if the primary key is a composite key. So the primary key is a key that is formed through multiple keys. So if we have a primary key that is the combination of keys, it's hard to say that it is in Boyce-Codd normal form. Now, it may still be. You may need multiple of these to be true in order to be able to separate it out or want to separate it out. But so what is not in Boyce-Codd normal form? If the primary key is a composite key, so if the primary key is multiple keys together, it may not be in Boyce-Codd normal form. If there is more than one candidate key, if you have more than one option for a potential candidate key, you may not be in Boyce-Codd normal form. And some attributes have keys in common. That is another one. Now, even if these are true, you may not always want to move to Boyce-Codd normal form. And the decision there is very much on the level of normalization and fault tolerance you're willing to take. Now, here is an example of something that is not in Boyce-Codd normal form. If we had a tutor database and we had a student ID and a tutor ID and a tutor SIN, and we said a tutor can tutor multiple students, but a student can only have one tutor. Well, then now, if we look at the functional dependencies, what are our candidate keys? Well, our candidate keys are the combination of either student and tutor ID or student ID and tutor SIN, because both of these values uniquely identify a tutor. So these are our candidate keys, right? We have the ability to form two different primary keys potentially that can uniquely identify a row. So we're already in violation of what we would say is not in Boyce-Codd normal form. And if we go ahead and we look at the functional dependencies, we can say that, well, tutor SIN is functionally dependent on tutor ID, because if you have a tutor ID, you can get one tutor SIN. There is only one tutor SIN for every tutor ID. And the same is true for tutor SIN. If you have a tutor SIN, you may have a singular tutor ID. Now, an option here to fix this may be to just get rid of tutor ID in general and just use the SIN number of the tutor to identify the tutor. Although this is in theory a correct practice, this is extremely private information, and you should not use a SIN number to deduce some type of primary key, in my opinion. But for all intents and purposes of this example, we're trying to figure out what should be in Boyce-Codd normal form. That said, these functional dependencies are correct. But when we look at Boyce-Codd normal form and we say tutor SIN is functionally dependent on a student ID, well, this is not true, because a tutor can teach multiple students. So we're going to get back two results. We're not getting back a uniquely identifiable result for either the SIN or the ID. So these functional dependencies are incorrect. But if we do a combination of student ID and tutor ID or student ID and tutor SIN, we can say that the SIN or the ID is functionally dependent on the combination of these candidate keys. Now, in this case, because both of these combinations form candidate keys, tutor ID and tutor SIN are considered what we would call prime attributes. Third normal form only removes the ability for non-prime attributes, things that aren't potentially going to form primary keys, to be removed. But in this case, we have prime attributes that can form candidate keys that may potentially lead to primary keys, and they have a functional dependency on another prime attribute, right? Student ID and tutor ID can have a functional dependency against tutor SIN, or rather, tutor SIN has a functional dependency against student ID and tutor ID. Tutor ID has a functional dependency against student ID and tutor SIN. And so this becomes extremely confusing. But what we're trying to say here is basically that in Boyce-Codd normal form, you're not allowed to have functional dependencies against a prime attribute, an attribute that can be part of a candidate key. Now, if we were to fix this in Boyce-Codd normal form, what we would end up doing is we would end up splitting out tutor into its own table, and we would have tutor ID and tutor SIN just separated out in its own entity, and student ID would link to a tutor ID. It's a very simple fix, but the nuance is very difficult to achieve, because with Boyce-Codd normal form, most of third normal form entities are already in Boyce-Codd normal form. There's just this one specific case where you may have multiple candidate keys that can be formed that you may cause a redundancy in data that you may want to solve through Boyce-Codd normal form. And with Boyce-Codd normal form, we are now in what we would call an extremely normalized state that is guaranteed to give you your most bang for buck in terms of the ability to achieve a normalized database procedure. Now, in most cases, again, I don't suggest going past third normal form. You may want to go into Boyce-Codd normal form, and that's why we're looking at the theoretical aspect of it. But for most cases, normalization as a procedure, third normal form should suffice for most cases. Now let's take a look at fourth and fifth normal form and what exactly they are in comparison to Boyce-Codd normal form and what they're trying to achieve. All right, we've climbed the mountain and we've reached the end. Fourth, fifth, and sixth normal form. Now, when it comes to the fourth, fifth, and sixth normal form, these aren't generally used in real-life database design. Well, given that sixth normal form doesn't actually exist just yet and is just a formalized set of talks and not a standardized methodology, it doesn't even really account for a formalized normal form. But fourth and fifth normal form, well, fourth and fifth normal form are trying to further achieve normalization by removing more anomalies and more redundancy. Now, with that said, what these normal forms achieve is a level of normalization that can almost incur over normalization. They're going a bit too far. And so in real life practice, you will not often see this used. You may not even pass the threshold of third normal form into Boyce-Codd normal form because for most scenarios, it's not really necessary. And that level of normalization, those concepts, they won't really help you in your day-to-day life. So it's good to know about things that are there, and it's good to research them if you're interested in the theoretical aspect. But in a real-life day-to-day job, you're really not going to cross this threshold if you even cross this threshold. So I encourage you all to go ahead and read up on fourth and fifth normal form and see what they're about. But in most cases, third normal form already takes you as far as you need to go. And most systems don't want to over-normalize because with over-normalization, you can even incur functionality loss because of the way that data is structured. You have so many constraints against your data. When you're in a business, you need some freedom to play with. And in a day-to-day business, going past some form of redundancy isn't really useful to you. Okay, as long as we get rid of all of the anomalies, we're solid. But beyond that, storage is cheap. Some form of redundancy is fine as long as it isn't core information that is super important. And so with that, we're closing off our knowledge on normalization. And we're closing off our knowledge on system design. We've seen phase 3 and we've seen the software development lifecycle. We've looked at how to design and we've seen the differences between top-down and bottom-up and how ERDs are formed versus how normalization works and how we can come to a similar outcome. But I implore you all to take these concepts and apply them in a pragmatic manner. Don't be extremely rigid in your implementations of these things because at the end of the day, all of this is a team sport. You have to make the correct outcome happen. You have to make the correct system design happen. But if you tend to over-normalize or extend outward too much in terms of how rigid you want your system design to be, you may end up going too far. At the end of the day, when we're running a business, sometimes good is good enough. And that said, we want to know how to be pragmatic with system design And being pragmatic with system design is knowing when to have your cutoff point based on the requirements of your system. If you're working in healthcare or some rigid industry and you need that data integrity, that system integrity, and you need those validation rules, maybe you'll dabble into the 4th normal form. I doubt you'll ever see the 5th normal form. And if the 6th normal form ever gets standardized, we'll see if it gets used anywhere in practice, because this cutoff point basically helps you with most of your data consistency and anomaly issues. Okay, so with all of that jibber jabber out of the way, we now know how to design in a top-down manner and a bottom-up manner. And the one thing to note here is that with system design, we can give all the examples in the world. We can give you all of the examples on how to design and the examples on certain scenarios, but nothing beats the real life thing. And experience is key with any design. You need to work with people who have designed systems at larger scales and learn the trade-offs that they have to make. The trade-offs are important. Every system has trade-offs. Every system is designed in a pragmatic way. And redundancy is sometimes a good thing. Over-normalization is sometimes a horrible thing. So it really becomes about what type of system you're going to build. And you always ask yourself, well, how am I going to design this? And you choose the right methodology, or you combine methodologies because they can check each other. You know, when you do a normalization procedure, you can go ahead and create your ERD diagram to validate your assumptions against the relationships and what they look like. I personally love ERD diagrams, and I will use them over normalization because I'm just a more visual person, and following the steps of normal forms for me is quite the mental exercise versus quickly drawing an ERD diagram and getting 60% of the way there and then discussing it with other people and maybe then going through a normalization exercise after I have my ERD diagram. And so with all of that, we now know all we need to know about database design in phase 3 of the software development lifecycle.
Hey, it's Bruno here. Listen, you've been tremendous help for us. We've actually been talking with the CEO, the president, and the board, and they just love having you on the team. They would actually like to set up a meeting with you and talk about some of the ways that they can improve their systems, their databases at Keiko Corp. What do you think? Can you prepare something for us to give us a strategy of how we can improve our database systems, maybe on performance, security, and just general guidelines? I think that would be super helpful. All right. Thanks a lot. Appreciate it. You're the best. All right, everybody. Now that we've solved the mystery, now that we understand how databases work, how SQL commands work, and we're quite good at them, it's time to have a big picture view now of how to think about performance when it comes to databases. What strategies are there? How can we think about security measures like backups and access control? And also, how do we decide on which database to use? There's so many databases out there. And we talked about at the beginning how there's 5 different database models that we can use. When do we use what? Let's dive into this topic to complete our picture of databases so that moving forward, not only do you know SQL, but you also can make smart decisions and have smart conversations with people at your company, and especially with the board members at Keiko Corp. Let's dive in. Let's talk about scalability. What does that mean? Well, scalability when it comes to databases is all about the capability of the database to handle the growing amount of data. So we either have more and more data that we need to store into a database, or we have more and more operations. Let's say we have lots of users that are constantly querying the database for more and more information. So how can we make it scalable so that as our data operations grow, we can keep making the database work? Because eventually this database is going to reach its limits on how much data it can store and also on how many operations per second it can solve. Now, when it comes to scalability, there's 2 different strategies. One is called vertical scalability. And vertical scalability is, as you see here, just adding more capacity to a single database, so a single machine. For example, adding more disk space to hold more memory. Maybe adding more power to the machine so that it can perform operations faster, maybe increasing the memory of the machine. It's all about adding physical device, physical hardware, such as adding new disk space to the machine so that it's more powerful. This is a pretty easy solution, right? You just add more to the machine, or you use a computer that has more power. Now, this can get really, really expensive and also has limitations because a vertical scalable machine can only grow so much. At one point, there's no more things that you can add to the machine to make it more powerful. Now, relational databases, usually this is how you would scale back in the day because, well, relational databases are really good on a single machine. So if you just needed more capability, you just vertically scaled. The other option is to do something called horizontal scaling. And horizontal scaling means adding capacity by adding more machines. So instead of just adding on more powerful hardware, we just add more databases. So you have 3 databases here, for example, and these 3 work together as a single database. Now, the reason that NoSQL or databases like MongoDB became popular was because they were able to do horizontal scalability around the 2000s. Because originally relational databases had this limit or restrictions on doing horizontal scalability because it's really hard to have all these tables on different machines, an easy storage system like MongoDB was able to horizontally scale very easily. Now, this idea of horizontal scalability is something that has improved and can be done with a relational database as well. But there are some challenges with horizontal scalability. I mean, one pro is that we can just keep adding machines. But as we keep adding machines, these different databases need to communicate with one another and understand how to work together so that there's no inconsistencies in data. For example, if one database updates, well, hopefully that same data isn't in another database that needs to be updated as well. Then there's a time difference between when each one of them updates. The more machines you add to a system, the more complexity it adds. Although it's nice because we can keep adding machines, every time you have different databases, that communication between those databases gets more and more complex and introduces a lot of problems. Something that we're going to talk about in the next video when we talk about sharding. But for now, when it comes to scalability, there's these 2 main options: vertically scale or horizontally scale. Let's learn about sharding in the next video. Now, we learned that there's a limitation with vertical scaling. And eventually, if you have large amounts of data, and I mean a lot of data, then you might want to do horizontal scaling. That is to add more machines that work together as one database containing a set of data. Now, when you start using different machines for your database, because you need to hold more data because it handles more operations and you need to manage that, then the best strategy is to do something called sharding. This idea of sharding is exactly what we need to handle the huge and growing amount of data that we have. Because we know databases are just computers, the computer's hard drive and memory starts to fill up and starts to stall. So we need to put our data and operations on different databases. So what we do is we do sharding. So imagine if we were Facebook and Facebook has a ton of users, a ton of user profiles that cannot be stored on just one machine. So what they do is they split that data into 3 different machines. Let's say, for example, all the names starting from A to J are stored in this database. All the names from K to T are stored in this database. And then all the names from U to Z are stored in this database. Sharding is essentially splitting up the data because there's so much data into different databases. And what usually happens is you have to implement a system, a routing system, that knows where each of the data is located. So if a user logs in, and let's say I log in under Andre, this router, another machine, another computer, is going to know that, hey, this name starts with an A, so I'm going to go to this database. In this way, we're able to distribute the queries to all these different databases so that not all users are querying one database and loading it. And we are also able to store more data, more user info, because we now have 3 databases for users. Now, this idea of sharding can get really, really complicated. We need the logic for, hey, how are we going to actually split the data? And this is one of the biggest topics of sharding. Do you want to split it logically? Do you want to split it by how much data there is? There's a lot of strategies involved, and you can write a whole book on sharding strategies. Also, how do you implement this routing system? At a high level, that's what sharding is, just splitting up the data so that we can take advantage of growing data that cannot be stored on one machine anymore. More to come in the next video. Welcome back. I want you to imagine another scenario. Let's imagine that our data, our user data, is just stored on one machine. What happens if this machine somehow breaks? I mean, who knows? A lightning strike could break it. Maybe a robber physically takes the machine, or maybe there's just some electricity problem. And all of a sudden, this database gets corrupted, gets broken. We're no longer able to use this data. Or maybe a hacker just decides to delete all our information from this database. That's really bad, right? Imagine Netflix, imagine Google, imagine Amazon having all their data deleted. The thing is, accidents do happen. And if you're a big company, you want to prevent such situations from happening, right? And one of the best ways to do that is through something called replication. And replication, as the name suggests, it's just about replicating our data across multiple machines. So, for example, we can have this database that interacts with users, with, let's say, data analysts, maybe business administrators. But we also, every once in a while, replicate this database so that this database holds the same information as this one, and same with this one, and same in this one. And maybe we put them in different locations instead of keeping them all in a warehouse together. Maybe one is across the world in India, another one is maybe in Poland, another one maybe in, Nigeria. This way, if something goes down, if somebody attacks a database, we still have copies of this database, and we can easily have users still access those databases. And the way replication usually works is that a client usually, let's say, writes data to a database, and then a little bit later, depending on what the situation is, this database sends that information, that new data, to all these 3 databases that it has a replication of, so that all of them eventually stay consistent. You may have heard the term eventual consistency, and that is, well, eventually these databases are going to stay consistent. And this is a way for us to also do horizontal scalability, right? This idea of having multiple machines carrying the same data. Well, now a user is able to query this database and this database, this database, and this database. And as long as it's eventually consistent, as long as we don't have any super important data that needs to always, to the second, be exact, well, then they can query any of these databases. This idea of replication usually happens in real time. So as we add data, we replicate and add that data to the other databases as well. Now, when it comes to replication, there's 2 big strategies. One is called synchronous. And synchronous means, hey, a client makes an update to a database, and the database isn't going to respond to that client until those changes are confirmed in all of the other 3 databases. And then it responds to the client. Hey, your data has been added. Or, hey, your user profile has been updated. The problem with that is that, well, if these things are across the world, it's going to take some time. So another strategy that is often used is called asynchronous. That means this database updates its data and says, success, your user profile has been updated. But in the background, it's going to go ahead and also send those updates to this other database. Now, the downside is that maybe if there's an error, we have just told our client that, hey, everything was successful. So we might have some issues there. So you have different strategies based on what you want to optimize for. As with everything in databases, it always depends on your situation. Is inconsistent data sometimes okay, such as number of likes on your Instagram photo? Or is inconsistent data, such as banking information, absolutely not allowed and you need to replicate synchronously? But in the end, replication is all about allowing us to horizontally scale, allowing us to prevent ourselves from having a system, a single point of failure, instead having different ways for us to manage our database needs. Let's talk about something similar called backups in the next video. Let's talk about backups. Now, this idea of backups and replication that we just learned about can be confusing. They kind of sound similar because both of them are all about replicating or copying the data that we have on one database and then storing it in a different database or in a different location. Now, replication usually happens in real time. We talked about synchronous and asynchronous, about eventual consistency. Usually, we want to do the replication as soon as possible. Backups, on the other hand, are something that is usually done not as often because they can be expensive. It takes a long time to do a backup and usually would happen, let's say, every night. A backup is all about storing regular backups of our entire database in order to protect from that disaster case of, let's say, a backup being deleted. So a backup usually happens by doing something called a dump of the data into a file. Usually it can be an SQL file. We copy all the data in our database and store it somewhere safe, in ideally multiple locations. And usually you'll see a title like database backup with the date on it, so that eventually you can just keep multiple backups, but you can always revert back to a location where the data was based on whatever happened, based on whatever your needs are. For example, back in the day, I actually messed up and deleted part of a production database. It was really bad, but luckily we had backups. So although we had to go back a few hours into our database and some users lost a bit of data, overall, because we had backups, we're able to revert back to a state that was working before. Having backups for a database is a must, and you need to have a backup strategy for your company, and you need to decide how often you need the backups to happen in those worst case scenarios. Let's talk about distributed versus centralized databases. Now, the names should be fairly self-explanatory, right? A centralized database usually means it's a database that is centralized, that is usually kept in a single location on a given network, or it's controlled by one company. For example, a centralized database can be a database that you have in your house or at a company. But it can also mean that it's centrally controlled. For example, if you're using Amazon's AWS and your databases are owned or controlled by Amazon, well, they're in a sense centralized because if Amazon somehow goes down, then your databases go down as well. So there's different layers to this idea of distributed versus centralized. A distributed database is, well, it can be described as composed of multiple databases stored in multiple physical locations. But it can also mean databases that are distributed, that are controlled by different organizations. For example, maybe you have your databases in different locations around the world. It can be a distributed database, but it can be centrally controlled by something like Amazon. Or you might use databases that you control around the world. Well, in that case, it's distributed, but centrally controlled by you. Now, distributed databases, like here, are usually more complex and require this additional work to keep data storage up to date and avoid inconsistencies. But again, have the advantage of being more resistant because they are in different locations, but also can serve different users instead of clogging everything up. Centralized databases usually make something called data integrity a lot easier. You can make sure that the data is more consistent. There's no outdated or inaccurate data because everything is centralized, usually controlled by one place or in one physical location. But again, you have that downside of having something happen where you lose all the data. That's why you may hear something like blockchain. Blockchain is a database, a type of database, and it's popular because it's completely distributed, but it's also decentralized. That is, it's not owned by anything. Everybody can own a part of the blockchain, and it's also distributed across many, many computers. But it has the downside of having a lot more complexity to the system versus something like just having one database that you control in-house or on-premise. There's a lot of ups and downs, and like I said, most of the time a company already has some sort of strategy that is based on pros and cons that they decide on. Usually what you'll see is that big companies like Google Cloud, like Azure, like AWS will have a distributed system of databases, but they're all centralized in that they're controlled by these big companies. But we tend to trust these companies because they do have all the engineering resources and the computers to make sure that our data is safe. Well, theoretically. Let's talk about security. Now, security is really important, right? We always hear news about how big companies get their data hacked or user information is leaked by hackers. And usually that's because they have poor security practices. So what are some of the common security practices when it comes to databases? Well, the main ones are, if you're working with a database, first is to ensure that users can only see the data they are authorized to see. So if you are working at a company, you should have maybe full access to the database, but a user of your app, if you're Facebook, you don't want to give everybody in the world access to your databases. So we want to ensure that whoever has access to the database has access. And for example, if you're Facebook, a user is only allowed access to their profile data, but not necessarily personal information of other users. Another one might be to keep unauthorized users from accessing the database, right? Going back to the Facebook example, they only want their employees, and even then, only certain level of employees to have access to this database. If anything, they don't want us to know where those databases are even located. Another thing is to prevent things like data corruption. Maybe the database is in a location that's really, really hot, and eventually those electrical systems are going to fail. So they want to make sure that it's in a safe location that is nice and cooled, that is safe from outside forces, but also any technical glitches. You might want to make sure that you are able to detect and stop any malware attacks. For example, you might look at database logs and make sure that there's nothing funny happening, some user behavior that shouldn't be happening. You might want to update the software used to make sure that it patches all the security vulnerabilities. And then finally, you want to make sure that the database availability is there, that the database is being able to be used by those who need it, and that there's no system crashes. Now, all these things require different level of security measure, and usually when you work at a company, a database administrator would take care of these things, at least initially, to make sure that the databases are always kept up to date, all the access patterns are correct. But at the end of the day, the key is to create a database in a way that it only stores the information necessary and it gives access to only the people necessary. The principle of least privilege states that you should only give privilege to exactly what is needed, not to give privilege to somebody or something that isn't necessarily required. Now, this idea of security is a big topic, so we won't get into it anymore, but I do want to talk about something super fun, and that is this idea of an SQL injection. It's one of the most common ways to get hacked, especially when it comes to databases. And using a command like this, you can do what's called an SQL injection. That is to inject an SQL command into a database to perform some malicious act. Now, in the next exercise, I'm actually going to show you how an SQL injection works, which is super, super fun, but it emphasizes this point of security. Don't let people that shouldn't have access to a database, and only allow certain action to a database that isn't necessarily going to do something damaging like delete an entire table. I'll see you in the next one. Bye-bye. Let's talk about the very first topic in our security star, or star of security, and this is injections, right over here. And we're starting off with injections because these are the most common attacks. For the last number of years, out of all these techniques, this is the most common, the thing that leads to most financial loss, and I'd say about 50% of the time, if you're preventing against injections, you've covered a big chunk of improving security. So probably the most important topic, and it's also really fun to teach. So we're going to start off with this one. Now, injections means injecting code into another piece of code. And there's a couple ways that you can do this, but it's a big principle. The idea that we receive code that we didn't really want from a third party, a user or somebody else, and they're trying to mess with our code and change our code and perhaps do bad things. And like I said before, it's the most common attack. And one of the most famous injections is something called SQL injection. And these are two examples of SQL injections. But you know what? We're just looking at a piece of text right now. It doesn't really mean anything. Let's actually perform an SQL injection and see how it works. I'm going to be using pSQL, which is a database for Mac, but there's tons of other versions for Windows and Linux that you can use. It's essentially a graphical user interface to play around with your database. So I'm going to be using this, and I should have it open right here. As you see, I have two tables here, login and users. But for this exercise, let's just create a new table, and I already have created the SQL statement here. And again, if you're not 100% comfortable with SQL yet, then I cover that topic in my other course, so I do recommend you check that out. Or you can find some really good resources online for it. All I'm saying is I want to create a new table called SQL injection. It's going to have a column of ID and a column of email. If I click Run Query, there you go. If I refresh now, I see that we've created a new table called SQL injection. Now, there's nothing in this table, but we do have the ID and email column. So let's add a new row here. And I actually have them prepared over here. So we'll just do the insert into SQL injection. So we're going to insert into the table the email field. We're going to add LOL to it. So let's run that query. All right. And if we go back to our table, we see that we have a new row, an ID of 1, because I've set it up so it's just sequential. It'll just keep adding 2, 3, 4, 5, and then email of LOL. Now here's some SQL injection that we can do. And we want to do something like this. Let's say that we're updating this email field because the user just changed their email. So if I, let's say, update my email to something like this that we had from our table, and make sure I have a quote here. So what I've just entered is I've entered my value of my new email to have this piece of code. And you see that it's kind of highlighted everything instead of just being a string like it would have been if we did this. So by just modifying that piece of code like this, and make sure we have that quote, see how the colors change? What I'm saying is I have played around with this SQL statement and made it so that we update the values to an empty string, but then add the semicolon, we have another statement that drops the table users, or let's drop the table SQL injection. And then I end the statement with this line. And we don't need the quotes anymore. You see that it's been highlighted as if it's an SQL query. And we just simply do drop table SQL injection. If I click run query, and now I refresh. Whoa, did you see that? Our SQL injections table was just dropped. That's right. By just adding this piece of line, I was able to drop an entire table. So you can see how vicious that could be if I change this to login or users. I can drop the entire company's database. And that was simply because I entered this line. So even though we were expecting an email value, instead of providing an email, I just sent over this piece of code that essentially extended the SQL statement to drop the table. That is extremely dangerous. And you just witnessed one of the most common ways that websites get attacked. People just keep copy and pasting these lines in different inputs on websites and apps and see if it does anything and drops tables. And if we go back here, we also see this top one that says comma or 1 equals 1, again, dash dash, ignore everything after. Well, this can be put in a password field. For example, you have to log into a website and it says username and password. By adding this piece of line, you're saying in the password field, I'm expecting a password and I'll pass it on to my SQL statement. But instead, I'm going to just leave it an empty string and then say or 1 equals 1, which is true. So what that means is the database is going to check, hey, does this user exist and does this password match? But then because we're adding this or, saying, does this password match or does 1 equals 1? And returns the full user information and logs you in. And don't worry, I'm going to leave a fun exercise for you after this video so you can actually practice this on your own. That's SQL injection. And that happens with databases, but injections can happen anywhere. Anytime that a user has to input something, you can do injections. Let me show you another example. I've created over here a security exercise. And don't worry, I'm going to give you access to these files so you can play around with them. But I've created a very simple website. If you look at index.html, not much going on here. And we just have a button that on click sends information to the server. And I have a server set up as well. And don't worry, we're going to go over this. That is an Express server. And all we're doing is we have a GET request. So if I go to, let's start the server actually. Let's say npm start. We're listening to port 3000. So if I go to my Chrome browser, and let's open up localhost 3000. We see the hello world text because the endpoint is going to return hello world. And then we also have another endpoint that is a post request to secret. And I'm going to show you what that does. On the front end, we can open up the index.html file in our browser, which looks something like this. Very, very simple website. All I have is an input field, and I can hit submit. Now this submit button, if we go back to the code, simply says send to server. We're going to grab the input.value, and then I'm going to run it through this function that simply just adds the text to our web page. So again, if I type hello, submit, I see the text hello on the web page. And after we do that, we also do a fetch call, an API call to our server and send the secret through post method using JSON.stringify. We're sending the user input and as JSON. So we're sending it into the body. Once we click hello and open up the network tab, let's click again. We see that we're sending the secret to the backend. That's it. Nothing too crazy. If you're not too familiar with node servers, then again, I recommend you check out my other course. But you don't have to worry about too much about that. What we want to do here is practice another form of injection. We expect our users to play around and type in whatever they want. But what if a bad person comes and says, what if I just do a script tag here because we're adding it to HTML, right? We're just adding whatever we've gotten here to our HTML tag. So let's do this, script.alert. Boom. And then we're going to close that tab, this script tag. And now we hope to run this script in here. Let's see if that works. Nothing happens. We didn't even print anything. Now, if we go back to the code, we see that we're getting the input, and then we're using inner HTML, which is bad, as you can see here, to a p tag. But luckily for us, when scripts are injected into the DOM via script tags like we have, and we're using inner HTML, they're not actually run at time when they're injected because the DOM has already run and HTML is smart enough to say, yeah, I'm not going to run that. That sounds like a bad idea. Because scripts like this, which are called inline scripts, are only run at the time that the original page is parsed. So if I refresh this, that's not going to run. On the other hand, there is something we can do. Check this out. If we enter something like an image tag with a source of nothing really, just a slash, and because there's no source, this is going to error, we can do a on error event that comes standard with HTML. And in here, I can say alert, boom, and close that tag. If I do this, so an image tag that won't be able to fetch any image and it's going to have an on error of alert, boom. If I click submit, and let's open up the console, and unexpected end of input because we should use double quotes here. Let's try that again. Boom. We just ran a script that we injected into our browser. And this is because images are injected into the DOM at the time of encountering the image tag. And if the loading fails, like you can see over here, on error event, the handler is called. So what we've just done is we've injected a piece of code that is really, really bad into a website. So if you go around to websites and copy and paste this and try to submit it and they don't have good security practices, you can inject whatever scripts you want into a website. Again, use this information wisely. Don't be bad with this information. we're using this as a way to learn how to prevent these sorts of attacks. So how do we prevent against this? Well, fairly simple. Instead of using this inner HTML, and that's why I say inner HTML is bad, don't use it, we want to use something like this. And let's comment that out. This creates a text node that is of input. So no matter what the input is, this create text node is going to convert it into just pure text and does something called sanitizing it. And because of this, we can just attach a text node to the p tag, and it doesn't matter how bad we are with our code, it's not going to do anything. Let me save and show you if that fixes it. So I'm going to submit again. Oh, and I have to refresh the page. Let me refresh. And let's try that again. This time around, I'm just going to copy and paste it. Again, same thing. If I click submit, all right, nothing happens. And this is just converted into text. That was pretty cool, right? All right, we've learned about injections. What can we do to fix them? Well, there's three main things that I want you to remember. One is to do something called sanitizing input. And that is something that we did with the input field on the website. The idea is called the whitelist philosophy. And what that means is for data validation or anything the user inputs, only allow the user to input data of your expected type. If you expect a text to be entered, an email to be entered, a phone number, make sure that you check using JavaScript that only those things are used. For example, with a phone number, make sure that it's only numbers that are, let's say, 10 digits. If it's not the proper type, discard it. So we're sanitizing it, we're cleaning it. And by sanitizing and cleaning it into a format that we want, using things like JavaScript, we make sure that no matter what, I can enter all these bad codes. It doesn't matter because I've already cleaned your input and it won't do anything to my system. And sanitization is typically performed by using either, like I said, a whitelist or a blacklist. So whitelist is good things that you can do. Blacklist is bad things that you shouldn't do. So some of the things that we can do is removing HTML tags while preserving perhaps the content or preserving only the textual content of a tag. Or prevent the user with a notification saying that, hey, you can't put that information in there, try again, put something in. The second point is something called parameterized query, and it's also called prepared statements. And it's a way to prevent SQL injections, like we saw. It precompiles an SQL statement so that all you need to supply are the parameters. Think of it as a function. If we go back to our example, instead of allowing the user to enter whatever they want, what we want to do is have a sort of function. So let me open up a tab here, a console tab, and you have a function, let's say that is SQL select statement. And within here, you give the name variable, the email, perhaps the ID variable. And inside of this function, you'd have something like if name equals number, then you can area it out, or you can say that if name doesn't have the length of this, or if name includes characters of this, you have control over what the user enters. Now, this is a big enough problem that there are a ton of really good solutions out there already. And they're called object relational mappers. That is, they provide these prepared statements, SQL statements for you, so that all you need to supply are the parameters. Just like I showed you, think of them as variables that need to be inserted into the statement for it to be executed. And this way, it prevents things that we done, like dropping that table and being able to enter whatever we want in an SQL statement. And one of the really good examples of this is connects.js that we use with our SmartBrain app, where we're able to use things like if we go to select, we're able to just give it parameters. All we say is connects.select, and we give it whatever parameters we need. Let's say we want to get the title, author, and year from the books table, and that's the only thing we can do. Connects takes care of actually building the SQL statement for us, but it parameterizes everything. So we can only provide the parameters to the statement. All right, so there you have it. Those are injections. You prevent those and you make sure that whatever the user inputs is something that your program expects, then you're going to avoid majority of the security issues that are out there. Like I said, injections are the number one cause of attacks on websites. So validate every last bit of user input using whitelists on the client side as well as the server, and never directly inject user content into anything. Again, user input should always be untrusted. The only thing that you can control is how you run your program, so you can modify any untrusted data into trusted data. I'll see you in the next one. Bye-bye. Welcome back. We're so close. We're going to talk about data management now and what we can do to improve security when it comes to data management. Data management encompasses many ideas, but there's a few topics. For example, you want to make sure you always have backups. Some people like backing up their website, data, static files somewhere safe. Never have one point of failure. That is one place that is weak, and if that gets down, then you have no place else to recover from. You want to make sure that you limit sensitive data exposure. That is, you want to encrypt data at rest, so that is jumbling it up so bad people can't see it, and in transition. Now, here's the thing. What I just said, encrypting data at rest and in transition, most of the time is not feasible, because encrypting data at rest means when data is just sitting there, pretty much, let's say, in a database. Encrypting all that data costs a lot of money, requires a lot of effort, and is just not feasible. And it doesn't completely cover your bases. In transition means when you're sending data. So when you're sending data from the database to the server, when you're sending data from the server to the client. We know that HTTPS is used in that case. Now, you want to be selective of what data you encrypt and what you don't based on your resources at hand. You might want to encrypt sensitive information like phone numbers, email addresses of your users, but perhaps not necessarily worry about pen names of the users. That pen names column on a database, maybe you don't need to encrypt. So what can we do with data management? Well, I'm going to show you a quick example of some of the things you can do. But the main idea is you want to use encryption for any data identifying users and sensitive data like access tokens, emails, and billing, like I said. And finally, as we mentioned, with backups, you want those backups to be stored, to be ideally encrypted as well. Again, that may not always be feasible, but you want to focus on the sensitive data first, and anything else that you can encrypt, you should do so. Now, I want to talk about two main topics. One is hashing passwords and how to store them. And the second is how to encrypt your database that has sensitive data. The second part over here is really dependent on your database. So I'm not going to go over it because it's too specific. But tools like PG Crypto allow you to encrypt a few columns on a Postgres database, one of my favorite databases. And they have great documentation, so that's something you can do. But if I was using PG Crypto, I'll probably encrypt the billing address or email column of the users or anything sensitive for a user column. That is just good practice. But one of the topics that really fascinates me and I actually love is password storage. And I know that's a geeky thing to say, but it is really, really exciting. I actually wrote a company blog in my past life on this topic, so I'm going to leave that for you at the end of this course. And it's also something that we've already covered in my previous course. But I'm going to do a quick rundown of what you should do with passwords. Any website that has username and password and sign in needs to have good data management, especially when it comes to passwords. So what can we do? Well, there's 3 libraries that are really, really good. And these 3 libraries are really good because they're tried and tested. When it comes to security, you want to choose packages that have been around for a long time because security experts, hackers, black hat and white hat hackers all have tested it and have stood the test of time. And these 3 have really stood the test of time. Aragon 2 is fairly new, but it's been doing really, really well. I personally like bcrypt though, so let me show you a quick demonstration. I have over here a file. Let me make this a little bit bigger. That I downloaded the bcrypt Node.js package just to have it working with Node.js very easily. And that's pretty much it. And if I go to their packages over here, we see that they have a synchronous option and an asynchronous option. So let's just copy the first part. And I'm going to explain what it does. And I don't like bacon. I'm going to go with soup here. So when your website has a username and password, what should we do? Well, the first thing you're going to do is you're going to let the user type in their username and password, and then they're going to click submit. When they click submit, you're going to make sure that it's HTTPS so that the password and the username, you put it in the HTTPS request in the body of the request. You send it over to the backend, and then it arrives. Let's say that this is your backend. Once it arrives, you grab that password, and we'll say that your password that you just typed is soup. Very weak password, I know, but we'll just use it for demonstration purposes. Now, what we do is we never store passwords like this in our database. Because if our database gets compromised or somebody enters it, they have all the passwords of everybody. Never ever do that. Instead, we use bcrypt, which allows us to hash. And if you remember hashing from our SSH section, it's a one-way function that will take the soup string and turn it into a jumbled up string that, well, we're never going to know that came from soup. So let me show you. I'm going to say console.log the hash. Let's save, run node script, and look at that. We got the hash. This, whoa, did not want to copy that. This really, really jumbled up string that represents soup. Even if a bad actor gets into our database and sees, oh yeah, Andre's password is this, they're not going to be able to do anything with it because they don't know. They can't go to the website and type in this because, well, that won't work. My password is soup. So how does that work? We store this in the database for the user, let's say Andre. And when Andre comes back, I don't like using my own name. Let's use Tim as an example. When Tim comes back, how can we check that when Tim types soup again, that is the same as this hash that we have in the database? Well, if we go back to bcrypt, they have another method called compare. And this compare is going to compare the string that Tim puts in when he comes back to the website again to sign in, and the hash that we have stored in the database. In my case, let's say I have this stored in the database. And again, if you're not too familiar with databases, I do recommend you check out my previous course. And there's our string. Let's actually make it into a string. So that's our hash that we just grabbed from the database. All right, now here we get a response. So let's see what the response is going to be. I'm going to say console.log response. I'm going to save, run this. Did you see that? I got true. So now I know that, yep, that's Tim's password. He can sign in. But if Tim misspells something, let's say I do capital S and an exclamation mark. I save and run this. Nope, that's not your password. Try again. And it's good enough that even a capital, it'll detect. There you go. Because a hash, any small change in the password is going to spit out a completely different hash. Now, in case you're wondering what null here is, well, in my article that I wrote, I talk about salt rounds and how it adds extra layers of security. It's a complex topic and beyond the scope of this course, but do read it if you're interested in it. It's just an extra security measure. But what it does is, if you notice how slow we get the hash, and then it takes a bit of time to get the true or false. Let me show you. If I save this and run this again, you see that pause where the hash was hashed really, really fast, but this took a bit of time. Let's see again. So what happens there is it's extra protection by bcrypt. It's saying, all right, if there was a bad person, I can just keep trying passwords until I get a match. So bcrypt, using something called salt rounds, makes these brute force attacks where the bad person just keeps trying passwords really hard because it takes a bit of time to actually check. So if I was a bad attacker, I would keep trying these, but because bcrypt is slow, it would take a really, really long time for me to guess a password. And it's another layer of protection that comes with bcrypt and most good hashing libraries. Again, data management is really, really important. And this goes back to environment variables as well. Any secrets, even including your SSH key, you want to manage it properly. Never reveal your secrets. Always make it as hard as possible for bad actors to access sensitive information. I'll see you in the next one. Bye-bye. Let's talk about everybody's favorite debate. Relational databases versus NoSQL databases. Mainly MongoDB versus PostgreSQL or MySQL. Especially in the web development world or mobile application world, this is a heated debate. Because in the early 2000s, MongoDB started to take over the relational database space because it allowed us to do horizontal scaling, allowed us to have a growing number of data easily and scale across different machines, something that relational databases had a really difficult time in doing. Now, since then, a lot of relational databases like Postgres have become a lot easier to horizontally scale, and there's a movement right now of relational databases coming back and actually becoming more and more useful compared to something like MongoDB. For example, if we take a look at Hacker News trends, so these are companies that are hiring for people with database knowledge, you'll see that the trend is, well, Postgres right here is in blue, is growing nicely. MySQL is kind of dwindling, but also MongoDB is dwindling a little bit. And again, around 2010, the popularity of relational databases like Postgres have become more and more popular as people start to see the value in them and how the horizontal scalability that MongoDB initially promised may not be as good as some of the benefits that relational databases have. So let's talk a little bit more about that. Here on the MongoDB website, we have a demo of how a piece of data is stored on MongoDB. Now, MongoDB has the document model for databases for storage. So documents are usually set in what we call a JSON format. So it kind of looks like this, where we have, let's say, a user, first name, last name, we have their cell phone number, we have the cars that they have, their profession. All the user information is stored in one record in one document. So in one location. Versus in a relational database model, we might have the user table, then we would have the cars table that are linked to different keys that link to the user. Maybe we have professions table, we have maybe a locations table. So in a relational database, these things are split apart versus in something like MongoDB, the information that is related is usually stored together. So why is one better than the other? Or when is one better than the other? Now, I do want to bring up one thing. The idea of NoSQL comes from the fact that we don't usually use NoSQL to query a MongoDB database. We'd use something different. Usually a NoSQL database has its own way of querying for it. For example, we would have a key in a MongoDB database to get a certain user. But when we talk about relational versus NoSQL, these aren't necessarily problems to do with SQL, but instead, it's all about the design decisions of popular relational databases like Postgres versus MongoDB. So although we call these NoSQL because we don't use SQL, it has nothing to do with the abilities of SQL. So let's talk about relational databases. The pros? Well, we saw that with a relational database, we do something called normalization, which allows us to optimize a lot of things. That is, we don't have duplicate results. If we need to update a user, there's one location to update the user in, because each table represents one concept. Versus MongoDB, we might have all the information in one location, but we might have different locations where data is duplicated, or we have to update in multiple locations. So the pro of using a relational database is that it has this idea of data integrity, this ACID model that we've talked about of being atomic, consistent, isolated, and durable. And we can usually guarantee that consistency. Now, another good thing is that while we use SQL, a standard way to query a database, versus something like MongoDB or any other NoSQL database has their own unique way of querying things. So you have to learn their own individual ways to work with that database versus just learning SQL and working with a lot of databases with just small minor differences. And SQL, as we've learned, is very, very flexible. It's very declarative. We're able to query a lot of things, and it allows the database management system to optimize their queries. But there's also some downsides to relational databases, right? It's always pros and cons. It's never black and white. One is that the idea of a schema. So our database needs to decide what type of data, what type of tables we want to hold from the beginning. We have to design our databases around this schema to understand what our data is going to look like. Versus MongoDB, because we just dump data, let's say related data together, you can update different pieces of data, you can change things on the database as you go. Versus with a relational database, it becomes a little bit more difficult to add new columns after we've already created the database. It's doable, but it adds more complexity. So this idea that relational databases resist evolution, ideally you have to define your schema, the way your data is going to look from the beginning, otherwise you're going to risk downtime. The next one is, well, relational databases are harder to scale horizontally. Because they were initially designed for that single machine use, and because these tables are linked to one another, it's really hard to split them up across different machines, versus with a document storage like MongoDB, that's really easy to just have this document style data across different machines because they're not related to each other as much as on a relational database with different tables. So another good thing about MongoDB is that all the related data is in one location, right? So because of that, when we query, let's say a user, all that information is in one location versus in a relational database, if we want to query a user, we have to go to the users table and then grab all the related table information from different locations. So that can become slow. So a MongoDB database has that extra performance, that good performance when we do queries for related information. So when should you use what? At the end of the day, you want to be able to make decisions. So let me give you an example. Let's say we have LinkedIn here, and this is my LinkedIn profile. Now, if I was LinkedIn and I was working on the user profile data, what type of database model would I want to use? Well, Looking at this, I have a lot of information on my profile, a lot of data on my profile that isn't necessarily linked to other places. For example, none of my profile information is probably linked to any of these people, or at least not a lot. So I might want to store my profile information in MongoDB and under one location as a user, because this will allow me to access this information of the user really fast. And if I ever need to update my name or my title, there's probably not a lot of locations other than my user profile that this needs to get updated. So this is a great use case for something like MongoDB. Or for example, you might have heard of WordPress or any other blogging website. That usually uses a relational database model. Most WordPress installations come with MySQL, a relational database, because blogs and comments and authors, those are different things that are interconnected, that are usually tables that will link to each other. So WordPress uses MySQL for that reason. If you want to create a blogging website or a community-based website, well, then maybe a relational database model might be best. Or let's say I go into my groups, and in the groups, we have the ZTM LinkedIn group. And in here, there's different people that are linked to this group. We have requests to join. We have group admins. This has a lot more connections. It's not about just me and one user. It's about many users that are connected in different ways. Well, in this case, maybe a relational database is more useful. Again, this is a simplified version of what database to choose. However, based on hiring trends, based on what a lot of companies use, and based on what we've learned in this course, there's a reason that relational databases are the most common databases. And most of the time, although it may require a little bit more effort on your part to design that schema, to design that database before you start using it, a relational database like Postgres is going to take you very far. But at the end of the day, the choice is up to you. You just need to understand the pros and cons, as we've discussed, and decide for yourself what is the way you want to use the data. And based on that, decide the database that you need. Hey everyone, I wanted to add a quick video about the future of databases, specifically relational databases, because there's some really exciting things happening right now in the industry. And there's something called new SQL. Sometimes you might even hear distributed SQL databases. Now, we learned that relational databases are harder to horizontally scale, to have relational databases across multiple machines. But this idea of a new SQL database is starting to emerge. And these systems usually take relational databases that we have, and they add a distributed logic on top of them to make them easier to horizontally scale. Essentially, the reason that NoSQL databases like MongoDB got popular because they were able to horizontally scale, we now have that benefit with relational databases, which makes them really attractive. So some of these new SQL databases to keep an eye on are things like Citus and Vitess. Google has something called Google Spanner or CockroachDB. The idea is to take relational databases and combine them with this idea of a distributed database system of multiple machines to improve that one big flaw that we saw with relational databases. So I guess what I'm saying is SQL is here to stay. And what you learned in this course is going to take you very far because SQL isn't going anywhere. And it's going to be a very important skill for many years into the future. So hopefully you get all those benefits for many years to come. Let's quickly talk about Elasticsearch. Now, Elasticsearch is an interesting database. It's very common, very popular, and you'll hear it a lot in discussions about databases. It's one of the more common ones that we encounter. It's mainly a document model database, but as the name suggests, It's really, really good for data that we need to search. So let's review that. If we're using a SQL-based database, which is usually a relational model database, it's generally not very good at doing what we call text searches. Imagine if you're Amazon and you're searching for a title of the book. We want a way for us to search for, let's say, Harry Potter. Now, if all our books was in an SQL database, it might take a while for that result to show because, well, there's a lot of books in the world. But a database like Elasticsearch is built specifically for this, for full text searches. Now, we don't need to actually know how it works internally. All we need to know is that, well, Elasticsearch, if you want to do some sort of searching on your company, you might want to use something like this database. So how would this work exactly? Well, first off, Elasticsearch is less reliable than something like a relational database, which is why we don't really care if maybe something is lost and it doesn't show up in a search result like a book. I mean, it sucks for the author, but for Amazon, it's not that big of a deal. But because it's less reliable and sometimes slower to write data to, it does have the trade-offs of those fast search results. Again, as we know by now with databases, there's always pros and cons, different strengths and weaknesses. So let's say at Keiko Corp, how can we use Elasticsearch? Well, we use a relational database, let's say Postgres, as our primary data store. It's where all our really important business information and storage is done. But let's say that at Keiko Corp, we allow authors to publish a book with us. So every time that author publishes a book, we add it to a relational database to Postgres with a book title, author name, maybe even the price. But then what we can do is copy that data of the book to a Elasticsearch database. And this Elasticsearch database will store all the book information. And we can tie our search box on the website to that Elasticsearch database so that when I type in Harry, it's going to show up Harry Potter. So the way it would work is we would copy over batches of data from an SQL database into an Elasticsearch database. And just like that, a company like Keiko Corp can have multiple types of databases based on different needs. A relational database to store maybe user information, and a database like Elasticsearch to allow users to search for books. So I want you to start noticing how it's not about just finding one right database for all business cases. Instead, it's all about using the right database for the right problem. And most of the time, as the company gets bigger and bigger, you'll notice that they have multiple types of databases based on different things. Let's talk about Amazon S3. And this is another popular type of database. And as you can see, it's object storage, built to store and retrieve any amount of data from anywhere. Now, the reason I mentioned Amazon S3 is that it's very, very popular. And why is it popular? And what is this whole object storage thing? Essentially, it's kind of like a document model. It's storing an object, a massive amount of data that we can just dump and use, and Amazon makes it really, really cheap. So Amazon S3, what is it really used for? It's used a lot for objects, and objects are often big document type. Let's say you can have user profiles with all this information about the user. But a really useful case for S3 is massive blobs of data, like videos, like user profile pictures. You can store it very, very cheaply, and it allows you to access, let's say if you want to upload a user profile to a user page very, very easily by storing it on an S3, what we call bucket. So S3 is used for storing these large amounts of data, but that doesn't require specific, very nitty-gritty querying. Instead, it says, hey, just send me back this image of this user. That's it. So this is a very cheap object storage that isn't super sophisticated, but again, the benefit is that you can just dump data into it and retrieve that data back. And Amazon S3, you'll see a lot of use from a lot of companies. Hey everybody, I want to take a quick second to give you some of my recommendations of the databases that I think are the most important or the most used. Now, everybody has their preference, and as I mentioned before, in your career, you're not going to encounter every single database. You'll most likely use a handful over and over and over. And these are the handful that I've used over and over and over and have gotten 90% of the job done. The first one is Postgres. This is my favorite. It's also very popular. Lots of job demand out there for Postgres, and it's the reason that we've used it in this course, because when it comes to relational databases, Postgres, I would say, is in the number one spot right now. For example, if we take a look at the Stack Overflow survey, we'll see that MySQL is number one. Again, WordPress websites use MySQL, so it does have a big dominance, but Postgres is becoming the dominant player in relational databases. Both of them are very, very similar though. We have Microsoft SQL Server, which again is Microsoft's own relational database. We have SQLite, once again, a very light relational database. And then we have MongoDB, where we get into document storage. Now, MongoDB is my second recommended one because it is quite popular if you're looking for that document storage of storing related data all together without having to necessarily define a schema ahead of time. Maybe the database might modify over time. Then MongoDB is extremely popular. They also have something called Mongo Atlas, which allows you to hand off the database management side of things to MongoDB Atlas, and they take care of all the scalability needs for you. Another interesting thing is this idea of Amazon Document DB. Amazon is doing something interesting right now, which is using essentially their own version of MongoDB. It's pretty much the same thing, named differently, Document DB, but again, storing as documents. Instead of relational model, we're using the document model. By the way, fun fact, if you want to hear about the issues between MongoDB and Amazon's Document DB, it's quite the read, so go check that out. Another one that I really like is Firebase. Firebase is, again, managed document storage. It's very similar to MongoDB. It stores documents. It works really, really well because they have user authentication out of the box. It's very user-friendly. You can use their graphical user interface. It's by Google, and it works really, really well when it comes to, let's say, mobile or web apps. So very easy to get started. You can get up and running with a database very, very fast. Another one that I've talked about is Elasticsearch. Again, if you're doing any sort of searching of text in your app or your projects, then Elasticsearch is definitely something you should take a look at. Redis, again, another thing that we have a section on. Redis is a in-memory storage. It's a key store model. So again, another one of those database types that we've talked about. And Redis is really, really good for things like caching or very simple storage. That is extremely fast because, again, it is using memory. Another one that we've talked about is Amazon S3. Again, great for storing large amounts of data that doesn't necessarily need to have complex logic like images, like big blobs of objects. And if we go back to our Stack Overflow survey of the most popular databases, those are pretty much it. Oracle is another relational database, same with MariaDB. We have Firebase in here, we have Elasticsearch. DynamoDB is again another database from Amazon. So we've covered the major ones that you will encounter. Obviously, there's a lot more. You can go and find out more on your own, but just by knowing these on the surface level, you'll be able to decide for your project which database you should choose. But most of the time, when you enter a company, they've most likely have selected that for you. So you don't need to worry about it. It's all about interacting with these databases, which is why this course was so heavily focused on SQL. All right, that was a fun one. I'll see you in the next one. Hey there, one last video to finish off this course. And this is it. A simple thank you. From both myself and Mo, thank you for taking this course. Databases sometimes may not be the most exciting topic, but you had fun with our little mystery that we had to solve. And more importantly, I hope you take what you learn now into your future careers. Most people start the course and drop it halfway through, but that is not you. You finish the course. You put in the time, you put in the effort to watch the videos, to do the exercises, and that's what it takes to succeed in the tech world. So congratulations, and thank you for taking your valuable time to learn from us. Hopefully it was useful to you. If you've enjoyed these courses, hope to see you in other ZTM courses. Leave a review if you like, because that's how the internet algorithm works. The more reviews we get, the more people discover our courses. And once again, thank you and congratulations on your hard work. I hope to see you in the next one. Bye-bye. Welcome back. Let's talk about big data and analytics. You see, when a company first starts out, let's say with a Postgres SQL relational database model, we can start learning about our users, about what products get sold the most, or just find useful information by just looking at these databases. But oftentimes, let's say we have somebody like a business analyst or a data analyst that's doing this. Maybe we don't necessarily want this person to query and use up the database power that we want to serve the users from. We want to make sure that whatever is using our database in production gets good performance. And if we have business analysts or data analysts constantly studying that data, that also adds to the usage of the database. So we might want to replicate that data so that we have a database that's not specific to production. But there's another problem. Sometimes the data that a data analyst or a data scientist might need requires different operations than a regular relational database that a user might want to use. Usually they want to aggregate data. They want to study massive amounts of rows, maybe calculate the average price that a user spends on a product. Doing all these calculations, maybe using lots and lots of tables. And these start taking up more and more time with relational databases. This is when you start putting big data, lots and lots of data, into something like data warehouses and data lakes, which we're going to talk about over the next couple of videos. When it comes to big data and analytics, it's a whole different discussion, whole different types of databases. Again, we can use SQL to analyze these, but usually we would put them in something different than, let's say, Postgres, because the types of queries that we need to do are very, very different than something that perhaps a user might do. So what would happen is we would replicate our data from our production relational database to something like Hadoop or another type of database that is optimized for big data and analytics. And we'll get into that over the next couple of videos. One thing that I really like doing in my courses is to actually understand the why of everything. Everything that we learn, there should be a reason we're learning it, right? And you might be asking yourself, why do we even care about machine learning? How is that useful, and how do we get here? Well, if you think about a business, because most technology evolves from business needs. We have the advent of computers, and the ability for businesses to use computers to do things really, really fast and efficiently so that they gain an edge. And then we got spreadsheets. Spreadsheets like Excel files and CSV files were amazing because we can store data that businesses generate, such as maybe customer data, into an Excel file. And then people got really, really good at analyzing these CSV files, these spreadsheets, to make business decisions. Maybe forecasting that December sales are going to be high because, well, the past 2 years we've had really high December sales because of Christmas. And then as companies got more and more data, we started getting this idea of relational databases. Spreadsheets were great, CSV files were great, but we started getting more and more information and data, and we needed a better way to organize things, to understand things from our data. That's when we got things like MySQL, which allowed us, instead of using spreadsheets, to use a language called SQL to read information from our database, write information to our database, but similar to spreadsheets, use the data that we gathered from the business to make business decisions so that our business becomes even more profitable. And then in 2000s, we had this fancy term of big data. We had big companies like Facebook, Amazon, Twitter, Google that started accumulating more and more data. An insane amount of data that you simply couldn't contain in a spreadsheet. User actions, user likes, user purchasing histories. This idea of big data meant that we had so much data. These companies had so much data. And sometimes, unlike relational databases, which had to be a structured form of data, sometimes we got really messy, unstructured data. And that's when we started getting this idea of NoSQL, where things like MongoDB came into existence, where you can store unstructured data and hopefully make business decisions out of that. Maybe if you were Amazon, you can use customers' purchasing history to recommend different products. And ever since then, this idea of data, getting more and more data, has turned us into using machine learning. Because at some point, we have so much data that as humans, we can't just look like we did at spreadsheets and look at columns and rows and make business decisions. I mean, we still could, but then we'd be wasting all this data that we've been getting over the years. So companies like Facebook and Google that collect massive amounts of data every single day are turning to things like machine learning, so that instead of humans looking at the data and trying to figure things out, we give this data to machines so that they're better able, even better than humans, to make business decisions. And this idea of machine learning really came to be because of this growth in data that we received from businesses, as well as the improvements in CPUs, GPUs, that is graphical processing units, and computer advancements. So using the massive amounts of data and massive improvements in computation, we can use these machines to give them this big data and make decision for us, just like we used to with spreadsheets. Now, this is a simplified version of how we got here, but I hope it gives you a reason as to why businesses like this idea of machine learning. Now, in this course, we're going to be using this framework. And don't worry, don't get intimidated. You're going to get really familiar with this framework because, well, we're going to talk about it a lot. But looking at this, just a brief overview, what do you think the hardest part is? Can you guess? It's this first part right here. Grabbing the data. You see, amount of data is doubling every 2 years in our world. With the internet, all the mobile phones and connected devices, we're creating more and more data. But this data doesn't mean anything unless we understand it. Yes, we are producing data, but a lot of this data that we generate is unused. And that's what data science is. How can we use this massive quantity of data that is completely useless right now to something that is useful? And not all data is made equal, right? Some are noisy, some are messy. Where do we grab this data from? How do we find it? How do we clean it so we can actually learn from it? We need to understand what data is and then apply machine learning to it. And the industry is now evolving into these people that we want to be, data scientists. That is, people that can turn data from useless to useful. Welcome back. I want to take a quick section to cover a topic that is often forgot about in data science and machine learning courses. However, In order to truly understand a topic, we need to understand the high-level principles and the landscape of that topic. In this case, we want to work as a data scientist or a machine learning engineer, so we need to at least understand the topic of data engineering. But what does that mean? What's with all these titles? Data scientist, data analyst, data visualization. This is madness. This is so confusing. Well, let's talk about data engineering and how it fits into this whole ecosystem that we've been talking about up until now. Now, we learned that data science is all about using data to make business decisions, right? One of the ways that we can make business decisions is to use a technique like machine learning that allows a computer to learn and figure out the solution to a problem that may be a little too complicated for a human to solve or maybe too tedious and takes too long of a time. So we want to automate it. So machine learning is a technique and data science is the idea of using data and converting it into something useful for a product or business. And data analysis is a subset of data science that allows us to analyze the data that we have. But the missing piece is that of data engineering. And not all companies have data engineers, but as companies get bigger and bigger, they need to hire for this role. Let's take a look at why. Who brings all this data to us in a nice little file? Where is this data coming from? How do we manage it? Do we throw it out after we're done? Who labeled this data? You see, a data scientist or a machine learning expert doesn't need to concern themselves, most of the time, with these topics. You ideally have the data accessible to you because this part of data is handled by a data engineer. So who is this mythical figure? Well, a data engineer would take all of the data points that are incoming. Let's say for a company, let's say this company has all these products and all these data are coming from their users, from their security cameras, from their website, from IoT devices. And a data engineer takes all this information and then produces it and maintains it in databases or in certain type of computers so that the business has access to this data in an organized fashion. So they're kind of like the librarians where they collect all this information and they organize it for us so that people like machine learning or data science experts can use this data. But this is a simplified version of what a data engineer does. In order for us to really understand this, we need to go back to the beginning and ask the question, what is data? I'll see you in the next one. Bye-bye. Welcome back. So, what is data? I mean, we've talked about it already, and we should have an idea of what data is. And we also know why business care about data, right? We live in a world now where data is valuable. And some of the most valuable companies are valuable because they collect data. Companies like Facebook and Google sell data to make money. They provide products for customers by using the data to improve their products. Data is the new gold. So businesses care because by understanding their data, it could be part of the product, such as creating a YouTube recommendation engine. We can ask if the company is doing okay to monitor the company's sales and statistics. And you can also use data to improve the company and ask, can we do better? What can we improve on? How can we make our apps faster? So businesses care a lot about data. But I want to take a bit of time to really understand what data engineers do by manipulating or collecting this data. So let's talk about the 4 different types of data. We learned that there's things called structured data. Now, this is data that is actually organized well for us to understand and read, because data gets collected in different ways from different sources, right? But once on a computer, there's a standard way, usually in a table or what we call a matrix, a table that makes it easy to read. Attributes are usually columns, and rows are usually instances. And sometimes we have the outputs in the rightmost column, like we saw with machine learning, where we predict an output based on the inputs. And structured data usually comes from things such as relational databases like MySQL, Postgres, and other relational databases that allow us to do something called SQL queries. That is, to perform actions on these structured data to collect information. Then there's semi-structured data. There's still structured data, but often in something like an XML, CSV, which we've seen, or JSON form. And these are just different extensions and different ways to store data in different files. For example, a really popular websites to grab data that's freely open online and find data sets, maybe even do competitions or see other people's notebooks and talk about machine learning topics. Well, Kaggle allows us to actually look at data sets that are available for us to use and play with. And in here, if I type something like XML, it'll give me all of the information or all the data, let's make this bigger, that are in XML format. So for example, if I click on blood cell images and I take a look over here, I see that the data sources, there's some CSV files, but there's also some XML files. And if I scroll down, there's also some images as well. So different formats of data that we can use. By the way, if you click on filter here, you'll actually see some of the file types available for data. Now we know about CSVs. There's also JSON, where JSON, if we take a look, and let's go to this beer styles one. If I scroll down, we see that it's in JSON format, and JSON format you can see has this tree-like structure to explore data. So just a little bit different than CSV, just another way to organize data. Like I've mentioned, on Kaggle, you'll find all these types of data sets using different things. SQLite, for example, is a type of database and using SQL, so structured data. So if I do SQLite over here and search for something using relational databases, you'll see that this uses SQL. And it tells us what kind of columns it has. So lots of ways to explore Kaggle. But these two types of data are usually well organized and easy for us to manipulate with tools such as pandas for CSVs, and you can actually do SQL as well with pandas. The third kind is unstructured data. And Daniel has already mentioned this, right? This idea of an unstructured data are, well, they're not usually in simple formats that we can really manipulate and analyze easily. These are often things such as emails or PDFs or any sort of documents where perhaps actually understanding them is a little bit more difficult. It's unstructured. Finally, we have binary data. These are things such as audio files, image files, video files. They're in binary, that is ones and zeros that computers can understand, but for us to categorize them, that's really, really difficult. As you can see, it goes from top to bottom. From really organized, well-labeled data to something that is a little bit harder to organize, especially for machines. So why do we have to talk about these four types of data? Well, because most businesses, the bigger they get, aren't only going to have structured data. They're going to have all sorts of data, all sorts of inputs that needs to somehow all work together. So one of the jobs of a data engineer is to essentially use the fact that there's all these types of data and somehow combine them or organize them in a way that is useful to the business. Let's take a break here and explore some more in the next video. Okay. So what does a data engineer actually do? Let's start off with 3 big words that we need to understand before we really understand what a data engineer does. Yes, I know I keep circling around data engineer and I keep getting you excited, but I promise we're getting really, really close. We just need to discuss these 3 words that you may or may not have heard of. One is data mining. And data mining simply means pre-processing and extracting some knowledge from the data. So we use some sort of data to extract knowledge from. That's what data mining is. Big data? Well, it means we have a lot of data, a lot of variables, so much data, in fact, that you can't run on your laptop. There's just too much data for your laptop or computer to hold. Usually, when we talk about big data, it's data that's so big that you need to have it running on cloud computing or multiple computers, such as AWS, Azure, and Google Cloud, because they have a lot of computers and a lot of storage to store this data. So that's what big data is. Big data is data that you usually can't have just on one computer. This usually happens because, data sets get so big. We have petabytes and petabytes of data now. So just having data in a database like MySQL or Postgres or any type of database becomes really difficult when that database is just one single machine. Now, new technologies were invented to solve this problem of big data, like Hadoop and NoSQL, which we'll talk about. Now, a data pipeline is essentially a pipeline that a data engineer builds to essentially use the fact that we have this big amount of data. We need to extract information from this data using data mining. So we need to bring or build a pipeline that allows us to flow from that unknown large amount of data to a pipeline that extracts data to a more useful form. So a data engineer essentially does this, creates a data pipeline where all the information that different devices like IoT devices, mobile applications, web apps, cameras, cars, and pretty much anything that collects data and stores information or logs data into servers or to the cloud, a data engineer essentially accumulates all this information into nicely packed databases and storage engines so that different parts of the company can create visualizations. They can monitor the performance of their product. They can get business insights and make business decisions from this data, and even use this data on their apps, for example, for user profiles. Before a data scientist or a machine learning expert or even a business intelligence or data analyst gets hired, for a big company, the thing that they need to do before all of that can be done is to hire a data engineer. They build the pipeline that allows us to work as data scientists. Remember this diagram and how we've been focusing on this part? Well, a data engineer allows us to do this data collection part. They bring in all this information, organize it in a way for us to do our data modeling. They really help us with this data collection part that usually as a machine learning engineer or data scientist, you don't have to concern yourself too much with. But you know what? My favorite demonstration of what a data engineer is in the next video. I hope you're excited because things are going to start to make more and more sense. I'll see you in that one. Bye-bye. Okay, so in the previous video, we understood that a data engineer essentially creates this data pipeline for us, for people like data scientists to have available data to work with. But I want to use a different example. Let's pretend that Keiko Corp has a need, and that need is for water. The employees need water to work hard, right? So let's think of this as a problem that a data engineer solves. Now, bear with me. We're going to be talking about water for a few minutes, but I promise it relates to data. You see, the very first thing for us to get water is rain, right? We need rain. And this is similar to the data sources that we had. That is the websites, the mobile phones, the cameras, the cars, the drones. All of these are collecting data. That's what the raindrops are. So in order for us to get water to our employees, we have to get water from somewhere, and that water comes from rain. Next, that water gets collected into different streams and rivers from all over the place, right? From all over the world, just like data. From all different places, these streams of water start forming. And what happens next? Well, these streams of water turn into lakes. They all flow into some sort of a lake. And that lake kind of sits still. But again, we as a Keiko Corp just want water from employees. Well, we obviously have a dam on a lake, and that dam on a lake or a system to use that lake, well, we transport that water to something like a filtration sanitary area so that we can clean the water, sanitize it so it's safe for people to drink. So we process that water that has been collected. And then finally, after all of that, we create all the plumbing and pipes for us to deliver water to Keiko Corp. That's how we satisfy the needs of Keiko Corp to provide water for their employees. And this is how data works. And this is what a data engineer builds. A data engineer starts off with what we call data ingestion. That is acquiring data from various sources. And we acquire all these different sources of data and ingest it into what we call a data lake. A data lake is a collection of all this data into one location. From there, we could just leave the lake as it is. But there's a problem. We don't want the lake to overflow, dry up. We need to manage this lake somehow. We don't want to flood the village. We need dams. We need pipes to the houses. We need to filter and clean the water. And we need piping to the houses. So after we ingest this data from various sources, we collect it in a data lake. We then perform something called data transformation. That is converting data from one format to another, usually into something we call a data warehouse. A data warehouse is a place that stores accessible data that is useful for the business. That is, although the lake collected so much water, so much data that was kind of all over the place, a data engineer looks at this data and forms or uses the parts of the data that are useful and puts it in a data warehouse so that other parts of the business can use it. Again, a good way to think about it is that a data lake is a pool of raw data, the purpose of which we still don't know what to do with, and a data warehouse is a location for structured, filtered data that has been processed and has a specific purpose. That is, we have data in here that is useful for the business. So that means that data lakes are usually less organized and has less filtration of data than something like a data warehouse. Now, why would businesses want to do that? Well, for one, it's a lot easier to analyze data when it's organized well. We also might have data in here that we don't really need. We also save on storage space, right? Because we don't have to store all of this data and just store structured data only that is only useful to us. We also save ourselves some money. So to review, a data engineer simply builds this pipeline of taking the data creation and data capture, using data engineering practices to build this pipeline so that data can now be analyzed by data scientists and data analysts. But we still have a little bit more to go. So I'll see you in the next video. Welcome back. So we just went through this whole flow of how data is used by a company. But there's a few more things I want to talk about, because right now we just talked about water and how does this really apply? What kind of tools do data engineers actually use? Well, you may have heard of something like Kafka. And we'll get to Kafka later on, but something like collecting these data streams and putting them into a data lake might be something that Kafka or Apache Kafka might do. For data lakes, for example, these are simply programs that companies can use. For example, you may have heard of Hadoop or Amazon S3 or the Azure Data Lake. These are programs that have been built by engineers to hold large amounts of data, like a data lake. And then for a data warehouse, we have tools like Google BigQuery, Amazon Redshift, even Amazon Athena. These are data warehouses that allow engineers to make queries or analyze this structured data. Now, I know what you're thinking. Who does what in this whole system? We've learned that the data engineer creates this entire system for us. They use different tools and programs to ingest data and then put it into a data lake or a data warehouse. So as a data scientist and a machine learning expert, which data do you use? Pause the video and think about it. Ready for the answer? Well, most of the time, you'd be working with a data lake. Because remember, if you're doing machine learning, the more data you have, the better, right? And with machine learning, you can use structured or unstructured data. So you can go into a data lake and actually grab a bunch of data to use for your models, whether they're in CSV forms or any other forms. And usually, data warehouses are used by BIs or business intelligent people or business analysts or data analysts to make visualization or analyze data. Because the data warehouse has usually more structured data that has been cleaned out than it was when it was a data lake, it's a lot easier to understand and use the data for information. Now, as a data scientist, you can use the data from a data warehouse. And this isn't just a rule. It's usually you use whatever data is usable to you. But this is a good way to think about things, that a data scientist uses as much data that they can, as much useful data as they can, while somebody like a business intelligence person or a data analyst has already the data cleaned, processed by a data engineer, and use something like a data warehouse to analyze data. And Google's BigQuery is exactly that. It allows somebody with not too much engineering experience or programming experience to analyze this data in a data warehouse. Another way to think about it is like this. Usually, a software engineer, a software developer, app developer, mobile developer, they build programs and apps that users and customers use, and that releases data. Then, a data engineer would build this piping and pipeline for us to ingest data and store it in different services like Hadoop, like Google BigQuery, so that that data can be accessed by the rest of the business. Next, we have data scientists that use the data lake as well as the data scientists to extract information and deliver some sort of business value. Finally, we have data analysts or business intelligence to use something like a data warehouse or structured data to again derive business value. And I hope that clears the picture a little bit when you hear all these titles out there in the industry. Now, the industry is fast evolving, And there's definitely some overlap, and sometimes what one job description might say might be different than the other, but these are general simplified rules that you can use to understand how each role plays into the part of a company. Let's finish up this high-level overview of what a data engineer does by describing the three main tasks that they do. One is that they build what we call an ETL pipeline, or an extract, transform, load pipeline. So unlike data ingestion, which simply means moving data from one place to another, an ETL pipeline is the idea that a data engineer extracts data that has been generated by all of these systems. They extract that data, and then when they extract that data, they transform the data into a useful form. That is, into a form that can be loaded into a data warehouse. So they extract the data, they transform the data, and they load it into something like a data warehouse so that the data can be used by the rest of the company. And they use programming languages like Python, Go, Scala, and Java to accomplish these ETL jobs, or extract, transform, load. So that's the first task. What's the second one? The second one is building analysis tools. You see, for us to understand how our company systems work, a data engineer needs to make sure that when any part of the system breaks, we are notified. So a data engineer allows data scientists, data analysts, business intelligence people to use tools to analyze the data, but also to make sure that the system that they've put in place is running correctly. Finally, their third main task is obviously to maintain the data warehouse and data lakes. That is, making sure that everything in there is accessible for other parts of the companies to use. So now that we have a high-level overview of what a data engineer does, I want to talk about some of the tools that you have definitely heard of in the industry. Things like Hadoop, Kafka, Apache Spark, all these terms that are really hard to understand. I'm going to try and give you an overview of this landscape so that next time when somebody asks you, hey, should we use Hadoop? Hey, what's Hadoop for? Do we need Kafka? You'll be able to answer that. And after this course, you can go off on your own and actually learn to use these tools if they ever come across in your job. Now, this landscape is fast changing. There's new tools popping up left, right, and center. So my advice to you is that what I'm going to show you over the next couple of videos, you don't take as the absolute must know for all data engineers. Instead, know that they exist. Go and read some of their documentation, some of the information online, but only learn or use them once the need arises. Because they're constantly being updated, and the world of data engineering is really fast-paced right now. But with that said, let's nerd out on data in the next couple of videos. Welcome back. Let's talk about the types of databases that exist. Now, here's the thing. The world of databases is extremely complicated. There's so many databases out there, so many new innovations, different databases for different things. It's impossible to know all of them. So we're just going to do a brief overview of what exists and why we have so many databases. So let's start off with the first one. Why do we have so many databases? I mean, look at this little diagram that I found. That is a lot. Well, because we have different needs with data, different databases are good at different things. So there's many different databases because we need them from different solutions. But the first thing we need to talk about when talking about databases is this idea. There's three main categories of databases. Now remember, databases are just computers. They're computers with a hard drive, essentially. Just like your computers is able to store files and have files available anytime, that's what a database is. Every time you turn off your computer and turn it back on, you expect your files to be there. And a database is that. you expect that your data persists. That is, the data that you save, whether we turn off the computer or turn it back on, it's still going to be there, and then we can access it, we can modify it. That's the role of a database. And we have three main types. One was the original type of database, which was relational database. A relational database is a database like Postgres or MySQL that allow you to use SQL to make transactions. That is, to write to the database, to read to the database using the SQL language. Now, relational databases were all great until around 2000s, when initially we just had one database, one master database that held all the information that we needed. But starting in the 2000s, we got more and more data. We collected more and more data, and all of a sudden, all that information cannot be stored on just one database. So we had an issue. We now needed two databases to hold that information. And although I'm simplifying things, the idea was that now because we need distributed databases, that is, we needed more than one database to store all that data, relational databases didn't have the necessary tools to have this idea of multiple databases working together. So NoSQL databases were born out of that. Databases like MongoDB became popular because for the first time, it allowed us to do distributed databases. That is, we can have different machines, 10, 15 machines, all working together as one database. Finally, more recently, we have this idea of a new SQL database. What does that mean? Well, new SQL databases are still fairly new, but they try to get the best of both worlds. You see, relational databases are really, really good for something called ACID transactions. They have some really nice guarantees when we read and write data to make sure that it's always accurate. NoSQL databases were a little bit more disorganized, but it allows us to store information on distributed databases. That is, as our data gets bigger and bigger, we can have a NoSQL database on different machines so that it scales up with our data. New SQL databases like VaultDB or CockroachDB are trying to have the distributed nature of NoSQL databases so we can scale up our data, but also have some of the guarantees of relational databases. Now, these new SQLs are still in the works, but definitely keep an eye on them. Another way to talk about databases is using databases for their own specific needs. For example, there's some data storage or databases that are specifically used for searches. For example, Elasticsearch or Solr are used as searching databases. So we put data in there and it allows us to search for things really fast. Then we have things like computational databases. Something like Apache Spark that allows us to use the data that we have in the database and make computations and calculations on them. And we'll get to Apache Spark shortly. Finally, I just want to introduce you these terms that you might hear when it comes to data engineering. OLTP and OLAP. You can think of OLTP databases as relational databases or SQL databases that allows us to make transactions. For example, if you have a web app and that web app has a user that you can store user information, you can upload photos and have that application interact with a database for a user, that's OLTP databases. An OLAP database is usually used for analytical purposes. Now, I'll leave some resources if you want to really dive deep into this topic. But as you can see, there's many ways to describe databases. We have many different types of databases, but at the end of the day, each database is good for its own specific use. If we look back at our diagram, databases are used everywhere. For example, these streams, these are usually OLTP databases, like relational databases that collect information. Let's say a user on a mobile phone updates their username. Well, that goes to a relational database, an OLTP database. And then a data lake. Well, a data lake is another database. usually something like Hadoop, which we're going to talk about. And then that data goes into a data warehouse. All of these things that we see here are essentially databases. We collect information from different streams. We have data lakes, which are databases, and data warehouses, which are databases. So over the next couple of videos, knowing what we know about databases and how we have different types of databases, let's try and figure out how this whole picture of a data engineer works. Let's talk about Hadoop. So as companies started to generate more and more data, our databases that we had, like MySQL, became too inefficient or unable to hold the large amounts of data. And Hadoop became a cornerstone of data engineering. You see, Hadoop is an open source distributed processing framework. It allows us to do data processing and storage for big data. And it was actually developed by Yahoo back in the day, and then later donated to the Apache Software Foundation. Hadoop was all the rage when the big data craze started. Hadoop was a solution that allowed all these companies with petabytes of data to store this information in Hadoop. Now, Hadoop was essentially a data lake, right? It's a data lake solution. It allows us to just store all this data for us. But the popularity of Hadoop was because of two big things. One was HDFS. That is the Hadoop Distributed File System. Hadoop was able to store so much data because of this HDFS, a file system, just like you have on your computer, that allowed it to store files on multiple computers. That is, we can use Hadoop on multiple computers to store as much data as we want. It was scalable. We could scale out. So data is stored across different physical computers. Then was MapReduce, because once we store data, we need to perform some jobs, some processing on that data, right? And MapReduce in Hadoop allowed us to perform jobs against this data that we had in a data lake. Using languages like Java or Python, you can use MapReduce in Hadoop to do what we call batch processing. That is, every night we can run some sort of a job to clean our data, to process our data, and make it useful for the company. Now, MapReduce isn't used as often anymore, as we'll see later on in the videos, because we have something called Apache Spark. That's actually a little bit faster, but we'll get to that. The idea here is that we finally had a tool with Hadoop that allows us to store a lot of data across multiple machines using the HDFS and run batch jobs using MapReduce on this large sets of data. And a lot of other tools started popping up around Hadoop. Tools such as Hive. Love their logo, by the way. Check that out. Anyway, Hive makes your Hadoop cluster feel like it's a relational database. Even though it isn't, it allows you to use Hive and write SQL queries against your HDFS file system. So in a sense, you kind of had this data lake of Hadoop and also a little bit of a data warehouse type thing with Hive by allowing SQL commands on your data that hopefully was processed using MapReduce. And you may not have heard of Hadoop before because it's used by data engineers. Remember, data engineers usually don't work on systems that are customer facing. That is, they don't build databases that you would use with your app or with a web app. Instead, they build the systems behind the scenes that ingests, collects, runs ETL jobs, that is extract, transform, load on data. So Hadoop is that behind the scenes storage layer that stores large amount of data running batch processing against this data so that we can have some useful information. And Hadoop is still very popular and very capable when it comes to large data, petabytes of data. Let's learn a few more tools in the next video. Let's talk about Apache Spark and Apache Flink. You see, before Apache Spark, usually people used Hadoop MapReduce to process everything. Spark came along and actually improved the MapReduce in Hadoop by doing something called in-memory processing, which essentially allowed Spark to run processing jobs much faster than MapReduce. So Apache Spark became really popular. And it's probably the go-to batch processing framework. So if you want to process a lot of data, well, you can use Hadoop to store that data in HDFS and use Apache Spark to run ETL jobs like extract, transform, load to clean and transform that data. Now, up until now, we had batch processing, which essentially means give me a chunk of data and I'll process this data over a bit of time. Usually, you'd run a batch processing job at the end of the night, and in the morning, after a couple hours, the job is done. But as of a few years ago, the idea of real-time processing started to happen. Things like Spark streaming came out, which almost made real-time processing possible. That is, instead of batch processing where you waited until the end of the night to run some jobs on an amount of data, instead, every time data comes in, you process that data. In this space, Apache Flink really took on the charge. It offers real-time stream processing. Now, although Spark is still popular, tools like Apache Flink are starting to become popular. Now, this idea of streaming data and stream processing is becoming more and more popular. It's still new, but there's some exciting things happening in this landscape, so let's talk about that in the next video. Welcome back. So we learned that as a data engineer, you collect data, you ingest data, and then you store it in a data lake, often a Hadoop cluster. Now, this idea of a data lake can also be used with something like AWS's S3 object storage. So those are the two most popular ones. And then once they're in your data lake, you can usually run batch jobs on this data to clean it up or modify it or wrangle it in some way. So Hadoop allowed us to do that with MapReduce. We can use Apache Spark. You can just manually write scripts on Amazon S3, or you can just even do batch jobs with common databases like SQL Databases. But this idea of stream processing is now becoming more and more popular. Instead of processing data using just batch jobs, let's say every hour or every day, there's now a movement towards this idea of real-time stream processing. That means when data is received, processing it right away instead of waiting a bit until we can do batches at a time. This allows us to have faster reactions to data. Now, this idea of stream processing is pretty complicated, but one of the main tools that's being used right now for stream processing is something called Kafka. Kafka, if we look on their website, is a distributed streaming platform. It allows us to read and write streams of data like messaging system. It allows us to process, and it allows us to store data as well. But as you can see, what Kafka does, it allows us to receive messages and pass it on to different places. So what you'll often see is we use Apache Kafka to receive all these messages, logs, and data from all these sources. We collect them in a central location, and then Kafka can pass it on to different locations. For example, we can pass off whatever Kafka receives to a Hadoop cluster to store that data, and then perhaps, if we want, use Apache Spark to process that data into a data warehouse. But now with the idea of real-time processing, Kafka allows us to now pass things on to, itself, or we can use something like Spark streaming, or Flink, which we've talked about, Apache Flink. that is used more for stream processing, or Apache Storm, or even Kinesis by Amazon, which actually can also be placed like Kafka here to handle all these messages from all these locations. Now, at the end of the day, all of this might have been confusing. You may be overwhelmed by all of these tools that are available. But remember what I said at the beginning of this section. A data engineer is somebody that you'll interact with as a data scientist. So it's good to know what they do, what their roles are, what their responsibilities are, and you'll work closely with them for you to have the data available to perform analysis on it or build machine learning models. But I hope that this diagram now makes sense. A data engineer creates this landscape for you, where they ingest data through Kafka, store information using something like Hadoop or Amazon S3. They process that data using something like Apache Spark or Kinesis. And then they even store data in data warehouses, so tools like Redshift or BigQuery can be used by people inside the business to learn something useful from the data. They build the structure for you to flourish. So be nice to them. And if you're ever interested in any of these technologies, they are changing very fast, but they're definitely worth a look, and they're not as intimidating to learn as you might think. I'll see you in the next one. Bye-bye. Caching is the process of storing some data in cache. Cache is a temporary storage component area where the data is stored so that in future, data can be served faster. Think of it as a little package box that we store information in so that we don't have to travel all the way back to wherever we're going to retrieve this information. We have a package that is a lot closer to us that can give us this information a lot sooner. Now, in order for us to really understand caching, we have to go to the very basic steps. That is talking about CPUs, random access memory or RAM, and hard disks. Now, CPUs are built with a special on-chip memory called registers, which usually consists of small amount of fast storage. So CPUs nowadays actually have a bit of memory as well, besides just doing all the work or being the brain of our computers. They're the closest and smallest memory storage in our computers, but also the fastest. Sometimes you may have heard of these registers as L0 cache, L1 cache, L3, L4 cache. And all these caches depend, whether they exist or not, on the architecture of the chip. But they're used as a super fast way to access memory, the fastest we can go. And then we have something like RAM, or random access memory. They're again closer to the CPU, not as close as the registers were, the small little pieces of memory that the CPU had, but large enough that can hold significant information that the CPU can access information from and use it. Again, because this is in memory, as soon as the power goes off of our computers, well, that information is gone. But because it is in memory, well, it's also fast to access. And then we have something like hard disk drives. And these were physical disks that we had in our computer. Now, these are, in newer computers, you'll find something like solid state drives that actually make accessing information a lot faster. But the difference between RAM and this hard disk drive is the performance, cost, and the proximity to the CPU. You see, as we go down the line, it becomes cheaper and cheaper. But also, it becomes slower and slower to access this memory. For the CPU to access disk memory, well, it has to travel a longer distance, and the disk takes a longer time to give that information to the CPU. But the added benefit is that even if the power goes off, this disk will remember our information. Again, versus the RAM that stores only temporary data, the disk is able to store long-term data. Okay, but why do we just learn about this? How is this useful to us? You see, because caching is actually everywhere. And most people might not realize how many places we can actually cache things. Similar ways in which we're able to access memory or access data a lot faster in our computers using CPU, RAM, and hard disks. Well, we can do the same similar principles in our applications. For example, we use CDNs to cache our HTML, CSS, and JavaScript files so that instead of the browser going all the way back to the server across the country, across the globe, it can just access the closest server, CDN, and use the cached files. There's also things that we can cache on the server. For example, on the server, if I was accessing some sort of an API that returns me robots, well, so that I don't have to request that every time, maybe I can cache that robot information, perhaps in a variable, perhaps in a memory storage like Redis, or perhaps even in a database if the API is really slow. We can also use caching on the database side. And database servers will be configured out of the box usually for optimal caching, but they do also allow you to control and change parameters based on your needs. And then we also talked about Redis. And we know all about Redis now. We use it to manage our session tokens. When I taught you about Redis, you thought, all right, Andre, he's teaching me about another useless database. This is a waste of time. But then you slowly started to come around and I showed you that you can manage sessions using Redis and it's really fast. What if I told you that we can use Redis for caching database requests as well? Something that we've talked about a little bit in the database scaling video. For example, if we had a node server and we had to make a request to the database, well, I can first place my Redis server right in between us. And I can ask the Redis server, hey, do you have this user information? If it doesn't, well, we go to the database, retrieve that information through SQL, and send it back to the node server. But before we just send it directly back, we go through Redis, store that information in memory, and then pass it back to the server. So that the next time the server asks for the same information, we go through Redis. Redis says, oh yeah, I have it. Here you go. And we avoid the SQL statement and the disk access that most likely would happen with a database. And that's something that you really want to do. Before you do any sort of database scaling where we start working with the database, you want to figure out, hey, can I cache? Can I use Redis or memcached to cache our requests or our queries? And there's so many other places that you can cache things. For example, the most common one and the one that you're probably most familiar with is caching on the client side or on the browser. You see, the browsers give us a ton of ways to cache information. And we're going to dive a little bit deeper into this topic because you can do some really exciting performance optimizations with it. So for that one, you'll have to wait until the next video. See you then. Bye-bye. With databases, there are a ton of them. And even in my previous course, we covered the differences between relational databases and NoSQL databases. Relational databases meant that you had to define your schemas or how your database looked beforehand. And you were able to build really complex databases this way. And that's what Postgres is, a relational database. It's a database that allows us to have different tables that are related to one another. And we define those relationships with what we call schemas. And again, we use Postgres as a relational database to hold our users and passwords in our SmartBrain app. But there's a reason there's so many databases out there. Different databases are built to optimize different things. Amazon, Netflix, Facebook, Alibaba, Joe's Donut Shop all have different database needs. To meet all these needs, a ton of databases can be found online. And today we're going to talk about one of the most loved and used databases called Redis. And it's a NoSQL database. So this way we're able to learn a bit of relational database with Postgres as well as NoSQL with Redis. Redis is what we call a NoSQL in-memory database. And by the end of the section, those words are going to mean something to you. So let's get started. Redis is an open source database that is often used to build really high performance scalable web applications. A lot of companies use Redis. Now, NoSQL databases can have many different types. You have things such as document NoSQL databases. You might have heard of MongoDB or CouchDB. These are really, really good at storing documents. So if you think of LinkedIn profiles, where your profile has all these different fields and categories, and one user has that document-like data, in that case, well, these are really, really good. You have things like wide column with Cassandra and things like graph databases, Neo4j. If you have a social media app, for example, that describes a graph-like connection between its users. Now, Redis is what we call a key value store. And this key value relationship is a little bit similar to how we handle objects in JavaScript. We have a object property that has a value associated with it, a key and a value. And we're going to go over how we're going to use Redis in the next couple of videos. But the one thing I want to get across is that it is an in-memory database, which makes it really, really fast. You see, Redis is used for short-lived data in our applications. And it's often used with things like sessions or web page hit counts. And in-memory means you don't have large data sets, such as you would with something like Cassandra or MongoDB. You have small pieces of data, so tiny little pieces of data, which allow us to keep it in memory, that is the machine's memory and not on disk. If you remember, memory is something that is very easy to access on a machine, and disk is a little bit slower. You can store a lot more information on disk, but it's a little slower to access. So with Redis, you want to use it when you have small pieces of data that you need access to, and you also don't care if you might lose some of that data. Now, even though the data is in memory, Redis does take a snapshot every once in a while to save the current database contents onto the disk, which is great to recover from when there's unexpected shutdowns, wherever you have Redis running. And you'll only lose the last few minutes of information. Then based on that information, we should be using Redis whenever we have small pieces of data that isn't super, super important, that if the service crashes, we'll be able to come back to a snapshot and we might lose the latest information, but we're sacrificing all of that for the speed of service. It is super, super fast, and it's very, very scalable. And Redis, like all other databases, has its unique set of data types that it can store. And we're going to go through some of them in the next videos. And you'll see that it doesn't use SQL. It's no SQL database. And we'll see how that works. In this section, we're going to get used to Redis. And then coming up, when we talk about sessions and JWT, we're actually going to use Redis in a way to manage session for us. Because as senior developers, we have to decide which tool is right for the job. We should know this by now. And although Postgres is amazing, when you have tools like Redis that can be really, really fast for managing small pieces of data, there are some use cases where you might want to have some information in Redis and some information on Postgres, depending on what your needs are. And in most companies, you'll see this. It's very, very rare that a big company has just one type of database. Most of the time, they have different databases all around because they have different needs, different ways that they need to read the data and different ways that they need to write the data. And again, based on that tool, they use different tools. So we're going to learn that skill of being able to use different pieces of tools that are as databases to work with what we have. All right, It's time to get started with Redis. I'll see you in the next one. Bye-bye. Welcome back. Let's install Redis onto our laptop or computers in order to actually use it and test out some commands. Now, keep in mind when it comes to databases, most of the time you won't actually be running it from your computer. In most cases, it's going to be on a server or another machine that is just dedicated to that database. And we're going to be doing the same for Redis. But because we want to test it out and make sure that we know the commands and we can run it locally as well, it's good to practice these skills. Now, in order to download it, it's very, very simple. We simply go to their download tab. And you see here that, they have Docker images as well, which we might use later on, hint, hint. But for now, we're going to get the stable version, 4.0. And you can click download here. Or if you keep scrolling down, you see that you have some commands that you can use to get it. So you have two options. You can either just click on the download link that is up here, which will download a file, as you can see over here. And with that file, you can actually just open it and then run these commands. But for now, just because we have these available to us, I'm going to run the commands. So the first one is to get this thing that will get us Redis installed. So let's open up a terminal here and run the command. You see that it's installing. And once that's done, we have to open it up with the tar command. And then finally, we can cd now into the Redis 4.0.9. You might have different version. As long as it's above 4.0, you should be fine. And this folder was created for us, so let's just go in there. I'm going to clear. And then we see that the final command that we need is make, which executes something called the make file. So let's do that. And this is going to be running to set everything up for us. If we go back to the documentation, we see that the only thing we can do now is to run the source Redis server. That is to run the Redis server just like we did with Postgres to make sure that the Postgres server is running, and it's probably going to be running on some port. And then we can run the Redis CLI command to actually have access to this database and run some Redis commands. So let's minimize this and go back, and all right, we see that everything has been loaded. It gives us a suggestion to run make test to make sure that everything has been installed correctly. And it'll run through some tests here. I'm not going to go through that just because I trust that everything was set, but it's always good to run make test. All right, so here you see that we've downloaded the tar file. We've opened it into the Redis folder, and now I'm inside of this folder. I have a nice background today. For any of those wondering where I'm getting these backgrounds from, I have this desktop app called ArtPip that has a different painting every day, which is nice. Anyway, back to what we're doing. I can go over here and type source, remember, just like the documentation suggested, Redis server to start the server. If I press enter, you'll see that it asks on my computer if I can give access so that it accepts incoming network connections. I'll allow it. And you see that we're now ready to accept connections. And it gives you a nice little graphic here too that you can see. All right. I'm going to move this on this side. So this server is running now. And I'm going to open up another window. And with this one, we're going to run the CLI. I'm going to say source, or I have to go into the Redis folder and then run source Redis CLI. And there we go. We're connected to this server and we can start running some Redis commands. In the next video, we're going to learn some of these commands and how we can actually enter data into our Redis server. I'll see you in that one. Bye-bye. Welcome back. Now, remember with databases, There's a ton of them, and each one of them is good for a particular problem. It has some benefits and some cons as well. Now, with databases, you always want to think about the big picture and what the benefits of that database is. In our case, we know that Redis is an in-memory storage, so that means it's super fast for us to access. We can get values really fast from it. But it has that downside where it only takes a snapshot and writes it on disk occasionally, so you might lose some data if the server goes down. And we know that Redis is often used for small pieces of the data like session management or maybe even caching some small data, which we'll talk about. But another part of databases you want to look at is what kind of data types can they support. And based on these data types that fit your needs, a database might be good or bad for your project. So in this video and the next couple of videos, we're going to talk about what some of these data types are that Redis uses and what we're going to use in the future section on sessions and JWT. The very basic one, and if you remember, Redis is a key value storage. That is, we give it a key and a value, and we're going to be able to access that value from that key. So let me show you. The very basic commands with Redis is to set, and look at that. It already gives me options and hints by downloading this Redis CLI what I can put. So I can set, key, and value, and some options as well. So let's say that I want to set name to Godzilla. And that's a string. If I press enter, I get OK. Now within here, I can now get this name whenever I want by saying get name. And I get Godzilla. And that's it. Key value storage is simply that. You give it a key, you give it a value, and now you can use the get command to get that value back. Another command you can run is to see if something exists. So if I do exists, name, I get, yep, I have one name. And I can also run the delete command. So I can delete the name command. Now if I run exists, name, nope, there's no name there. And if I do get name, nope, I have absolutely nothing. Before I keep going into more commands, I want to show you that, once again, documentations are your friend. If you go to their documentation tab, which I have opened over here, they have a ton of resources for you. But the one we're interested in is the full list of commands. And as you can see here, they give you a really nice breakdown on what everything does. So let's have a look on one of these. We see that we want to try the expire command. And if I click on here, we see that it sets a timeout on key. After the timeout has expired, the key will automatically be deleted. All right, so let's say that we want to try this out. We can just simply say expire, or we have to set something first. So let's just set let's say session, and it'll be Jenny's session. And we'll say that expire session in how many seconds? Let's say that we want to have it in 10 seconds to expire. Now if I do get session, I get Jenny. I wait 10 seconds though and try get session again. Session is gone because I made it expire. How cool is that? Again, each database has its own set of features, and Redis has this nice expire where you can just expire things to be deleted from the database whenever you want. Another really useful tool was something like perhaps sessions. If you want to expire a session, for example, of a user where after, let's say, a day, they have to re-sign in into the app, that's an easy thing that we can do right away with Redis. Let's try a few more commands. We can set counter to 100. Again, we're just doing a simple key value storage. Now we can do another command, increment by. That's a little tough to spell, but increment by. We give it a key counter, and we can say 50, or let's do 33. Look at that. Now our counter is incremented by 33. Very cool. And as you can imagine, there's also the decrement or decrement key, and we'll decrement the counter, and we can give it, let's say, 33. And yeah, it actually, with decrement, the default and the only working default is that it is just decrementing by 1. If I run this, you see that the integer has now been decremented by 1. All right, a few more things to go through, but let's take a break, and I'll see you in the next video. Bye-bye. Welcome back. Let's try a few more commands and then explain to you what data type we've just been working on. So the first command that we're going to add to our arsenal will be mset for multiple set. So in here now, I can add multiple things. Let's say that I want A to be 2, and I want B to be 5. And I can keep tacking them on. Now I can just say get A, get B. And I've set multiple items in the database. I can also do multiple get and get both A and B, just like that. All right, we just learned some basic Redis commands, but you may have noticed something. The only data type that we've been really working on are strings. Even if I set the number over here, we see that it returns it as string. And we just learned the first data type that Redis handles, and that is a simple string. But there's actually a few more things that we can use in Redis. You see, Redis can handle 5 data types, or 5 major data types. There's a few extra others and things that they're adding on, but the 5 main ones that you're going to use are strings. The next one is hashes, lists, sets, and sorted sets. And we've just learned how to handle strings, but we need to learn how to handle the other data types as well. So let's cover those in the next upcoming videos. I'll talk to you soon. See you in the next one. Bye-bye. Welcome back. The next data type we're going to talk about, again, we've covered strings. The next data type that exists in Redis are called hashes. And hashes are maps between string fields and string values. And the best way to think about them are simply like objects. Just like in JavaScript, we have objects. Redis hashes are very, very similar. Let me demonstrate. I can set a hash type, data type, by saying mset. And now within here, I can say user ID, let's say 45, name, let's go with Johnny. And here we've just created a hash with a key user, and this key has both ID of 45 and name of Johnny. So if I do get, hash get, and I do ID, and that doesn't work because I have to say what is the hash, that is, what is the key that is identifying this object. So it would have to be get user ID, and I get 45. If I do get user name, I get Johnny. And if I do something like get all, and I just give it the key, look at that. I get all the identifying criterias of the user. Again, a good way to think about hashes in Redis is simply like JavaScript objects. All right, let's talk about lists in the next video. The next data type we're going to talk about in Redis are called lists. And lists are implemented using something called linked lists rather than arrays. And that's getting into a talk about data structures. So we're not going to get too into it. But the main principle is that insertion is really, really fast with lists. So if you're adding things to the lists, it's really, really fast. But it takes a bit of time than arrays when you're searching for a key. So think of it this way. Lists are useful if you have really long lists and you need to add elements quickly to that list, and you want to use something like that. Otherwise, you want to use something like sorted lists in Redis, which is better for when you're searching or getting those elements. So let's give it a try. The first thing we're going to do is say L push, that is left push. So from left of where the head of the list is, we're going to add 10 as a key. Or sorry, I have to name the key. So I'm going to say that this is going to be, let's say, our list, and we're going to add 10. And let's say I also want to do a right push. And this right push is going to be again on our list. And it's going to have, let's say, hello as a string. And this is going to enter it from the right of the list. Now, if I do something like get our list, we see that, because our list is a data type list, we can't just use our string get on Redis. We even get a wrong type operation against a key holding the wrong kind of value. Now, the way we can actually read some of these lists is if I do something like L range, and we give it a range that we want to grab the data from. You see the key, start, and stop. So I'm going to say I want our list, and we want from, let's say, 0 to 1. I get 10 and hello. If now, let's say I do a left push to our list of 55 and do the range, L range, from 0 to 1, I get 55 and 10 because I only get the two values from 0 to 1. If I do 0 to 2, I get the 5, 55, 10, and hello. You can also run commands like ltrim to trim your list, or you can run things like rdrop, which is drop whatever's on the right-hand side, and I can just say drop from our list, or sorry, instead of rdrop, it's actually rpop, just like in JavaScript. So it's our list. So now if I go to the L range, our list 0 to 2, nope, there's no more hello because we popped that. Not drop, pop. All right, so these are lists. Let's talk about the next data type. Welcome back. There's two other data types that we want to talk about in Redis, and they're called sets and sorted sets. And sets in Redis are unordered collection of strings. And that's why we have two types. We have sorted sets, which are ordered, and unordered, which are sets. And with sets, it's possible to add, remove, and test for existing members in a group. And you might be thinking, sets kind of sounds like lists. But the one major difference with sets is that you have this desirable property of not allowing repeated values or members. So adding the same element multiple times, it's actually not going to work, or it's just going to give you a single copy of that element in the database. And this is a really, really nice property to have. We make sure that we don't have any duplicates in our items. Let's try out some set commands to see how we can add sets, again, unordered collections of strings. We simply say s add for sets add, and we give it a key. So let's say our set, and we'll say that we want to add a collection of numbers. Let's go with 1, 2, 3, 4, 5. And we just added some elements to our sets. Now I can say s members and give it the key our set, and we get the members of whatever our set is. Now, if I do s add our set 1, 2, 3, or let's do add 1, 2, 3, 4, I get integer 0, and if I do s members our set, I still get the original 1, 2, 3, 4, 5. Again, because this has already existed. We've already created our set right up here. Another nice feature of sets is I can run the command s_is_member. And now with is_member, I can say our set and is 5 a member of our set. Yep, I get 1. But if I say if 20 is a member of my set, and nope, I get 0. Means it's not a member of the our set value or our set key. Now, there's also such thing as sorted sets. Now, Redis sorted sets, just like sets, do the no repeating collection of strings that we've already demonstrated. But the difference is that every member of a sorted set is associated with a score. And this score allows it to be ordered from smallest to greatest. So let's have a look at how this works. If I do sorted sets by saying z_add instead of s_add, I can add different things. Let's say that sorted set is going to be team. We'll give it a number. Let's say team has 50 members. We'll also say wizards. Now, let's say that the next team, which is not wizards, will be the Cavaliers. Oops, that's not what I wanted to do. And this team has 40 members. I can now access this by saying z range. And this z range, I'll give it the team key from 0 to 1. And you see that now I have the range, however, it's ordered. Even though I've inserted wizards first into the sorted sets, the Cavaliers appear first because the team number is lower with Cavaliers. And remember, it goes from lower to higher. So if I add another team, let's say that only has 1, and they're going to be called, let's say, bolts. I can now say z range, and we want to grab all 3, and I have bolts, Cavaliers, and wizards all sorted. And there's other useful commands that we can use. We can say z rank, for example, and we can find out what the team wizards rank is. And we get that their rank is 2. Again, it's not 3 because the order starts from 0. So 0, 1, 2. All right. There's plenty other commands that you can learn with Redis, and they're really easy to follow just with your documentation. However, you should have a good idea of why we'd want to use Redis. If we want a fast database that scales really, really well if we have a lot of users, but also helps us out that we want to store the data types that it supports, like the ones that we have, well, we can do some really neat things with it. And like I said, we're going to be using Redis to manage our sessions in the sessions and JWT section of the course. Now that we have a good understanding of Redis, go try out some of these commands, play around with it. It's a lot of fun, and I'll see you in the next video. Bye-bye. Welcome back. In this section, we learned about a new database that we're going to use called Redis. It's extremely popular, and you're going to see a lot of companies using it. So I really wanted us to get comfortable with it. And I also wanted you to get comfortable with it because we're going to add it to our SmartBrain app. You see, up until now, we don't really have a way to manage sessions of the user. That is, a user has to log in every single time, every time they visit the website, and the website doesn't really remember them. We're not really able to update profiles or create profiles and have that ability without sessions. So we're going to be including Redis in our next session to actually show you how we can implement sessions. We're going to add it to our Docker container, which we've created, and then have our API communicate with the Redis server to check if a user is logged in or not, so that we're able to keep users logged in. And this is a bit of a special section because it's going to keep going into the next section, because if you remember, Bruno asked us to have these added to our ability of the SmartBrain app, or to the ability of the SmartBrain app. And knowing what we just learned about Redis, we're now finally able to add it to our Docker container for development, and then finally connect it to our API. And because Redis is so fast, again, an in-memory data storage, Bruno's going to be extremely happy with us because we found a way not to slow down our website while also keeping these user sessions. Interesting, right? It's going to be a lot of fun when we finally see all of these dots connected. And that's when you're going to have an aha moment. These topics of Docker, Redis, and containers is really, really difficult and really hard to teach because there's so many moving pieces. And I hope you stay patient with me because I know not everything is 100% clear yet. But I promise you, if we'll follow through with the next section, we're going to understand how everything is connected, how everything works, and how you're going to be able to do the same thing on your own projects. So that finally, when you go work for a company, you can have a setup, not just like this for development, but also for production, where you have different Docker containers. You can have different Redis clusters. You can have different database clusters, with the idea being the same. You're just connecting these services together, and each service does one thing really, really well. So stick with me. Looking forward to the next section. I hope you are too. I'll see you in that one. Bye-bye. Welcome back. I am so excited for this section because we're finally combining everything we know into one place. By the end of this, we have a unified understanding of how everything works in the world of web development. We have our front end, SmartBrain here, with the sign-in page. And we have our app built in React. We also have our server running on port 3000, listening to requests, but now we don't need this database anymore. We can create our own Postgres database now and have the server interacting with it through SQL, updating everything, and then responding through Express back to the front end. It's going to be so much fun. I'm so excited. But before we actually start to code anything, we have to design our database. Let's create a database, and we'll call it SmartBrain. All right, perfect. Now that we have our database created, I want you to think of these three separate things as their own individual computers that when we deploy is going to be different parts. We have our server living on a computer. We have our database living on a computer, and we can actually connect here to it. And we also have our app in a separate computer as well. So let's close this quickly and connect to our database, to our local host, and we called it SmartBrain. Click connect, and there you go. But no tables yet. To get started, as we did when we created our API design for our server, we really want to think about how our database would look. And we're using relational database here because, in my opinion, in 2018 and moving forward, relational databases are really, really good. Although databases like MongoDB are really easy to get started with and they're dynamic, you don't have to think too much about when you're starting off. I think relational databases offer a really strong way to think about how your app should be structured and how everything and all the pieces come together. It's a really, really powerful tool that I see the industry shifting back to more and more. Whether you use Postgres or MySQL or SQLite, all these databases are pretty much the same. They're super powerful, and we're going to do the exact same thing with our app because we're not necessarily storing information like LinkedIn or Facebook where everything is a document model. We have users that are interacting with each other, but within our app, we can have different things. We can have login information. If we expand our app, we can have maybe information about the type of images that they've submitted. Now, looking at what we've built, there's definitely a few things that we want to create. If we go back to our database example here, we have our users table, which we're going to have to create. But remember what I said about passwords and the way we store passwords. We don't necessarily want to create a user object or a user table with all these columns. We want to separate things out and connect them through foreign keys. So we're going to create a users table and then a login table and have those tables connected through perhaps the email field. Let's go back to our GUI and create these tables now. I'm going to open up the query. Let's remove this from now, our old query, and let's create our users table. As you remember, it's create table users. I have brackets around here just so it's clean. And within here, I'll say ID is going to be serial, and this will be our primary key. We will also have name, and the name will give it a variable character of 100. We'll just assume that nobody's name is going to be more than 100 characters, which, again, I don't think we will. Otherwise, our database will give us an error. We can also create an email field, and this will be a text. We also want to make sure that this is a unique email. Otherwise, we don't want to register the same user over and over. And it cannot be null. It must always be there, because this is what we're going to use in our login table. We also know that we want entries. And the entries can really be quite a big number. If we have a really dedicated user, well, then that person can keep submitting those photos. So let's just do a large int here. Oops, and instead of large, it's big int. There you go. With big int, we will also say that we want the default, and this might be new for us, but default value should be 0. Unless we somehow insert with entries and a number, if we don't specify what we're inserting the number with, it should be default to 0. Finally, we also want to get the time that they joined our app, and we can use a timestamp data type for that. And again, we want to make sure that this is not null either. All right, let's run this and see if it works. And I get an error at or near, and that's because I added a comma at the end here. Let's try that again. There you go. If I refresh, we have our users table. Amazing. So we have the users table, which we're going to store all this information. And we also want to make sure that we store our login information. the email, and the hashes. Because remember, we're never storing plain text passwords. Let's create that. I'm going to go back to the query, remove this, and change it to login. And this login will now have an ID, once again, of serial. And the serial data type will just increment. It'll be a primary key. And we'll have a column hash that has a variable character of 100, once again, because we know that bcrypt always gives us a certain length hash and it'll never be over 100 characters. Not null. We absolutely need this information. And then finally, email, which will be the same as the users table. And this email will be a text. It must be unique and definitely not null. Let's run the query and refresh. All right, we got ourselves our tables design. So now that we have these tables, we understand what our data is going to look like. This is going to be a database that will persist no matter if the server goes down. It's going to make sure that this data stays put. Now that we have these three pieces running, we can start to work with the server, remove the database variable, and actually connect to our database. I'm excited to show you how we're going to do that in the next video. Bye-bye. Welcome back. Let's connect our database to our server. And in order to do that, there's tons of tools. As you might have known, yes, we're using npm again, a node package that allows us to connect to a database. There's many options, and in this video, we're going to work with my favorite, connects.js. It works with Postgres, MS SQL, MySQL, MariaDB, SQLite, Oracle, pretty much any relational database Connects works with, and is super simple to use. I absolutely love it, and you're going to love it too. Just to show you there's different options, there's something like PG Promise here that, again, is very popular. And you can see it here that it's very easy. You just import it and do .any and do your SQL statement. And you can pick whichever one you want. Although PG Promise really allows you to write simple SQL queries, Connects is just a really good tool that if you're ever working on a project, I would recommend. So I'm going to use Connect.js to do it. And if you go into installation and Node.js, of course, they have good documentation of how to install it. In our case, we can just npm install Connects. I'm just going to stop the server for now and run npm install. Let's open up the package.json file, make sure that it's working. There's Connects. And they also say that we need to install the Postgres or whichever database we want. In our case, we want Postgres. So we're going to npm install PG. All right, we have Postgres installed as well. Amazing. Again, the reason that I love this library is it makes things so simple. You can see over here that in their document, it tells you exactly what you need to do to connect to the database. So let's copy this. Go to our server.js. Let's import by doing const connects equals require connects. And in here, we'll just copy and paste. And we can remove the variable and just use it like that. Now, this syntax might be confusing to you, but all it's doing is, if we remove this, it's just doing connects and running the connects function that we just had. So let's just keep it like that because it looks better. We want to update our client to Postgres. So again, if we do Postgres, it'll be
PG, because that's what we just downloaded. And then we have to tell it where this database lives. And we would modify this according to where we set up our database on a hosted platform. But for now, we have localhost. And localhost is the same thing as this number. 127.0.0.1 is home. There's a funny t-shirt that I saw a developer wear once that says, there's no place like 127.0.0.1 because it means localhost. And it was a play on there's no place like home. I thought it was funny. Anyway, this is the same thing as localhost, so we'll just keep it like that. And we have our user. In our case, if you remember, and we go to our database, the user, I guess, will be me. So I'll just do my name. There's no password to our database, so we can just leave it blank. There's actually no user either, but for now, it's fine. And the database, if you remember, is called SmartBrain. Now, if I actually exit this and start over, you see that it's the same thing that we're entering here. We're just saying where the host is, the user, password, and database. And because we were able to log in here without the user and password, well, we don't really need that information. Let's give that a go. I'm going to save, do npm start. All right, I'm not getting any errors here, which is good. Let's go back to the page here. And copy and paste just a simple, maybe select statement to make sure that everything is working. If we go back to the left-hand side over here, we have the query builder and select. So let's just grab something from our database, even though we don't really have anything. You see that we just have connects.select and then whatever we want to select from the database. All right, let's do that. Let's do connects.select star from users database. I'm going to save. And I get an error, which is good. It's reading here, but it says unexpected token because, well, I have to wrap this as a string. Let's try that again. And you see here how I get connect select is not a function because here I have to assign this to a variable. And the way we do that is we can just say const database equals, just like we had before, connects.select. But let's just do Postgres for now. Save and change this to Postgres. Let's save. And now there's no errors. That's awesome. If we perhaps console.log now and save. All right, we get a ton of information here, but it looks like it's responding with something. That's perfect. It looks like we're connected to the SmartBrain, but this isn't exactly how we return information from connects. And we'll get into that into the next video. But for now, we've connected our server to our database. I'll see you in the next one. Bye-bye. Welcome back. We left off in the last video with this console log of the connects query that we just did. Now, this on the right here is what connects does. It builds our SQL statement for us. So what we just console logged was the query statement that Postgres or connects created for Postgres. You can see over here that the builder is an object that has all the information we need to speak with the SmartBrain and do this query. If I actually want to access something from the users, I will have to do our friend.then because this returns a promise and we get our response. In our case, it'll be data. This data, again, we don't have to do JSON because we're not sending it through HTTP. we get back a data, and if we just console log this data, let's see what we get. Save, and go down, and it's an empty array. That's a good sign. We don't have any users yet, but we're getting a response. So let's do that. Let's create a statement to insert users when they register. I'm going to change this into the DB variable, just so it doesn't get confusing, and we'll just keep that as database. All right, let's go to the register endpoint, and I'm going to minimize this database because we're going to stop using it and delete it afterwards. And if we go to register, we see that now instead of doing the database.users.push in the variable, we can just use connects. We can remove this and do db dot, well, we'll have to insert, right? Let's look at the connects docs and see, and we see clear methods, insert. All right, look at this great documentation. We can just find out exactly what we need. In order to insert something, we have the insert method with the data and what we want to, well, what is going to get returned. We can just copy and paste this. Okay, so we can just do db into users. We want to insert, and it just reads so nicely. I love connects. We want to insert an object, and this object is going to contain whatever we had in the user's information. So we want to insert an email, in which case it will be email. We have the name, which again is the name that we receive from the body. We also have the password, but remember in our table, we don't have the password under the users. So we'll leave that blank. And if we go back to our table example here and connect back to here, we see that users ID is automatically generated, name, email, entries defaults to 0, so we don't have to enter anything. And joined is the date that they've joined. So let's just do joined, new, date. And once we insert, let's just do a dot then console.log to see what we get back. I'm going to save. We don't get any errors, which is good. And we can go back to our app. Actually, just because it's faster, instead of doing register through here, we're going to open up Postman. And Postman already has all our previous commands here, which I love. So let's click on the register endpoint with the body of Anne, apples, Anne. Let's click send. All right, we get a response, but remember, we never changed the response. But if we go back to the server, we get result, insert. All right, it looks like it worked. If we go back to the database and do select star from users, how cool is that? We have Anne, who has been entered as our very first user with default entries of 0. Amazing. It's like magic. How simple was it to just use connects and Postgres and create our first database? All right, in the next video, we're going to work on this response. I'll see you in that one. Bye-bye.